In this section, we're going to start working on our next big machine learning algorithm. So let's get to it. So the next algorithm that we're going to work on is linear regression. Now, when I call this thing an algorithm, that's not exactly correct. A better way of referring to this would be to say that we are going to try to figure out some relationship between some dependent variables and independent variables using a linear regression approach. And we're going to implement an algorithm to do that for us. So just to be crystal clear, that's what we would say. Anyways, so I want to quickly tell you about some pros and cons of linear regression, and then we're going to start to discuss exactly what it is. So one of the big reasons that we are going to use linear regression is that it is usually relatively fast. When we were working on k-nearest neighbor before, we had to rerun the entire algorithm every single time that we wanted to make a prediction, because we had to recalculate all those distances, we had to sort them all, and then take the top k records. With linear regression, we have a little bit different paradigm. So with linear regression, we're going to do some initial training of our model. Once we have a model that has been trained, we can then use it to make a prediction very, very quickly. So we are going to take some amount of time to do that initial training. We don't get everything for free. It might take some number of seconds, minutes, hours, depending on the size of your data set. But then once you create that model, you can use it to very easily make predictions. The next thing that's going to be nice about learning linear regression is that we're going to solve it using methods that are very commonly used in many other machine learning algorithms. So we're going to go through this kind of solution very, very closely, very detailed. And once you get on the other side, once you pick it up, you're going to be able to apply that knowledge to many other algorithms that you're probably going to work on in the future. Now, the one downside I would say to linear regression is that it's a lot harder to understand intuitively compared to k-nearest neighbor. With k-nearest neighbor, the solution or the algorithm just made a lot of sense, right? We tried to find some other data points with similar attributes, and then once we found those data points, we averaged their labels and we said, okay, that's probably going to be the label for our new prediction point. That was an algorithm that just made sense, in my opinion, at least. The same is not quite true of linear regression. You're going to see that there's a lot more math going on with this algorithm, and sometimes that math is not going to be super crystal clear. But I'm going to do my best to make sure that it's at least somewhat obvious or at least somewhat clear as to how everything is working. All right, so let's take a quick pause right here. We'll come back to the next section and start talking about how linear regression works. In the last section, we started talking about linear regression. We're now going to continue and discuss some of the inner workings of this thing. This is just going to be a little bit of a high-level discussion. We're going to start diving into some more mathy topics very shortly. So first things first, what's the goal of linear regression? With linear regression, we are trying to figure out an equation to relate some independent variable to a variable that we're trying to predict, usually referred to as the dependent variable. So in this case, we might try to figure out some type of mathematical equation to say, given some particular square foot lot size, I predict our house price to be blah, or whatever it might be. And this might sound like a very similar operation to what we were doing before with k-nearest neighbor. And in truth, absolutely yes, totally is. Every single algorithm that we look at, that is a regression type algorithm, is always going to have the same goal. We're going to have some input data, and we're going to use the algorithm to predict some output data. Every regression algorithm is going to work in that similar fashion. So everything we do is going to be very similar to k-nearest neighbor in purpose at least, but we're going to use some very different methods to get at this final answer or to figure out what the relationship between the independent variable and dependent variable is. Now, very much like k-nearest neighbor, we are not restricted to having just one independent variable. We can very easily have multiple independent variables, and we'll take a look at that in just a second. First, I want to show you a quick example of what the output of all of our work is going to be. So in this chart right here, I've got my square foot lot size, and then on the vertical axis is my price. So again, I'm trying to predict my price given a square foot lot size. The goal of linear regression is going to be to predict or create a relationship between those variables that takes the form of an equation that looks like this. So in particular, what we're really trying to do is figure out what these numbers are, like the 200 here and the 3000 over here. We want to figure out some coefficients, as we might refer to those, that are going to somehow take our lot size value and turn that into a prediction for our price. This equation is represented by a line that might be used to kind of predict or fit between all of our different data points. many things that we're going to do around linear regression is going to revolve around making nice looking charts like this one right here, so we can kind of visually inspect our data and figure out whether or not the relationship that we're trying to predict makes sense or not. All right, so now, like I said, with linear regression, we are not limited to just one independent variable and one dependent variable. We can have as many, within reason of course, independent variables as you might want to have. And so just a moment ago, as we saw with our other problem, k nearest neighbor, we might have a variety of different independent variables or features that we use to try to figure out or predict some label or dependent variable. Now, the instant that I start showing you this chart right here, I don't know about you, but if you have a background in like Excel or Google spreadsheets or the Numbers app, you might be immediately asking yourself, what's the point of this algorithm? Like, how is this any different than plugging some data into a spreadsheet and then using that spreadsheet to plot a chart and then add a trend line to it? Well, really quickly, let's go through that operation. So here is a Google spreadsheet. I've got some lot sizes and house prices. So I'm going to select all that data, and I'm going to insert a chart. And then on this chart, I'm going to add on a trend line, and I'll put the equation on here. Use equation. There we go. So there we go. We just basically did the same thing as linear regression. We plotted out some independent variable and dependent variable, and then we found a mathematical relationship between the two. So again, you might be thinking, why are we spending so much time to reinvent what has essentially already been done for us and is very easily accessible in the form of any common spreadsheet program? Well, the big difference is that with the version of linear regression that we are going to put together, you can very easily have as many different independent variables as you want, which is not true of many similar spreadsheet applications. In the vast majority of spreadsheet applications, like Google Sheets right here, you are limited to relating a single independent variable and a single dependent variable. Like I said, we can use linear regression to relate an arbitrary number of different features to a single output. So that's why we're going to go through this big exercise. We have a tremendous amount more power to look at many more features and relate them all to our single output. All right, so with that in mind, let's take one more quick break, and then we're going to start to discuss our strategy for putting this algorithm together in the next section. In this section, we're going to start laying out the basics of our approach to solving linear regression problems. We have a lot to talk about, so let's get to it. Now, the first thing I want you to understand is that there are many different approaches to solving linear regression problems. If you do a Google search right now, you're going to see references to methods called ordinary least squares, and generalized least squares, and many other algorithms. So there are many different ways of solving linear regression problems. We are going to use a very particular approach referred to as gradient descent. The reason that we are using gradient descent is that it is an approach that is used in many other very complicated machine learning algorithms. One of the easiest ways to learn gradient descent is by applying it to linear regression. So essentially, the reason we're going to take this approach is that it's going to be a very relatively easy way for you to understand gradient descent. And once you understand it, you can then apply that knowledge to more complicated problems down the road. All right, so with that in mind, let's take a look at how we're going to do this. Now, in this video, I'm going to lay out a couple of steps, some framework or some groundwork to help you understand how gradient descent works. I'm not going to just come out and tell you exactly how it works right now. I'm going to lay out a couple steps, and then we'll dive into it more in the next 1 or 2 videos. So with that in mind, let's take a look at this little example right here. I want you to imagine that we are trying to develop a mathematical relationship between the square foot lot size of a property and the price paid for it. So we might abbreviate the square foot lot size as a variable x, and we might abbreviate the price as a variable y. On this chart, I've laid out a couple of existing data points. And so down here at the very far left-hand side, we've got a data point of 800 square feet. That cost $200,000. And then up here at the top end, 1250 square feet cost $259,000. So I want to figure out a way, some type of mathematical relation, or an equation, really, to somehow guess at the price of a property based on its square foot lot size. I'm going to take a really bad guess right now. I'm just going to make a guess. It's going to be awful. It's going to be a really bad guess at relating these two together, but we're going to take a look at this really bad guess and understand what this bad guess really means. Okay, so here's my bad guess. I'm going to guess that to relate or to guess the price of a property, we are going to use an equation of 0 times our lot size square footage plus 1. Now we're working in units here of thousands of dollars. So the one right here is really like $1,000, like so. But we're going to, again, use units of thousands of dollars. Now, without a doubt, this is a very bad guess at the relationship between my square foot lot size and my price. The red line that you see right here is the line of this equation. So no matter what the square foot lot size is, we are always guessing $1,000. So it doesn't matter if you've got 1,350 square feet, or if you have 800 square feet, I'm always going to say your property is worth $1,000. Now, if I take that equation, which we might simplify to look like this right here, remember y is equal to the price, and x is the square foot lot size, we would end up with a table that looks like this. So this says that if we have 800 square feet, I would guess that your property is worth $1,000, when in reality, it is worth $200,000. And if your property has 1,350 square feet, I would guess $1,000, when in reality it's worth $262. All right, so at this point, we've definitely established it's an awful guess, no two ways about it. But one thing I want to point out here is that you and I are kind of only able to easily say that this is a bad guess because we have eyeballs. And we can look at this chart right here and say, this line right here, this equation does not go through our data points one bit. It's a bad guess because we can look at this chart and say, yep, this is not good. Now, who doesn't have eyeballs? Your computer. Your computer does not have eyeballs. Your computer cannot just somehow look at this chart right here and understand that this is a bad guess. Even if you give your computer this table right here, it's still kind of hard to get your computer to understand that this is a bad guess for the relationship. So I'm kind of curious, is there some equation that we could use? Some formula that we could run that could somehow tell our computer exactly how bad a guess this is? Well, there actually is. So there is an equation called the mean squared error equation. This is the equation right here. I know it looks a little bit nasty with some special syntax in here. We'll walk through it in just a second. This equation essentially produces a value that tells you how wrong or how bad your guess at that equation is. So we could use this equation right here to get some output or some metric to tell our computer, hey computer, just so you know, this is a really bad guess. Like this equation right here, no good whatsoever. Let's try running this equation with this mean squared error calculation with our guess of that relationship, and we're going to see exactly how to calculate the mean squared error and understand what that number really means. Now, one thing I want you to understand is that this symbol right here is a summation symbol. It essentially means take every one of your guesses and every one of your actual values, find the difference between the two, square the result, and then sum them all together. That's all this symbol is really saying right here. Now, the other thing that I want to point out is that guess minus actual right here is essentially this dotted line distance. So the dotted line distance at the very top is the actual value, and then the line down here that it goes to is the value that we guessed. So this dotted line right here would have a length of 245 minus 1 because our guess is 1. So we were essentially 244 units or $244,000 wrong. And that's what this line right here is supposed to represent. And that's what this little equation or the inside right here is attempting to calculate. All right, so if we run that equation with our data, this is what it looks like. So that summation symbol has gone away. I've taken every one of our data points, both my guess and the actual value. I find the difference between them, and then I square the result. I then repeat that for every other data point that I have, and I add them all together. And then finally, the n right here is the number of data points that we have. So in our case, we have 6 data points. So the end result is the 360,000 for the numerator divided by 6 because we have the 6 data points. And the output from the entire equation is 60,132. That is the value of our mean squared error. Now you might be curious, okay, 60,000, like 60,000 what? What are the units to this? What does that number actually mean? Well, it turns out that running this mean squared error equation by itself in isolation is not actually that useful. We cannot actually just look at this number right here and say very easily that this is a good guess or this is a bad guess. So if we have just that number by itself, you really cannot say, oh, Stephen, this guess of this equation right here was awful. In order to be able to quantify this thing and say 60,000 is good or bad, we have to run the mean squared error equation again with some other guess. So we have to come up with a new equation for the relationship between those variables. We have to build out this table again, and we have to run that mean squared error equation again. And once we have a second value for mean squared error, then we can say whether or not this thing was good. So in other words, to phrase that another way, the mean squared error is really only producing a value that we can compare in relation to other values to say whether or not a particular guess is good or not. So with that in mind, let's try making another guess at our equation. So a new equation down here, and then we will build this table up again, run the mean squared error again, and then we'll take a look at the output and kind of walk away with some interesting facts about the output. All right, so here's my new guess. My new guess is an equation of 0x plus 200. So that equation essentially means no matter what the square footage is, I'm always going to guess that your house is worth $200,000. Now, technically, this line should now be like right here and intersect that first line, but you get the idea. I'm just going to put it down here. So now if we try to build up this table again with this new equation, you'll see that this time around, we're doing a little bit better. So if we have 800 square feet, I'm going to guess $200,000, when in reality, it was worth $200,000. So for that first data point, we are dead on. And if we were to find that dotted line distance right there, it would actually be equal to 0. The distance between our guess and the actual value is 0. And so for the first term of the mean squared error equation, we would have 0. Now, as we go through, we can calculate more of these values. We go all the way down to the end. For 1350 square feet, we guess $200,000, and it's actually 262. So our line is still, or our relationship is still not as good as it could be, but it's definitely better than it was before. So given that it's better than it was before, let's try running that mean squared error equation again and seeing what number we come up with. Okay, so in this diagram, I've got our previous guess right here. So this is the equation that we had just ran a second ago where we came up with 60,000, and we've got the y is 0x plus 1. And then down here is our new guess. So with a new guess, I ran all the numbers right here, found all the distances, squared them, added them together, and then divided by 6. And then this time around, I ended up with 4287. So now that we have calculated mean square error twice, it kind of gives us a benchmark or a relationship between the two. We are now able to say that because this value right here is lower than this value up here, this new guess that we just made must be significantly better than the original guess that we made. So essentially, the smaller a mean squared error that we get, the better our guess is. Now that's kind of an interesting thing to think about. You might be thinking, okay, if we could ever get our mean squared error down to like 0, then we must have like a perfect guess. Well, one quick thing I want to mention is that even if we come up with a extremely good guess here, like, look at this line right here, it looks like it's probably as good a guess as we could possibly get with a straight line. Notice how there's still some distances in there. And so we would definitely still have a mean squared error not equal to 0. And so it's unlikely in most scenarios that your mean squared error equation is going to be exactly equal to 0. But we can at least say that the lower our mean squared error is, the more correct our guess is. So if we could find a very low value of mean squared error, we would have a very good equation or a very good guess. Okay, so at this point, I want to pause the video here in just a second, or I kind of want to stop talking or cover any new topic, and I want to review what we discussed in this video so far. So we are trying to predict or guess at an equation of this form right here. I've got m to represent whatever we are multiplying the lot size by, and b to represent the number that we are adding on. And so we're essentially saying that the better job we do of guessing values of m and b, the smaller that MSE or mean squared error equation is going to be. Put another way, this is And the last note I want to leave here is that M and B, like our guess at that equation, is going to be as correct as they possibly can be when MSE, or the mean squared error, is as low as possible. Remember, we just made a new random guess, and when we made that random guess, we saw that MSE value drop significantly. So as we get closer and closer to the correct guess, the mean squared error is going to be lower and lower and lower. All right, so I want to leave this discussion right there, and I just want you to remember that the better our guess is, the lower the mean squared error value is going to be. So let's take a pause right here, and we're going to continue in the next video. In the last section, we started talking about linear regression. At the very end of this section, we arrive at a very important fact. We realized that we will have a very good guess for M and B when we get our MSE value as low as possible. In other words, if we could find out some way to get a very low value of MSE, that means that we have a very good guess for M and B. Now, in this section, we're going to start to investigate one possible way of doing that. One possible way of guessing values of M and B to get low values of MSE. Now, just to be clear, in this section, we're not going to be discussing gradient descent just yet. I'm going to show you one possible way that you might think that you could solve this problem, and I'm going to tell you why it's not going to quite work out. And giving you this knowledge is going to help you understand how gradient descent works a little bit more. So, like I said previously, still laying a little bit of foundation, a little bit of groundwork to eventually understand gradient descent. Okay, so let's get to it. So in this section, I want to just kind of temporarily forget this value of M over here that we're trying to calculate to build up this relationship. And I want to focus on just guessing B for a minute. As we have already, as I've said, oh yeah, I've got guesses of like 1 and 200 for those values of B. So again, let's just focus on B for a moment. All right, so here's one possible way that we could guess at a very good value or approximation for B. We might try to guess different values of B. So like, let's say I'm going to guess a value of B of 100, and then we'll run that MSE equation, get some output like we just did for 100, and we came up with a value of 60,000. And then we can chart that or plot it on a graph like this right here. And then we can start guessing different values of B. Like let's say over here, maybe I guess 200. And then we run that MSE thing again, and then we'll chart it. And as you saw, we had gotten a value of 4,000 for MSE. And then we can keep on repeating this process over and over. Like, let's say maybe we guess at 100 right there, and we end up with a MSE value of, I don't know, let's say just 30,000. I'm just going to guess that value. I'm going to say maybe 30,000. So as you can kind of see right here, it's almost forming a line of sorts. We're almost forming a line. And maybe this line is going to have some minimum point, some minimum value of MSE. So at that minimum value, like maybe right here or so, that would be our optimal value of B. Because remember, the lower the MSE, the better our guess is. Now, I took the liberty of putting together a quick spreadsheet to show this. Now, in this spreadsheet, there's a lot of data, but on the left-hand side up here is our lot size and our house pricing data. And then in this column right here, I have a bunch of different guesses for the value of B. And then I calculated MSE for each of those different guesses. You'll recognize, hopefully, this first entry right here. Let me zoom in a little bit. So for a guess of 1, I got an MSE of 60,000, which is what we had calculated in the last section. So then I basically just incremented B by 10 in a bunch of different steps, and then for each of these different values of B, I calculated the MSE value. And then I plotted it in this chart right here. So again, as you can see, as we start to increment B, so we're guessing B of 0, then B of 100, B of 200, B of 300, we have these different values of MSE. And when we start to get to this minimum point right here, that means that we've got as good a guess as we can possibly have for our value of B. All right, so I know at this point some of this stuff seems a little bit esoteric. As a quick reminder, I just want to remind you our entire goal right now is to try to get a good value of B and M so that we've got a good relationship between our lot size and our house price. So what I'm saying with this chart right here is that we have a error metric, or we have some metric that we can use to evaluate how good or how bad our guess is. And if we have a very good guess, this value of MSE is going to be very low. So it stands to reason that if I get a very low point on this chart, that means that my guess for the value b is very good. Now, it might seem like this would be a very good solution. It might seem like, oh, okay, we can use this approach right here of just guessing values of b to get some minimum value of MSE. And that could be how we do this linear regression problem. It might seem like that, but as I said earlier, this is not going to be an approach that actually works in the long run. So let me tell you a little bit why. Let's first begin by taking a look at a little code snippet that I put together. So this would be a code snippet that you might run to guess a value of b using this approach that we just discussed. So I put together an array up here called MSE history. So that's going to record all the different values of MSE for the different values of b that we guess. We can then start off b at 0, we'll go up to a b of 500, and we'll increment b by 1 each time. And then for each different value of b, we'll essentially calculate our MSE value, and we'll push it into that history array. So then after we guess a whole bunch of different values of b, we can then run some, this code right here doesn't quite work, but I bet you can guess what it does, or what the intent here is. We can look through that MSE history array, we can find the minimum value of MSE inside of it, and then use the associated b value. So again, it looks like this might be something that could kind of work, but again, doesn't quite work the way you expect. Let me tell you why. All right, so quick diagram over here. Okay, so issues with this approach. Here's why it's not going to work. First off, we don't really know what the possible range of b is. So we need to write a for loop like this at some point in time if we want to take this approach. And you'll notice that I guessed a starting value of 0 and then a final value of 500. But that was just a total guess. It might turn out that the true best value of b is actually like negative 5,000. And if that was the case, my for loop right here would not try to guess a b of negative 5,000. So it'd be kind of hard for us to write a for loop that correctly iterates over the range of possible values that b could be. Now, even given that, we also don't know a correct step size for incrementing b. So in this for loop right here, I was incrementing b by 1 each time. And back in this chart over here, you'll notice I was incrementing b by 10 each time. If you go down to the minimum value of MSE right here, we see that it was 241. So that's kind of saying that like the best possible guess I could get was 241. Well, what's to say that like 242 isn't actually a better guess? Let's try that. If I do 242, you'll see that that goes down to 605. And so that indicates that 242 is a better guess than 241. It might even be the case that like 242.5 is a better guess. Well, it looks like it wasn't quite, but let's try like say 242.25. Okay, that's still a little bit off, but I think you probably get the idea here. It turns out that as I start to increment or change that value of b, I can't just assume that increments of 10 is going to lead to the best guess. It might be that the absolute best guess I could possibly do would be like 242.00001. And so if I wanted to actually guess at that value of b, I would have to write this for loop over here to say, rather than incrementing b by 1 each time, do b plus like 0.0001 like so. And so I'd end up having to run this for loop an extraordinary large number of times to guess the correct or most correct value of b. Now, one last thing to keep in mind here, and the reason that this approach does not quite work out so well, is that if we start to add in more features or more variables that we're trying to guess, the computational demands start to get absolutely extreme. So remember, I had said at the start of this section that we're just going to be talking about b right here, but we also have to try to calculate that value of m. And the other thing to keep in mind is that the value of m and b are going to kind of like play off each other more or less. So we can't just consider m and b separately when trying to guess them. We have to consider all different possible combinations of m and b. And so the code for that might look a little bit like this right here. We would have a double nested for loop. We would have to consider all different possible combinations of m and b together. We would have to run that MSE equation for every possible value, and then we would have to come up with a good guess for b and a good guess for m by looking at the minimum value of MSE. And so as we start to add in more variables that we're trying to guess, we start to get into tremendous computational demands. Okay, so that is why it might seem like this would be a good approach, but in effect, just guessing at values of m and b does not quite work out. However, I still kind of feel like we've got something here. It still kind of feels like using this knowledge that MSE being as low as possible is going to give us the correct value of m and b, it still feels like maybe there's some approach here, some clever approach that we could take to try to minimize that value of MSE to guess at our value of m and b. So clearly, as we've established in this section, just iterating through possible values of m and b does not work. We can't just have some really long for loop that's going to iterate through all possible values and then find that MSE value and then find the minimum amount of MSE. That doesn't work. But maybe there's some way that we could very cleverly pick and choose values of m and b in a very intelligent fashion, and then evaluate our MSE metric and say whether or not we are getting a good guess or a bad guess. And that's where this entire idea of gradient descent starts to come into play. So let's take a quick pause right here. We're going to come back in the next section and start talking about gradient descent and one other very closely related topic. So I'll see you in just a minute. In the last section, we spoke about how brute forcing or iterating through all possible values of b was not going to be a good solution. The reason for that is that we would have some pretty crazy high computational demands. However, it still feels like guessing different values of b and then evaluating the MSE metric until we get a very low value of MSE is a good approach. So it feels like there's something to this, but clearly we cannot just brute force this or iterate through all values of b. So in this section, we're going to take a look at this chart and really pull it apart piece by piece. We're going to figure out whether or not there's some way that we can make a more educated guess at the value of b. If there's some way that we could avoid having to look at every single possible of b, this approach might work out pretty well. So let's get to it. All right. So first off, I'm going to take that same chart we were just looking at. Remember, as a quick reminder, the MSE metric over here is telling us whether or not we have a good guess or a bad guess. So the higher the MSE is, the worse our guess is. The lower it is, the better our guess is. You'll notice that on this chart right here, I've taken all of our data points, or a couple of imaginary data points for that matter, and I've drawn a trend line through them. And so this trend line looks like a parabola of sorts, or kind of a valley or a trough. Let's make a quick assumption here. Let's assume that anytime we make a chart of guesses of b versus the MSE up here, let's assume that this valley is always going to be present. Maybe some of the numbers on here change, like maybe instead of b of 241 being optimal, maybe if we have a totally different data set, maybe we have an optimal b of like negative 5,000. But at the end of the day, let's just assume that this trend line is going to always more or less look like this. So with that in mind, I'm going to take these original data points and I'm going to delete them. I want to just take a closer look at that trend line by itself. Now you'll notice that as we get very bad guesses of b, this trend line starts to get more and more vertical. But when our b is getting a little bit more correct, like towards this somewhat optimal value of 241, it looks like the line or the trend line starts to get flatter and flatter. So with that observation in mind, I want to show you a couple more charts that are going to kind of break this thing down piece by piece. So I want you to imagine that I show you just a tiny, tiny, tiny portion of this chart, or the trend line for it. If I showed you just this tiny piece right here, and you saw that the line was mostly vertical, and I asked you, hey, do you think that this trend line right here represents a good guess or a bad guess? You'd probably say, well, that trend line looks like it's vertical. And because it's almost vertical, that means that we probably have a pretty bad guess. Remember, the more vertical that line is, the worse a guess we have. And as that line gets more and more flat, the better a guess we have. So if I show you just that tiny, almost vertical portion, you would say, yeah, that's probably part of a trend line, and that portion of the trend line probably means that you have a poor guess. Now let's try doing another guess here. Let's say that we take another guess a little bit closer to optimal. And we now notice, if I show you just this tiny portion of the trend line, that it looks a little bit more flat. And so because it's a little bit more flat, you'd probably say, oh yeah, you know what? That actually looks like we're almost correct. It looks like we're closer to the optimal guess. And so the takeaway here is that the steepness of that line tells us how far away from the optimal guess we are. And as we start to get to the optimal guess, that trend line goes almost flat. So we can say that when the line is flat, we probably have our optimal guess. Now, the last thing I want to point out here is that the direction in which this line is sloping, if we look at just a tiny portion of the line, the direction that it's sloping kind of tells us whether or not the optimal guess is to the right or to the left. And so when the trend line is sloping downwards towards the right, it means that our optimal guess is probably somewhere towards the right-hand side. But if we have a trend line where it's sloping downwards to the left, it means that our optimal guess is further to the left. So it looks like by just taking a look at this trend line and the shape of the trend line, or the slope of it, we can kind of get a better idea of how far away we are from the optimal guess. So clearly, knowing the value of MSE at any particular location is not super useful. Remember, the very first time we calculated that MSE value, like back over here, or was it like right here? When we first calculated this and I showed you that number 60,000, that was not a super useful number to just have in isolation. And I had said, oh yeah, this number only starts to make sense when you run MSE multiple times or have some other metric to compare it against. And so it's very clear that just knowing the value of MSE at any given location is not super useful. But if we could somehow figure out just the slope or the rate of change of this trend line, then we can have a much better tool to get at our optimal value of b. So if we had some way of guessing or calculating the slope of this trend line at any given location, we would probably have a better tool of guessing b. Because again, if we see an almost vertical line, that means we're very far away. If we see a almost flat line, that means that we're almost at our exact optimal guess. So we've now made a couple observations about this trend line that I added into that plot. But we don't really have a tool just yet of actually calculating a slope or just a tiny piece of this trend line. Let's take a quick pause right here, and when we come back to the next section, I'm going to show you a tool that we can use, or an equation of sorts that we can use, to determine the slope of this MSE line at any given location. So quick pause, and I'll see you in just a minute. In the last section, we spoke about how this chart that relates different guesses of b to our MSE value is actually sharing us a lot of information. If we look at the slope of an imaginary trend line in here, we could use that slope to determine whether or not the true value of b is off to the right or further off to the left. So this slope is how we're going to be able to make educated guesses of values of b and avoid having to just iterate through a continuous series of values for b. Now, the one awkward thing about this is that, if you recall just a second ago, when I initially put the trend line on here, I just kind of arbitrarily drew that trend line through a collection of points. When we're actually going through this problem of solving all this stuff or evaluating values of b versus MSE, we don't have this trend line. The trend line doesn't exist. If we wanted to calculate the trend line, we would have to calculate MSE for a bunch of different values of b and then attempt to build the trend line out of that, which is something that we definitely don't want to do. So we need to have some way or some method of determining the slope or the rate of change of MSE for any given guess at this value of b. To do so, we're going to take advantage of a little technique or a little method, little tool from the field of calculus. Now, at this point, you might be thinking, oh my gosh, really calculus out of left field, just like that? Well, yes, we're going to have to learn just a tiny bit of calculus here. Now, if you've never taken a course or have no background in calculus, that's totally fine. I'm going to go through a couple of very basic steps to show you what is going on. So let's get to it. Now, as we start to go through this example of calculus, we're going to completely forget all this linear regression stuff for just a minute. And we're going to just focus on calculus 100% for a couple minutes here. Okay, so again, we're going to forget about all that linear regression stuff. Let's just focus on this problem right here. So let's imagine that we have an equation, y equals x squared plus 5. If we were to plot this equation right here, we would end up with a parabola that looks a little something like this. And so if you take a look at that, yeah, it actually looks pretty similar to the parabola we were working with just a second ago. Now, one thing that we can do with that equation is do something or an operation on it called taking the derivative. When we take the derivative on an equation, we get a new equation that can be used to tell us the slope of the original equation at any location. So what you see here is our original equation. That's this thing right here. We did an operation on it called taking the derivative. The derivative of this blue equation over here is 2 times x. we can use this equation right here to determine the slope at any point of x in this equation. Now, we're not going to talk about exactly how we took the derivative here. If you want to learn how to take a derivative, you can do a quick Google search for something called the power rule, or alternatively, there's a nice little website called wolframalpha.com. You can type in here derivative x squared plus 5, and that will take the derivative for you. So in this case, it is in fact 2x. Okay, so now that we've got this derivative right here of the original equation, let's take a look at it and try to figure out what's exactly going on with this derivative. Okay, so in this chart right here, I've plotted both our original equation and the derivative over here on the right-hand side. So this line right here, a straight, simple line, can be used to tell us what the slope of this line is at any given point. Let's take a look at a couple of examples of how we would do that. Okay, so I've labeled a couple of points in here. Let's imagine for a second that we want to get the slope of this original equation at x equals -5. So when x equals -5, we would have a y value of 5 squared, which is 25, plus 5 is 30. So up here, this would be -5, 30, so 30y. I want to find the slope of exactly that point right there. Clearly, the slope is going like downwards to the right, but I want to find some numeric representation of what that slope is. So to find out what the slope would be, I would take that -5 and I would plug it into this equation over here. 2 times -5 is -10. And so the slope at that point right there is equal to -10. Another way of figuring that out would be to look at this chart over here. This chart, this line, tells us the value or the slope on the y-axis for any value x. So if I want to find the slope of this line over here at -5, I would go to -5x, I would go down to my line, and the y value for that is -10. So the slope up here must be -10. In general, we can say that all the negative values of the derivative, so this -4 and -10 right here, means that the original line is sloping downwards to the right. So take a look. If I have -5, I get a slope of -10. That's that point right there. That means it's sloping downwards to the right. And if I have an x of -2, I get a slope of -4. So that means at -2 right here, my slope is -4, which means it's going downwards to the right. But because it's -4 as opposed to -10, that means that it's slightly less steep than it was before. So in other words, the slope right here is slightly less than the slope up here. Now, if we plug in values of x that lead to positive slope values, that means that our original equation over here must be going up. So in other words, if I take 2 and plug it into my derivative equation over here, that would give me 4. That means that the slope right here is +4. And likewise up here, it'd be +10. Now, the last thing to consider is the slope right here at the very center. So at the very center, which we refer to as the vertex, the slope is essentially 0. We can tell that from the derivative over here, because if we put in 2 times 0, we get 0 back. And that means that our slope of the original line is 0. So what does all this tell us? Well, it means if we can take the derivative of some arbitrary equation, we get a new equation that we can use to determine the slope at any arbitrary point. So that means that when we start thinking back over here to this issue with our value of b and MSE, if we take the equation that relates b to MSE and take the derivative of it, we can then use that new equation to predict the slope at any of these given arbitrary points that we want to figure out the slope at. Okay, that's a lot to digest, so let's take a quick pause right here. We're going to come back to the next section, and we're going to go through an example of how we would take the derivative of the relationship between b and MSE, and then we're going to sit down with a spreadsheet and actually walk through this process with some real numbers, so we can get out of the realm of like theoretical stuff and actually see some hard facts. So, quick pause, and I'll see you in a minute. In the last section, we spoke about a technique of taking a derivative of an equation. When we take the derivative of an equation, we get a new equation that can be used to calculate the derivative at any arbitrary value of x in the original one. And so that's going to be used with this problem that we were discussing over here. Remember, we do not have an actual trend line that relates our values or our guesses of b to the mean squared error. All we have is a simple equation that we can use to predict the value of MSE or calculate the value of MSE at some particular point. So if we take the derivative of that equation, we will have a new equation that can be used to determine the slope at any given value of b. Let's take a look at an example of how that's going to be done. Okay, so remember, this is an equation, mean squared error, that tells us how wrong our guess for the value of b is. So we're going to take the derivative of this equation right here, and it's going to give us a new equation that can be used to calculate the slope at any arbitrary value of b. And we can use that slope to get a signal on whether we need to increment our value of b or whether we need to decrement it or make it some lesser value. Now, when you take a look at this equation right here, you'll notice that the only big change to it is that we drop this squared term. So in total, we're going to take some guess of b, so like a fixed value, like 0, 100, 200, whatever our guess is, and we're going to subtract each individual actual house price value. And then we're going to sum those all together, multiply by 2, and then divide by the number of data points we have, which for the running example that we've been using has been 6. Now, one very important thing I want to point out here is that this equation is assuming that we have a m of 0. So remember, the entire goal of what we're trying to do right now is relate a lot size to an actual house price. And as we said a couple of videos ago, we're just going to assume that m is always equal to 0 right now, just because it makes understanding this gradient descent stuff a little bit easier. The only reason I'm telling you this and kind of making a big deal out of it is I just want you to understand that after we go through one run of the gradient descent algorithm and understand how it works, we're going to come back and do a little bit of a revision to add in this m term as well. Okay, so we now have enough knowledge to actually go through our first iteration of the gradient descent algorithm, because we have this equation that we can use to take the derivative or get the slope at any particular value of b. So let's talk about how the gradient descent algorithm works, and then we're going to write it out more or less from scratch in a little Excel spreadsheet, and you'll be able to see all the calculations done right in front of you. All right, so here we go. Gradient descent, long time coming, a couple of videos to get to this point. So here's what we're going to do. We're going to pick some arbitrary starting value of b. Just b, again, we're just totally forgetting about that m value for right now. So we might pick a starting value of 0, 100, 200, whatever you want to do. We're then going to use that derivative equation to calculate the slope of MSB or MSE using that chosen value of b. We're then going to look at that value of the slope. If the slope is very, very small, it means that we have a value of b that is appropriate and probably optimal. Why is that? Remember, if we have a slope that is very flat, or essentially equal to 0, it means that we have an optimal guess. So if we calculate our slope using that derivative, and it's very close to 0, that means that we have a good value of b. And back over here. Now after that, if we don't have a slope that is very small, we are going to multiply the slope by an arbitrary number called a learning rate. And we'll talk a ton about what this learning rate is in just a second. We'll then take the result from that. We're going to subtract it from our initial guess of b, and then we're going to repeat this entire process over again. So we're going to keep updating this value of b over and over and over again until we get a value of our slope that is very, very small. Okay, so this is the overall outline. Now, it might either seem really simple or really complicated. I don't know which it is for you. But at any rate, let's walk through an example of gradient descent using some very real numbers, and you're going to see how this thing works right in front of you. Now, to go through this initial example, I'm going to put some numbers into a spreadsheet. If you want to go through this process with me, I've put a link to the spreadsheet that I'm going to use here on the screen. So you can go to this link, and you'll see a spreadsheet like this pop up. So I'm going to have a couple of different tabs in the spreadsheet. I'm going to leave sheet 1 in this initial state right here so you can follow me along in this video and put in the same numbers I'm putting in and really see how this thing is progressing. And then I'm going to do my work here on sheet number 2. So if you want to see the completed work, go to sheet number 2. Otherwise, if you want to work along with me, start on sheet 1. Okay, so on sheet 2, I've got our data points up here on the top left-hand side. Then right here, I have an initial guess for my value of b. I have an initial guess of 0 in this case. And then in the cell to the right of it, I have calculated the slope for MSE at a b value of 0. So this is that derivative equation right here. I already typed it in for us just to save a little bit of time. So now that we have that slope equation and we've calculated the slope at a value of b, we need to figure out how much to adjust that value of b by. Remember, to get that adjusted value of b, we're going to multiply the slope by an arbitrary small value called a learning rate. And I have an example learning rate over here on the left-hand side. Again, we'll talk about the purpose of this thing in just a second. So I'm going to take my slope and I'm going to multiply it by my learning rate, like so. Now, when you enter the slope, make sure that you make this cell B10 over here an absolute reference. You can do that by putting in $B, $10. I know it's really small. Oh, right there. So $B, $10. That's going to make that into an absolute reference. So as we start to drag this cell around, it's still going to refer back to that 0.001. Okay. So we now have a number here that tells us how much to adjust b by. It says negative 0.49. That means that we want to take our initial value of b right here and subtract negative 0.49 from it. Let's do that right now, and then we'll talk about what this first row right here means. So I'm going to say right underneath this initial value of b, I'm going to say equals my current guess of b, so that's going to be this cell right above, minus this cell over here, where we just calculated how much to adjust b by. So I've now got a new guess of b of 0.49. Now before we go through any additional steps here, I want to very quickly talk about this first row right here. So at this point, our initial guess for our value of b is 0. Now here's our original chart for relating MSE and b. We had said that if we guess a value of 0, our MSE is going to be about 60,000. And as you can see, the line is going downwards towards the bottom right here. So we've got a negative slope. That means that our optimal value of b must be greater than 0. And so as you can see, after we went through this initial step of the gradient descent algorithm, we now have a slightly larger value of b. Now we're going to take this updated value of b, we're going to calculate the slope again, we're going to calculate this adjustment factor again, and then repeat the whole same process over and over and over again until our calculated slope value is very small. So to calculate the slope for this next step, I'm just going to select the cell right here. I'm going to drag it down by 1. So now my new slope is negative 489. So that still means that we're going down to the bottom right, but it means that the slope is slightly less than it was before. And that means that my guess for b is slightly more correct than it was during the original step. Now I'm going to select the cell over here. I'm going to drag it down by 1. And that's going to give me the new amount that I'm going to adjust b by. And so now to update the value of b, I'm just going to drag this cell again. And essentially, we just have to repeat the same process of dragging these cells down and down and down. So I'm going to select this row right here, and I'm just going to drag down this little grabby thing right here a couple of rows, like so. Okay, so we have now gone through a couple steps of the gradient descent algorithm, and we now have a guess value of b of 6.29. Now it's very clear that we are incrementing our value of b, and we are getting towards our optimal value, which we had previously guessed was around like 245 or so. But we're doing that increment at a very slow rate. We are updating b in very, very small steps. We can use this learning rate over here to adjust how quickly our algorithm is going to increment this value of b, and how quickly or how many steps it takes to eventually get at our optimal value. So I'm going to update the learning rate over here to be 0.01. And now when I do so, you'll see that my values of b are now incrementing much more quickly. The reason that they're incrementing much more quickly is, remember, this learning rate is being used to modify how much we are adjusting b by each and every time. I'm going to now try incrementing the learning rate a little bit more. I'm going to go to 0.1. And now you'll see that I am very quickly getting towards that optimal value of b of around 245 or so. Now I'm going to drag down on these rows a couple more to do a couple more iterations of gradient descent. And now you'll see that the rate at which my number or my predicted value of b is changing is very much slowing down. Initially, we modified the value of b, or this initial guess, by 49 to 88 to 119. Big jumps in b. But as we get closer and closer towards our optimal value, it starts to slow down a lot, and we are doing very small updates. So we go from 244.4 to 244.5, 244.6. So I'm going to go a couple more drag down rows here. And as you can see, it's just going to get closer and closer to what is probably our optimal solution or our optimal guess for b of about 245. One other thing we could do to get this solution to converge a little bit more quickly is to further adjust our learning rate. So I'm going to try out a learning rate of 0.4. Now, when I do so, we can see that we get to our optimal value of b very, very quickly. So in just a couple of steps, I have gone from an initial guess of 0 to my optimal guess of 245. So this algorithm is telling me that the optimal value of b is exactly the number 245. Okay, so that is how the gradient descent algorithm works. It required a ton of buildup, but essentially all we're really doing here is guessing a value of b. We then calculate the slope of that MSE function to figure out how far away from the optimal we are. And then we use that slope as a signal to tell us how much we need to adjust b by. Now at this point, I'm sure that one of the most mysterious parts around this is why we are taking that slope value and subtracting it from b. And in addition, what the purpose of that learning value or learning rate is. So let's take a quick pause right here. When we come back to the next section, we're going to look at a couple more diagrams that are going to help you understand what's really going on with this step right here and why the overall gradient descent algorithm works. So I'll see you in just a minute. In the last section, we finally went through the gradient descent algorithm. I want to very quickly walk through what we did one more time and do a quick overall review of everything that we've learned up to this point. Understanding this gradient descent algorithm is kind of just a little bit important because, like I said, it's something that we're going to be using on some more advanced topics down the road. So let's do a quick review here. All right, so here's a review of everything that we've covered in the last couple of videos. The first thing that we did was we realized that we wanted to find an equation that somehow relates an independent variable and a dependent variable. So in our case, we had some square foot lot sizes. We wanted to find some arbitrary variables. We just gave the names of m and b that could somehow take our square foot lot size and give us a reasonable prediction of the house price. Now we said that we were going to set m equal to 0 and just completely ignore it, just to make this process of learning gradient descent a little bit easier. The next thing we did was attempt to guess at various values of b. Whenever we guess at a value of b, we could use that mean squared error equation to figure out exactly how wrong we were. It gave us some big random large number that supposedly would tell us, hey, you're this amount wrong. We could then run the MSE equation multiple times and be told throughout multiple guesses of b which one was better than another. Next, the slope, or the rate of change of MSE. So as we put in various values of b, we would see that there was distinct changes between each one. So we could use that slope to figure out whether our value of b was too low or too high. Remember, back at this chart right here, we had said that if we had a negative slope, or a slope that is going down to the right, then that must mean that the optimal value of b must be greater than whatever our current guess is. And if we had a slope that was positive, it meant that we had a value of b that was greater than what the optimal was. All right, next up. So our goal was to take the slope of MSE at some random guessed value of b, and we would use the derivative of the MSE equation to do so. So we were only able to get the slope of a given point by using that derivative equation. After that, we took the slope and we subtracted the slope from b to update our guess. And then we repeated the entire thing over again. Now I want to very quickly show you a couple diagrams to help you understand kind of behind the scenes what's really happening with these numbers as they're being updated. So let's go through one or two iterations of that algorithm on this diagram right here. Now for my initial value of b, I guessed 1. And I got a slope of negative 488. So on this chart over here, I've got my 1, and at that point, I found a slope. This is a slope right here, not the value of MSE. It is a slope of negative 488. Because this number is negative, that means that my ideal solution for b must be somewhere to the right. I then updated my guess of b by taking this slope right here and multiplying it by the learning rate. Remember, we're going to talk about what the learning rate is in just a second, but for right now, let's just accept that it's some random number, more or less, that we are multiplying our slope by. So we decided to update our b guess by 48.8. So we took our initial guess of b, and we subtracted negative 48.8 from it. And so our new guess of b was 49.8. So our next guess was right around here. Let's say that's 49.8. And now when we plugged in 49.8 to our slope equation, or the derivative of MSE, we got back a slope of negative 390.4. And so we went down to a slope of negative 390.4. Again, remember, this is a slope. It's describing how far downwards facing this line is right here. It's not the actual value of MSE. So because this number is negative, it's telling us, hey, we still have to go further to the right to find our ideal value of b. So now we took the learning rate again, we multiplied it by the 390.4, and we decided to take our current guess of b and subtract negative 39.4.04 from it. So our new guess of b is 88.84. And so we dropped another guess, essentially, we made another guess with b at 88.4. And we took the slope right there, we got 312, negative 312. Again, it's negative, so we decided to go further to the right, and this process repeated itself over and over and over again until we eventually got all the way here to 245. At around 245, and even slightly less than that, we can observe that our changes, or the slope at that point, are getting very, very small. We have very small slopes at this point in time. And so because these slopes were small, we could take that as a signal that we do not have to go through our progression of updating or doing the gradient descent any longer. So essentially, as soon as we see that the slopes are small, and there are some rules that we'll use to enforce this, some actual equations we can run, as soon as we see that the slopes are small, we're going to say, okay, that's it. We've done enough iterations. We can stop iterating. And whatever our final guess is right here, that's going to be the value of b that we're going to use. All right, so that's a quick review on what's going on. Now, I'm sure at this point, you might have some really big questions about this entire process that we've gone through, especially around that learning rate thing that I keep saying, oh yeah, we'll talk about that in a second. So let's take a quick pause right here. We're going to come back to the next section, and we'll talk about why some of these things worked out the way they did, and of course, address this learning rate issue. So I'll see you in just a minute. In this section, we're going to address a couple of very common questions that come up when you first learn about gradient descent. So the first big question, why the learning rate, right? I kind of threw in that learning rate at the last second without really explaining what was going on. So as you might recall, over here on the left-hand side of this sheet, we had a learning rate, and we had it around like 0.4 or 0.3 or 0.1 or so. Let's go back to 0.4. The learning rate is used to decide how much we are going to adjust our value of b by. So if I select this cell, whenever we decide to update our value of b, we're going to take our slope, and we're going to multiply it by that learning rate. If we have a learning rate around 0.4, it looks like we converge at our solution, or the optimal value of b of 245, in maybe about 15 or so steps, or 15 or so iterations of gradient descent. If we update the learning rate to be a very small value, like let's say 0.0001, then that means that we are going to make very small adjustments to our value of b for every iteration. These adjustments are so small that it's going to take many iterations of our algorithm to eventually arrive at our ideal solution of 245 for b. Now that's not really answering what the learning rate is doing for us. And in fact, I'm not even going to really tell you directly what the learning rate is, not up front anyways. I will in a second, but not just yet. In order to help you understand the purpose of the learning rate right here, I'm going to actually answer a completely different question. Okay, totally different question I'm going to answer. And when I answer this one, I think you'll get a better idea of why this learning rate exists. So remember, we just said the learning rate is used to decide how much to adjust the value of b by. But I got a question for you real quick. How do we decide how much to adjust b by? Well, it's the learning rate and it's the slope. So the question that I want to answer is not, why are we using the learning rate to adjust b? My question is, why are we using the slope to adjust b? Why are we using the slope? Now you might immediately respond back to me and say, Stephen, you just made like, I don't know, 30 minutes, an hour, whatever this has been, videos talking about how we use the slope to update the value of b. Well, I want to clarify a couple things here really quickly. We've been saying that we make a guess around b, we get a calculation for our slope, so that's my slope right there. I'll put a slope next to it just to make sure it's really clear. And then we've said, yeah, we're going to use that slope to update our value of b. Well, here's a little secret. This slope right here, being used to update the value of b, is total magic, total facade, total black magic, totally meaningless. Using the slope directly to update the value of b makes no sense. There's no actual relationship directly between the slope value right here and our actual value of b. The only real signal that the slope gives us is whether or not it is positive or negative. That's the only meaningful signal. The fact that we actually use the number 488 to update our value of b right here is just some made-up construct that someone says, hey, if we just use the slope, it looks like things kind of work out. So the only reason that we use the slope is the fact that it has the negative sign or the positive sign. The negative sign means that we need to increment or increase our guess of b. If it's a positive sign, it means that we are over here and we have a positive slope, and it means that we need to reduce our guess for b. So having said that, why do we use a value of the slope to update b? Like, why do we use the slope at all? Well, there actually is kind of a good reason to it. There is some science to it, but again, it is still kind of made up mumbo jumbo to use the slope. So I want you to notice how if we have a learning rate here of like 0.4 or so, notice how the slope starts off very large, but then after just a couple steps here, and maybe even if we do a learning rate of 0.3, it'll be a little bit more evident. So if we do a learning rate of 0.3, the slope starts off very large. And so if we use the slope to update our value of b, that means that initially we're going to make these huge, gigantic jumps towards the correct solution. But as we get closer and closer to our ideal solution, and we get further and further down into this trough right here, our slope gets less and less because the line is leveling out. And so we might end up like right here with a slope of like negative 0.01 or so. So what this means is that when we use the slope to update our value of b, we're going to initially get these very large slopes that cause us to do these big jumps or these big updates to our value of b. And we're going to very quickly get towards our ideal solution. But then as we get closer and closer to the ideal solution and our slope is less and less, we're going to start updating the value of b less and less as well. So we're going to make these very fine-tuned adjustments to our value of b as we get closer to our solution. So these tiny, tiny little adjustments, the closer that we get, because we have a value of our slope that is less and less and less. So that's the only reason that we are using the magnitude here of the slope. The only real true signal, like the only rooted in reality mathematical reason that we're using the slope is the positive sign or the negative sign or the positive sign that tells us whether to increase b or decrease b. Besides that, the fact that we use the slope is just because it is convenient and that it allows us to make smaller and smaller adjustments as we get closer to the solution. Now you might say to me, well, Stephen, that's still a good reason to use a slope. Like, hey, we're making small adjustments. We're getting there closer and closer. Well, yeah, I'm not going to disagree with that. But at the same time, we don't really have to use a slope to get these smaller and smaller adjustments. Let me show you a quick example of why. I'm going to put a third column over here, or a fourth column, excuse me. And I'm going to call it countdown. And I'm going to make this start off at 0, or excuse me, 100. And then for every iteration through gradient descent, I'm going to divide this value by 1.5, like so. So initially, this countdown column is going to be some very large number, but then over time, as we go through more iterations of gradient descent, you're going to see that the number gets smaller and smaller and smaller. Very similar to how our slope gets smaller and smaller and smaller. So now, when deciding to adjust my value of b right here, rather than just taking the learning rate and the slope, I'm going to look at the slope, and I'm going to pull off the one meaningful piece of data from it. Remember, the only actual rooted in reality piece of data here is whether or not that is negative or positive. So I'm going to put in a little if statement. I'm going to say if that number is greater than 0, then return 1, otherwise return negative 1. So now if the slope is negative, I'm going to get negative 1 right there. And then in addition to getting that negative 1, I'm going to multiply it by the countdown, which again is just some random arbitrary number I made up that is going to start off very large and then get smaller and smaller over time. Okay, so I've now adjusted this cell right here. So it's now pulling off the negative sign from the slope and then multiplying by that countdown value. And then I'm going to drag that formula down, like so. So now we have this completely arbitrary, made-up, random number, and if you look at my value of b, it is converging around 245 rather quickly as well, even though I'm not using a learning rate and I'm not really super directly using the slope. Now you'll notice that it kind of bounces between 244 and just above 245. So I could probably do a couple more adjustments to the countdown over here to converge at 245 even more quickly. But my point here, the overall point, is the fact that we use the slope to update and adjust our value of b in the real version of this algorithm is just totally made up, hoo-ha, and the only meaningful part of the slope is the negative or the positive sign. Okay, so that's my indirect answer to the learning rate. That's the indirect answer. Remember, I said I was going to answer a different question. Now I'm going to undo everything I did and go back to just using the slope. Okay, so I'm back to where I was before. Okay, so now that we understand that the slope is more or less a meaningless number here to use to update the value of b, why are we using the learning rate? Well, the only reason we're using the learning rate right here is that if we always update by just the slope, we might accidentally overcorrect our value of b. So we might use the slope right here, and if we just use the slope directly and do not include this learning rate, we might update our value of b and adjust it too much. Let me show you why that would be a danger. Now, this is actually going to be a pretty easy demo to show you. I'm going to delete a couple of these lines just to make things more clear. Okay, so let's now imagine that we have an initial guess of 1, and we get an initial slope of negative 488. So that means that if we're going to ignore the learning rate, let's say that the learning rate doesn't exist right now, when we go to update our value of b right here, we would do 1 minus negative 488. And so that tells me that I need to adjust my value of b to be 489. So that means that I would jump. My second guess of 489 of b would be 489, which would be way over here. So in that single step, I've completely overshot my optimal value of 245. Totally overshot it. Now, if I look at my slope over here now, maybe I do calculation of the slope, and I find that the new value of the slope over here is 1500. And so now, again, I'm going to use my slope with my new b value of, it was 489, and I'm going to try to update my b value using this new slope. So again, I would do 489, which is my current value of b, and then I would subtract 1500. So now I've got a new b value of negative 1011. So that means that I'm now going to, again, way massively overcorrect, and I'm now way over here. And so my new value of b is negative 1011, like so. And now let's say way over here, my value of the slope is negative 1500. And so now I'm going to do another correction. So I do negative 1011 minus a negative 1500. Oh, let's do a different value. I didn't mean to do 1500 there. Let's say that the slope over here is negative 2500. That's better. So now I'm going to do negative 011 minus negative 2500, like so. And now my new value of b is 1489. Are you detecting a pattern here? Yeah, the pattern is that if we try to update by too much, or if we try to change b by too much, and we accidentally overcorrect, then we're going to just get increasing values of b that just nonstop increase, and never actually converge at our meaningful value. You can actually see this in action with our learning rate right now. Try putting in a learning rate of 2. When you put in a learning rate of 2, that means that we're going to correct our value of b by 2 times the slope. And so after our very first adjustment to b, we end up with 977. So we completely overshot our optimal value of 245. And now when we calculate the slope again, we get 2928, and we realize that we need to jump way back over, and now we get a value of b of negative 1951. And so we repeat this kind of rubber banding back and forth process until we end up with these incredibly large values, and our solution never actually converges. So, what's the lesson here? I answered this question around learning rate probably way too much in depth, but honestly, this learning rate stuff ends up being a huge pain in the rear, and we're going to go through a tremendous amount of work to optimize our learning rate. So I hope the lesson here that we've learned is that the purpose of the learning rate is to deal with the fact that we're essentially updating our value of b with this totally made up number. And the only reason that we use the learning rate is to kind of tame how much we are updating b by at any particular point in time. And the last thing I want to say here, or second to last, is that with the learning rate, there is no like hard and fast rule of a learning rate to use. It just so happens that with the numbers that we have for house price right here, a learning rate of 0.4 ends up working out pretty well. We're going to work on some other problems where a learning rate of 0.0001 is optimal. And then we might work on another problem where a learning rate of 10 is optimal. It really just comes down to the nature of the data set that we're working with that decides what our learning rate should be. All right, so one last thing. I know this is a super long section. I apologize, but the last thing I want to show you very quickly that I find really interesting personally, I took our spreadsheet and I put it on sheet 3 right here, and then I put together a little chart right here. The chart is showing my value of MSE versus my value of B. So notice this is my mean squared error. It is not the slope. So I added in a new column here that just calculates the error of any particular value of B. And so we could use this chart right here to really see everything that I was just trying to show you in this diagram right here. So you can see that we start off with some initial guess of around like 0 or 1 right here, and we get an MSE value of 60,000. We then decide to update our guess for B. Our next guess is at 49.8, and we get an MSE of about 38,000. And then you can see that with each successive guess of our value of B, we are making smaller and smaller adjustments over time until we eventually arrive at that 245, and we're making those tiny, tiny, tiny adjustments. Now, if you want to see something really interesting, we can play around with the learning rate here. I'm going to change the learning rate to like 0.5, and you'll notice that when we change it to 0.5, we're going from the initial guess all the way down to our optimal solution extremely quickly. But if we increase the learning rate too much, like let's say 0.6, we start to get something kind of interesting. Our first guess is still right here, but then after we do the first update, we overshot our optimal value of 245, and we overshot all the way up to 293 over there on the far right-hand side. And so that means that we now need to jump back to the other side of 245 and then do successive smaller updates. And so you can play around with the value of the learning rate here and make very small adjustments to it, like 0.7, 0.8, 0.9, 0.9, and you're going to see the actual bouncing back and forth of our ideal value of B. So there's the first data point right there, and then we overshot way too much, and we ended up over here with a value of B of, I keep bringing that up, I apologize. We ended up with a value of B of 440. And then so for our next correction, we were at 88.4, and then we were over at 369, and then 145, and so on. And then we can really adjust around 0.9, so I could do like 0.91, I could do 0.92, 0.93, and you can see that we're just kind of increasing how far we overshoot each time. Until if we set our learning rate too high, like let's say 0.95 or 0.96, 0.97, you'll see that these are the values where we start to never actually converge around 245. And we start to always consistently overshoot that optimal value. And so now if I look at like what appears to be the closest value, we only ever get to 226. And if I now start to increment this more, we're just overshooting more and more, and we're never converging. And we'll go to 0.99. We're still never converging. We'll go to 1. And now we are in a pretty, well, 1 is kind of a weird value here. Let's try 1.01. There we go. So now we are at a learning rate where we are successfully increasing our value of B, and we are never, ever getting at all closer to 245. All right, so that's basically way more than you probably ever wanted to know around B. Again, the real lesson here is that using the slope to, everything you want to know around learning rate, the real lesson here is that using the slope to update our value of B is just like total made up, like it just happens to work out. And it's only by the fact that we use the learning rate to curtail exactly how much we do the update by that this algorithm actually ends up working out. Okay, so sorry for the super long section here. Let's take a quick pause. We're going to come back to the next section, and we'll quickly address 2 of the other big questions that you might have. So quick pause, and I'll see you in just a minute. In the last section, I spoke way too long about learning rates, so we're going to very quickly go through the answer to these 2 other questions you might have. So second big question here, we made a big deal about calculating that derivative. You might be kind of curious why we went through that process of calculating the derivative. And why did we not just calculate MSE twice and then compare those 2 values? So what I mean by that is back over here on sheet number 3, I've got my value of b. I've got the MSE right next to it. Now remember, this is my MSE, my mean square error. It is not the slope. It's the mean square error, which is that metric that says how wrong my guess is. So why did we have to go through the process of calculating the derivative? Why did we not just make 2 successive guesses of b, like say 1 and then 2? If we had just guessed 1 and then 2, we could have seen that the MSE value went down. And because it went down, we could have then said, oh, well, clearly as we increase our value, MSE is going down. That means that our value of b should be going higher. So again, the question here is, why do we have to go through the the complicated calculus stuff, and why did we not just use MSE directly? Well, the direct answer to this is pretty simple. Calculating the slope, or using the derivative to calculate the slope, is essentially the same exact thing as calculating MSE twice. The only difference is that when we use the derivative, we are calculating the slope in one single operation. When you run this calculation of MSE with 2 successive values of b like so, you're essentially just finding the slope between these 2 points. And so you're using the same signal from the derivative as you would be if you were using 2 successive numbers. So again, that's why we're using the derivative here as opposed to just calculating MSE multiple times. Okay, so now last question. We want to have a slope of our MSE derivative equal to 0. Remember, that was the whole big reason that we went through this update process. We wanted to get a slope as close to 0 as possible, because if we got a slope of our MSE equal to 0, we would have our ideal value of b. And so if you are from the world of calculus, or you've taken courses on calculus before, you might recall that one very easy way to find where the slope is 0 is to just take the derivative, set the derivative of your equation equal to 0, and then solve for your unknown, which in this case would be the value b. So this is a classic solution for finding what we would call a vertex point, or essentially the bottom point of that parabola, like this optimal guess right here. So again, why did we not just take this classic solution to how you would normally solve this problem? Well, very easy answer again. Remember, we have done a tremendous simplification of the entire gradient descent algorithm in that we have said that we were going to ignore that value of m right there. So we completely ignored m, we just set it equal to 0, and we've only been considering b. So as we continue into the next section and we start to look at the real complete solution to gradient descent, where we consider m as well, you're going to see that although we could take the derivative of this thing and set it equal to 0 and solve for b, that actually does not work out because there are 2 unknowns that we have here. We have one unknown of b, the second unknown is our value m, and we just have not been including that into our equation for MSE just yet. So that's why, again, if you're coming from a calculus background or a math background, that's why we were not able to take that shortcut. All right, so with all that in mind, another quick pause. We're going to come back to the next section, and we're going to talk about expanding our gradient descent solution to include not only b, but also our value of m as well. So quick pause, and I'll see you in just a minute. I think that we now have a much better idea of exactly how gradient descent works. Now, before we move on and use this algorithm to solve some problem in our code editor, one last quick thing I want to remind you about. We've been trying to find some value of b that's going to help us relate a lot size over to the house price. But just to make learning gradient descent a little bit easier, we've been saying that we were going to set m equal to 0. Again, by setting m equal to 0, it just makes going through the gradient descent algorithm a little bit easier. So now I want to update our understanding of our algorithm a little bit. We're going to also include some calculations to make a prediction or get a guess around what the value of m should be as well. So we're now going to revise our algorithm slightly so that we are now not only trying to guess a good value of b, but we're going to try to guess a good value for m as well. In order to do so, we're going to introduce one more equation, and we're going to make a slight change to how our algorithm runs. So let's get to it. All right, so first things first, here is the equation that we've been using to calculate our slope of MSE with respect to that value of b. So it's almost the same equation as before, but now, because m is not equal to 0, there's going to be an actual m times x term inside of here. So previously, the equation that I had showed you and the equation we had entered into that spreadsheet looked like this right here, and we just took b minus the actual value. So now that we are also going to include m as well, we're going to add on that little term right there. Previously, we had said that m was going to be equal to 0, and so it essentially turned into 0 times x. And so that was always going to be 0, and so we were able to drop out that term like so. And then boom, it looks like what we had before. So now that we are including some attempt at calculating a value of m, this equation for finding the slope with respect to b changes ever so slightly. And then now, in addition to that equation that gives us the slope with respect to b, we also have a second equation here that finds our slope of mean squared error with respect to m. So equation 1 right here gives us a signal, basically that positive or negative sign that says how we need to adjust our value of b. Now we are going to have a second equation, a second signal that tells us how we need to adjust a value of m as well. So that's the only thing that's changing here. We just get one additional equation that we're going to use to make a guess and then update our guess for the value of m. So now our algorithm flow for gradient descent is going to look like this. We're going to pick a value for b and m. It can be any random value we want to start with, maybe 0 or 1 or whatever seems appropriate. We're then going to calculate the slope of our MSE, or mean squared error, with respect to both m and b, using these two equations. Next, we'll say, okay, are both of those slopes very small? If they're very small and close to 0, that means that we have very good estimates for both m and b. If that's the case, then we're going to say we are all done with our algorithm. Otherwise, we're going to take both those slopes and we're going to multiply our slopes by our learning rate. We're going to use the same learning rate for both slope calculations. And then finally, we're going to take those slopes and subtract the results from both b and m. Now, I know that introducing this additional term here, like saying, oh yeah, we've got this new number that we need to calculate, I know it might seem like, wow, this is starting to get really complicated. We're doing the same thing we were doing before, the exact same series of steps, the same calculations. The only difference is that now we are going to be doing twice as many calculations. We're going to find the slope for both b and a slope for m. And we're going to use those two slopes to update our guesses for both b and m at the same time. That's the only difference here. We're just doing a slightly larger number of calculations, but the ideas behind all this are all exactly the same. All right, so let's take a quick pause right here. When we come back to the next section, we're going to do a quick run through this algorithm in a spreadsheet again. The only reason we're using the spreadsheet here is just so you can kind of see the progression of these numbers and understand how they all relate together, and also kind of see the calculations and the exact formulas line by line before we go over to our code editor, at which point in time a lot of these equations are going to be kind of abstracted out and a little bit more challenging to understand what's going on. Okay, so quick pause right here. I'm going to come back to the next section and we're going to update our mean squared error equations. So quick pause, I'll see you in a minute. In this section, we're going to update our spreadsheet to walk through the gradient descent algorithm again, but we're going to be using both, where is it? Here we go. Both our updated equation for getting some signal on how to update b, and we're also going to implement our equation for getting some signal on how to update our value of m. So I'm going to flip back over to that spreadsheet. Remember, here's a link to it right here. Here's the spreadsheet, and you'll notice that I've got two tabs down here. I've relabeled all the tabs. Hopefully that has not been too confusing. I've now got a version that says m plus b empty, and then an m plus b completed. So if you want to follow along with me, come over to the empty tab right here, and you can add in the numbers at the same time that I do. Otherwise, if you just want to see the finished solution, you can go to the completed tab. That will be my completed version of all this work. Okay, so you'll notice that I've added on a couple columns here. So I've got my value of m, essentially my guess at what m should be, and I've got my value of b, my guess at what b should be. So now I'm calculating two separate slopes here. I'm calculating the slope of mean squared error with respect to m. This gives us our signal on how to update that value of m. Do we need to make m larger or do we need to make it smaller? I've already entered in the equation for this because it's just a little bit long. Again, it's the same equation that you're seeing right here with respect to m. This equation, that's what's in there right now. That's what's inside that cell. The only reason I entered it in is just because you can see it's kind of long and I didn't want you to accidentally make a little typo here. And also, I don't know if you have any background with Excel or anything like that. But again, essentially, it's just the same equation that you're seeing right there. And then we still got that second column right here. That is the slope of our mean squared error with respect to b. And again, just as before, this is just giving us a signal telling us whether we need to make b bigger or smaller. So now over here on the right-hand side, two columns that I did not put together, we've got how much we need to adjust m by and how much to adjust b by. So just as before, to adjust m and adjust b, all we're going to do is take our slope of either m or b and we'll multiply by the learning rate. So I'm going to add that in right now. And I'm going to make this just a little bit bigger so we can see everything more easily. All right, I'm going to collapse that a little bit and that a little bit. So how much to adjust m? That's going to be our slope of MSE times our learning rate, like so. And then again, I'm going to make sure that I put dollar signs in front of b and 10, like so, to make it an absolute reference. So when I start dragging this cell around, I'm not going to accidentally refer to some other cell besides the learning rate. Okay, so we are going to use our slope of MSE with respect to m to decide how much to adjust m by. And now we're going to do that same thing for b as well. So how much are we going to adjust b by? Well, we're going to take our slope of MSE with respect to b, and we will again multiply it by our learning rate. And again, I'm going to make sure that I put some dollar signs in front of both the b and the 10. Okay, I'm going to zoom out just one more time here so we can see the entire spreadsheet. There we go. And there we go. Okay. So now we've gone through one iteration of gradient descent right here. We've got our initial value of m and b, we calculated the respective slopes, and we calculated how much we should update each m and b by. So now we need to take these updates and apply them to both m and b. So for updating m, I'm going to say take my previous value of m, so take cell D2, and subtract H2, or subtract how much I want to update m by. And then for b, I'm going to take my previous guess at the value of b, and I'm going to subtract how much to adjust b by. Like so. So here are our new values of m and our new value of b. And then just as before, we're going to calculate our slope with respect to m. To do so, all I have to do is drag that calculation cell down, and same thing for b. And then I'll figure out how to adjust m by and how much to adjust b by. And now, as you might guess, I can really just take this entire row, highlight the entire row, and drag those cells down with the little grabber here on the bottom right-hand side. And so I'll go through a couple iterations of gradient descent. Now, the instant I do so, you're going to notice that I'm getting those very, very large numbers, which is something that we had seen previously when we had updated our learning rate to be too large. Remember, this is a signal that we are vastly overshooting our optimal value, and we're going way, way, way past the optimal value, which causes us to basically just bounce back and forth, never actually converging on the appropriate value of m or b. So the way that we combat this is to adjust our learning rate and to just decrease it. So I'm going to try putting in like a 0.000001, like so. Now, when I do so, you'll notice that it looks like I'm getting some convergence for my value of m. It looks like down here, during the last couple steps, I see 0.22, 0.22, 0.22. So that looks pretty good. That looks appropriate. However, if you look at my value of b, it is never changing from a value of 0, which doesn't really seem like it's appropriate. That doesn't seem right. I would really suspect to have a value of b that is not 0. So what's going on here? Not only are we seeing that we've got this non-changing value of b, but we've also got a very, very low learning rate. So essentially what you're seeing is the result of using some features that have not been scaled. Anytime that you are using features that have rather large range of values, as we do here, we start at 800 and we go up to 1350, you're going to see kind of an artifact. The artifact you're going to see is that you're going to get these crazy changes in the value of m with this very, very small learning rate, and you're going to see that your value of b is just about never going to change. So again, anytime you've got these rather large features, you're going to have a small learning rate, and you're not going to see changes in b. In order to fix this, all we have to do is apply either min-max scaling or the other standardization method using that standard deviation and variance and mean average that we had spoken about previously. So if you apply either of those methods to your feature set here, it's going to fix up the issue of the very small learning rate and the unchanging value of b. Now, I don't want to go through the process of doing the min-max calculation here. I think we already understand how that works. So I'm just going to arbitrarily change my lot sizes to take a guess at what the min-max values would be. Remember, when we apply min-max, we say that all of our features get ranges of values between 0 and 1. So I'm going to make my smallest lot size here 0, and I'm going to make my largest lot size 1, and then I'm just going to kind of guess at the values in between. So maybe I'll do like a 0.25, a 0.5, a 0.65, and a 0.8, like so. And now I can adjust my learning rate back to a learning rate that was similar in scale to what we had on our previous exercise. I'll try like a 0.1. I'll try a 1. Okay, that was definitely too high. Let's try like a 0.5, maybe a 0.6, 0.7, 0.8. Okay, 0.8 is clearly too high, and I know that because I can see that not only am I kind of gravitating between positive and negative values of m, but I can also start to see that my values here are starting to get larger and larger. And so I think that it looked like things were kind of in a sweet spot around 0.7. Even then, though, it looks like we're kind of knocking back and forth. So maybe I'll do like a 0.65, like so. Now it looks like I'm starting to get some convergence around 71 and 205. If I wanted to, I could take this row right here and drag it down a couple more rows. And okay, well, it looks like the B is at least stabilized, but it does look like the M is staying like it's changing. Okay, that's looking better. So it looks like I would probably end up saying that I've got a solution around 65 and 210. And I know that because my slope values here are getting rather small. All right, so hopefully at this point in time, one thing I want to point out here, it's very aware that picking your learning rate is kind of a capricious exercise. You know, I'm just randomly toggling my learning rate around until I can do some very subjective inspection of these values. And so it might seem like the learning rate is just this bizarre factor. Yeah, in reality, it kind of is, as we had discussed previously. We are only using the learning rate because our method of updating these values is kind of bogus. You know, we're just using the slope that doesn't really have a relationship in magnitude, at least, to how we should update our values of m and b. Now, in reality, when we start writing code around this, we don't really have to worry about tweaking the learning rate so much because we can just pick some arbitrary learning rate, like say 0.1, like 0.1 or something. We know that that's not going to cause us to jump way out of proportion here, and then we can just continuously run the gradient descent algorithm for many, 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 many iterations, like hundreds or even thousands. So even if we have a small learning rate and we're making very small changes to m and b, eventually we will converge at some appropriate values because we're just running the algorithm enough times. If we are really concerned about making sure that we are not going to have to run the algorithm too many times or through too many iterations, that's when we would start to play around with the learning rate and try to get some optimal value to it. Okay, so we've now understood how we can update both the value of m and b using the gradient descent algorithm. So we've now established more or less how we can take some random data set and find a relationship between some feature and some label by guessing repeatedly at values of m and b and then updating those values over time. So now that we've got at least a somewhat reasonable idea of how this works, we're going to take a pause, we're going to flip back over to our code editor, and we're going to start working on a new project where we're going to start to actually implement this entire gradient descent algorithm with code and specifically with TensorFlow. So quick pause and I'll see you in just a minute. In this section, we're going to start implementing the linear regression gradient descent solution inside of our code editor as a native project. We'll then be able to use it on some more interesting real applications at some point in the future. Back in my terminal, I'm still inside of my KNN-TF folder. I'm going to go up one directory back to the MLKits folder. Remember, this is the project that we had cloned or downloaded off of GitHub. I'll then change into that regressions directory. Now inside of here, I'm going to start up my code editor, and then I'm also going to run npm install inside of here. Okay. Now I'm going to open up my editor, and I can see a couple of files and folders already inside this project directory. You'll notice that there's still the load.csv file that will load up some CSV data and give it to you in a collection of different arrays. We've also got a package.json file that has a couple of dependencies for our project. Now, one thing I want to mention really quickly, remember I had said previously that I put together the load.csv file. We're going to eventually write that thing together at a later section in the course. So if you want to learn how to load up a CSV file effectively, we do eventually get around to that. Now, first file inside of here, cars.csv. So this is going to be the data set that we're going to use to practice the implementation of the gradient descent algorithm. Inside of here, you're going to find some information about a collection of different cars that were produced during the 70s. So you'll see some columns at the top, like MPG, which stands for miles per gallon. That is essentially the efficiency of the car, how many miles it can travel or how much distance it can travel per gallon or per unit of fuel, or petrol, gasoline, however you might refer to it. You'll also see the number of cylinders that the engine has, the displacement, which is more or less the size of the engine. You'll see horsepower, which is the power of the engine, weight, acceleration, model year, and car name. So a CSV file of the same structure, same one, or similar structure to what we had previously had. So what are we going to do with this data? Well, I want to try to put together a little bit of a relationship between two of the different columns that are inside of that CSV file. I want to try to figure out if there is a relationship between the car horsepower, or essentially the power of the engine, and the amount of fuel that the car consumes. So I would wager that if we have a very high horsepower vehicle, it maybe is not that fuel efficient. And so we should see some type of relationship between these two factors or these two variables. Now our goal here is going to be to guess and calculate some optimal value of M and B that will make this relationship true. So we need to apply that gradient descent algorithm in order to solve for M and B, or at least some optimal solution for it. Now, last thing I want to talk about very quickly, if you remember our k-nearest neighbor algorithm, when we put that thing together inside of our code editor, we had kind of a messy file structure. Really, we just had that single index.js file where we stuffed in a whole bunch of logic. And inside there, we had a single function called knn, and that was really responsible for running our k-nearest neighbor algorithm. Now, on this project, we're going to have a lot more discipline and a lot more code structure. So we're going to write code in a very professional manner so that it's easily testable, it's easily updatable in the future, and in general, it's clear as to what is going on. So with that in mind, I want to give you a quick preview of what we're going to be trying to do when we write out this implementation of the algorithm. We're going to be creating a JavaScript class that we're going to call linear regression. This class is going to contain a couple of different methods and a couple of different instance variables that's going to allow it to behave essentially as its own individual unit. I've listed a couple of different methods that the class is going to have on here. The class is going to have a couple more methods beyond what you see right here, but they're not going to make sense right away until we actually start going through the implementation. So we'll have methods like gradient descent, which will be responsible for running one iteration of the gradient descent algorithm and then updating our values of M and B. We will have a train method, which is going to take in some training data set and run that gradient descent method until we get a optimal value or a suitable value for both M and B. We'll have a test method that's going to take in some test set of data and give us an accuracy rating and tell us whether or not our calculated values of M and B are appropriate. And then finally, we'll probably have a predict method that we can provide some new value of horsepower and get out a prediction of what the vehicle's miles per gallon will be. One of the big reasons that we're going to do this refactor over to a class is I want you to remember kind of how the k-nearest neighbor algorithm worked. Remember, every time that we wanted to do a prediction, we had to rerun the entire algorithm. And so we had to always hold on to our entire training set of data, and anytime we wanted to make a prediction or do a test run to verify its accuracy, we had to feed everything back into that knn function. With linear regression, we only do the training step one time. We run training step one time, that's it, we get our values of M and B out. And then we can very easily use those values of M and B to do our testing or our prediction in the future. And so when we get those values of M and B, we're going to set them as instance variables on this class so that we can easily reference them in a future. Again, essentially the idea here is that we're going to have this class that kind of wraps up everything that we could possibly have to do around running a linear regression analysis. Everything is going to be included into this class, and that's going to make it very relatively easy to use for our projects in the future and easy to test and understand and so on. Okay, so now that we understand what we're trying to achieve, let's take a pause here. When we come back to the next section, we're going to start implementing this project inside of our code editor. In this section, we're going to start working on our new project. Remember, the entire goal here is to load up some data from the cars.csv file and then try to determine a relationship between our car horsepower and our miles per gallon using gradient descent. So to get started, inside of my code editor, I'm going to make a new file called index.js. Inside this file, we're going to load up our data and then reference our linear regression class and do our training and then some testing and validate our accuracy. The actual code for the gradient descent algorithm and the entire linear regression class that we just discussed is going to be placed into a separate file. So we're going to have two files, our index.js file and a linear regression file. The linear regression file is going to have everything related to running the algorithm. The index.js file is essentially going to be a driver of sorts. It's going to require in that file and use it to do some analysis. So let's get to it. Now at the top, we'll add in a couple of require statements. So I'm going to require in the TensorFlow library by first putting require at TensorFlow tf.js-node, and then I'll also get the TensorFlow library itself with require at TensorFlow tf.js. I'm going to add one other require statement here right away, my load CSV. So load CSV, like so. Now again, remember I put this file together just to load up the CSV file. We are going to go through the process of writing out all this logic at some point in the future. And it's totally optional. Loading up CSV files isn't the most exciting thing, but it's something that you definitely have to do all the time with machine learning. So I do want to make sure that you have the opportunity to figure out what's going on inside of here. So now after requiring in load CSV, I'm going to use that function to load up my cars.csv file. So I'm going to say let, and we're going to get features, labels, test features, and test labels. And that's all going to come from calling, let me condense this on the left-hand side, load CSV. And the location of our CSV file is in the current working directory, so /cars.csv. Let's double check that name. Yep, cars.csv. Now, as a second argument to load CSV, we're going to give it an options object and tell it exactly what we want it to do when this data gets loaded in. So after that string of the file name, I'm going to put in a comma and then an object. So I've got a opening curly brace over here and a closing over there. Let me get that on one line just so you can see it more easily. All right, I'll zoom back in just so you can see it more easily again. So now remember, there's a couple options that we can optionally pass this thing. The first thing I want to do is shuffle the data set. So I'm going to say shuffle true, like so. Next up, I'm going to make sure that I split my data set into a test set and a training set. So we want to have a ton of records in our training set, and we'll have a couple records in the test set just to validate our model's accuracy. In total, our cars.csv file has, let's see, 393 records. So we just need to make sure that we don't take too many records to put into the test set. I think that maybe a test set size of like 50 records might be appropriate. In many other applications around machine learning, if we have larger data sets, you'll very frequently see a test set size of about 50% of the pool. So we could optionally take 50% of all of our records and put them into the test set pool, and then the other 50% might go into our training data. I think that we'll just start easy and say, you know what, yeah, let's do the split here. So we'll say split test, but we're just going to take 50 records and put it into the test set. Okay, next up, we need to tell the load CSV which columns that we want to pull out and have placed into this features array and test features array. So the columns that we care about for our features is going to be solely horsepower. Because remember, we're trying to prove that there might be a relationship between the horsepower of the vehicle and its miles per gallon. So all I care about for the feature set is horsepower. So I'm going to say data columns is horsepower. And then finally, we need to specify the label columns. What inside the CSV file is going to represent some data that we want to use as our label? Well, that's going to be the thing that we're trying to predict. And the thing we're trying to predict is our miles per gallon. Remember, miles per gallon, if you're from a country that uses the metric system, that might be a metric of something like, I don't know, kilometers per liter or whatever it is that you might use over there. But again, in the US, it's miles per gallon. So I'm going to say label columns is MPG, like so. Okay, so that looks good. Let's save this file right here. We'll take a quick pause. And when we come back to the next section, we're going to create a second file inside of here where we're going to start to write out all the logic of our actual linear regression class. So quick pause, and I'll see you in just a minute. In the last section, we put together a little bit of code to load up our cars dataset. I want to very quickly make sure that we did this correctly, so I'm going to add in a console log for features and labels to the bottom of the file. I'll then save the file, and then I'll flip back over to my terminal. I'm going to make sure I'm inside my regressions directory, and then I'll run node index.js. I just want to do this to make sure that everything has been loaded up appropriately. Now I can immediately see a console log right here. These appear to me to probably be values of miles per gallon. Just so you know, if you are from a country that uses the metric system, typical values for miles per gallon can range anywhere from about 9 miles per gallon all the way up to 50 or even 100 on some extremely, extremely high efficiency vehicles. So given these values of stuff like 16, 26, 10, 39, this definitely looks like a series of values for miles per gallon. Now, if we scroll up a whole bunch, we'll see values of like 90, 150, 75, 110. These are all values of horsepower. Horsepower values traditionally will range between maybe about as low as 60 all the way up to sports vehicles that might be around 650 horsepower. Okay, so it looks like everything has loaded up appropriately. So I'm now going to flip back over to my code editor. I'm going to remove that console log statement because I just wanted to make sure everything was being loaded correctly. And then I'm going to create a second file inside my regressions directory. Again, the purpose of this file is to house our actual linear regression class. So I'm going to make a new file, and I'm going to call it linear-regression.js. Then inside of here, we're going to immediately add on one require statement, and that's going to be for TF, or TensorFlow. So we'll say require at TensorFlow TF.js. You'll notice that when I put the TensorFlow require statement into the second file, I only put the require TensorFlow.js, and I did not have to put together the tf.js-node require statement. We only have to put this require statement in one time, preferably at the file that is actually starting, or the kind of entry or root file of our entire application, which is definitely going to be the index.js file. Then after that, I'm going to go down a couple lines, and I'm going to create a new JavaScript class that is going to be our linear regression class. So I'm going to say class linear regression, like so. And then at the bottom of the file, right away, I'll put on a module.exports linear regression. Cool. Okay, so eventually we're going to add a tremendous amount of code to the body of this class. Even though that implementation of gradient descent that we went through in that spreadsheet, it looked relatively straightforward, at least from the formula and math side. There's actually going to be a lot of extra functions that we put in here to facilitate not only all that testing and training and accuracy stuff we spoke about, but we're also going to put in a bunch of helper functions that are going to allow us to kind of optimize how everything around this algorithm works. We'll see what they are over time. Now, the first thing I'm going to do inside this class is define a constructor function. Remember, a constructor function has to be given the name constructor, and it's going to be called whenever we make a new instance of this linear regression class. The constructor function is traditionally where we are going to do some initial setup of our class. We are also going to traditionally provide the constructor our feature set and our labels and any other relevant options for running this algorithm. So I'm going to assume that we want our constructor to be given a first argument of our feature set, which I will refer to as features, and then I'll get a second argument of labels, and then a third argument of options, like so. So now when we eventually try to create an instance of linear regression, we will end up writing something like this. This is just a quick example. You don't have to write this down. So we'll probably have to pass in our features, our labels, and then a couple of options. Examples of options that we might want to put in here might be like the maximum number of iterations that we go through for the gradient descent algorithm. It might also be, say, the learning rate. That might be given as an option on here as well. So anything that we want to pass in that will customize the algorithm, we'll probably want to add to that options object right there. All right, so I'm going to delete that. Again, that was just a quick example of how we're going to eventually make use of this class. So now the first thing I'm going to do in here is make sure that I take the features and the labels and assign them to instance variables inside this class. So I'll say this.features is features, and I'll say this.labels is labels, like so. Now we're going to make a little bit of an assumption here. We're going to assume that when we pass in features and labels, they will already be instances of TensorFlow tensors. So we're going to assume that rather than passing in raw arrays of arrays for features and labels, we will have already wrapped them inside of TensorFlow tensors. We could, in theory, we could either say, oh yeah, this is going to be an array or it's going to be a tensor. It's really up to you. There's no particular reason that I'm saying, yeah, I'm going to make this into a tensor before I pass it in here. Again, it's totally up to you. So then after that, I'm going to make sure that I process all these different options as well. So I'm going to say this.options is options. So then in the future, if we ever want to reference something like, say, our learning rate, we will do so with this.options.learning rate. That's what we will write in the future anytime that we want to access some properties on the options object. Now, one quick thing to keep in mind with this options object right here is that it kind of sounds like there are going to be some options in this thing that are very critical to making sure that our algorithm, gradient descent, works the way that we would expect. In other words, if I try to create a new instance of linear regression and I do not pass in a learning rate property inside of options, then chances are my entire algorithm is not going to work correctly, because I will eventually try to reference this.options.learning rate. And if that is undefined, I'm going to try to multiply a number by undefined, and that's going to return the JavaScript value, not a number, which is going to throw my entire algorithm out of whack. So just to make sure that we get some appropriate default options inside of here, I'm going to take this options object and we're going to assign essentially some default options, for lack of a better term. So I'm going to say object.assign and then put in an empty object and then options as a second argument. So what this does is it takes all of the different properties inside the options object and it copies them into this empty object right here. This object does not necessarily have to be empty. We can put some default arguments or some default properties for the options object inside there. So for example, I might say learning rate of 0.1, like so. So now the result of this line of code will be if you call linear regressions and you do not provide a learning rate inside that options object, we will default to using a learning rate of 0.1. If you do provide a learning rate here, then it will overwrite the default. So that's all that's going on this line of code right here. If you've never seen object.assign before, again, all it's really doing is taking all the properties and values out of this object and overriding them or copying them into this one. We're going to eventually come back here and provide a bunch of other default arguments as well as we start to add in more features to our gradient descent algorithm. Okay, so again, one more time, the end result of all this option stuff right here is just to make sure that when we reference this.options.learning rate, there's always going to be a value there no matter what, whether you provided one inside of options or we had to use the default value. Okay, so this is looking pretty good. Let's take a quick pause right here. When we come back in the next section, we're going to start working on iterating through our features and our labels and actually thinking about how we're going to run the gradient descent algorithm. In this video, we're going to continue working on the setup of our linear regression class. We're going to start to scaffold out our train method. Remember, our train method is going to run the gradient descent algorithm until we get some acceptable values for both m and b. So back inside my class definition, I'm going to define train. And then inside of here, we're going to assume that maybe in some cases, we might not ever come across appropriate values for m and b. Remember, if we pick a learning rate that is too low, then we will not converge on a solution or an optimal solution for m and b quickly enough. And so I don't want to have my training loop just running here forever and ever and ever. I want to eventually call it quits. So we're going to say that in this options object right here, in addition to maybe providing a learning rate, we're going to assume that we'll also be provided some argument that we will call iterations. This is going to be a number, and it's going to specify the maximum number of times that we want to run our gradient descent algorithm. If we come to a ideal solution faster than whatever we put in here, well, that's great, but otherwise we're just going to cap out our algorithm and say you can only run X number of times. So I'm going to start off with a default value of iterations of 1000. So that means that we can run my gradient descent algorithm, or the function, up to 1000 times before I will eventually call it quits and say, this is as good as it's going to get. Now remember, by putting in that iterations 1000 right there, all I'm doing is putting a default value for options into this.options. So ideally, whenever someone creates a new instance of linear regression, like this, ideally they will give us features and labels and an options object that will have an iterations count. So that's going to be the ideal world, but if our user or whoever is using this class does not provide that number, we'll use a default of 1000. Okay, so now that we understand that we are going to have some max number of iterations, we're going to put together a simple for loop inside of here that's going to eventually try to call gradient descent up to iterations number times. So I'm going to say for let I, so we're just going to say simple variables here, just I, nothing fancy needed. We'll start off at 0, and then we're going to run as long as I is less than this.options.iterations, I++. So then inside of here, we're going to run our gradient descent function. We have not put it together just yet, but we'll imagine that we eventually will. So I'm just going to say this.gradient descent. And when I save this file, you'll notice that my code just jumped right there. That's just my automatic code formatter jumping in. I didn't actually change anything, just this formatting around the options object got slightly adjusted. Okay, so we've now got some scaffolding for running our training loop right here. Let's take a quick pause. When we come back to the next section, we're going to start a real big discussion. Sorry, like everything in this course is really big. We're going to have a really big discussion about exactly how we are going to be calculating our gradient descent inside this class. So quick pause, and I'll see you in just a minute. All right, my friends, in this video, we're going to start working on our initial implementation of gradient descent. Remember, this is going to be a single function placed into our linear regression class. This function is going to have a single purpose, or I guess two purposes. It's going to calculate our slope values for m and b, and then use those to update our current guesses of m and b. That's it, just one iteration. And then it's going to be up to this train method right here to repeatedly run that function so that we eventually get an optimal solution of m and b together. Now, before we start working on the actual function, I got one quick note, something that I want to tell you right now that's going to help you understand what we're going to be doing in the next couple of videos. So in this video, we're going to put together an initial implementation of gradient descent. It is going to work, but it's also going to be relatively slow. Now, don't get me wrong, it's still going to run over our current data set of like 391 records or whatever it is in fractions of a second. But if we had a larger data set with hundreds or tens of thousands or many thousands of records, then it might actually take some amount of time. After we put together this initial implementation, we're then going to come back and replace it with a much faster version that has way less code, but is also going to be a lot harder to understand. Now, it's still going to be gradient descent, and it's still going to be doing the same basic steps of calculating a slope for m and b, and then updating our guesses. So what's going to be different here? Why is it going to be harder to understand? Well, put simply, we're going to use some really fancy code with TensorFlow to dramatically simplify the code and make it significantly faster during the step right here. So that's what's going to be going on there. We're basically going to come back and replace our initial implementation with some really fancy stuff that's just a little bit harder to understand. The reason that we're going to go through this in a two-step process is that when we do this initial implementation, we're going to use plain arrays of data, like our classic array of array data structure, so that it's really easy for you to follow and understand that we are still doing this exact same series of steps that we're doing over in the spreadsheet. If we just jump to the faster version down here right away, I can almost guarantee you it would not make a lot of sense. So we're going to do the easier to understand version first, and then come back and replace it with the faster, less code, but harder to understand version. Okay, so enough of that. Let's get to it. So I'm going to flip back over to my editor, and over here, we're going to start our initial implementation of gradient descent. And so I'm going to implement that as a new function called gradient descent. Remember, we want to be updating some possible value or our current guess of m and b inside this function. we have not yet actually defined or initialized our initial guesses for the value of m or b. So I'm going to make sure that I do that right away at the bottom of my constructor function. So right here at the bottom, I'm going to say this dot m gets initialized to 0, and this dot b equals 0 as well. So these are our initial guesses of m and b. We could have just as easily started them off with initial guesses at 100 if we wanted to, or even have them be different if we wanted to, because no matter what, remember, our gradient descent algorithm is going to eventually mold and shift these values over to the optimal solution. But usually, by convention, we start off with initial guesses of 0, or sometimes, possibly, initial guesses of 1 as well. Okay, so now we can start putting together our gradient descent. To do so, we're going to have to go back and look up our functions on how we actually calculate our slope of m and b. So here we go. Here's our functions on how we calculate our slope with respect to b and slope with respect to m. At the top, you'll recall is our mean squared error equation. This is the original equation that essentially tells us how good or bad our guess is. And then we've got the two slopes right here that essentially are just giving us that little signal that says m and b need to be larger or possibly smaller. So we have to actually write these functions out, more or less, inside of our editor. The process of writing these out is just going to be, a little bit cumbersome, so I just want to very quickly go through the series of steps that we're going to use to translate these to actual code. So first, quick example of how we would calculate the slope of MSE with respect to b. I want you to recall that this ugly symbol right here is a summation symbol. And so it essentially means run or calculate this inner value right here, calculate this inner value for every data point that you have. So we're going to take this initial data point. You'll see that I kind of put together this little test data set or fake data set right here. So we'll take our initial horsepower value of 60, and I will plug it in to X right there. And I'll take my initial mile per gallon, or my label, and I will plug it in for the actual value. And then if I have initial guesses of b equals 10 and m equals 1, I only made those different so you understand which one is b and m in this equation down here, then it would give me the first term in this summation series. So you'll see that for x, I put in 60, because that is my value for horsepower. And for actual, or kind of the y value in this case, I put in 30 right here, because that is the actual value of miles per gallon. So then after that, we go on to the next row. We take the 75, put it in for x, we take the 27, put it in for actual, put in the m and the b as well, and that gives us the next term. And we repeat that process for the entire data set and then add them all together, and then make sure that we multiply that number by 2 and then divide it by the number of different data points that we have, which in this case is 4. Now, of course, these are just using this fake data set right here. Our actual data set has like those 390 or something records inside of it. Now, before we start to write out the code for this, one last quick little thing. You'll notice that there's the mx plus b term inside of here. The mx plus b term is essentially our current guess of what our miles per gallon should be. And so when we calculate mx plus b and subtract actual, that's returning a number that essentially is saying, here is the difference between what the actual value was for this data point and what we just predicted it to be. So again, mx plus b is our guess at what the miles per gallon is, given our current guesses of m and b as well. Now the reason that I point that out is you'll notice back on the other equation that we have, so we were just looking at slope of MSE with respect to b. On this other equation with the slope with respect to m, we have that same mx plus b term right here. So I think that to make our lives a little bit easier and make these calculations a little bit easier, we could very easily do a two-stage calculation process. We can do one calculation step where we loop through all of our different x or feature variables and we calculate mx plus b. And so we would run through all of our features, or in this case, our horsepower values, and we would calculate mx plus b for all those. And then once we have an array that has all those current guesses for our miles per gallon, we could then very easily put together the rest of both these equations. And so again, just a two-stage calculation process. We're just going to break this up into 2 steps to make our lives and the logic here a little bit easier. So back over here, gradient descent, I'm going to put together an array that's going to be my current guesses at our miles per gallon. So I'll say current guesses for MPG, like so. I'm just going to use a very direct variable name here. We're going to eventually replace it with something that makes a little bit, or is a little bit more generic, because obviously this one is currently very tailored for miles per gallon. So then we're going to iterate, we're going to map over our features array that you'll recall has all of our different horsepower values. So all the different horsepower values. Remember, that is an array of arrays, so I'm going to receive each inner array as a variable that I will call row. And then in this inner function, I'm going to calculate that mx plus b. So I'm going to return this dot m times row at 0, because row at 0 is my horsepower value, plus this dot b, like so. Okay, so I've now got my current guesses array. Again, this is an array of data right here. And so that represents all these inner mx plus b terms. So like the 1 times 60 plus 10, 1 times 75 plus 10, and so on. So now that we have this array, we can do another map statement or even a for loop if we wanted to. And all we have to do is iterate through those guesses and subtract the actual values and then sum them all together. So again, the only purpose of this was to make this calculation a little bit easier to read. Let's take a quick pause right here. When we come back to the next section, we will take these calculated guesses that we just put together, we'll subtract the actual values, and continue from there. So quick pause, and I'll see you in just a minute. In the last section, we put together an initial calculation step that's going to find our current guesses for our MPG values. So this is going to be an array. Inside of it is going to be all of our guesses of mx plus b. Remember, the xi value right here is each of our initial feature values. So in this case, x at 0 would be our first observation for our horsepower of a car. X at 1 is going to be the horsepower at the second observation, and so on. Now that we've got the guess values right here, we can run the entire or calculate the entire equation or value of our slope with respect to b. And all we have to do is take our guess, subtract each of the observed actual values, which is going to be our labels, and then we will divide all that by the number of observations we have and multiply it by 2. So let's get to it. Back inside of my function, I'm going to make a new array here, or excuse me, a new variable that I'll call bSlope, because we're going to take care of calculating the b value slope first. I'm then going to reference current guesses for mpg.map. And then on this inner function, my first argument is going to be the guess, or the current value of mx plus b, because we're going to iterate through all those. And then I'm going to take in the optional second argument here, which is I. I is the index that we're currently mapping over. And you're going to see why we need this I, or index value, in just a second. So now inside this function, all we have to do is run the inner logic that you see right here. So we're going to take our current guess, which is mx plus b, and we're going to subtract the actual value, or our label, or our y value. Essentially, this is our miles per gallon, what the real mile per gallon value was for the car. So I'm going to return my current mx plus b guess minus the actual miles per gallon value for the car. The actual value is stored inside of our this.labels property. Remember, this is an array of arrays. The inner arrays all contain a single value, and that is the MPG value. We saw that console logged out at our terminal just a little bit ago. So back down here, we're going to say guess minus this.labels. I want to look at the I row, because remember, I right here is the index of the guess that we are currently iterating over. All these indices line up between both the features, the guesses, and the labels. So to get the appropriate mile per gallon value, we're going to look at this.labels at I. And then remember, this.labels is an array of arrays. So when we reference at I, that's going to give us our row, or essentially that entire inner array. We want to get the first element out of there, which is the actual mile per gallon value. So I'll put on the 0 like so. Okay, so that's pretty good. Now that gives us back an array that has all the calculated values for this inner term right here. So we now need to sum up all those values, multiply by 2, and then divide by the number of observations that we have. So to do the summation step, we're going to use Lodash just because that makes it really easy. We could always do a vanilla JavaScript reduce function as well, but using sum is just a pretty straightforward way of doing it. So at the top, I'm going to make sure that I require in the Lodash library. So I'll say const underscore is require Lodash. And then back down here, I'm going to wrap that entire calculation with a underscore dot sum call, like so. Make sure you get parentheses for the sum function on both sides. Now, after adding up all these terms, we need to make sure that we multiply by 2 and divide by the number of observations. So I'm going to multiply by 2, and then I'll divide by my number of observations, which is essentially just the length of either features or labels. Remember, both these have identical lengths, and it's the total number of observations or data points that we have. So I'm going to divide by this .features.length. Okay, so that's pretty much it. Now when I save this file, you'll notice that my code does a little bit of a jump here. Again, that's my automatic code formatter that's just kicking in and putting together a different way of formatting this line, but still the same exact code I had before. So now that we've got the b slope put together, we're going to go through that same exact process, but we're going to calculate our slope with respect to m. Now the equation here is generally the same. The only big difference is that we need to multiply that inner difference by our feature value, or essentially in this case, our value of horsepower at index of I. So we're going to make sure that we get that little change in there. Underneath our b slope, I'll do my const m slope. So this is going to be how much we need to modify our value of m by. We're going to again map over current guesses for MPG. I'm going to get my current guess and my index. And then inside of here, we're going to return -1. The -1 is because the x right here is supposed to be negative. So I'm going to say -1 times, and then I need to get my current x value, which recall is my horsepower. To get my horsepower, I need to go back up to my features array, because features has the original x values, or the original feature values inside of it. So -1 times this dot features at I. Again, remember that is an array of arrays, so I'm going to pull out the 0 or the first index at that inner row. And then we're going to multiply all that by our current actual guess, so actual at I, which is this dot labels at I, and again, array of arrays, so I'm going to get the first element out of there. And then I'm going to subtract by my mx plus b value, which is my guess that I'm currently mapping over. Now again, we need to make sure that we sum the array that gets returned from this. We get back an array because it is a map statement, so we need to sum all those terms together. So I'll do my underscore dot sum. I'm going to wrap it with parentheses. I'm going to multiply it by 2, and then I'll divide by this dot features dot length again. Now once again, I'm going to save this file, and you're going to see all my code jump as it gets automatically reformatted. Okay, that looks good. Now let's take another quick pause right here. When we come back to the next section, we're going to take our b slope value and our m slope value and use those to update our current guesses for m and b. So quick pause, and I'll see you in just a second. In this section, we're going to finish off working on our initial implementation of gradient descent. Now, looking at this code, I think you can already agree with me that it's kind of messy. Well, it's really, really messy, let's be honest. So there's probably some clever tricks we could do in here with Lodash to clean this up, but I think you'll agree with me that in general, this is some messy looking code right now. And so this is part of the reason why we are going to eventually come back to that function and re-implement it with TensorFlow. And I think that you're going to be really shocked at how many lines of code we're going to reduce our gradient descent to. Really, it's going to be quite surprising how condensed down that function is going to be. All right, let's stay on track. So we've now calculated our values for the slope of MSE with respect to B and with the slope with respect to M. So we now need to take these slope values and use them to update our current guesses of M and B. Remember, we had initialized M and B as instance variables up inside of our constructor, and we started them off at 0. So now to update those values, you'll recall all we have to do is take our slopes, multiply by the learning rate, and then subtract M and B by that product. So just a quick reminder here. Here we go. We found the slopes. We're going to multiply them by the learning rate, and we're going to subtract the results from b and m. Okay, so down here at the bottom of my gradient descent function, I'm going to say this dot m equals this dot m minus my m slope times our learning rate. And remember, we put our learning rate, or we said that we were going to provide it by default, or either provide it as an option to our constructor when we make our class of linear regression. We stuff that thing inside of our options object. So back down here, here's my m slope. I'm going to multiply it by this dot options dot learning rate. And then I'll do the same thing for b as well. B slope this time around, make sure you use b slope, not the m slope, times this dot options dot learning rate. Okay, so that's pretty much it. So I'm going to flip back over to my index.js file now. I'm going to make sure I save this one. Make sure you save linear regression. And then I'll go back over to index.js. And then inside of here, we're going to require in that linear regression class that we just created. So I'm going to say const linear regression is require, and the name of that file was linear-regression. And that's in the same directory, so I'll put in /. All right, that looks good. Now, one quick thing that I just want you to triple check and make sure that you have in here, if you go back over to your linear regression file, go down to the very bottom and make sure you've got that module.export statement. That's how that class actually gets exported from this file so that we can eventually require it into the index.js file. All right, so now back over inside of index.js, we're going to take a quick pause. When we come back, we're going to create an instance of our linear regression class. We're going to pass in our features and labels and try to calculate our optimal values of m and b. So quick pause, and I'll see you in just a minute. In this section, we're going to make use of our linear regression class, and we're going to start running our gradient descent analysis with our features and our labels. So let's get to it. At the bottom of my index.js file, I'm going to create a new instance of the linear regression class. So I'll say const regression. So that's going to be the name of my instance of the class. New linear regression. And then remember, when we make an instance of this class, our constructor function is expecting that we're going to pass in features as the first argument, our labels as the second, and then an options object as the third. So back over in index.js, I'm going to make sure that I pass in my features and my labels, which we had just loaded up out of that CSV file. And then as a third argument, I'll put in the options object as well. Right now, the only possible property so we can put into our options object is the learning rate and the number of iterations that we want to run our gradient descent algorithm for. We have default values for both those properties being set up inside of our constructor, but in this case, I'm going to override both those default values because I want to tailor them. Remember, these defaults right here are essentially fallbacks. Usually we are going to override them, but just in case we forget to enter one of these properties into the options object, the default will kind of take care of it for us and prevent us from having just a catastrophic error in our algorithm. So I'm going to start off with a learning rate of 0.001 like so. Remember, the learning rate is more or less a pretty arbitrary value, and there's not just some like hard fixed number that I can tell you is always going to work out really well. It's a series of trial and error. And so we might start off with some like, I don't know, just random guess. This is essentially random guess. And then after running our regression a couple times, I might come back here and optimize it to be like, okay, 0.057 seems like it's working out pretty well. Oh, come on, 0.1. There we go. Now the other option here is the number of iterations we want to run our algorithm for. For this first time around, I want to run it just one single time by itself. So just one iteration of gradient descent so we can make sure that we are getting back some realistic output when we update our values of m and b. So now after that, I'm going to call regression.train, like so. Remember, we have the gradient descent function and we have the train function. Right now, all the train function does is call gradient descent for some preset number of times. So we could definitely call gradient descent directly if we wanted to, but in general, the idea here is that we're going to call train instead and have our class automatically run gradient descent for us for however many of iterations. So in this case, because we said iterations 1, when we call train, gradient descent will be executed exactly one time. Now after that, I'm going to put a console log in here, and I'm going to print out our updated values of m and b after running gradient descent for one iteration. So I'll say updated m is, and then to print out the m, all I have to do is reference regression.m, like so. And then I'll say updated b is, and that will be regression.b, like so. I'll zoom out for just a little bit so you can see that line a little bit more easily. Remember, on our class inside the constructor, we set up m and b as instance variables. And so that's why we're able to very easily reference them like so. Okay, so I'm going to save this file. I'm going to make sure that both the index.js file and the linear regression file are saved. Make sure they're both saved right now. And then I'm going to run this by flipping back over to my terminal. I'm going to make sure I'm inside my regressions directory, and I'll execute node index.js like so. Now you'll notice that I get that nasty output here that we can completely ignore. Hopefully you are watching this course at some point in the future where you can turn off these messages a little bit more easily. You can actually turn this initial one off right here by setting an environment variable, but I'm just going to skip it so you see what I see, or you are seeing what you are probably seeing on your own screen here. Okay. Forgetting those messages for just a second, you'll notice we have our console log right here. So we have an updated m value of 4.42 and an updated b value of 0.04. And so it looks like after one iteration of gradient descent, we have successfully updated our values of m and b. Now these are probably not the ideal values. Remember, even when we were back using that spreadsheet to do the gradient descent by hand, we saw that we had to run gradient descent a set number of times, like at least about a dozen or so, before we ever once saw our optimal values of m and b start to appear. So in order to make sure that everything really is working correctly and that we get a real solution here, we need to dial up our number of iterations. Remember, ideally at some point in time, we would put in some type of convergence check to say, hey, if our slope of m and b are sufficiently small, then we probably have a good solution and we can stop going through the iterations. But for right now, we'll just skip that step, and we're just going to say that we are really just concerned right now with running for a preset number of iterations. So I'm going to dial up iterations right here. I'm going to say that I want to run for 100 iterations of gradient descent. So I'm going to update that. I'll save the file. And then I'll go back over to my terminal and rerun node index.js. So now this time around, you'll see that m has gone negative, and it's at 4.85, and my b value is negative 4.10. But if you look really closely at these numbers, you might notice that something is very, very wrong here. At the very end of the m value is this little e plus 136, and on the b term, I have e plus 134. So this is scientific notation in JavaScript. This is essentially saying that our current value for m is negative 4.85 times 10 to the 136 power, which is a almost unfathomably large number, like impossibly large. That is incredibly, incredibly, incredibly large number. So what this means is that we are calculating some values of m or b and b, but we are using a very poor learning rate. Remember, we actually saw this occur back over on that spreadsheet. If we put in a learning rate right here that is too large, then whenever we do our correction of m and b, we're going to jump over the optimum value. And we're going to essentially ping pong back and forth with increasingly large values, always skipping over the optimal point. And so we could very easily see that back over here. If I put in like a learning rate of 1000, we saw that these values just get increasingly larger and larger and larger and larger. So there's two ways that we can fix this. We can either start to update our learning rate right here and tune it down a little bit. So rather than a learning rate of 0.001, I could add in another 0. So now the learning rate is 10% what it was previously. So then I could save this and flip back over and rerun node index.js. And now in this case, you'll see that, again, it's very clearly a large number. So we could continue to tweak our value of the learning rate if we wanted to. But one other possible solution here would be to do what we had discussed when we were looking at the spreadsheet over here, and we were initially talking about these very large values of m and b. Remember, I had said that we could run a min-max normalization, or we can do a standardization on our feature set. when these input feature sizes are more towards the 0 side of things, when it's a very small range, we end up being able to put in much more flexible values for our learning rate. And in general, it does not actually output our end analysis. So we had seen that here when I entered in these kind of min-max values that I just kind of made up off the top of my head. When I put those in, I was then able to put in a very reasonable learning rate here of like 0.1. And then we eventually saw these numbers start to like really stabilize around like 72 and 206 or so. So again, that's the two possible solutions that we can use to address the issue of these numbers just spiraling out of control. So we can either update the learning rate and tweak that a whole bunch, or we can just do the min-max or standardization. Now remember, one quick thing I want to remind you about here is that we are doing kind of a initial implementation of gradient descent, where I just wanted to show you the calculations using array of arrays. And then eventually we were going to refactor that stuff to use TensorFlow. So at this point, I think you will agree with me that our current implementation is not perfect by any stretch of the imagination, and we're not getting an actual result during our analysis. But rather than going through the process of putting together the min-max stuff or spending a bunch of time tweaking the learning rate, I'm going to say, you know what, we've more or less proved that we can run gradient descent with arrays of arrays. And I think that you probably can see like the underlying calculations occurring here in the gradient descent function. So at this point, I'm going to say, yep, we can do it. We understand it. We put these equations together and we ran the gradient descent process. Rather than wasting any more time with this, we're now going to say, okay, like we learned that, we got it, it's down, we saw the calculations. So now moving forward, we're going to take a quick pause. When we come back to the next section, we're going to start to refactor that gradient descent function to use TensorFlow instead. After we do that refactor, we'll then go through those additional steps of like tweaking the learning rate a bunch or implementing the min-max or standardization. And then we'll see the true analysis start to shine through for our horsepower versus miles per gallon. So with that in mind, let's take a quick pause. When we come back to the next section, we're going to start to replace our gradient descent algorithm with TensorFlow, and it's going to be a pretty fun process. So let's get to it. In this section, we're going to start to take our gradient descent function and re-implement them using TensorFlow. The end result is going to be some code that is much faster, and we're going to have way less code, but it's also going to be a little bit harder to understand. So in this video and the next couple, I'm going to give you a little bit of baseline knowledge to understand exactly what the nature of this refactor that we're going to do is. It's going to require you to learn a little bit more mathematics in order to understand exactly what's going on. So let's get to it. Now, the first thing I want you to understand is what we are trying to achieve here. I want to be able to calculate both these equations that we're currently calculating inside that gradient descent function using only TensorFlow methods. If you go back over to the gradient descent function right now, you'll see that we've got some map statements, we've got some manual multiplication and addition, and we've got some Lodash logic in here as well. So I want to remove every single map statement, I want to remove every single Lodash function, and I want to remove all of the manual multiplication, addition, and subtraction down here. And I want to replace every single one of those operations with a TensorFlow method instead. So that's the end goal. That's what we're trying to achieve. In order to achieve that, like I said, we're going to have to go through a little bit of mathematics. So in this section, to give you your first little taste of some additional math that we need to learn, we're going to start talking about matrix multiplication. This is a linear algebra operation between two matrices. Now, we've not really spoken about matrices or a matrix so far in this course. For all of our intents and purposes, for as far as you and I are concerned, we're going to say that a matrix is the same exact thing as a tensor. So we've been speaking about tensors throughout this course nonstop. I'm going to start referring to these things called matrices or a matrix. Whenever I say that, I essentially am just saying the same thing as a tensor. There are some very small differences between the two, and we'll talk about the differences later, but for right now, again, we're just going to assume that a tensor is a matrix and a matrix is a tensor. Okay, so let's get to it. What is matrix multiplication? We're going to learn about matrix multiplication by going through 3 steps. We're first going to learn how we can check to see whether or not two matrices, so two separate tensors, are eligible to be multiplied together. We'll then figure out exactly what the output of matrix multiplication is and what it means, and then finally we'll go through the actual operation of how we do matrix multiplication by hand. We're going to not actually have to do matrix multiplication by hand. I just want to walk you through the process so you understand exactly what's going on with the mathematics and why it's relevant for what we are trying to do here with gradient descent. So let's get to it. First thing we need to discuss is how we can figure out whether or not two matrices are eligible to be multiplied together. So in order to determine that, we have to look at two different matrices or two different tensors, and we have to examine the shape of both of those different tensors. So in this case, I've got tensor A and tensor B. I'm going to refer to these in the future or the next couple slides as matrix A and matrix B as well. Remember, matrix and tensor interchangeable definitions as far as we are concerned for right now. So the shape of tensor A over here is 4 rows, 2 columns. So the overall shape is 4, 2. Tensor B over here has 2 rows and 3 columns. So the overall shape is 2 and 3. In order to determine if two tensors are eligible for matrix multiplication, we put those two shapes right next to each other, like those two little arrays. We sandwich them up to each other, and then we look at the two numbers that are touching. So let's take a look at an example of that. So here's the shape for matrix A and the shape for matrix B. We can imagine that we take those two shape values, we stick them up right next to each other, and then we say, are the two numbers that are now touching equal to each other? If they are equal to each other, then they are eligible for matrix multiplication. So the inner shape values in this case are the same. They are both equal to 2. We can safely multiply matrix A by matrix B. Now let's take a look at an example where this operation would not work out. So I've now got matrix A up here with a slightly different shape. It now has 4 rows and 3 columns. Matrix B on the right-hand side has 2 rows and 3 columns. So if I now take these two shapes and stick them next to each other, these two numbers right here are not identical. They have different inner shape values, and so matrix multiplication is not allowed between matrix A and matrix B in this case. Now I want to show you something interesting. As you very well know, in the world of simple addition and simple subtraction, if we write out a simple equation, and I'm just going to do this in my terminal just for lack of a better place to write, you and I know that if we do an operation like 10 plus 5, that is the same exact thing as 5 plus 10. In other words, the order in which we list out these addition arguments makes no difference. We can flip the order, we can jumble it all around, and it's always going to lead to the exact same result. The same is not true in the world of matrix multiplication. So when I looked at this first example here and I said I want to multiply matrix A by matrix B, that is making a very distinct operation, A times B. A times B in the world of matrix multiplication is not the same as B times A. So in other words, if we flip the order of these two matrices right here, we would end up with an extremely different result. So in this case, we would have to compare the two shapes now in a reordered fashion. So let's take a look at that. So let's say that I want to multiply matrix B by matrix A different order than what we were looking at before. So I would now list out the shape of matrix B, which is 2 by 3, and I would list out the shape of matrix A, which is 4 by 2. So now I sandwich these two things together, and I see that the inner values here are no longer the same. And so now matrix multiplication would not be allowed. So the lesson here is that the order in which we try to conduct matrix multiplication makes a tremendous difference on the actual output that we get. So we need to be very aware of the order in which we are applying a matrix multiplication operation. Okay, so in this section, we spoke a little bit about matrix multiplication. We still don't really know what it is at all. The only thing we've said is how we can check to see if two matrices are eligible to be multiplied by each other. In order to do so, we look at the inner shape values. If they are the same, then we are allowed to multiply the two matrices by each other. So let's take a quick pause right here. When we come back to the next section, we're going to start to talk about what the output of matrix multiplication is. So I'll see you in just a minute. In the last section, we started talking about matrix multiplication. We first discussed how we can determine whether or not we can multiply two matrices or two tensors by each other. We're now going to discuss what the output of matrix multiplication is, and then we'll talk about how it is actually done by hand. Remember, the entire goal of all this is to dramatically simplify the logic inside of our gradient descent function. All right, so first off, what is the output of matrix multiplication? When we multiply matrix A by matrix B, the result is some new matrix that we call matrix C. The values inside of matrix C are determined by the values inside of A and B. We'll walk through the actual process of how that multiplication or how the values inside of C are determined in just a second, but first I want to tell you how we determine the shape of this output matrix C over here. In order to determine the shape of C, we're going to again look at the shape of A and B. So we're going to again take these shapes, we're going to stick them together, we compare the inner values, and we make sure that they are identical and equal to each other. We can then imagine that we kind of delete those inner shape values. Then the output matrix C over here is going to have shape of these two leftover numbers, which in this case is 4 and 3. So the shape of matrix C over here would be 4 and 3, like so, because we have 4 rows and 3 columns. All right, so again, in order to determine the output of matrix multiplication, we look at the shape of our input matrices. Let's now start to go through the operation by hand and really understand how matrix multiplication is done. As soon as we go through this last step, we'll then be able to very quickly take a look at our actual gradient descent algorithm and see how our real values of M and B and our features and labels and whatnot are going to be working with matrix multiplication. So don't worry, there is a light at the end of the tunnel. All right, so let's imagine that we are trying to multiply matrix A by matrix B and determine the values that will be inside a matrix C. In order to do so, I'm going to write out matrix C. I'm then going to write out matrix A to the left-hand side, and then matrix B right above it, like so. We're going to determine what the values inside of matrix C are, cell by cell. So we're going to first start off with this first cell right here. In order to determine this first cell, we're going to look at the top left value of matrix A. I'm going to color code that as blue, and then I'm going to find the top left value of matrix B, and I'll color code that as blue as well. So now the first cell right here is going to be equal to those two values times each other. So I would do 1 times 10. Now that's not it, that's not the complete answer. The complete answer would be then to go to the right on matrix A, so the next cell over to the right, which I'm going to mark as green, and then on matrix B, we go to the next cell down. And I'll color code that as green as well. So we'll now multiply these two values together and add that to the multiplication that we already did in there. So that would now be 5 times 20. And now on matrix A, we would try to go over to the right again, but in this case, nothing else over here. And on matrix B, nothing else underneath it. And so the total value inside of this first cell right here would be the product or summation of those two terms, which in this case would be 110. So I would put 110 in there like so. So the rule that you want to follow here is whatever you wrote out to left-hand side, you're going to go from left to right. The matrix on top goes from top to bottom. So now we can move on to the next cell here. The next cell will be 2 times 10. So notice how we went down one row on matrix A, but on matrix B, we stay in the same column. So this would now be 2 times 10 plus 6 times 20. So 6 times 20, which would be, what is that, about 140. So now we go down to the next row, 3 times 10 plus 7 times 20. So that's about, let's do 7 times 20, that's 140 plus 30, which would be 170. Now the last row here, we'll do 4 times 10 plus 8 times 20. So 8 times 20, that's 160 plus 40, 200, like so. My apologies if I made any mistakes in the math here as I'm going through this. Talking about this stuff and doing the math at the same time, sometimes a little bit challenging. Okay, so that has determined the values in each one of the indices in this first column right here of matrix C. So now we would move on to the next column over. So to do so, I would now start to look at the second column of matrix B, and we're going to again iterate through every row of matrix A. So this first value right here in the second column of matrix C would be 1 now times 30. So I would do 30 let's just write out the entire term here rather than each individual number. And then we'll do 5 times 40 to be 200, so we get 230. Then we would do 2 times 30 and 6 times 240. Or excuse me, 6 times 40. So that's 240 plus 60, 300. Then we would do the 3 times 30 and 7 times 40. So what is that? 280 plus, I think that's around like 360 or so, and so on down to this last row down here as well. And then when we would repeat the process for the last column too. So we would then go to 50 times 1 plus 60 times 5, and then just keep on going down that column like so. Okay, so that's how we calculate the actual values inside this output matrix over here. Now, again, you don't really have to understand exactly the operation because we're never really going to have to do this by hand. I just want you to understand that the values inside of matrix C are composed of the values inside of matrix A and matrix B. So now that we've gone through this example, let's take this newfound knowledge around matrix multiplication, and we're going to start to understand how we can dramatically simplify some of the logic inside of gradient descent. So quick pause, and we'll get to that in the next section. In the last 2 sections, we started to talk about matrix multiplication. I'm really excited because now we get to start to pull this idea of matrix multiplication together with all the code that we've written so far and really understand how matrix multiplication is going to allow us to simplify some of the logic inside of our gradient descent function. Before I tell you exactly about how all this stuff is going to work together, a quick reminder on gradient descent. There's one real key thing inside of here that I want to pull your attention to. Inside this function, we first calculated what our current guesses for mile per gallon was using m and b. We then calculated our b slope, or essentially our change in mean squared error with respect to b and with respect to m. And inside of both of those equations, we were doing a little bit of math, but then more importantly, we had that big sum operation using Lodash. Remember that? In both cases, we were using sum. And then once we calculated the m and b slopes, we used them to update m and b. Now, as we were just talking about matrix multiplication 2 seconds ago, I want to remind you about one thing, and this is what's going to kind of tie our current code together with how we're going to refactor it with matrix multiplication. So when we were just talking about this 2 seconds ago, we did a quick example right here. I cleared out some of the numbers. Remember, we had said that we take this blue value, so top left of matrix A and top left of matrix B, we multiply those together, which would give us 1 times 10, and then we add the product of the next column with the next row on matrix B. So that would have been 5 times 20. So what does it kind of seem like this operation right here is that we're doing as we go through each step of matrix multiplication? It kind of seems like we are taking a sum. We multiply a couple different terms together, so like 1 and 10 and 5 and 20. We multiply each of those pairs of numbers together, and then we sum them together. That summation step seems like it's incredibly relevant when we start to think back to that slope of MSE with respect to B and with respect to M equations. Remember that big ugly symbol right here, that is a summation symbol. And it essentially is saying we need to find some inner value inside of here for all the different values of our feature or all the different observations that we have, and then we need to sum those all together. And so it kind of seems like at least that aspect of matrix multiplication seems very similar to this summation step right here. And so that's essentially what we're going to be doing inside of this refactor of gradient descent, that it's going to allow us to do a really awesome refactor and get some very concise logic. It's all tied to the fact that we have to take a summation, and when we are doing that matrix multiplication step, we are doing a summation in there as well. So let's start to talk about how we're going to use the idea of matrix multiplication to dramatically simplify how we find the slope with respect to B and M, and then use them to update our values or our current guesses of M and B. All right, so here we go right here. This is going to be our new equation that we're going to use to update or find the slope of MSE with respect to M and B at the same exact time. So we're no longer going to have 2 separate equations. Remember, back inside of gradient descent right now, we have one calculation process for B slope and one for M slope. So we're going to condense all that down to a single equation where we are going to do a little bit of math here and then find how much we need to update m and b by in one step. So the general equation that we're going to use is going to be features matrix multiplied with our weights. Now we've never used the term weights before. The term weights right here is going to be our values of m and b inside of a tensor or inside of a matrix. So rather than having m and b separated out as separate instance variables, as we initialize them up here, we're going to instead stuff them into a matrix instead, or inside of a tensor. So then we'll do features matrix multiplied with our weights. We'll then do matrix subtraction here. So this is element-wise subtraction with all of our labels. And then the result of all that, we're going to do matrix multiplication with our features again. And then after we do all that math, we'll then divide the result by the total number of observations that we have, or n. And that's going to give us, as an output, a single tensor that contains the slope of MSE with respect to m and b. Now, I'm sure going from the equations that we've looked at so far, like these right here, and then jumping over to this vastly simplified one right there, is a little bit of a shock. It might be a little bit surprising. We're going to walk through the steps of how we're going to get from more or less these nasty looking equations right here over to this much nicer looking one right here. So we're going to look at this thing, we're going to kind of substitute in a couple terms to understand why we're multiplying what by what, and eventually after we walk through all this multiplication and all this arithmetic and whatnot, you're going to see how if we have all of our data in tensor form, this is the equation that we have to run instead to get our slopes with respect to m and b. So when I had previously told you that we were going to do a refactor to our gradient descent function, and it's going to have dramatically less code, and it's going to be much faster, this is pretty much why. And we're going to do a couple of very straightforward, simple operations. And after we do so, it's basically like what? 1, 2, 3, 4 operations total, as opposed to before where we had, well, I'm not even going to count here. We had a lot more operations that we had to do by hand. We're still technically doing all the same exact math, but the math is being wrapped up for us automatically inside of all these matrix operations or this matrix multiplication. Okay, so at this point, I haven't really given you a lot of detail on how this is going to happen besides just say like, oh yeah, here's like the function we're going to run. So let's take a quick pause right here. When we come back to the next section, we're going to start to look at how we can convert these two equations into this single equation that essentially does all the same math for us. So quick pause and I'll see you in just a minute. In the last section, I made the claim that we were going to take these two separate equations and condense them down to one equation, this one right here, and we would be able to do this thanks to matrix multiplication and a couple other steps as well. Now remember, these different variables that you see in here, for the most part, are different tensors, or again, we can somewhat interchangeably refer to these as matrices, just for the purposes of what we're doing right now, even though there are some other small differences between the two. The only variable inside of here that was a plain number was n, our total number of observations that we have over our whole data set. So starting in this section, I want to start to show you how we can more or less convert these two equations into this one single equation that will calculate both our slope for m and b at the same exact time. In this section in particular, I want to show you how we're going to abstract out this inner term right here of mx plus b. You'll notice that that term shows up in both these different equations. So we have right here mx plus b and mx plus b right here. I want to show you how we can essentially calculate that series of numbers using matrix multiplication. You'll recall that we already put together some code to calculate that exact term back inside of our gradient descent function. And so that was this stuff right here. We had said current guesses for MPG. We looked at all of our different features. We mapped over them. And for each different feature value, we ran m times x, this is essentially our x right here, plus b. So I want to figure out how we can essentially rewrite this chunk of code using matrix multiplication. So let's get to it. All right. So the first thing I'm going to do is take all of our different feature values. So in our case, our engine horsepower, and I'm going to put them all into a single tensor. So I've got x1, so that would be like my horsepower for car number 1, my horsepower for car number 2, horsepower for 3, 4, 5, and 6, and so on. Now the other thing I'm going to do here is take my values of m and b, and I'm going to stick them into a tensor, or a matrix, that we are going to refer to as weights. We're going to start to use this term quite a bit throughout this course, this term weights. anytime that we refer to weights, we are referring to some values that we want to calculate to relate our feature set to our label set. So in this case, our weights are our guesses or our current guesses of M and B that we want to optimize through our gradient descent algorithm. Now, in order to calculate the same thing that we were calculating back over here, we're going to do matrix multiplication between these two separate tensors. As we do this matrix multiplication, you're going to start to see how it's going to essentially run through the same exact code that we wrote right here. In order to do matrix multiplication, we first need to look at our shape values and make sure that these two different tensors are compatible for matrix multiplication. So I'll get my shape for my engine horsepower. Again, we're just going to assume that we have 6 different records here. That's good enough for a kind of fake sample size data set. So my shape would be 6 rows and 1 column. And then I'll get my shape for my weights over here. Now over here, I have 2 rows and 1 column. So in order to see if these two tensors are compatible for matrix multiplication, I would sandwich them up to each other like so. And then we need these two numbers to be absolutely equal. But in this case, well, it's immediately evident that those two numbers are in fact not equal. They're not the same, which means we cannot do matrix multiplication with our engine horsepower and our weights tensor. So it might seem like I just let us down like, 15, 20 minutes of a dead end here. Well, not quite. You see, we're going to use a little bit of a trick to get the matrix multiplication here to work out between our features tensor and our weights tensor. Now, the trick that we're going to use here is going to remind you of the min-max normalization that we had done previously. Remember, when we looked at min-max previously, I had put together that one video where I said, yeah, we're just arbitrarily changing these numbers, and it probably seems like we're just completely arbitrarily changing our data set here for like no good reason. And you would think that it would really dramatically alter the output of our algorithm. But in the end, we saw that, well, no, it didn't really change our results all that much at all. In fact, it dramatically improved them. So we're going to do a somewhat similar trick here to get the matrix multiplication to work out. When we do this trick, you're going to again say, Stephen, I do not see how this could possibly not completely mess up our calculation. But we'll walk through the calculation and you'll very quickly realize that it does in fact make sense and it does not actually change the output of our matrix multiplication here. Okay, so what's the trick? Well, essentially what we're going to do is we're going to take our feature set, so our feature tensor over here, and we're going to add on an arbitrary column of ones. So when I say arbitrary column ones, I mean we're just going to take our entire original feature set tensor and we're going to add on another column where every value inside that column is equal to 1. Just throw it on there. What the heck? So once we throw it on there, and we'll talk about why it's not going to change the output in just a second, we can then calculate our shape values again. So now we have 6 rows, but we have 2 columns. So our shape is 6 and 2. And then for our weights over here, we have 2 rows and 1 column. So when we now put these shapes together, those inner shape values are identical. And so we can say, yep, now these two tensors are eligible for matrix multiplication. And the output tensor from multiplying these two together is going to be a 6 by 1 tensor. That's going to be its shape. All right, so again, we're using a little bit of a trick here of just throwing on this column of ones. Let's now walk through the actual matrix multiplication math here, and you're going to very quickly see why adding on this column of ones does not actually output or affect our output whatsoever. Okay, so here we go. Now, I put the math in here already. I'm going to take these out and we'll walk through this together just to make sure it's really clear what's going on. Okay, so on the left-hand side, I have our first matrix. That's our feature matrix. And then on the top, I put what we might refer to as like our B matrix, the matrix that we're multiplying against. And then down here in the middle, I again have our output matrix, which we might refer to it as matrix C. So remember how we calculate all the different cells inside this output matrix. We're going to start at the top left of both these input matrices, and then we're going to look at the rows or we're going to alternate over the different columns. I should say we're going to go across a row on the matrix over here, and we're going to go down a column on the matrix up top. So we would do x1 times m plus 1 times b. So let's write that out. It would be m times x1 plus 1 times b. 1 times b. Now, quick question for you. What is 1 times anything? 1 times anything is just an identity equation. It's essentially saying the same as 1 times b is the same as just b by itself. And so we could really rewrite this right here as simply b, like so. So now you'll see that we get an output here of mx plus b, and it did not actually, that's exactly what we want right there. Adding on the column of ones did not actually adversely affect our output or change these numbers in any way. So putting on this column of ones right here is done just so we can get the different shapes to line up between our feature tensor and our weights tensor so that we can multiply them by each other. So now we can go to the second cell right here. To do so, we'll drop down a row on the left-hand side, and then we're still going to go from the top down on the matrix above. So this one would be m times x2 plus 1 over here times b. And once again, the 1 times term falls out because 1 times b is the same as b. And so we'd write that like so. And then as you might guess, this just goes down and down and down. Same thing over and over. Like so. x5 plus b and m times x6 plus b, like so. Awesome. Okay, so this new tensor that we just produced through matrix multiplication right here is the same exact thing as what we wrote over here, long form, with the map statement and this dot m times our mile per gallon, or excuse me, our horsepower value plus b. So at this point, we have now determined how if we just take our feature tensor, we add on a column of ones, and then put our m and b values into a tensor, and then multiply these things together, we'll end up with the same array of mx plus b values that we had produced previously. All right, so that's a good step right there, but there's still a lot more that we have to understand before we can truly say that these two equations right here are the same as this equation right here. So let's take a quick pause, and we'll continue in the next section. In the last section, we continued to try to figure out how to condense these two separate equations down to this one equation using some matrix operations. So at this point, we've gone through multiplying our features by our weights and then subtracting out our labels. And so if I took just this term right here and summarized it into one single diagram, what went on with all that, we would end up with something that looks like this right here. So we took our features, we appended on or concatenated on that column of ones, then did the matrix multiplication by our weights. So that right there, everything in the gray box essentially calculated the mx plus b values. That gives us back an array with all of our different mx plus b values. Then the next step was to subtract the actual values, or the actual mile per gallon of all of our different cars. And that left us with a single tensor that we referred to as our differences. So differences right here essentially represents, in these two different equations, it represents this part right here on equation for b, and just this part right here for equation m. So now on equation m, you'll notice that we've got the multiplication of the difference by x at I. So that's our individual feature value. But then on the b one, we don't have any multiplication by x at I. So now if we're really going to figure out how to combine both these equations down to this one, we need to figure out some way of multiplying the differences by the feature values when we're trying to calculate m, but not when we're trying to calculate b. Now, I'm sure that gets like really confusing very quickly when I start to, list all that stuff out, but let's go through this last section, and we're going to go through the last step of how we reduce these two equations down to the one, and I think you're going to very quickly start to connect the dots and understand how these matrix operations are the same as running these two separate equations at the same time. Okay, so let's get to it. So if I go back to my single equation over here, you'll see that we want to take essentially that differences tensor, and we want to do matrix multiplication, that's what this symbol right here is for, with our features tensor. So let's kind of walk through that process. How do we multiply features by that differences tensor that we've now learned how to calculate? All right, so right here we go. On the left-hand side, I've got my features with the concatenated column of ones on there. And I want to do matrix multiplication with the differences that we just calculated in the last section. And the first step to matrix multiplication is to look at the shape and determine whether or not these two tensors are eligible for matrix multiplication. So the shape over here on the left-hand side is 6 rows and 2 columns. And then over here on the right-hand side, we get 6 rows and 1 column. So we can then take these two shape values together, and we will compare the inner shape values. Are they equal? Are they exactly equal? Well, in this case, no, obviously not. 2 and 6, not equal. So how are we going to multiply these two matrices by each other? Are we just going to add on a bunch more columns of 1s? Well, not quite. In order to be able to multiply these two matrices, we're going to use another little trick. A trick similar to what we did previously in concatenating on this column of 1s. Now, again, very similar to the column of 1s, you're going to say to me, Stephen, I don't understand how doing this trick does not dramatically change the result here. How does this not dramatically change the calculation? You're going to say that. But just bear with me. Just trust me. Because as soon as we start to walk through the matrix multiplication, after doing this little trick, I am pretty convinced that for you, everything is just going to kind of click. And you're going to say, oh, I see what you did there. Okay? All right, so let's do it. Let's see what this little trick is that we're going to use to be able to multiply these two matrices. So the trick we're going to use is to take the transpose of the matrix on the left. We have not spoken about transposes yet. When we take the transpose of a matrix, we essentially take each of its columns, and we take that entire column right there, and we turn it into a row instead. And so you can kind of imagine that we're twisting this matrix, or this tensor, so to speak. Let's take a look at the next diagram, and you're going to see what the transpose of this matrix is. There we go. That's the transpose of the matrix we were just looking at. So we took the entire column right here, and we turned it into a single row that spans out to the right. We then take the second column right here, and we turn it into the second row that spans out to the right. So there's no math involved with it. We're essentially just kind of reshaping the entire thing. Take the entire column, turn it into a row. Take the next column, turn it into the next row, and repeat the process for however many columns we have. So again, we've taken the transpose here, and now you're probably thinking, how does this not dramatically change the result? Again, just bear with me for 1 second. Let's go through the math now. So I want to again calculate the different shape values. So now for the transpose of our feature matrix on the left, our shape is going to be 2 rows and 6 columns. And then for the differences tensor on the right, we have 6 rows and 1 column. And so now when we put these two shapes together, yep, 6 is equal to 6. This is eligible for matrix multiplication. And the resulting shape of the matrix that we get from multiplying these things two together is going to be a 2x1 tensor, a 2x1 matrix. That means it will have 2 columns, or it's going to be 2 rows and 1 column. All right. So, looks like this will work out. Now let's try going through the actual math here of how we would actually do the matrix multiplication on these two tensors with each other. Okay, so I did the same little sequence again. Here's what we might refer to as matrix A and matrix B. So we're going to go along each row, or each column here. Sorry, I mean to say along a row. That's why I say each row. So we're going to go along the row, and we're going to take each one of these values and multiply it with the corresponding value in this column right here. So let's go through it element by element. So it'll be x1 times difference 1. Now, rather than referring to this as difference 1, let's just abbreviate it as d1 and d2, d3, d4, d5, and d6, just to make writing this stuff out a little bit more easy. Okay, so we'll do x1 times d1. So that will be x1 times d1. Now the next term will be x2 times d2. So we're going to add on x2 times d2. And then the next one is going to be x3 with d3. And I think you get the idea. Let's just write out the rest of the terms here. x3 d3 plus x4 times d4 plus x5 times d5 plus x6 times d6. Oops, 6. All right, so now we'll move on to the second row here. We're going to go across this row and still span the same columns. So we'll do the first term. That's going to be 1 times d1. Remember, 1 times d1 is equal to d1. So we don't need to write out the 1 times part. We can just put in here simply d1. And then the next term will be 1 times d2. We're going to add that on. And so we'll go right along that row, and it's all going to be 1s times d1, 2, 3, 4, 5, 6, and 6. So this would be d1 plus d2 plus d3, d4, d5, and d6, like so. So that's the output right there of matrix multiplication between the transpose of our feature matrix and the differences tensor that we had previously calculated. Now, these two terms right here might not look super meaningful. Remember, this represents an output matrix or an output tensor, and it has 2 rows and 1 column. Now, before I tell you exactly what these things are, I'm just going to copy these and pull them back to a diagram that we've been looking at quite a bit throughout the last 24 videos of this course. Okay, so I'm going to copy those two back over here. I'm going to zoom out for just a second. I'm going to paste in both of those cells, and then I'm going to match them up with one of these equations. So I'm going to take that one right there and put it there. I'm going to take that one right there. I'm going to put it there. And now my question to you is, does it look like we just calculated the same thing that's mentioned in each of these equations? Let's omit the 2n term out here in front and just consider the summation terms in here. So remember, this entire thing right here represents that difference that we had calculated. We just went through that entire calculation in the last section. We had said that was this stuff right here. Remember, we had just said differences, d1 through d6 represents just that term, and differences represents just that term without the xi's on there. And so we had said that for m, we need to make sure that we multiply the differences by our feature values, x at 1, x at 2, x at 3, x at 4, and so on. And so when you look at these, well, it looks like we kind of succeeded in doing exactly that. For the slope with respect to b, we have taken all of our difference values, or all this differences that we calculated with that term right there, and we've gone through that summation step, which is indicated by that ugly little symbol right there. So we found d1 plus d2 plus 3, 4, 5, and 6. And then for the second, or the slope with respect to m down here, we took all of our differences, we multiplied by them by the respective feature values, so like x1 times d1, x2 times d2, and so on, and then we went through that entire summation process, which is what was indicated by that nasty little symbol there, and said that we had to take all those different multiplications or all those different products and sum them all together. So the product, or the end result of doing the matrix multiplication between the transpose of our feature matrix and our differences tensor over here, is a 2-by-1 tensor that contains the exact slope values for m and for b. So all that stuff, all the calculation we just went through over here, the end result of it is this 2-by-1 tensor where the first entry in it is m and the second in it is b. Well, sorry, I say m, I mean to say m slope, and the second is b slope. So that's it. That's how we went from taking the two separate equations and then using a lot of clever little tricks with a little bit of linear algebra mixed in there as well to calculate our m slope and our b slope with exactly one equation instead. All right, so I'm hoping that at this point some of this stuff makes a little bit of sense. Now, a couple things I want to remind you about. Remember, we've only calculated the slope at this point in time. If we go back over to our code editor, remember we calculated the b slope right here and the m slope right here. And so once we got those slopes, we still had to use them to actually update our guesses of m and b. But hey, considering that we just reduced all this stuff down to a series of simple operations, well, if you look at this stuff right here, it's going to be just as easy, or it's going to be incredibly easy to do these steps right here using some more matrix operations. So notice how we take the m slope and b slope. All we do is multiply by the learning rate, which we can easily accomplish with TensorFlow by using the mul or multiply function. And then we do subtraction between our current weights of m and b with the result of that operation. So even though we didn't quite go all the way here, we definitely got through all the by far the hardest parts of learning how to calculate b slope and m slope at the exact same time. Okay, so that's pretty much it. Now the last thing I want to mention here, why did we go through all this trouble of I don't know, why did we go through all this, right? You're probably thinking Steven, this seems like a lot of work, right? Well, there's a really good reason. Up until this point, everything that we've done around this linear regression and this gradient descent stuff has all assumed that we had one single feature, right? We've said all along that our only feature here is the car's horsepower. But if you look back at our data set inside of that cars.csv file, you'll recall that we have many other features in here. Cylinders, displacement, weight, acceleration. And those probably all factor in very much to the mile per gallon value of the car. So even though it seems like we just made our lives like more challenging than they have to be, in reality, this equation or all this work that we just figured out and put together, we can actually throw it as many different features that we want at the same time, and the exact same process is going to work for additional features that we add in. So even though we, made things maybe a little bit more challenging than we had to, if we wanted to add in dramatically more features than what we have right now, we can use all the same exact code that we're going to write in just a second to include many more features at the same time. And you're going to see an example of this very quickly as we start to add in more than just our current feature of the horsepower of the vehicle. Okay, so enough of me ranting about this stuff. Let's take a quick pause right here. When we come back to the next section, we're going to work on our linearregression.js file. We're going to do a big refactor to this thing so that it starts to use this equation here as opposed to the two separate equations that were a real pain in the rear to code up previously. So quick pause and I'll see you in just a minute. Over the last couple of videos, we spent a lot of time learning a lot more about TensorFlow and how to take our original two equations and condense them down to one. So now we're going to go back into our project and replace our gradient descent function with a very faster version with way less code. And I think you'll agree with me at this point in time that, yeah, it was a lot harder to understand. And if we had just jumped straight to this solution, well, it probably would have been a little bit too confusing. All right, so I laid out a couple of steps on how we're going to do this refactor. So here's what we need to do to get from the current state of our code base to making sure that we use matrix operations and TensorFlow for all the math that we have to do around gradient descent. So the first thing we're going to do is make sure that we refactor our constructor function in that linear regression class to turn the features and labels arguments into tensors. Next up, we're going to make sure that we take a column of ones and append them to the feature tensor. Remember, that was one of the very key steps that we had spoken about, in order to be able to multiply our feature tensor by our weights tensor that contains our guesses of M and B. Now, one quick thing I want to mention when we append on this column of ones. In the last couple of videos, when I described this process, I showed the column of ones being appended on the right-hand side. In reality, in a lot of practical projects that you're going to eventually take a look at the source code for and whatnot, a lot of other people tend to append the column of ones onto the other side, like so. So rather than putting the column of ones on the right-hand side, they put it on the left-hand side. Now that might sound like a huge difference. No, not at all. It's not a big difference. All of the math ends up completely identical, totally identical. The only effective difference here, when you put the column of ones on the left-hand side, is that the order of these weights inside of this weights tensor, so M and B, they get reversed. So when you put the ones on the left-hand side, B shows up first inside there, M shows up second. That's the only effective difference, is the order of weights in there get changed. None of the other math that we've discussed about up to this point changes whatsoever. Now, of course, I'm sure you're wondering why I told you that it works this way with the ones on the right hand side. Well, it's just because me personally, I think that always imagining the weights tensor as M and then B, because the equation is mx plus b, I feel like that makes a little bit more sense to me personally. So that's why I showed it to you in that fashion. Again, no difference whatsoever, just some people choose to show or put the column of ones on the left hand side. And so we're going to do it that way as well, just to stick with that kind of convention. All right, so after we do that, we then need to make sure that we create a tensor for our weights. And then finally, we're going to refactor gradient descent to use the new single equation as opposed to the two separate ones. All right, so let's get to it. First thing to do is refactor our constructor. So I'm going to open up my code editor again. I'm going to find the linearregression.js file, and inside there is the linear regression class. So we've got our features and our label arguments right here. We want to take the array of arrays that these currently are, because they've been loaded up by our CSV file at this point, and I want to turn them into TensorFlow tensors. So I'll say tf.tensor, and I'll wrap it like so in both cases. And that's pretty much it. So we just turned features and labels into TensorFlow tensors and assigned them to the instance variables of features and labels. Now the next thing we need to do is make sure that we append a column of ones onto the feature tensor. So again, talking about this operation right here. I want to generate a column of ones and then put it on the left-hand side of the features tensor. Let's take this one step at a time. So the first thing we have to do is just generate a column of ones with a length identical to the number of observations or the number of rows inside of the current feature tensor. So this dot features right here currently does not have the ones column on it. So let's take this one step at a time. Like I said, how do we first just get a column of ones? Well, there's actually a helper function in the TensorFlow library for generating a tensor with just values of ones that looks exactly like that. So just to give you a very quick demo over here, we can do tf.ones, and then we'll pass in an array that has the shape of the ones tensor that we want to generate. And so if I were to try to generate like exactly that thing right there, that has 6 rows and 1 column. And so I would pass into this inner array 6 and 1 like so. And then if I do a t.shape, I get 6, 1 like so. So again, tf.ones creates a tensor with just values of 1 with the given shape. All right, so let's flip back over here. Right after we create our features instance variable, I'll then make my single column of ones. And I can do so by saying tf.ones, and then I'll put in my shape that I want here. So the shape is going to be the number of rows of features, and then it's going to have only 1 column. So the number of rows of features will be this.features.shape at 0, like so. Remember, the first value in the shape is going to be the number of rows. And then for the number of columns, we want just 1, like so. Okay, so that's going to generate our column of ones, and then we need to concatenate that onto this.features. So I'll say this, or excuse me, just concat like so, and I'll put in this.features. Now remember, anytime that we make use of the concat function, we need to specify the axis of concatenation, because by default, TensorFlow is going to try to join these two things on the edge of this vertical edge right here. And if we do that, well, I say that on that vertical edge, again, remember, this is a little bit misleading. When we use the 0 axes, which is the default, it's essentially saying we're going to try to continue the rest of values here along this vertical axis. And so again, remember that kind of shortcut I gave you to remember how this works. You can imagine drawing on an arrow along that 0 axis, and that describes where the next set of values are going to occur. So if we concat this stuff along the 0 axis, we're going to end up with something that looks like that, which we definitely don't want. Instead, we want to concat along the 1 axis, which we can imagine is along that direction, like so. So when we call concat, back over here, as the second argument, I'm going to put in a 1 to specify the concatenation axes. And then the last thing to remember, anytime that we do a concat operation, it does not update an existing tensor. We cannot make changes to existing tensors. We can only create new ones. So the concat operation returns a new tensor. So we need to make sure that we take the result of this entire operation right here and assign it back to this.features, like so. And I'll zoom out for a second just so you can see that entire line. Okay, so now this.features, after going through all that stuff, is going to look exactly like we've been describing, exactly like that right there. Okay, so that looks good. So let's take a quick pause right here. In the next section, when we come back, we'll make a tensor for our weights, and then we'll go ahead and refactor our gradient descent function. So quick pause, and I'll see you in just a minute. In this section, we're going to continue by creating a new tensor for our weights m and b. If we flip back over to our code editor right now and find our constructor function, you'll recall that at the bottom of the constructor, we had initialized our m and b as separate instance variables. So we now want to combine these two into a single tensor, and we probably want a better name for it than m and b. So I'm going to delete both those, and I'm going to replace it with a new instance variable called this.weights. Now, to initialize this tensor, we want to think at least a little bit about the initial values of m and b. Remember that we had previously, just a second ago, initialized them both to be 0. And I had previously said, when we put the zeros down there as well, that we could initialize them to be 1s if we wanted to. Now, this time around, just to stick with similar values, we'll initialize both m and b to be the value 0. So they're going to start off at 0, and then eventually get corrected over time to be the optimal values. To initialize them as 0, we're going to use a little helper function, very similar to tf.ones. So another helper function that belongs to TensorFlow is tf.zeros. And 2 zeros, we're going to pass in a shape. So in this case, we want 2 rows and 1 column. So I'll put in 2, 1, like so. So as you can see, tf.zeros creates a new tensor that has values of 0 inside of it with the given shape. And so this is perfect for initializing our starting weight values. All right, so back over here, I'll say tf.zeros, and then I'll give a shape of 2 and 1. And again, we're using 2 right now because we have only 2 weights, just m and b. All right, so that looks good. So now the last thing we have to do is the big refactor to the gradient descent function itself. Now, if you want to, I would encourage you to go ahead and maybe like comment out this entire function and then rewrite a new gradient descent if you want to. Just save the like old version of all of our code. Alternatively, you can just copy out the, comment the stuff here or copy it out to another file, whatever you want to do if you just want to keep it around for reference. But for me, just to keep my editor nice and clean so you can read it more easily, I'm going to take everything inside the gradient descent function and I'm going to delete it, like so. And so now we're going to start over from scratch with our gradient descent. All right, so here's the fun part. And you know what? Actually, I'm going to keep the old stuff around here. I'm just going to make a second file just so we can compare and contrast how much of a distinct change it is when we do this refactor to use just these matrix operations instead. Okay, there we go. All right, so now inside of here, we're going to essentially write out, where is it? This function right here. Okay, so let's give it a shot. We'll first take care of the mx plus b term, which is features multiplied with our weights tensor. So in order to do so, I'll say this.features.matmul, like so. Matmul stands for matrix multiplication. Remember, we've also spoken very briefly about the mul function as well. That is a completely different operation. The mul function does element-wise multiplication. So in other words, it's just multiplying each element inside of a tensor on an element-by-element basis. Matmul is the matrix multiplication operation that we've been discussing at great length throughout the last couple of videos. So I'm going to take my features, and I'm going to multiply them by this dot weights, like so. And then I'll assign that to a variable called current guesses, because that's essentially our current mx plus b values, which is really our current guesses of what our label values should be. So then after that, we need to take those current guesses and we need to subtract off our labels. So in order to do that, remember we had said that we can very easily use the sub method, and we could subtract our label values or our label tensor. So on the next line down, I'll do const differences, just to use the same terminology as we've used in all the diagrams we've looked at so far. And we'll say current guesses dot sub with this dot labels, like so. Okay, so that takes care of the first little bit. So that's essentially giving us that term right there. And now we need to make sure that we multiply by the transpose of our features. Don't forget, we got to do that transpose operation, because if we leave the features tensor as it normally is, that shape is going to be incompatible for matrix multiplication with our differences. So we need to make sure that we take the transpose of it ahead of time. Now, in order to do a transpose operation with TensorFlow, really straightforward. I can even reuse the same zeros tensor I have right here. I'll just call it zeros. So to take a transpose, we call simply transpose, like so. That's pretty much it. That's all we have to do. So back over here, I'll say this.features.transpose. That's going to transpose it, and then we want to do matrix multiplication with our differences. So I'll say matmul differences. And I'm going to just do a little bit of new lining here to clean up the chaining. And then finally, the last thing we need to do here is a term that we did not really talk about too much just because it was pretty straightforward in how it worked. We need to make sure that we also include the n division term on there as well. And so n, remember, is the number of observations that we have. In order to divide by that n, all we have to do is use the div function that's included with TensorFlow. And so just as a quick example of div, just in case you don't recall, let's say I've got a tensor t with 1, 2, 3, and 4 and 5. I can do t.div like 5 like so, and it's just going to do element-wise division on every element inside there. So the last step here, I'll do div, and I'm going to divide by the number of different features that we had. So essentially the rows inside of this.features. So I could do this.features.shape and then retrieve the first element out of there like so. Okay, so that pretty much gets us up to speed with this function right here. Now there is one tiny little factor that we're not including in here. Remember back in the original equations, let's see, I deleted some stuff out of that. So let me go find like the original ones. Here we go right here. Remember it shows we have the 2 factor in there. Now in many different implementations of gradient descent using mean squared error, you're gonna see that a lot of people actually omit the 2 on there and they just like leave it as 1 and they don't include the 2. So this is probably another location where you're thinking, wait a minute, we're going to just like leave off an arbitrary number here. Why in the world would we do that, right? Well, remember that whatever we get for the slope right here, I made a big deal a couple of videos ago saying that the purpose of the slope of b and m is just to give us that positive or negative sign to help us understand whether we need to increment m and b or decrement m and b. After we calculate the slope, we were then going to multiply it by a learning rate. And so it doesn't really matter if you multiply this number right here. Yeah, we can multiply it by 20, or we could like divide it by 500 if we wanted to. It doesn't really matter what coefficients we have on here because we're just going to multiply it by a learning rate anyways. And as we discussed previously, the learning rate is essentially a completely random number just to rescale the slope into like a pseudo appropriate value. So like I said, in reality, these equations are supposed to have the 2 on there, but you're going to see a lot of documentation and maybe like blog posts and whatnot, and they're going to drop off the 2 there, and they're just going to have it be the 1. And again, the reason for that is when the learning rate comes into play, it's going to modify this value anyways. And the only reason we're really calculating this stuff is for the positive and negative sign. Okay, so if you want to, you could do like, a mul2 here if you want to, but I'm just going to leave it off because it doesn't really add anything for us. Okay, so then the result of all this, I'm going to assign to a variable that I'll call simply gradients, because that's what is inside of here. Or excuse me, not gradients. Gradients is a term that we've not really used so far. Let's call it slopes instead. Sometimes people call this gradients because it represents the gradients in gradient descent, but we've been calling it slopes, so we'll just leave it as slopes. Okay, so that kind of gets us up to speed with this equation right here. But remember, that's just the slope. We now need to make sure that we take those slopes and we use them to actually update our values of m and b. So let's take a quick pause right here. We'll come back to the next section and do that very last step, and then we'll try running our algorithm. So quick pause, and I'll see you in just a minute. We've now written out the logic to calculate our slope of MSE with respect to m and b, and we've stored it inside this temporary variable here called slopes. So now we need to take the slopes and we need to make sure that we update our weights tensor. And remember, weights has both our m and b values inside of it. So to do so, all we have to do is very similar to what we did before, take our slopes, so m slope and b slope, which is now condensed down into that single variable called slopes. We're going to multiply both those by our learning rate, and then we'll subtract our existing m and b by it. So again, like I said previously, just 1 or 2 videos ago, with TensorFlow, this is a really easy operation, even easier than what we had before. You just have to have a good idea of how to work with TensorFlow. So I'm going to take my slopes and I'm going to multiply it by our learning rate, which is accessible as this.options.learning rate, like so. Then I'm going to take that entire thing and I'm going to subtract our weights by that term right there. So to do so, I'll say this.weights.sub. And then I'm going to take the result of all that and assign it to this.weights. And that's what's going to do the actual weight updates. So I'll zoom out for just a second so you can see the whole line. All right, so I went through that kind of quickly compared to everything else. So just one more time, take the slopes, multiply it by the learning rate, take our weights, and subtract the result of all the slope and learning rate stuff. Remember, anything that we do to a tensor does not update a tensor because they are immutable. So we take the resulting tensor from all that operation and assign it back to this.weights. So essentially doing the same thing that we were doing before in 2 separate lines of code. All right, and that's pretty much it. So that's the entire refactor over to what we would refer to as a vectorized solution. This entire refactor here, where we use matrices or tensors for all the math in our gradient, is what we refer to as a vectorized solution. So if you want to, you could actually go over to Google and search for like linear regression gradient descent vectorized, and maybe even put vectorized first so that Google weights it a little bit more heavily. And you'll see a couple articles over here about like, oh, hey, here's how you like do vectorized implementation of this stuff. Now, as you can see here, this is like this is like the same math right here, but yeah, you know, nasty terminology, as you can see. So if you can learn this stuff from the like math version of this stuff, well, like, you know, hats off to you. Personally, I have to like break this stuff down into more simple numbers, but everything you're seeing here is essentially what we are currently doing inside of our code. And it's been exactly what we've been talking about, with the exception of the width regularization. We haven't gone through that process just yet. And you can look at some of the other links on here, and they're all going to be about essentially exactly what we are doing. Okay, so that's pretty much it. I think that we've got everything up to date, and I think you can agree with me at this point in time that the code that we have right here is like orders of magnitude easier to read than what we had previously. This is the old version of the gradient descent function. So without a doubt, what we have here is so much easier to read. But yeah, you know, it's you got to understand what's going on. You can't just like pick this stuff up too easily. Now, one last thing I want to mention here before we try to actually run this code. If you want to, you could easily probably condense this down to like a single chained function. It would just have some nested arguments inside of it. So if you wanted to, you could probably do something like, I don't know, put a sub this dot labels over here, and then take this entire term right there, take that entire term and put it in for differences like so. And then we wouldn't need any of that stuff right there. Just something I want to throw out there if you want to condense this even more. I like to leave it a little bit more long form so that I can see kind of the different values floating around. So again, it's totally up to you if you want to condense it down even more. I'll leave it up to you, but I'm kind of happy with how it looks right here. Okay, so enough talking here. Let's get down to business. It's time to actually run this inside of our terminal. So I'm going to go back over to my index.js file. Remember, at present, we're creating a new instance of regression, passing in features and labels, doing the training, and then updating or printing out our value for m and b. The only problem is that regression is trying to print out or access the instance variable m and b right there. That's not, or that is no longer an instance variable inside of our regression class. So if we actually want to print this out now, we would have to do regression.weights. And remember our accessors that we spoke about way long ago for tensor values. To access individual values, we can do a get and then pass in the index here. So remember, the first element inside of our weights tensor is the value b, and the second element inside there is m, because we did that reshuffle there at the last second around the ordering of our appended stuff right here. Remember, we shuffled that at the last second. So the first value is going to be b, and then the second is going to be m, and it is a shape 2 and 1 tensor. So in other words, to get to m, we'll do a get for row 1, 0, like so. And over here, it'll be weights.get 0, 0, like so. And when I save that, it's just going to condense it down to be a single or multi-line like so. Okay, so enough kind of lollygagging around. Let's try to save this file, and we'll run it inside of our terminal. So I'm going to flip back over. I'm going to make sure I'm still inside of regressions. I'll do a node index.js. And it looks like we got, I don't know, somewhat reasonable value here. It looks better certainly than what we had previously, I can tell you that for sure. So I think that's looking pretty good. We're running 100 iterations with a learning rate of 0.0001. I like what we have, so let's take a quick pause right here. When we come back to the next section, we're going to start to think about doing some analysis on this, make sure that we're getting realistic values for m and b and whatnot, and maybe add in some standardization, normalization, and a bunch of other stuff to make this solution a little bit better than it is currently. So quick pause, and I'll see you in just a minute. In the last section, we finally got our gradient descent algorithm working with this new vectorized approach. Remember, when we use these matrices or tensors to do all the math for us, we refer to that as the vectorized approach. When we ran the newly updated algorithm in the last section, you'll see that we got an m of like 0.178 and a b of 0.049. Now, the first thing I want to point out here is that you'll probably notice that the numbers that we have right here are without a doubt different than the numbers that we had ran previously with the older version of our algorithm. So right here is the contents of the old gradient descent algorithm, right? You'll recognize it as being pretty nasty looking. And we had seen that the last time we ran this thing with identical parameters inside the index.js file, so same iterations, same learning rate and everything else, we had gotten values that were like, I don't know, 80 trillion or 80 quadrillion or something like that. They were very large numbers. And so now it appears as though our newer algorithm is giving us much smaller results, which might make you a little bit concerned because we have identical inputs, but the outputs are without a doubt different. Well, remember, in reality, the two algorithms are ever so slightly different after all. So back inside of the backup of my gradient descent algorithm right here, remember that we were calculating our b-slope and our m-slope, and we were multiplying them by 2. And just like 2 or 3 videos ago, I was telling you how, oh yeah, some other people out there decide to drop off this multiply by 2, and they just leave it as like, essentially multiply by 1, or really just divide by n would be the appropriate thing to say. And the reason for that is that this all gets adjusted anyways with the learning rate. So in the old version of gradient descent, we included that times 2 factor, but in the newer version, we did not include, or at least I did not include the times 2 factor in here. So in order to test to make sure that our two implementations actually are identical, you could go back over to your parameters when we create the linear regression class, and you could actually just multiply the learning rate by 2. So whatever you have here, just multiply it by 2, and that has the exact same effect as that times 2 term inside of the slope equation that I had just told you, yeah, we're just going to drop off that times 2 because it doesn't really have any impact. So if you put on where you multiply your learning rate by 2, you'll have the same thing essentially that we had before. So I can now save this file and then rerun it with node index.js, and you'll see that we get like the same exact values as we had gotten previously, these really, really large values. So clearly, yeah, it looked different initially. There was a very small change. All right, so I'm going to change back the learning rate there to be the old 0001. So at this point in time, we definitely have an algorithm that works, but we don't really have any way to verify that it's giving us the correct answer. We don't have any way to run our algorithm against our test set and gauge its accuracy. We really have just the algorithm itself and nothing beyond that. So let's take another quick pause right here, and we're going to start to figure out how we're going to take this linear regression class right here forward and add on a lot more robustness to it, so to speak, and then do a little bit of play around with it and try to optimize it in some fashion. So quick pause, and I'll see you in just a minute. Our linear regression class is definitely working, but it's definitely not working too well just yet. So in this section, we're going to start thinking about how we're going to make sure that the value of m and b that we're calculating is the correct or most optimal value possible. In order to do so, we're going to start to evaluate the accuracy of our model's predictions. So here's how we're going to do this. We're going to first train the model with some amount of training data so that we get some calculation or initial guess as to what the value of m and b should be. Now just to be clear, we're already doing this with the train method that we've implemented inside the class. After we've trained the method and gotten some initial guess for m and b, we're then going to use our test data to make predictions about observations with already known labels. So in other words, we're going to feed in the horsepower value for a bunch of vehicles where we already know the mile per gallon value. We'll then predict what the MPG or mile per gallon will be, and then we'll compare it to the actual value. To actually gauge our accuracy and get some meaningful number that tells us how correct or incorrect we are, we're going to calculate something called the coefficient of determination. In this section, we're going to first begin by talking a little bit about exactly what the coefficient of determination is, and then we will code that thing up inside of our linear regression class. So let's get to it. That coefficient of determination is also known as an R-squared value. You might have seen R-squared terms before anytime that you look at charts that are generated by tools like Excel or Google Sheets or what have you. This R-squared value, or coefficient of determination, is essentially a score of how good our fit is with the actual data. So we can kind of think of it as a almost accuracy value. To calculate R-squared, we need to find two subterms in here called sum of squares residual and sum of squares total. So that's where the real work here is. Once we calculate those values, we'll then do 1 minus sum of squares residual over the total, and that will give us our R-squared value. The R-squared value can run anywhere from 1 all the way down to negative basically infinity. So we expect ranges of values from negative a lot all the way up to 1. A value of 1 means that we've got just about a perfect fit or a perfect relationship between our feature data and our label data. But it's very rare that we ever approach we ever get exactly 1. Much more frequently, we'll see values of like 0.9, 0.95, 0.99, and that indicates that we've got a pretty good guess at the relationship between our feature and our label. Negative values means that we are very far off from some correct guess, and we'll get a better sense of what negative values really indicate. All right, so let's now talk a little bit more about these SSRes and SSTotal values. All right, so first off, SSTotal. That's the total sum of squares, and you can take a look at the equation for it right there. We'll talk about exactly how the equation works in just a second. First, the other term is the sum of squares of residuals. Now, the big difference between these two values is that the total sum of squares is essentially intrinsic to the data set itself. It has no relation to the actual predictions that you and I are making. If you look at this equation very closely, it's actual minus average. And so that's the actual data point minus the average value of all data points over our data set. And so that has no value inside of it to calculate that's related to the calculations that you and I are doing. On the other hand, the sum of squares of residuals is going to use a predicted value that you and I are going to actually generate ourselves. So we can kind of imagine SSTotal or total sum of squares as being a property of the data set itself, whereas sum of squares of residuals is kind of a gauge of the accuracy of the work that you and I are doing. All right, let's keep going here. So first off, total sum of squares. How do we calculate this, and what does the number really mean? The total sum of squares, essentially you can think of, is kind of a baseline accuracy value. With a total sum of squares, we calculate the mean value of all the different labels inside of our data set. And so if we imagine that we have a new data set here of like years of experience of an employee versus the salary that they get paid, you might see that as an employee has more years of experience, their salary is going to generally go up. You can see that the general trend line here is upwards to the right. With the total sum of squares, we're going to look at all the different label values. So in this case, the salary for all of them. We'll take the average salary value, which might be a line like somewhere right here. We then find the distance from all the actual values to that average value. And so that would be like this distance indicated by the dashed line, that distance, and that distance. And so we take all those differences or those distances and we're going to add them all together. Again, the total sum of squares is intrinsic to the data set itself. And it's kind of like a worst case scenario for your best fit line. It means to say that if we can't get a line or a guess at the relationship between our years of experience and salary better than the average, well, then we did a pretty bad job. All right, so then next up, to calculate the total sum of squares, we're going to first calculate the average using all those label values. So in this case, we would take 50, 78, 78, 95, 95, 120, 120, add those all together, and then divide by 4. And then that gives us 85.75. We'll then essentially loop over all the actual label values, so 50, 78, 95, and 120. We'll subtract that average, and then square the result from each one. So you can see the actual math for that right here, and then the end result would be 2596.75. All right, so next up, the sum of squares of residuals. Very similar, almost identical process. The only difference is that we're finding the distance from the kind of relationship line or the mx plus b line that you and I are calculating or trying to find the relationship of to the actual data points themselves. And so if we found this line right here as the trend line for the relationship between years of experience and salary, we would find all these distances indicated by these smaller dotted lines, and we would sum all those up. And so to find those, if this was our years of experience and we had predicted these salaries right here, and these were the actual salaries, we would take 50 minus 45 and square it, and then add that to 78 minus 70 squared, 95 minus 90 squared, and 120 minus 17 squared. And so you can see the math for that right there, and we would end up with 123. Once we calculate both the sum of squares of residuals and the total sum of squares, we then go back to the old coefficient of determination equation. So we'd plug in the SSRes and SSTotal. That would be 123 over the 2596, and then we would take 1 minus that ratio, and we'd end up with 0.952. Remember, the closer we are to 0.1, the better. And so a value of 0.952 means that we are doing pretty darn well. Anytime that we get a value less than 0, so a negative number, that means that the accuracy of this essentially kind of like very average guess here of SS total was better than our prediction of SS res. So anytime we get a negative number, it means that we would be literally better off by just taking the average value and using the average value as our prediction for any given feature value. So in this case, if our mean here, what was the mean? It was 85.75. If we had a better prediction from the total sum of squares, then for any feature value, like 0 years of experience, or 5, or 10, or 15, or 30, we would be better off to just guess a salary of 85.75 than to try to use our predicted value using our particular model. So again, if we get a negative value, that means that we're doing a very poor job, and we definitely need to improve our ability to calculate the relationship between our independent and dependent variables. Okay, so now that we got a better idea of what's going on here, we now have a tool that we can use to gauge essentially how well we are doing at calculating a value of m and b. So let's take a quick pause right here. When we come back to the next section, we're going to start to implement a new function inside of our linear regression class that's going to do some predictions over our test data set and then calculate these SS res and SS total values. So quick pause and I'll see you in just a minute. In the last section, we started to talk about how we're going to gauge the accuracy of our algorithm. We're going to do so by calculating that coefficient of determination. Before we can do that, we need to make sure that we have the ability to use test data to make predictions about observations with known labels. And so to do so, we're going to implement a new function inside of our linear regression class called test. This new function called test is going to take in a test data set and a test label set as well. It will then make predictions about all those test labels and then run the logic to actually calculate our coefficient of determination. So let's get to it. Back inside of my code editor, I'll find my linear regression class, and then I'm going to go down to the very bottom of the class, and right underneath that train method, I'm going to create a new function called test, like so. This test function is going to be called with our test feature set and our test label set as well. Recall that we are already generating those two test data sets when we load up our CSV. And so back in the index.js file, we've got test features and test labels. Those are both arrays of arrays, and these are what are going to eventually be passed into this new test method. So back over here in the test method, I'm going to receive two arguments that are going to be called test features and test labels. We're just going to use the same name as the actual variables themselves back over here. Now, the first thing to remember is that these are both arrays of arrays. And just about everything that we are now doing around this class, like all the calculations inside of gradient descent, require us to be working with TensorFlow tensors. So the first thing I'm going to do inside of here is reassign these variables, these two arguments that are coming in, to use the data that they contain inside of TensorFlow tensors. So essentially, we're just going to say test features is tf.tensor, test features, and test labels is tf.tensor test labels. And it looks like I made a little typo there. It should be labels, like so. That's better. All right, so that looks pretty good. So we've now got our test function, and we've got our test features and labels inside of here. So now the next thing we need to do is use all that data to make observations that will then compare with all the data inside of the test labels tensor. In order to make predictions, it's going to be pretty straightforward. We're going to do essentially the same thing that we had previously done back inside of our gradient descent function. So what we have to do here is take our feature set. So this is all of our test features right here, a single column that has all of our engine horsepower values. We're going to append on that arbitrary column of ones, and then we're going to do matrix multiplication with our current values for our weights, which are assigned to this.weights. When we do that matrix multiplication, remember that it essentially runs the mx plus b calculation for every single feature inside of this input data set. And remember that one column right there is going to essentially fall away because it's going to be 1 times the b value, which is the same as just b by itself. All right, so the first thing we have to do is make sure that we take our test feature set and add on that column of ones. We already wrote out some code to do that, but we had placed it inside of our constructor function. And we had done so to operate only on the this.features instance variable. So we essentially need to do this same logic right here again, but inside of our test method instead. So I'm going to go back down to my test method, and underneath our existing declarations, I'm going to say test features is tf.ones. Remember, the input to the ones function is an array that describes the shape of the ones tensor that we want to generate. So I want to have a number of rows equal to the number of rows in test features. So I'll say test features dot shape at 0, and that will give me the number of rows in there. And then I only want to have one column of ones. Then I'm going to concat that onto my test features. And I'm going to make sure that the concatenation is done on the one axis, for the same reason that we've described many times in this course so far. All right, I'm going to zoom out for just a second so you can see that entire line. There we go. Okay, that looks pretty good. So now to make some actual predictions, we're going to do our matrix multiplication with our weights. Now, one thing I want to remind you about is the order in which we do this multiplication makes a very big difference. So we want to multiply our feature set times our weights. We do not want to do our weights by our feature set like so. If we try to do this, we're going to get an error because the shapes of these two tensors in this order do not match up correctly. So it needs to specifically be our features or our test feature set matrix multiplied with our weights tensor. All right, so back over here, I'm going to zoom back in. And then we're going to make a new variable here called predictions, and that's going to be my test features matmul, which is the method for doing matrix multiplication, with our weights tensor, which is this dot weights. Remember, we had created this originally inside of our constructor function right here, and then we were doing the update to it for every iteration of our gradient descent algorithm. All right, so that's looking pretty good right there. We've now got our predictions. Now, before we do anything else, I just want to print out our predictions and make sure that we're going down the right path here. So I'm going to do a predictions.print at the bottom of this test function. Let's just train our model very quickly, then run the test function, and then we'll look at this predictions output and just make sure that, yeah, it looks like we're getting the correct structure of our data put together. In order to make sure that we call test, we do have to go back over to our index.js file, and then down at the bottom, rather than doing the console log down here of our weights of m and b, we're going to delete this and replace it with a call to that test function. Even though it was kind of nice to look at our values of m and b, it turns out that we don't really care about what their specific values are, or the specific values of our weights, outside of some like very specific conditions. It's frequently much more useful to look at the accuracy values, which we are now going to report as our coefficient of determination. So if we're going to ever print out anything around accuracy from our algorithm, it will be an accuracy metric like this right here, as opposed to the actual m and b values. Okay, so again, I'm going to delete that console log, and I'll replace it with a regression.test. And we need to make sure that when we call test, we pass in our test features and test labels. So test features and test labels, like so. All right, that looks good. So I'm going to flip back over to my terminal, and I'll run that file after I make sure that I save it. Don't forget to save both files. And we'll do a node index.js. All right, I see the output right here. So this is that predictions tensor, and we're getting values inside of here that look very much like they could possibly be values of miles per gallon. So it looks like maybe that learning rate that we had somewhat randomly guessed right here might actually be doing somewhat okay. But we won't really know for sure until we actually run some accuracy metrics around our analysis and are able to say like, yes, we did do a very good job. So let's continue in the next section where we will keep working on implementation of this coefficient of determination. So quick pause and I'll see you in just a minute. In this section, we're going to continue working on our implementation of the test function. We left off having made our predictions for all of our test features. So now we need to use our predictions, our test labels, and the two equations that we just spoke about, or three, I suppose, our coefficient of determination and our total sum of squares and sum of squares of residuals. We're going to calculate all three of these different values and then print out the result so we know what the accuracy of our model is. So I'm going to remove the predictions.print line that I have in here right now because we don't really care about that anymore. And then underneath that, we're going to first begin by calculating our sum of squares of residuals. It doesn't really matter what order we go in. It just turns out that in my notes, I did the sum of squares of residuals first. No big difference though. All right, so to calculate this, we're going to take all of the actual values, so that's essentially the values out of our label set, and we're going to subtract the predicted values that we just calculated in the last section. After that, we're going to square the result of all that, and then sum everything up. So as you might imagine, this is going to be a great location to make use of some TensorFlow methods. In fact, this is going to be almost surprisingly easy to do with TensorFlow. So the first thing we're going to do is take all of our labels, so that's going to be test labels right here, and we're going to subtract, or sub, as we refer to it, all of the predictions that we just made. So I will sub predictions like so. After that, we then have to take all those differences and square each of them. So to square them, I'm going to chain on a .pow2. Remember, the pow method right here attached to any tensor is going to do element-wise power operation. So this is going to essentially look at every element inside of this tensor that is generated by the subtraction and square every element inside there. After that, we then need to sum all of those values together. Now, I don't think we've spoken about this before, but it turns out, oh no, we have. We've spoken about the sum method. Yeah, we spoke about it a bunch. Remember, with the sum method, we've used it so far, and we've tried to put in an axis here, which is going to sum values along some particular direction. In this case, we want to take just the sum of all the numbers inside of this tensor after squaring them. And so we don't have to provide an axis here. We can just call sum by itself. And then finally, after that, we want to get the actual number out of this tensor. Remember, sum right here is going to return a new tensor. And we want to get the actual number out of there, the single number that's in there, so that we can eventually use it in this equation right here. So to get that actual number out, I'm going to call get, like so. We don't have to pass any arguments to get because there's just one single number inside this tensor after running that sum operation. Let me show you just a quick example of that, just so it's really clear what's going on there. So I'm going to flip back over to this little editor, and I'll say const test is tf.tensor, and I'll just put in, like, I don't know, 1, 2, 3, and 4, like so. So then we can call test.sum, which is going to sum up all the numbers inside there, and then to get the actual number out, remember, right now, when I call test.sum, it does return a tensor, even though it looks like there is not one right there. This is, in fact, a tensor. And then I can do a get, and that's going to return just the number by itself. Just to prove to you that this right here is, in fact, a tensor, you could actually wrap it inside of an array, which will cause it to print out without the nice printing of what's actually inside there. So when I wrap with the array, I see, yeah, that is, in fact, a tensor, but when then I put on the .get, it does in fact just return the number by itself. Okay, so hopefully that's more clear. So that's going to give us the output from the operation of, come on, where is it? Here we go. That's going to give us our sum of squares of our residuals, or SSRes. So I'm going to take the output of all this right here, and I'm going to assign it to a variable that I'll simply call res, like so. So then after that, immediately after that, as a matter of fact, we'll go through the process of getting our total sum of squares. And so in this case, we're going to take our actual label values. So again, I could rename this right here to label if I wanted to. And I'll subtract out the average label value. So we definitely need to find somehow the average label value. Fortunately, again, with TensorFlow, this is really easy and straightforward. To give you a very quick example, if I come back over here again, I can do test.mean, like so. And mean is just going to give me the average value of all the numbers inside of a given tensor. So really easy to get the average. All right, so back over here, I'll say const tot, short for total, and then we'll do our test labels, because remember, we want to take our labels right here and subtract the averages. And I'll do a sub of test labels.mean. So pretty straightforward. Find the average value of every number inside of test labels, and then subtract that element-wise from all the numbers inside of test labels. Then after that, we'll go through the same operations. We're going to square the result, add it all together, and then get a single individual number out of it. So I'm going to chain on a .pow2, a sum, and a get. So now res and tot right here, or total, I suppose, are simple numbers, no tensors involved, and we can use both those numbers to calculate our actual coefficient of determination. So after those two calculations, I'm going to return 1 minus res divided by TOT like so. And that's pretty much it. All right, so now anytime that we call test, we're going to load up our test features and our test labels. We'll make some predictions, do some accuracy analysis, and then return our r-squared value, or our coefficient of determination. So to actually run this, I'm going to flip back over to my index.js file. Remember, when we call test right here, it's going to return the coefficient of determination. So I'm going to assign that to a simple variable that I'll call r-squared, or r2 like so. And let's do a console log that says r2 is, and then I'll print out r2 like so. All right, so I'm going to save this file, and then I'll flip back over to my terminal and do another node index.js. All right, so there we go. As you can see, we've got a value of -3. Remember what we had said about negative values. The r-squared value is only going to be negative if for some reason the residual sum of squares is larger than the total. The sum of squares being larger than the total means that our calculation is so bad that it is multitudes worse than just doing the kind of very simplistic, straightforward approach of getting that sum of squares, total sum of squares, which is to use the mean or average value of the data set. And so right now that negative value, or -3, is telling us that we would be better off trying to find a relationship between our horsepower and mile per gallon values by just taking the average rather than trying to actually do any fancy analysis or anything like that. So without a doubt, it appears that we still need to do something here to get some better result or some optimization than what we're doing right now. But at least we have some metric here that tells us how good or how bad we are doing. So let's take a quick pause. When we come back to the next section, we're going to start thinking about some different strategies that we can use to increase the accuracy of our analysis. We now have the ability to run our analysis and say that, yeah, we're doing a really bad job here. So in this section, we're going to start looking at different ways in which we can update our analysis and get some more accurate results. One of the easiest ways that we could improve our analysis right now is going to be to do some either data normalization or some standardization. Remember, with normalization, we usually look towards that min-max method. With standardization, we usually look to using the standard deviation and the mean over all the values inside of our feature set to get a range of values between -1 standard deviation and +1 standard deviation. We already went through that process a little bit ago on our last project, but let me just give you a very quick reminder on how we calculate it. So if we have some data set here called features, in order to apply standardization to it, we're first going to get our mean and our variance using TensorFlow. So I'm going to say mean and variance is going to come from tf.moments, features, and we're going to look along the 0 axes to calculate this. So remember, this is one of the very few methods that is a property of the TensorFlow library itself, as opposed to the actual tensor. In addition, calling this method returns a mean and variance. The variance is not exactly the standard deviation that we're supposed to use to actually do the standardization. So when we apply this variance right here, we need to square root it before we actually use it to standardize our data set. So now that we've got these values, we can do something like features.sub mean, and then divide variance.pow to the 0.5 power, like so. And then so we end up with a result here that's going to span from -1 standard deviation to +1 standard deviation. And so given 10, 20, 35, and 95, we would end up with outputs that look like this. So remember what we had said previously about our data set. Anytime that we have data where our, let's pull up the little spreadsheet view right here. Here we go. So anytime that we have values like our horsepower right here, that have a range that is not close to 0, we're going to find that it takes many iterations, like many iterations, to successfully train this data set. So a very easy way to address this is going to be by using this standardization. All right, so that's a quick reminder on what's going on here. Now, before we actually implement this, there's one quick thing I want to mention to you. Remember that when we apply standardization, we have to use the same exact mean and variance on our training data set as we do on the actual predictions that we make later on. So in other words, if we start to apply standardization to the data that's coming in on this .features right here, we have to make sure that we also apply the same mean and the same variance to the test features that come in later on down here inside the test function as well. So we need to make sure that we are applying this essentially same set of data or same set of standardization values in both locations. The other quick thing that I want to mention here, just something I want to point out very quickly, I want you to take notice how both test features right here inside the test function and in the constructor, this.features, both those locations have the same exact logic for appending on that column of ones. So what am I getting at here? Well, I just want to make the point that it looks like both our features inside the constructor and our test features inside the test function really need to go through the same type of pre-processing step. Like same steps, we have to apply these ones and do the standardization. And even when we do the standardization, we need to make sure that we apply the same exact data. So rather than just trying to do the standardization in line, like right here underneath where we put together test features, and rather than trying to put in our standardization up here in the constructor right after we put together this.features up here as well, I think that we should make a helper method. Some helper method that's going to take any arbitrary feature set and add on this column of ones, and then go through the process of either first applying the z-score standardization or reapplying the standardization in the case of the test features down here. So let's take a quick pause. When we come back to the next section, we're going to take a look at a quick diagram that's going to give you a better idea of what we're going to try to go for here. So quick pause, and I'll see you in just a minute. In the last section, we started to talk about the fact that we have some repetitive logic inside of our constructor and inside of our test function around not only trying to append on that ones column, but also very soon around standardization of our feature set as well. So as a solution, I think that we should make a new helper method called process features. Anytime that we pass in a feature set to the constructor or the test function, the constructor and the test function can call process features. And it will be up to this helper method to return a scaled, so that means either standardized or normalized, feature set that has a ones column appended onto it as well. So let's give this a shot. We're going to put together our process features helper function. All right, so back inside my code editor, I'm going to go down to the very bottom of the class, and I'm going to add on a new function called process features. And again, this thing is going to be called with our features. So now inside of here, I want to extract all of the common logic around handling those features from the test function and the constructor function. And so at present, that includes both this ones generation and concatenation and the fact that we are casting test features as a tensor right here as well. So I want to take care of this initial tensor thing and the appending or a concatenation of that ones column inside of process features. So down inside of process features, I'm going to say features is tf.tensor features like so. So that's going to make sure that we take the array of arrays and put it into a tensor. And then we're going to add on the ones column with features is tf.ones features.shape at 0 with one column on there as well. And then we're going to concat that to features along the one axis. And then finally, for right now, we'll just return this thing as is. Okay, so that looks good. Now let's go back to the test function and the constructor function, and we're going to replace the existing logic in there around putting our features into a tensor and adding on the ones column with the process features function. So back up inside of test, here's where we add on the ones column. So we don't need to add that on anymore. So I'm going to delete that line entirely. And then right here with test features, we do not have to put this thing into a tensor anymore. That's going to be taken care of inside of the process features function. So I'm going to replace that with this dot process features, and I'll pass in test features like so. Okay, so that looks pretty good. Now we're going to repeat the same process up inside the constructor as well. So up inside the constructor, here's where we're adding on that ones column. So we don't need that anymore. I'm going to delete that. And then right here is where we put this thing into a tensor. Don't need that either. So I will replace it with this dot process features, and I'll pass in features like so. All right, so this is looking pretty good. Now I'm going to save the file right here, and we're going to rerun this file just to make sure that we have not broken any of the logic inside of here. Once we've made sure of that, we'll then come back to this thing and add in that whole standardization thing as well. All right, so I'll flip back over to my terminal and I'll run node index.js, and I still see the very bad r squared value right here. So it looks like our new process features function is doing pretty well. Let's take a quick pause right here. When we come back to the next section, we're going to walk through the process of adding in some standardization to this thing at the same time. So quick pause, and I'll see you in just a minute. In the last section, we put together this process features function, which is going to take care of some initial processing on our feature set. So at present, we are putting this thing into a tensor and then adding on that ones column. So now the next thing I want to do is make sure that the process features function is going to standardize our data or our features as well. Now, before we do that, I want to point out one thing about this function that's going to be just a little bit more challenging than you might think. So, quick reminder, again, here is our quick example of standardization. Now, this only standardizes something that we call features right here. Once we've found the mean and variance for this initial feature set, if we ever try to do future standardization, we have to use the same exact mean and variance. So in other words, if we come across this thing with a new feature set called test features, which we are exactly this, and this is a tensor of test features with numbers like, say, 15 and 25, then when we standardize test features right here, we have to use the same mean and the same variance that had previously been calculated on the original feature set. So in other words, we only get mean and variance one time, and then we reuse that same mean and variance for all new pieces of data from here on out to the future. So in other words, I would take my test features and I would sub the same mean and div by the same variance.pow 0.5 like so. So when we start to put this logic together inside of process features, we just have to be aware of whether or not we are doing standardization for the first time or reapplying the same standardization factors. So with that in mind, let's try to take a quick stab at this. The first thing I'm going to do is create one or two more helper methods that's going to take care of the case in which I need to do standardization for the first time or standardization for the second time. So I'm going to make a helper method underneath process features called standardize. And this will get some features as well. You'll see where we're going with this in just a second. I would give you kind of a more in-depth explanation here, but at the end of the day, I think once you see the code for this, it's going to be pretty straightforward. So now in standardize, we're going to assume that we're doing standardization for the very first time. So I'm going to get my mean and my variance using tf.moments on features on the 0 axes. Now here's the key. I'm going to save this mean and variance on instance variables that I will refer to as this.mean and this.variance, like so. So now I've got a record of the mean and variance for this feature set right here. And then as the last step, I'm going to return features.subMean div variance.pow 0.5 like so. All right, so now the way that we can decide whether or not we are doing standardization for the very first time or reapplying it at some point in the future, for example, on our test features right here, is whether or not this.mean and this.variance are initialized and defined. So when we first make our instance of our linear regression class, this.mean and this.variance are going to be undefined properties. So if those things do not exist, if they are not defined, that means that we need to call standardize and do first-time standardization. Otherwise, if these two properties do exist, it means that we've already gone through the standardization process once, and we need to reapply these two variables or these two mean and variance tensors as opposed to recalculating them again. So inside of process features, we're going to take advantage of the fact that we now have these two new instance variables. So inside of here, I'm going to say if this.mean and this.variance. So that means if we've already calculated these things and these are defined properties, then we need to reapply those to standardize this new features variable right here, or essentially to restandardize. So if that's the case, I'm going to do features equals, and then we're going to do the same operation as we saw right there. So I'll say features.sub this.mean, and then we'll also do our, what's the other line? The div step. Div this.variance.pow 0.5 like so. And now we'll handle the else case. So if this.mean and this.variance are not defined, then we have to do the first time standardization using the standardize method right here. So in that case, we'll say features is this.standardize with features like so. Okay, so that's pretty much going to take care of it. Now, one thing I want to mention here really quickly, with standardize, we have the logic in there for actually doing the standardization, and so we've just duplicated that logic right here as well. So if you want to, you could also kind of pull this stuff out to a separate helper method, so we're not repeating that same line of logic in both locations. But I'll leave that up to you, totally optional if you want to put that in or not. Okay, so we've now got our process features function that's going to first put our features into a tensor, apply the ones column, do the standardization, and then save the standardization values for future use as well. And then finally, return the future set too. Okay, so I think that we're ready to do a quick test of this. So I'm going to again save this file. I'll then flip back over to my terminal and I'll do a node index.js. And now, lo and behold, we have a r² value of -10, which is even worse than before. So it looks like we still have a little bit of troubleshooting and debugging to do here. So let's take a quick pause. We'll come back to the next section and figure out exactly what's going on. In the last section, we started to apply standardization to our feature set. However, when we then ran our code again inside the terminal, we saw an r² value of -10.9, which means that we're still really not doing that well. So in this section, I want to investigate one possible reason that we are running into this really bad r² value. Back inside my index.js, I'm going to find where I create the linear regression class instance. And then right underneath that, before we do any training whatsoever, I want to show you something that's just kind of a little bit interesting, okay? Here we go. We're going to do a regression.features.print. So at this point, we are going to print out our features just after we did that initial processing step on them, where we concatenate on that column of ones and then go through the standardization process. Now, I want to print out those numbers because I want to show you something that's kind of interesting about it. Okay, so I'm going to save this, and then I'll flip back over to my terminal again and do another node index.js. And so take a look at the output that we have now. We have two columns, which is totally expected, but take a look at the column of ones, or supposedly the column of ones. When we applied the standardization process, we did not only do it to only our feature columns, we did it to the ones column as well. And in this case, during that process of standardization, for some reason, those ones came out as -0.999995. So no longer do we have a column of ones on there. So this is clearly an unintended consequence because we are putting on the column of ones and then doing the standardization right after it. So apparently the standardization process is affecting the column of ones in a kind of negative way. In order to fix this, all we have to do is take that concatenation step, cut it, and then only apply it after we have gone through that process. Okay, so now we can save this thing, and we can try rerunning our node index.js again. And you'll notice that now we have the correct values in that first column, just plain ones, no negatives, nothing like that. However, you will notice that we still have a bad r² value. So clearly, while that's definitely probably something we wanted to do, it did not actually improve the accuracy of our analysis at all. So I'm going to flip back over, and I'm going to remove that print statement for now. At least we've kind of fixed that one issue, and we know that it's not causing a problem and giving us an issue with the accuracy. Now, before we move on, one more quick thing I want to show you, because this was a real surprise to me. So I'm going to flip over to this little coding tool over here that we've been using quite a bit. And you'll notice I've already put a little bit of code in here to create a features tensor full of ones. And it's got 10 rows and 1 column. So if I print that thing out, you'll see, yep, we got a whole bunch of ones in there. So here's the surprising thing, something that I didn't really expect to see coming. I'm going to apply the same standardization process on this ones column right here, but rather than doing it inside of essentially the Node.js runtime, we're doing it inside of the browser here instead. So I want to show you some really unexpected behavior. I'm going to do features.sub, mean, and then divide by the variance, pow 0.5 like so. And now take a look at the output right there. 2 seconds ago, we just ran the exact same operation on a column of ones in the Node.js environment. And we saw that the output was a bunch of negative values, -0.9995. essentially -1. But when we run this in the browser, we get a completely different result. So why is that? Well, it really comes down to the TensorFlow runtime that we are using. TensorFlow internally is not doing all these calculations itself. It actually delegates a lot of these calculations to the native components in the environment that it's in. So in the browser, TensorFlow uses what's called WebGL to do a lot of these calculations for it, because WebGL can handle matrices, or essentially tensors of values, extremely efficiently. So what we're seeing here is just an artifact of these different environments that we are running TensorFlow in. And like I said, very unexpected behavior. So this is just something that I want you to be aware of, and it's probably not going to cause any issues for us anywhere else in this course, but if you ever start to see different behavior between Node.js and the browser when you're making use of TensorFlow, well, it might be an issue similar to this one right here. Okay, so I think that we learned a little bit more about TensorFlow, and we also did a little fix-up on our process features function. Now, one thing I want to mention here really quickly, I'll be totally honest with you, I did not know about this difference in how Node treats this once column when doing that standardization versus the browser. And so moving forward, I actually already kind of recorded a couple videos where you're going to see that line of code back up there. So if you watch a video in the future or after this one, and you see that once column being concatenated ahead of time, well, just ignore that. Stick with putting the once column on after. Like I said, this is something that I only learned a little bit later on because I kept on doing that calculation inside the browser like this, testing it out and saying, oh yeah, standardization doesn't affect it at all. No problem whatsoever. And it only came through a little bit of trial and error later on that I realized, no, that's not really the case. All right, so let's take a quick pause right here and continue in the next section where we will get back to doing a little bit of troubleshooting around that really poor accuracy value. So I'll see you in just a minute. In the last section, we implemented standardization on both our training set and test set. But when we reran our analysis, we very quickly got an R-squared value right here, even worse than it was before. So remember, the more negative the R-squared, or coefficient of determination value is, the worse our analysis is doing. So what could be going wrong now? Well, let's recall. Anytime that we start doing an analysis, we end up having to do a little bit of tweaking on our learning rate right here. We could also try adjusting our iterations as well. Now that we are standardizing our data set, a learning rate of 0.0001 is generally going to be a little bit too low to get any meaningful results over 100 iterations. So I'm going to try increasing my learning rate up to 0.1 like so. So I'm going to save this, and I'm going to rerun my analysis. And now when I do, you'll see that I get a far more reasonable R-squared of 60%. Now that's still not perfect, but it gives us a far better value than we had before. So now that we have some idea or some proof that we can get some correlation between the mile per gallon, or excuse me, the horsepower of our vehicle and its fuel efficiency, we can continue to play around with our learning rate and our number of iterations a little bit more. For example, maybe I want to try a learning rate of 0.5. Let's try that out. Now when I rerun my analysis, well, it looks like I've got just about the same as I did before. Let's try a learning rate of 1. How's that do? Same as before. So what this tells me, with this changing learning rate, but not seeing any increase in the accuracy of our analysis, it's telling me that we are essentially getting to convergence, or we are getting to our optimal solution for our weights of M and B with just a couple of iterations. And we don't really need to toggle or increase anything here much more to increase our analysis, or increase the accuracy of our analysis. So at this point, I would say that a R-squared value of 0.6 right here is good, but it's still not great. So I'm now kind of wondering, is there some other way in which we could increase the accuracy of our analysis? Well, remember, inside of our cars.csv file, we've got a lot of other features inside of here that we can start to play around with. So in addition to just the horsepower, we also have vehicle weight, acceleration, we've got our model year, which maybe is not super relevant, but we've got cylinders as well. So maybe we can start bringing these other features into play and see if we can increase the accuracy of our analysis. Now, before we do that, we need to make sure that all the logic that we put together for our gradient descent algorithm is going to be able to kind of add in these additional features. Remember, at present, we've only got these two weights, M and B. And M and B are only used to relate one singular independent variable to one singular dependent variable. So let's take a quick pause. When we come back to the next section, we'll start doing a quick review on how we might need to change our gradient descent algorithm to account for additional features inside of our data set. We've now got our r-squared value up to 0.6, which is better than what we had before, without a doubt. It means that we're now making estimates or predictions that are better than just taking the average value and assigning it to all possible vehicles that come across. But I think that we can still do a little bit better than what we have right here. So the next thing we're going to start working on is making sure that we take into account multiple features besides just the horsepower of a vehicle. So I would argue that maybe the engine displacement or the weight or the acceleration of a vehicle all have an impact on the final mile per gallon value. So we need to figure out a way to adjust or massage our gradient descent algorithm to make sure that it can take into account multiple features at the exact same time. So how are we going to do this? Well, we actually don't have to do too much work to actually make this happen. In general, this is the equation that we want to come up with right here. So we want to find the mile per gallon value of a vehicle using its weight, its displacement, and its horsepower. We could add in acceleration to this analysis as well. Remember, that's one of the fields on here too. Acceleration right there. But I'm going to say for right now, let's just say we'll try using these three features first, and then maybe add in acceleration after that. So given the weight, displacement, and horsepower of a vehicle, we want to find a m1, or essentially a slope or a coefficient to multiply by the weight, an m2 value that's going to be multiplied by displacement, and an m3 that's going to be multiplied by the horsepower, plus some constant b. So we're going to try to relate or find a relationship between these three features and the final mile per gallon value of the vehicle. The general equation of essentially what we're trying to solve here is this right here. So we're saying that we want to find an M1, M2, and M3 that's going to relate these X1, X2, and X3 features to some output value or some label that we might refer to as Y. Now, everything that we've done up to this point has only been concerned with one single feature at a time. Because we were only concerned with one feature, we would refer to everything we've done up to this point as univariate linear regression. The word univariate here means that we have one variable or one feature, which was X. That was it, just one feature. Now that we're going to introduce multiple features or multiple different X values, so to speak, we would refer to this as multivariate linear regression because we've got multiple variables. Now, again, we've essentially got all the code already put together to do multivariate linear regression. But rather than just throw a ton of data into our algorithm and say to you, hey, look, you know, it magically works, I want to very quickly take this section to walk through the math kind of behind the scenes and go through the same process we went through previously when we first started looking at our single equation right here, and essentially just show you how all these tensor values kind of multiply off each other and work out to give us a reasonable solution. So let's get to it. All right, so we're going to start right here. So just as before, we're going to first take a matrix of features and we're going to multiply it by a tensor of weights. And remember, I just said the term matrix and tensor. I'm using those terms somewhat interchangeably here. There is a very subtle difference between the two, as I've mentioned before, but for our purposes, we can kind of use those terms interchangeably. So remember, the first operation we want to do to calculate our slopes is multiply the features by the weights using matrix multiplication. So that's what this step right here is doing. So over here, I've got my weights, and it's now been expanded to include new values of m, so m2 and m3. We can imagine that m2 and m3 might take the form or might be responsible for kind of adjusting the value of the engine displacement and the weight, whereas before we had just a single m value that was going to adjust our engine horsepower. In addition, you'll notice that our feature matrix over here has changed as well. So we've still got our arbitrary column of ones on the far left-hand side, but then I've added in more columns to represent the new features that we want to do some analysis on as well. So I've got my weight and my displacement here in addition to the horsepower. Now you'll notice that I put the weight and displacement columns in between that column of ones and the engine horsepower over here. It doesn't matter in the slightest what order you put these different features in. We could put engine horsepower first, or we could put it second, we could put weight last. It doesn't make a difference. The only difference is that when we eventually go to adjust our weights tensor over here, the final weight, or M3 right here, is going to correspond to the third listed feature. The second weight is going to correspond to the second listed feature, and the M1 is going to correspond to the first listed feature. So again, as we start to massage the order of values inside this thing right here, all that's changing is the weights, or the order of the weights that come out. And it doesn't make a difference if we change the order of those weights. There's no difference whatsoever. So let's go through the process of doing this matrix multiplication. So we need to first check our shape. So the shape over here, we've got 6 and we've got 4 columns. And then on the right-hand side with the weights, we've got 4 rows and 1 column. One last thing I want to mention here very quickly, you'll notice that before I had been reflecting in this diagram the engine horsepower using values like, x1, x2, well, you get the idea, x3, and so on. But now, just to make the terminology a little bit easier, I'm going to say that all these x1 values are essentially different observations of my weight. All the x2s are different observations of displacement, and all the x3s are different observations of engine horsepower. You're going to see in a lot of kind of like documentation and blog posts and what have you, what they'll sometimes do to represent these different values is they'll write out like, the x variable here, which is supposed to represent a feature, and then they'll put on like both a superscript and a subscript to it. Oops, come on. That and that, like so. And then they'll make these numbers. So they might put like x1 and like x2, and frequently the superscript will be in parentheses to make sure that that's not supposed to square the number. And so this right here might be trying to say, oh yeah, this is supposed to be the 1th feature, so in this case maybe our weight, and it's the second observation of the weight. So you might sometimes see this notation right here. I could definitely massage this diagram right here and change it out to use that notation. I think that it would just make things a little bit more challenging to understand, which is why I left it in the more simplistic form. But again, I just want you to know that sometimes you'll see that alternate notation. Okay, so there's the matrix multiplication. So now we can go through the multiplication here. Don't worry, I won't make you watch me do too much of this. Again, we put our matrix A to left, B to the top, and then C is going to be a 6 by 1. So we would do 1 times B plus x1 over here times m1. x1 times m1, and I think you know where this is going. It would then be x2 times m2 plus x3 times m3, like so. And we could continue that going all the way down. So as you can see, the end result here is that we're essentially making guesses, just as we were before, about the mile per gallon of our vehicle. And we just were able to do this equation or do all this math right here very easily by doing simple matrix multiplication. Okay, so that's going to give us essentially our current guesses of what the mile per gallon for each of our different vehicles are using our weight, displacement, and engine horsepower. So now, the next thing we would do in our big equation over here, we've done our guesses through that matrix multiplication. We would now subtract out the actual values, or our labels. And so for those labels, really straightforward, we would take the guesses, which you'll see I've left out in the kind of long form equation, and then we would subtract out the actual mile per gallon of cars 1 through 6 or whatever it might be. And that would leave us with our differences, so to speak. And then after that, we've got our differences as the result of that entire term right there. So that's our differences, like so. And so now we're going to do matrix multiplication with the transpose of our features matrix. So the T right there, the capital T, is meant to represent transpose. So that would be this right here. So I took the same feature matrix, but I took the transpose of it. Remember, when we do a transpose, we essentially look at all of our different columns and we turn them into rows. So this column right here would turn into the first row. This would be our second row, third row, and fourth row, and so on. Then we could very quickly look at our shapes. So the shape over here would be a 4 and 6 because we got 4 rows and 6 columns. And then over here we've got a 6 and 1. And so they're definitely eligible for matrix multiplication because we got 6 on the inner values here. And the output matrix that we would get as a result would be a 4 by 1, or 4 rows and 1 column. And so again, we could very quickly go through that matrix multiplication. Again, not going to really make you watch me do too much of this. So I would take 1 times d1. I would take 1 times d2, and so on. So the first term here would be d1, d2, d3, d4, d5, d6. And then the second one would be a little bit more interesting. So we would take our weight times d1. So x1 times z1. And then our weight, second observation, right there, times d2. So So x2 times d2 and so on. Again, you get the idea. So the end result here would be a 4x1 matrix, or 4x1 tensor. And just like before, this tensor right here represents our slopes, or essentially how far away, or kind of that, remember giving us that negative or positive sign that tells us how we need to update all of our different weights that we're using to find our relationship between all of our different features and the mile per gallon label values. And so we would take those slopes, and just as before, we would attempt to update our values of B, M1, M2, and M3 using the same equation we had previously. So we would multiply those slopes by our learning rate. We would then take our existing values of B, M1, M2, M3, and then subtract by the learning rate times those slopes. All right, so again, all I'm trying to say here is it's the same stuff. It turns out that when you do these vectorized solutions for just about all these different algorithms in the machine learning world, you can kind of throw tons of different data at it, and it's going to usually just work out a-okay. You can kind of imagine that if we try to put this solution together, our gradient descent algorithm right here, if we try to put the solution together using that old logic that we had, where we had been trying to calculate, our B slope and our M slope very manually using Lodash and the for loops and map statements and whatnot, we would have had to do like M1 slope and M2 slope and M3 slope and so on. And that would have been a total nightmare to write that out. So by using this vectorized solution, we can just throw tons of different data with huge different sets of features, 1 feature, 2 feature, 10 feature, 20 feature, and all the math is just going to work out a-okay. Now, before we get too happy, there is one tiny little update that we need to do to our linear regression class. So let's take a quick pause right here. When we come back to the next section, we're going to do one tiny update to make sure that everything is going to work okay with a multivariate analysis. So quick pause, and I'll see you in just a minute. In this section, we're going to make a tiny change to our linear regression.js file to make sure that the class is going to work with a multivariate analysis. We'll then run our analysis and see if we can get a better coefficient of determination than that current 0.6 or so that we have. All right, so the only change we have to make is to make sure that our weights tensor gets initialized with the correct shape. At present, inside of our linear regression class, if you find the constructor, at the bottom of the constructor, we have hard-coded our weights tensor to always have 2 rows. However, we're now saying that the weights tensor needs to have a number of rows equal to the total number of columns inside of our feature matrix. So however many columns we have in the feature matrix, we need to have exactly that many weights. So essentially all we need to do here is remove the hard-coded 2 and replace it with the number of columns inside of features. So I'm going to delete the 2, and then I'll look at the shape value of features, and I'll just take the second value out of the shape array that gets returned. Remember the nomenclature that I told, the little mnemonic essentially that I told you to memorize, row column, row column, row column. The second element inside of the shape array is the number of columns inside of this dot features. So I'll say this dot features dot shape at 1, like so. And that's pretty much it. So now weights is going to be initialized to have a number of rows equal to the number of columns inside of our feature matrix. So if we decide to drop off, say, the displacement and engine horsepower, like so, then we go down to only 2 values inside of our weights. But if we have our 4 different columns inside of features, then we're going to end up with 4 rows inside of weights. And so we'll be able to track the M1, M2, and M3. That's going to give us some type of relationship between those features and our actual label values. Okay, so enough of that. That's the only code update we have to do to our linear regression.js file. Now the last thing we need to do is flip back over to the index.js file and make sure that when we create our new instance of linear regression here, we give it some additional number of features. So right now we're only giving it the feature type of, what was it? Where is it? There we go, horsepower, right there, out of our CSV file. So now we want to give this thing multiple different features in addition to horsepower. So I think that we'll start nice and easy. Maybe we'll add in our engine displacement and our weight. And then we'll run our analysis, see how we're doing, and maybe we can include some other features inside of here as well. So in order to include those additional features, we're going to find our data columns property right here, which determines what different columns are going to end up inside of our features and test features. And I'm going to add on weight and displacement like so. Make sure you spell displacement correctly. If you spell any of these terms incorrectly, then they're not going to be properly read out of the CSV file, and you're going to end up with some pretty weird errors when you try to run this analysis. All right, so that's it. That's all we have to do. We can now run a multivariate linear regression. So let's try it out right now. I'm going to flip back over to my terminal, still inside of the regressions folder, and I'll do node index.js. So it looks like we get a r² value right here of -infinity, which is definitely not good. So you might be thinking, all right, well, this is awful. We must have done something wrong. Well, not really. We actually did everything just fine. Remember, all of our analysis is incredibly impacted, so incredibly important, this learning rate right here. If we have a learning rate that is too high, then our different m values and our single b value are going to spiral out of control and eventually go towards positive infinity. And so that's what's happening in this case. Our learning rate is too high, so we're never finding optimal values of m and b because we're always overshooting our optimal values. So all we have to do here is start to adjust our learning rate, and we're going to very quickly see that we do in fact have a valid analysis. So I'm going to replace the learning rate. Let's start a little bit smaller with 0.01. I'm going to save this, and then I'll rerun my node index.js file. And now I see that I do in fact have a more realistic r² value. It's negative, which you'll recall means that if we took the average value of our mile per gallon for each vehicle, we would be better off than the analysis that we're doing right now. But at this point, we can now start to kind of play around with our learning rate a little bit and hopefully come to some better result. So let's try going up to 0.1. With 0.1, I get all the way up to 0.66, which is definitely an improvement on what we had before, that 0.6 value. Let's try going a little bit higher. I'll go up to learning rate of 0.5. And now I go down, actually, to 0.65. Whenever we go down in our r² value with an increase in our learning rate, that means that we've gone to some value of our learning rate that's causing us to kind of ping-pong back and forth on our correct value of our ping-pong back and forth and never really reach our optimal value of b and all those different m's. So if you start to adjust your learning rate and you see that r² goes going down, that means that, yeah, the learning rate is probably still a little bit too high. So I would maybe just leave it at a learning rate of 0.1 for right now. And then one easy thing that we could do to try to increase our accuracy would be to now increase our number of iterations. So maybe we'll go up to 1,000 iterations. I'll run this again. And now it looks like our r² value went down again. So again, whenever the r² goes down, that means that we're kind of ping-ponging back and forth right around those optimal values of m and b. And so at this point, I could either reduce my iterations back down to 100, or I could go to an even smaller learning rate. So let's try 0.5, which is half of what it was before. And okay, it's still getting that 0.65. So maybe we would just be happy with the learning rate of 0.1 and 100 iterations like so, which gave us the r² value of 0.66. Okay, so it looks like our analysis is working, and we are getting some more accurate analysis when we include the weight and displacement of a car than when we were only looking at the horsepower alone. One thing I want to mention here is that at this point, it's probably very clear to you that this learning rate factor right here is a real pain in the rear. And I bet you're kind of getting the feeling that having to tweak that number all the time and then go rerun your analysis, that doesn't really seem like something that's going to scale very well. We might be trying to run some analysis that takes several hours to run. And there's no way in the world that we would want to sit down and do a multi-hour analysis and then say, oh, hey, our learning rate is wrong. Let's start toggling it around a little bit, right? We don't want to be rerunning our analysis 5 or 10 or 20 different times, just toggling the learning rate and trying to find some optimal value. So let's take a quick pause right here. When we come back to the next section, we're going to start to think about how we can start to do a little bit of optimization on the learning rate and maybe figure out some way in which we could not have to toggle this thing repeatedly or change it all the time just to get some realistic answer. So quick pause. When we come back to the next section, we're going to start to look at how we can adjust that learning rate on the fly. I don't know about you, but in the last section, I started to get really frustrated with the learning rate right here. We had made some changes to our linear regression class, and then we reran our analysis with a learning rate of 1, like so. And when we did so, we got an r² value of -infinity, which meant that our answer was incredibly wrong. When we then updated our learning rate to 0.1 and reran the analysis, we got a much more reasonable R-squared value of 0.66. And so it seems like this learning rate value right here is the difference between us having our algorithm working and us thinking that we had made a huge programming error. So I don't know about you, but that makes me a little bit frustrated. And it makes me wonder if there's some way that we can get a better value of our learning rate in here and make sure that, we're not kind of erroneously seeing crazy values like negative infinity. So in this section, we're going to start to talk about how we can adjust this learning rate over time and make sure that we're not going to get crazy results like that negative infinity. Before we talk about how we're going to optimize that value, I want to give you a quick reminder on exactly what the learning rate does, because it's really key for you to understand what the learning rate is really doing for us. So, quick reminder here. Remember, the entire idea behind gradient descent is that we're going to make a guess for our current value of some factor like b or m or whatever it is we're trying to guess. In this case, we're going to walk through this example with our value of b. So we're going to make an initial guess of a value of b, and then we're going to calculate the mean squared error value. Remember, the mean squared error is essentially a metric that tells us how good or how bad our current guess of b and m are. And so with our initial guess of b, we're going to run mean squared error, and maybe we get a result of like 60,000 or so. So if we get a 60,000, that means that, hey, maybe we did good, maybe we did poorly. I don't really know. So rather than looking directly at the mean squared error, we instead usually try to find the slope of mean squared error at that very specific point. And the slope is why we were using this equation right here. We were calculating the slope of mean squared error. So we would calculate the slope of that thing, and maybe we got a slope value of like negative 999. Remember, a couple of videos ago, we had discussed about how the magnitude of that slope is really a meaningless number. And it's really just the negative or positive sign that tells us if we need to increase our guess of b or decrease our guess of b. So in order to account for the fact that the slope or the magnitude of that number was meaningless, we would multiply it by our learning rate. So the entire purpose of the learning rate was essentially just to do an arbitrary adjustment to the magnitude of the slope and make sure that we did not increase or decrease b by too much in any one go. Now the downside to this was that if we had a very large learning rate, then we might accidentally completely overshoot our ideal guess of b. And we ran through an example a while back where we saw if the learning rate was too large, we would actually increase our guess of b by too much, and we would eventually spiral out of control by increasingly increase, that's kind of a crazy way of putting it, but eventually our b value would spiral out towards the value of infinity, and it would get just too large. So that's a quick reminder on what the learning rate does. So now that we remember what it does, let's start to talk about how we're going to adjust it and optimize it over time. Now the process of updating our learning rate or getting some value that we feel like we can be very comfortable with is going to use what we refer to as a learning rate optimization method. There are many ways of adjusting our learning rate over time as gradient descent runs. So with every iteration of gradient descent, every time that we go through all those different steps, we might use one of these different methods to adjust our learning rate. So some of the existing methods out there you might see in blog posts or documentation, and you'll see terms like atom or RMS prop or momentum. Again, these are methods to help you adjust your learning rate over time so that you do not get a learning rate that is too large or a learning rate that is too small. Now, the actual implementation or the kind of behind the scenes math on all these different methods is a little bit complicated. And it's a little bit more complicated than we probably want to get into right now. So believe me, if I thought there was value to implementing one of these optimization methods from scratch, we would definitely do it in this course. But I personally don't feel like we really need to understand how these things are written from scratch. So rather than trying to put any of these specific methods together from scratch, we're going to instead put together our own kind of custom approach to learning rate optimization. So we're going to put our own custom approach together. It's going to have a very similar effect to all these other much more popular methods. So essentially, they're all working the same way. We're just going to take a more straightforward, easy to understand, and easy to code version of this stuff. So here's our custom learning rate optimizer. We're going to say that with every iteration of gradient descent, we are going to calculate the exact value of mean squared error and store it. So essentially with our initial guess right here, when we run our first iteration of gradient descent, we are going to find the mean squared error at that point. And so it might be something like, say, 60,000 right there. So we'll record that number. Remember, this is the mean squared error. It is not the slope. So the mean squared error is the metric of how good or bad our guess is. Then, with the next iteration of gradient descent, we're going to record our MSE again, and then we'll look at the current MSE and compare it to the old MSE. So in other words, we're going to run another iteration of gradient descent, and maybe we have a second guess right here, and we will calculate our mean squared error right there at 30,000 or so. So once we do that, we're then going to compare the current mean squared error with the previous mean squared error. If the mean squared error went up in value, if it got larger, then it means that we must have done a very bad update, and we might have a learning rate that is too large. And so we might divide our learning rate by 2. Now, if the mean squared error went down, as it did in this diagram that I showed you right here, so if the mean squared error went down, then it means that we are getting closer towards our solution. And so in order to get towards our solution more quickly, we are going to increase our learning rate by 5%. So that's the whole idea. We're just going to look at our mean squared error. If we're getting closer towards our solution, we're going to increase the learning rate so we get towards our solution more quickly. But if for some reason we record our mean squared error, and in between two guesses, we see that it goes up, like let's say over here it goes to 70,000. So this would be guess 1, this would be guess 2. If we saw that the mean squared error went up for some reason, then that means that our learning rate is probably too large and we need to decrease it. So in that case, we would divide our learning rate by 2. And one thing I want to mention here, these factors that I'm mentioning, like dividing the learning rate by 2 and increasing it 5%, totally arbitrary. We could just as easily say that we're going to divide the learning rate by 3 or 1.5 or 1.6, whatever you want it to be. But it kind of seems like the numbers of 2 and 5% usually make a pretty good amount of sense, and they work out pretty well. And if you want to, you can test around with these factors a little bit and adjust the learning rate by different amounts if you're getting closer to the solution or further from the solution. Okay, so that's the entire idea. So let's take a quick pause right here. When we come back to the next section, we're going to start to implement this learning rate optimizer inside of our linear regression class. In the last section, we spoke about how we're going to start to optimize our learning rate with every iteration of gradient descent. Now, as a quick reminder, here is the equation for our mean squared error. Remember, huge difference between the equations that we've been looking at so far. This is the slope of mean squared error with respect to m and b. That's what we've been working with so far. So at this point, we don't care about our slope anymore. We care about the actual mean squared error value. And that's this equation right here. We had looked at this way long ago. Now this is the kind of long-form equation version of mean squared error, but as you well know by this point in time, we've been looking at kind of vectorized solutions that allow us to use tensors to dramatically simplify the logic that we have for doing all this gradient descent stuff. So a vectorized version of mean squared error would look like this right here. We're going to take our features matrix, we'll multiply it by our weights. Remember, when we multiply features by our weights, that essentially gives us our current guesses. We'll then subtract our labels tensor, and then we'll square all of the numbers inside there. Finally, we're going to sum up all those numbers and then divide by n, and that's going to give us a single value that represents our mean squared error. So let's flip back over to our code editor. We're going to put together a function that implements the mean squared error equation, and then we're going to run that function with every iteration of gradient descent. So back inside my code editor, I'll change to the linear regression.js file. And then I'm again going to go down to the very bottom of the class. And down here, I'll put together a new function that is going to calculate and record our current value of mean squared error. So I'll call this function something like record MSE, like so. Record mean squared error. So inside of here, we're going to look at this.features. We want to multiply that by our weights. So I'll say matmul this.weights. And then I want to subtract out my labels. So I will sub this.labels. After that, I want to square all the values inside there. So I'll do a .pow2. And now before I run out of space, I'm going to put a couple new lines in here very quickly. Okay, and then finally, we want to sum up all the values inside there. We want to condense all the values in this newly created tensor after squaring everything into one single number. So I'll do a .sum like so. Finally, we need to divide by the total number of observations, or the total number of records that we have inside of our feature set. So for that, we will .div, and we're going to divide by this .features.shape, and remember, we would want the number of rows here, so I would get the first value out of shape. And then finally, at the very end of all this, we do not want to work with a tensor anymore. We want to work with just a plain number. And so I would put on a .get like so. Now I'm going to assign the result of all this to a variable inside of here that I'll call MSC. And then finally, we need to somehow record this mean squared error that we have now calculated. So I think that we should make an array, and every time that we calculate this mean squared error, we will store it inside of that array. I'm going to first create the array up inside the constructor, and I will initialize it as an empty array. So up here, I'll say this dot, we need a name for this thing. What would be a reasonable name? I don't know. How about like MSE history? I think that makes sense. So mean squared error history over all the different iterations of gradient descent that we've gone through. And then I'm just going to initialize it as a simple array like so. So now back down inside of our record MSE function, we'll call this .msc history, and I will push MSC into it like so. So we've now got a function that's going to calculate our mean squared error and store it inside of MSC history. So now the last thing we need to do is make sure that this function gets called every time that we go through the gradient descent function. So I'm going to scroll back up to my train function. Here's train right here. This is where we call gradient descent. So right after we call gradient descent, we will call this record MSC like so. Now we do not need to record our MSC when we are going through the test process, because remember, with test, we are not updating our weights anymore. We only have to record our mean squared error when we're going through the training phase. Last thing I want to remind you about, if you put capital MSE right here, make sure that you've got the same capitalization down on the function that we just put together, because that's a very common and easy little typo to make. Just make sure you've got the same capitalization. Okay, so that looks good. Let's take a quick pause right here. When we come back to the next section, we're going to start to inspect the value of those MSC values. Funny way of putting it, sorry. And if they go up over time, we're going to divide our learning rate by 2. Otherwise, we will increase it by 5%. So quick pause, and we'll take care of that in the next section. In the last section, we put together a record mean squared error function. So that thing is going to record our mean squared error with every iteration of gradient descent. So now we need to implement a second function that's going to look at the 2 most recent mean squared error values. If the mean squared error went up, then that means that we did a bad update and we need to divide our learning rate. Otherwise, we are going to increase it. So back inside of my linear regression.js file, I'm going to again go to the very bottom of the linear regression class, and I'm going to add on a new method to this thing called update learning rate. So this function is going to look at this.msc history. It's going to look at the last 2 records and decide on how to update the learning rate. Now the first thing we need to be aware of inside of here is that we do not want to run this function if we do not yet have enough records inside of MSc history. In other words, the first time we run gradient descent, we're only going to have one single MSc value. And so we do not yet have enough records to actually do a meaningful update. So at the top of update learning rate, I'm going to say if this.msc history.length is less than 2, then that means we don't have enough MSc values to do any meaningful update. And so I'm just going to return from this function without doing any additional work. Now, if we get past that if statement, then it means we have enough history and we can do a meaningful update. So we need to pull out the last value and the second to last value and compare them. So to get out the last value, we could say something like last value is this.msc history at this.msc history.length minus 1. And then the second to last value would be second last, and it would be a minus 2 like so. Now, I just want to point out something here. Seeing code like this makes me kind of unhappy. I don't really like getting the last record inside of an array by using this .length -1 stuff right here. So we've got two options here to kind of clean this stuff up. We could either use Lodash to pull out the last two records, or there's actually a even better way that we could update this code to look a lot better than it currently does. Remember, right now, inside of record MSC, we're going to always take the most recent version or the most recent calculation of mean squared error and push it onto the end of the array. That means that the MSE history is going to go from the oldest value of mean squared error to the latest value, which is why we had wanted to get the last two values. A different way that we could approach this problem, just to clean up some code in here, this is going to have no impact on the actual logic that's going on, just to clean up our code, we could say that rather than pushing the latest value of MSE to the end, we could add the latest value to the front of the array instead. So essentially, the mean squared error history array would have values that range from the newest value of MSE to the oldest. And so it would just make life a little bit easier to get the two most recent values of MSE history out of that array. So to do so, we could use a unshift function instead of that push function. Let me just give you a very quick demo here. So I'll say const MSE history is an empty array. And I'll do MSE history dot unshift 100, and then maybe 500, and then maybe 999, like so. And now if I print out MSE history, you'll see that the most recent shifted record, unshifted record is going to be at the front. And so essentially we would want to compare these two records right here to decide whether to increase or decrease our learning rate as opposed to the last two. So again, the only reason that we're doing this is just to make our code look a little bit nicer. That's the only reason. So inside of record MSE, rather than doing the shift right there, I'm going to do an unshift instead, like so. So we are now doing an unshift for MSE history. All right, so now to get our two most recent values of MSE history, we don't have to write out that ugly logic anymore. Instead, we can simply say if this.MSE history at 1 is greater than this.MSE history at 0. And I kind of put that in a funny way. Let's swap the indices there. Let's do 0 and 1 like so. That makes a little bit more sense. So now this right here is going to say if our MSE just increased, so if it went up with the latest calculation of MSE history, then that means that we are getting more incorrect, in which case we would probably want to reduce our learning rate. And so I'm going to say this.options.learning rate is equal to this.options.learning rate divided by 2, like so. An alternate way in which we could adjust this value right here would be to simply do an abbreviated operator like so. So that's the same thing right there. It's just going to update the learning rate without having to reference it separately. Okay? So now in the else case, so this is the case in which our mean squared error went down, we would increase the learning rate by saying this.options.learning rate times equals 1.05 like so. So that right there is going to increase the learning rate by 5%. Okay, so that's pretty much it. I kind of apologize for throwing the unshift in here at the very end, but as you see, it just kind of makes the logic here a lot more legible, easier to understand what's going on here. All right, so now the very last thing we need to do is make sure that we call update learning rate. So I'm going to go up to our train function again. Here's train right here. Right after we record our mean squared error, I'll then call this.update learning rate. So we're going to run our gradient descent, then we will record our mean squared error, and then we will attempt to update our learning rate using that mean squared error. Now, a quick question that you might have around why we put these two things into two separate functions. Well, honestly, there are occasions where we might not want to update our learning rate, but we still might want to record our mean squared error. Because you're going to see later on that we can actually put together some interesting charts using the mean squared error. So there might be times where we want to chart out our mean squared error and how it changes over time, but we might not want to actually update our learning rate at all. So that's why we put these things into two separate functions. All right, so let's take a quick pause right here. When we come back to the next section, we're going to try testing out our new kind of self-adjusting learning rate over time. So quick pause, and I'll see you in just a minute. In the last section, we implemented a new function to update our learning rate over time, and then we made sure that we called that thing from our train function back up here, after we do our initial gradient descent and record our mean squared error. So we're now ready to test this new change out and see if we can get away with some more dramatic changes to our learning rate and still end up coming to a reasonable solution. So I'm going to flip back over to my index.js file. I'm going to find my new linear regression class right here. And rather than putting in an initial learning rate of 0.1, I'm going to put in a learning rate of 10. Now, without doubt, a learning rate of 10 is going to result in values of m and b that are going to be extremely large. We definitely know that was the case in the past when we put in even just a learning rate of 1. So I'm going to try a learning rate of 10 and see if our analysis is still going to work out the way we would expect. All right, so I'm going to flip back over to my terminal, and I'll run node index.js. And now you're going to see that we get a r-squared value right here of 0.65, which means that we did, in fact, correctly update our learning rate over time, even though we had that initial crazy learning rate value. Now, if you wanted to see something interesting, we could actually print out the changes to our learning rate over time. So how about inside this train function right here, again, I'm going to put inside of the for loop a console log this.options.learning rate. I'll then save this file, and then I'll rerun my analysis, and we'll be able to see the learning rate change over time. Awesome. Okay, so up here at the very top, we can see that we started off with a learning rate of 10. Now, the first 2 iterations have 10 because remember, with the very first iteration, we don't have enough data to actually make a change to the learning rate just yet because we've only got one single mean squared error value. So then after we get through 2 iterations, we then start to update the learning rate. And we first go down to 5 by dividing it by 2. We divide by 2 again and divide by 2 again. And then eventually at around 0.625, we find that the learning rate is a little bit too low. And so we increase it by 5%, increase, then divide, and then increase. And essentially you get the idea. So the learning rate is constantly adjusting to make sure that we are making optimal progress towards our optimal values of m and b, or all the different m values in our b value. And so we eventually end up with the learning rate down here of 0.0367. And so that means that by the very end of our analysis, we are doing these very tiny updates to all of our m and b values to make sure that we get to just the right optimal values. Now, the other thing that we could print out here that might be a little bit interesting would be our MSE history array. Remember, the MSE history array records all of our different mean squared error values. So I just removed the console log for the learning rate inside that for loop. And now to console log out the mean squared error history, we can actually do that back inside the index.js file because the mean squared error history is a property on the class. So back over here, right above the existing console log, I'll throw in MSE history, and that's going to be regression.mse history, like so. And so now we can do another run of node index.js, and we'll see our mean squared error values. Now remember, in this case, we're going to see from the latest mean squared, or the earliest mean squared error, that's the best way of putting that, up to the latest, or the newest mean squared error. So essentially, at the time that we put together our final solution here, so this is the final mean squared error value, we ended up with 17.98. But if you go down to the latest values, all the way down here, you can see that we had like absolutely stratospheric values of mean squared error, which means that we were very, 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 very wrong at these initial values back here. Okay, so this looks pretty good. So let's take a quick pause right here. We're going to come back to the next section, and there's just a little bit more that I want to do around these mean squared error and these learning rate values. So quick pause, and I'll see you in just a minute. In the last section, we logged out our MSE history and our learning rate. Now, it's definitely nice to see those numbers at the terminal, but I think what would be really neat is if we could make a plot or a chart of sorts that kind of tells us how our learning rate is changing over time, or even what our MSE history is doing as well. So in this section, I want to show you a tiny little package that we can use to put together some pretty simple and straightforward little plots. To get started, I'm going to go up to the top of this file, and I'm going to create a new variable called plot, and then assign it a require statement, and we're going to pull in a library called node remote plot, like so. Now, this is not a standard Node.js library. It has already been pre-installed inside of your package.json file. So inside of here, you'll see that there is, in fact, node remote plot right there. All right, so we can now use this plot function right here to put together a very simple chart and save it into our current working directory. So to do so, I'm going to go down to the bottom of this file. I'm going to delete the console log with our MSC history, and I'm going to replace it with a call to plot. I'm going to put an empty object in, and I'm going to give it one property, x, like so. And then I'm going to assign it our regression.msc history. All right, so now all we have to do is run our index.js file, and this plot function will automatically create a chart out of our MSC history. Let's try it out really quick and see what we get. So I'm going to flip back over to my terminal and run node index.js. I can then flip back over to my code editor, and then in my folder explorer, I'll see that there's a new file inside of here called plot.png. So I can open that up, and I'll see my plot. Now, if you cannot open up the PNG file inside of your code editor, that's totally fine. You can always use your native folder explorer to navigate to your project directory and manually open up the PNG file. So now we can take a look at this thing and try to interpret what's going on. It might be helpful if we add on some labels to our Y and X axes to get a better sense of what data this is showing. So back inside the index.js file, I'm going to add on two more properties to that plot options object. The first one is going to be xLabel, and I will provide this a reasonable name. So in this case, our MSC history is the value of MSC for every iteration that we go through. And so a reasonable xLabel here would be iteration number. And then I can also provide a ylabel as well, which in this case could be MSC or mean squared error. All right, so I can now save this file again, and then rerun the node index.js command, and then I can see my new plot right here. So now I see, yep, that's my mean squared error and my iteration. Now remember, the iteration as we are storing, or the mean squared error as we're storing it inside of that array, is going from the latest value of mean squared error to the, oops, didn't mean to zoom in there. It's going from the latest value of mean squared error to the very first time we ran gradient descent over here on the right-hand side. And so right now the iteration numbers are kind of in reverse. One easy thing we can do to make the plot make just a little bit more sense would be to reverse the MSC history array. So I'm going to save this one more time. I'm going to rerun node index.js one more time. And now I can look at my plot, and it's going to start making a little bit more sense. Okay, so what's going on here? Well, essentially we start off with a mean squared error that is very low. It starts off very low because, remember, we get some initial m and b values at 0. That's what they start off at. However, with our very large learning rate, right now the learning rate that I have is 10, that causes the m and b values to absolutely explode to very large values until eventually our learning rate optimization algorithm kicks in and reduces those values down to more reasonable levels down here. If we want to see our plot make a little bit more sense, then we could put in a more reasonable learning rate right here than the 10 that I currently have. I'm going to try putting in a learning rate of 0.1, and then we might see a kind of nicer, more sensible chart. All right, I'm going to save the file one more time and node index.js one more time. And I can again open up that plot.png file. All right, so now this looks a little bit more reasonable. We can actually use this plot right here to make some pretty interesting inferences about what's going on with our data. So our mean squared error, you'll notice, essentially is leveling off around whatever that is, maybe like 17 or 20, I think it was, after only 20 iterations. At present, we're letting everything go through 100 iterations, and so this is kind of a sign that we don't need to run so many iterations. We could get away with running 20, 30, or 40 and essentially get the same result as we did running up to 100 iterations. So looking at this mean squared error chart helps us understand how many times we have to go through this iteration if we do not have some other type of mechanism in here to automatically stop once we've reached some acceptable bounds or acceptable accuracy for m and b. All right, so this looks pretty good. Let's take a quick pause right here. I want to show you one other pretty interesting chart that you might find a little bit interesting in the next section. In the last section, we tried plotting out our mean squared error, and we got a nice little plot that helped us understand a little bit more about what was going on inside of our algorithm. Before we move on, I want to show you one other plot that you might find kind of interesting. And this other plot that we're going to take a look at, you've kind of technically already seen over in the Google Sheets version of gradient descent that we put together a while ago, but I still want to show you how to put this together with code in case you want to use it at some point in the future. So inside of my linear regression class, I'm going to create a new array inside the constructor, and I'm going to assign it to a variable called bHistory. So this is going to be an array that is going to record all the different values of b that we attempt to find a relationship with between our car attributes and the car's mile per gallon. So very similar to the MSE history, it's just going to record how our different guesses of b are changing over time. Then down inside of my train function, right above gradient descent, I'm going to say this.bHistory. I'm going to push into there our current guess of what the b value should be. And so to get that, I can look at my weights tensor, and I'll get the first element out of there. Remember, the very first element inside the weights tensor is our b value that we're trying to change and change and change through gradient descent. So now back inside of my index.js file, I'm going to make a little change to our plot function call right here. First off, for the MSE history that we're currently plotting along the x-axis, I'm going to instead assign it to the y value. And then I'll also introduce a new x-axis value here. It'll be regression.bHistory. Then I'll update my x label here. This is now going to be value of b. And then we're still going to leave a y label here of the mean squared error. Okay, so let's try running our node.index.js command again and seeing what this plot looks like. All right, so open up plot.png. So this is actually a pretty interesting little plot. Remember, we kind of already looked at ones very similar to this a while ago, back on that Google spreadsheet, but again, this still conveys some pretty interesting information. So what you can read in here is that our value of b first starts off at 0, so 0 up here. When b was equal to 0, we had a mean squared error right around 500. After the first iteration of gradient descent, we then updated our value of b down to maybe about negative 2.5. So when it went down to negative 2.5, we got a mean squared error of about 400. We then continued to update our value of b until eventually it appears that b converged or found a ideal solution at around maybe negative 20 or negative 30 or so. And at that point, that's where we found a mean squared error of maybe that 17 or 20 that we ended up with. So this curve right here is a curve of our mean squared error against different values of b. And it's essentially the same plot that I've been showing you over and over, this one right here. So I've got my current guess of b and my mean squared error. And so we start off with some initial guess of b, and then we try to make our way down this curve all the way to the ideal guess. Now, of course, this plot right here looks slightly different than this one. The only reason it looks a little bit different is that in this case, our value of b ends up being negative. And whenever I've been showing you this chart, I've always been assuming that the value of b would be positive. So essentially the same chart, just in this case, the b value ends up being a little bit negative. All right, so I just thought this is a interesting little plot. I just wanted to show it to you very quickly because it kind of shows you all the things we've been talking about in action. All right, before I move on, I am going to clean up that bHistory code because I don't really want to leave this stuff around for right now. So I'm going to take the bHistory.push line inside of the train method. I'm going to delete that. And then inside the constructor, I'm going to delete this.bHistory as well. And then finally, back inside the index.js file, I'm going to revert this plot to what it was before by just doing a quick little couple undos. So now I'm still going to plot my MSE history against my iteration number and mean squared error like so. Okay. Now I know that we've been working on this linear regression stuff for quite a while, but there's just a tiny little bit left stuff that I want to tell you about. So one quick pause, we'll come back to the next section and get through another couple quick topics. So I'll see you in just a minute. I'm sure at this point you're kind of tired about talking about this linear regression stuff. We've definitely spent a tremendous amount of time on it, but there's still just a couple more quick topics that we need to get through. The reason that we're spending so much time on linear regression is that it turns out all these techniques around adjusting the learning rate and thinking about plotting stuff and all the other work that we've done so far is incredibly relevant for many, many, many other algorithms as well. And so if we just learn all this stuff right away around linear regression, we can then move on to other algorithms and essentially use all the same techniques to get all the same benefit. So with that in mind, another quick topics. Let's start talking about it in this section. All right, so one thing I want to point out here is that right now, if we go over to our terminal and we run our analysis, we complete the analysis pretty darn quickly, right? That took like a second at most. And chances are that a lot of the time that was taken to run that analysis was spent on just starting up Node.js and then maybe loading up the CSV file off of our hard drive. The actual analysis portion probably took fractions of a second. However, in just a little bit, we're going to start working on some data sets that are significantly larger. Data sets where it's going to take a good number of seconds to actually run the entire analysis. And even on your own projects in the future, you might start working on some data sets where it takes many minutes or even hours to run some analysis. So in this section, we're going to start looking at some ways to improve the performance of our linear regression algorithm. Let's get to it. All right. So here's what's going on currently with our gradient descent algorithm. As you know very well at this point, we pick a starting value of b and m, and in the case of multivariate gradient descent, we also have the m1, m2, m3, and so on values. We then calculate the slope of mean squared error using all the observations inside of our feature set and our current m and b values. We then multiply those slopes by the learning rate and use them to update b and m, and then we go back to this same step and repeat the process over and over and over. Now, the important thing that I want to point out right now is that when we are calculating the slope of MSE, or mean squared error, we are using all of our observations. So every last record inside of our feature set is included in the current calculation of that slope. We're going to start to look at two slight variations on gradient descent where we no longer are going to use all of our observation. So let's talk about the first alternate version of gradient descent. Okay, so this is still going to be the same algorithm, all the same processes, there's just going to be one tiny difference. So the next version of gradient descent that we're going to look at is called batch gradient descent. With batch gradient descent, we're still going to guess a starting value of b and m, and possibly m2, m3, m4, and so on. And then during the second step right here, when we go to calculate our slope of mean squared error, we're going to instead use just a portion of all of our observations in the feature set and our current m and b values. And then we're still going to multiply the slope by the learning rate and use that to update b and m. So with batch gradient descent, rather than taking our entire observation or set of observations, like all the different rows from that CSV file, let's open it up really quickly. Here it is right here. Rather than taking all the data inside of here and feeding this all into our algorithm in one big gigantic chunk, we're going to instead get little batches or little portions of our observation set. So I might just take like these first 10 or so rows right here and run my gradient descent for one iteration using just this set of data. So using just this set of data, I'm then going to update the values of m and b and m2, m3, and 4 if I'm doing multivariate analysis. I'll then move on to the next portion, so the next 10 records. Run that, update m and b, and then the next 10, next 10, next 10, and so on. And so we refer to this as batch gradient descent because we are taking batches of our observation set and then running gradient descent with that. Now, in theory, we're going to get some convergence on our optimal values of m and b slightly faster than with normal gradient descent because we are updating m and b more frequently. Let's take a look at one other variation on gradient descent that's going to be very similar to batch as well. Okay, so we refer to this as stochastic gradient descent, and you'll very frequently see this referred to or abbreviated as simply SGD, like so. So again, very similar to batch gradient descent, we're still guessing a starting value for b and m. We are then going to calculate our slope of MSE, but then this time we're going to do this one observation at a time. So with one observation, we're going to take our values of m and b, we're going to run through that same equation that we've been taking a look at nonstop, this one right here. So we're going to run through this equation with just one single observation, and then we're going to use the output of that to update m and b. And then we'll move on to the next observation and go through gradient descent again. So if we look again back at the CSV file, I would use just this first row right here and use just this first row to calculate an update to m and b. And then I would take just this row and then just this row. So just one row at a time, moving down my feature set. And I'm going to use just these single rows at a time to update my values of m and b. So why would we do this? Well, again, at the end of the day, we end up getting some convergence on our values of m and b much faster than if we attempt to loop through our entire data set before we update m and b just one time. With batch and stochastic gradient descent, we're going to be updating m and b constantly as we are iterating through our data set. And so we might end up finding optimal values of m and b after only 1, 2, 3, or 5 iterations using stochastic gradient descent. And we might end up getting some optimal value of m and b with batch gradient descent in only 10 or 15 iterations. And so it can significantly speed up the time that it takes to train our model and get some idea of how we can relate all of our different vehicle attributes to the miles per gallon. Okay, so let me give you a quick summary here of the difference between these. So right now we are doing gradient descent, where we take our entire feature tensor, so this entire thing with all the different rows. Remember, each row inside of here represents one single observation. With batch gradient descent, we're going to take just a portion of all the observations we have and run gradient descent and then update m and b. And with stochastic gradient descent, we're going to take one observation at a time and use just that one observation to m and b. Last thing I want to make sure is really clear here, with batch and stochastic gradient descent, we're still going to iterate over the entire data set. So we're still looking at all the records. The only difference here is how often we are updating the values of m and b. Okay, so let's take a quick pause right here. When we come back to the next section, we're going to start to implement batch gradient descent inside of our linear regression class. So quick pause, and I'll see you in just a minute. In this section, we're going to start to implement batch gradient descent inside of our linear regression class. It turns out that when you implement batch gradient descent, you can actually simultaneously pretty much put together the stochastic gradient descent at the same time. When you really think about it, stochastic gradient descent is the same as batch gradient descent, just with a batch size of 1. So if we batch everything out to one observation, we end up getting the same thing as stochastic gradient descent as well. So we really just have to implement this, and we will get this as a side effect. Now, one other quick thing that I want to mention that you might be kind of curious after going through the last video, remember, this is the equation that we use to calculate our slope of mean squared error with respect to m and b. And of course, that's supposed to be like, m1 and m2 and so on if we're doing multivariate analysis. So you might be kind of curious, does all of the matrix operations that we do in here, do they get kind of thrown off when we only take a portion of our data set? Well, no, not at all, actually. It turns out that all the matrix math that you have to do in here works out completely identically, even if we only take a subset of our features. I can very quickly show you a couple of quick examples of this. So here's our first operation right here, where we take our feature set and we multiply it by our weights. So if we take only a portion of the feature set, then we are essentially dropping off a couple of rows from this thing. And that would be our little batch right there of just 2 records. So the shape would change, and it would now be a 2x4 being multiplied with a 4x1. And so the output of this would be a 2x1 matrix. But the point is that it's still a permissible operation. So now, when we produce that guesses tensor, rather than being the 6x1, it would be a simple 2x1, like so. And now when we subtract our actual values, rather than subtracting the entire actual value or the entire label set, we're going to only take a portion of our labels as well. So I'm going to drop off the last 4, and I would get just the 2 actual values, or the 2 label values for car 1 and car 2 that correspond with these first 2 observations right here. And then, of course, my differences would only be a 2x1 as well. And then finally, that gets carried on down to the transpose right here. So when we do the transpose, we're going to again take off the last couple observations and leave only the first 2. And that will be matrix multiplied by the new 2x1 differences tensor. And so it turns out that all the math ends up being totally fine. It all works out with no additional changes. So all we really have to do here is make sure that we pare down our feature set, or the number of observations inside of it, and we're basically going to get the right result. So let me tell you how we're going to do this refactor to our class. Right now, inside of our linear regression class, we have our train method, which calls gradient descent. When we call gradient descent, it reaches out to 2 properties on the class, and it grabs the entire feature set and our entire label set. So all we really have to do to convert everything over to batch gradient descent is to make sure that the train method is the one who is going to access the features and labels instead. So we're going to make the train method responsible for looking at our features and labels. It's then going to carve both those up into tiny little batches, and then call the gradient descent function and pass those batches in as arguments. So moving forward, the gradient descent function is going to receive its features and labels as arguments, as opposed to just directly accessing them as properties on the class. All right, so with all this in mind, let's flip back over to our code editor. I'm inside of my linear regression class again, and I'm going to scroll on down to my gradient descent function. So all we have to do here is find wherever we are referring to this.labels or this.features, and we're going to replace it with a reference to features and labels that are being passed in as arguments to the method. So on gradient descent, I'm going to add in an argument of features and an argument of labels. And now I'm going to find every instance of this.features inside this file. So I think we got 3 in here, 1, 2, and 3. And all I have to do here is remove the this. So it goes to features. Right here on slopes, it's going to go to features. And finally, down here on the div, it's going to go to features. That's it. And now we can do the same thing with labels as well. I think there's only one reference to labels inside this function. I think it's right here on the differences line. And so I can change that to simply be labels like so. And that's pretty much it. So we've now refactored gradient descent so that it receives features and labels as arguments. So now the next thing we can do is go down to the train method, and we can make sure that this thing looks at the real this.features and this.labels and make sure that it attempts to carve them out into little batches and then pass them as arguments into gradient descent. So let's take a quick pause right here, come back to the next section, and we'll start working on that next step. In the last section, we put together an update for our gradient descent function. So now it's going to expect to be passed its features and labels as arguments. The next thing we have to do is update our train function down here, so that anytime that it calls gradient descent, it's going to pass in just a small batch of all the data inside of our total features and labels tensors. Now, before we start putting that thing together, I want to give you a quick overview on exactly how we're going to be changing this train method. All right, so quick diagram right here. On the very center, this is a tensor of our features matrix. So inside the features matrix, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations total. So each row here is one observation or one single record. The first thing that we have to do is specify how many records we want to be in each single batch. So we might say, I'm going to say, like kind of arbitrarily, I'm going to say I want batch sizes of 3 observations. So that would mean that I would take the first 3 right here, split it off. Then I would take the second 3 right here, split it off, and then I'm left with the bottom 3 down here as well. And so I'm going to put just a little bit of space in here like so. So our batch size is of 3. The next thing I want to point out here is that for the purposes of our train method, it might be kind of useful if we know the total number of batches that we have. So we know that we have 9 observations, and we know that we have 3 batch sizes of 3. That means in total, we would have 3 total batches. So that means that for every single iteration that we go through our current for loop, every time that we go through this for loop right here, we are going to run the gradient descent function 3 times. One time with this batch right here, the next time with this batch right here, and then finally with this batch right here. Now, in order to pull all this stuff off, we're going to have to make a couple of adjustments to our gradient descent class besides just to that train function. The first thing I want to point out is that at some point in time, we're probably going to have to specify how many records go into each batch, or essentially the batch size. That's always going to be some parameter that we're going to want to provide as an option to our overall gradient descent class. There's really nothing that no logic we could put together inside of the class itself to figure out how many records should be in a batch. So we're going to require that anytime someone makes use of the linear regression class, they should pass in the batch size as an options property. So to do so, I'm going to flip back over to my index.js file. Here's the linear regression class right here, and here's my options object. So now, in addition to my learning rate and my total number of iterations, I'm going to pass in a new option here that I will call batch size. And maybe for our data set, rather than using the 3 that you just saw in that diagram, I'm going to use a batch size of like 10, like so. So that means now, out of all of our different car records inside of car CSV, I want to take the first 10 right here or so, and run gradient descent, and then the next 10, next 10, next 10, and so on. All right. So now back inside of our gradient descent.js file, the options object now contains a new option, batch size, that says how many records we want to have in each batch. So that means that down inside of the train method, we could get the total number of batches, or how many records should be in a batch, with this.options.batch size. Now to start to refactor the train method right here, the next thing I think we have to do is figure out how many total batches we have. Because at some point, we're going to have to probably write out a for loop or something like that that's going to iterate over our data set this number of times. So I want to take my total number of observations and I want to divide it by my batch size so that I know how many times total I have to run gradient descent for each iteration. So to do so, right above the for loop, I'm going to add in a new statement right here. I'm going to say batch quantity, so this is the number of batches we have, is going to be the total number of feature rows we have, or total number of observations, which is this.features.shape at 0. That's our total number of rows. And then I'm going to divide that by this.options.batch size. Oh, forgot my const on there too. So now batch quantity will be the number of times that we have to loop through our data set, or the number of times that we're going to loop through and call gradient descent for each separate iteration. Now, one quick thing that I want to point out here, we're kind of making a big assumption right now. We're assuming that however many observations we have, we're going to have an even number of total batches. So in other words, we're kind of assuming that 9 divided by 3 is always going to give us exactly 3 batches. But what happens if we have like 10? If we have 10 observations instead, what would we do? Well, 10 divided by 3 would give us something like 3.333 total batches, which is not super appropriate. So to fix that, I'm going to take this division right here, our number of observations divided by the batch size, and I'm just going to wrap it with a math.floor. So that's just going to round down and find the total number of batch quantity or batches that we need to run. And it's just going to aid if we have a number of observations that does not get divided by our batch size evenly. All right, so this looks good. We now know how many records are going to be in each batch, and we've got a number right here that says how many total batches there are. So let's take another quick pause. When we come back to the next section, we're going to start to update the for loop right here and make sure that for every iteration, we run through each of our smaller batches and call gradient descent with each one. So quick pause, and I'll see you in just a minute. In the last section, we updated our train method, and we now know the total number of batches that we're going to have to loop through when we're running our gradient descent. So the next thing we need to do is put a second for loop inside of here. The outer for loop that we have right now is going to track the total number of iterations through our total data set. But we need a second for loop inside of here that's going to tell us how often or how many little batches that we're going to run for each of these different iterations. So I'm going to put a second for loop in here. I'm going to use a new variable called j that's going to start at 0, and I'm going to run this until we get all the way up to batch quantity. And I'll increment j by 1 each time. I'm then going to take my gradient descent function call, and I'll put it into the for loop like so. Now only the gradient descent function call should really go into this inner for loop. We really only want to update our mean squared error value and update our learning rate after we have gone through an entire set of batches. So that's why we're only going to put gradient descent inside there, but leave the other two function calls out. So now inside of this for loop, we need to somehow use the variables that we have available to us, batch quantity, I, and j, to take our entire feature set and our entire label set and somehow get just a subset or just a batch of each of them into the gradient descent function. To do so, we're going to use that TensorFlow function that we spoke about way long ago called slice. Now, before writing out the code to do this right here, let's get a quick reminder on how the slice function works. So I'm going to flip back over to this little coding tool very quickly. As a reminder, here's the link to it. Don't forget JSP is capitalized. Inside of here, I'm going to create a new tensor that I'll call features. So I'll be a tf.tensor, and I'm going to give it a couple of different rows and a couple of different columns. There we go, that should be enough. So now let's say that we have a batch size equal to 3. So I want to take this entire features tensor and I want to extract just these first 3 rows right there. So to get just the first 3 rows, we could do features.slice. And then remember, the first argument to this thing is going to be an array that provides coordinates or the index of the start of the slice. So for the very first slice, it's going to be at 0, 0 right there. So I'll put in 0, 0. Then the second argument is going to be the size of the slice. This is as well going to be an array, the first element is going to be the number of rows in the slice. So in this case, I would want 3. And then the second element inside of that array is going to be how many columns we want. Remember, we can use a little shortcut here and just put in -1 to essentially say, give me all of the columns that are available. All right, so that will give me the first 3 rows. So now I want to try getting just the next 3 rows. So the next 3 rows will be features.slice. And now I'm going to again put in a starting coordinate here. So row 0, row 1, row 2, and now row 3. So the starting coordinate would be 3, 0, like so. And then again, we have to put in the second argument here, which is also going to be 3 rows, because I want only the next 3 right there. So 3, and again, -1. All right, so it looks like in both cases, I got 3 rows and the 3 columns. It's kind of hard to tell if I actually got the right values here in the second slice. So just to make sure that I'm doing the right thing here, I'm going to change the leading numbers. I'll go 0, 1, 2, 3, 4, 5, 6, like so. And so now we can see very plainly that in this first slice, 0, 1, and 2, yep, we got the right ones. And then in the next slice, yep, we got the right ones, 3, 4, 5. All right, so that's just a quick reminder on how we do slice. So now that we got that reminder, let's flip back over to our editor and finish up this train function. So now inside the inner for loop, we're going to make a couple of temporary variables right here. The first variable I'm going to create is feature slice. So this is going to be the current little batch of this.features that we're going to run gradient descent with. So I'm going to look at this.features and I'm going to slice it. So now remember, the first argument here is going to be an array that has the starting coordinate that we want to start making this slice from. Now we can't really just put in hard-coded 0 and 3 values like so, because we are iterating through this entire slice. And we need to progressively essentially jump over from 0 to 3, then to 9, and so on. So the pattern that you might notice here is that this leading coordinate actually ends up being j being this inner for loop counter right there, times our batch size. That's what it ends up being. Because when j equals 0, let's say j equals 0 and batch size equals 3, then 0 times 3 would give us 0 like so. And then when we go through the next iteration, or the next pass of the inner loop, j would be equal to 1. So then we would do 1 times 3, and that would give us the next leading coordinate, and so on and so on and so on. So for the first leading coordinate on the slice right here, we could do j times this.options.batch size. Now that's definitely kind of a long statement right there. So I'm going to just take that entire initial coordinate and I'm going to assign it to a variable right here that I'll call start index, like so. So my start index is going to be j times the batch size. And I could put simply start index in there like so. Now the second element inside of that array is always going to be 0 because I always want to start from the first column. And then remember, the second argument is going to be the size of the slice that we want to take. So the number of rows that we want to take for this slice is going to be equal to, again, our batch size. So I would put in here this.options.batch size. Now once again, that's kind of a long expression and it makes that line just a little bit long. So I'm going to make another temporary variable right here. And I'll just say batch size is going to be destructured from this.options like so. And so now I can simply put in batch size like so. And then finally, the last argument or the last element inside there is going to be the -1. All right, I'm going to save that line so that it kind of collapses like so, so we can see that entire feature slice on a single line. All right, so now we'll do the same exact thing for our labels as well, because remember, we need to pass in the matching labels to gradient descent too. So I'm going to do const labels slice. One thing that's kind of awkward here, if you want to call this label slice or label slice, you can go either way. Personally, I like to always stay consistent, so I'm going to stay with labels slice, plural. If you want to, actually, you know what? This would technically be feature slice up here, huh? All right, I'll just make it label slice. That works. So then this will be this.labels.slice. And this is also going to be my start index, 0, and batch size, -1. And then finally, last thing we have to do is take the feature slice and the label slice and pass them into gradient descent. So I'll say feature slice and label slice like so. All right, let me zoom out just so you can see that entire for loop. And that's pretty much it. So we're now ready to test this thing out and see how we're doing. Let's take a quick pause right here. When we come back in the next section, we'll try running our train function and see if we get a good solution still. So quick pause and I'll see you in just a minute. In the last section, we finished up our train method and we implemented everything we needed for batch gradient descent. Now, before we actually test this thing out inside of our terminal, I just want to put a quick note out there. Batch gradient descent is primarily about performance. It primarily means that if we have a very large data set, we can run our linear regression analysis rather quickly with far fewer iterations. And so that means that with a large data set, we can get through the analysis more quickly. At present, our cars.csv file only has about 300 or 400 or so observations. And so we're not going to really see a big jump in performance here. It's only going to be when we start working with far larger data sets that you're going to say, wow, that ran way faster than it did otherwise. Nonetheless, we can still run batch gradient descent here and make a couple of observations about the output of it. Now, before I actually run this, I want to show you one quick little plot. I made a backup of one of the plots that we had made previously, the number of iterations versus our mean squared error. So this is with our old analysis. This is with the normal gradient descent. With the normal gradient descent, we started out at a mean squared error of about 500, and then we saw that it leveled off around 20 iterations or so, maybe at around, 20 mean squared error or something like that. So keeping this plot in mind, I want to now run my analysis using a learning rate of 0.1, 100 iterations, and a batch size of 10. So I'm going to flip on over to my terminal, and I'll do a node index.js. All right, so our analysis runs. To me, it seemed like it was about the same duration. Seems like it didn't get any faster or slower to run that analysis. And it looks like we've got the same r² value. Let's go take a look at the plot that was generated. So remember, we're still plotting out our MSE history on that plot. So I'm going to open up the new one right here. So when I look at this, you'll notice that, well, it really looks pretty darn similar. We've got a little jump here, but our mean squared error is only leveling out around iteration number 20 or so. So you might look at this and be a little bit disappointed. But before you get disappointed, I want you to look really, really closely at this plot. If you look really closely at it, you might notice that the scale of mean squared error, or the range of mean squared error that we have, is way different than what we had before. Here's the old plot. This is the old one. With the old version of gradient descent, where we ran all of our observations through at one time, we had a starting mean squared error of 500. And then we only dropped down to like 100 or so after about 9 or 10 iterations. So we had to go through our entire data set 9 or 10 times just to get down to 100 on mean squared error. But now that we're doing batch gradient descent, after the first iteration, we are already down at 18.7. That's a tremendous decrease in our mean squared error. So this means that after just one iteration, we've already got some weights, or values of b and m, that are pretty darn good after just one iteration. We then do another set of iterations, we get all the way up to 20, and after those 20 iterations, we've only made a tiny improvement to our mean squared error. So what this tells us is that we could run the same analysis that we were running before, but we can run the analysis with far fewer iterations. So if we have a very large data set, we don't have to run through the entire data set multiple times to get our good values of b and m. We can just run our iteration like 1 or 2 or 3 times and get a pretty good result out of just that. In fact, let's try doing that right now. I'm going to go back over to my constructor options right here, and I'm going to adjust my iterations down to, how about just 3? Let's go to 3 iterations. And then I'm going to rerun my analysis. So with just 3 iterations, I think you can probably agree with me that it felt like that ran significantly faster than how it was before. You'll notice that our r² value is even a little bit better than what we had previously with 100 iterations. And so this definitely tells me that we can get away with much greater performance, not having to run through as many steps through our data set as before. Okay, so this looks pretty good. Now, last thing I want to mention here very quickly, remember we've been implementing batch gradient descent. The only difference between batch gradient descent and stochastic is that with stochastic gradient descent, we're only going to use a single observation at a time to update our values of m and b, or our different weights. once we implemented batch gradient descent, we can actually convert it over to stochastic very easily by simply adjusting our batch size. So rather than using a batch size of 10, I could just say a batch size of 1. And now we're going to effectively be running stochastic gradient descent by only using a single observation each time. So now we can save this, and we can rerun with node index.js. And we're going to see that we actually get a slightly lower r-squared value here, but it's still reasonable, 0.56. So in this might be a case where we would stick with batch gradient descent as opposed to stochastic. We are going to work on some projects later on in the future, or a project, where we're going to want to use, or we are going to prefer stochastic gradient descent over batch gradient descent. And at that time, we'll take a look at some of the pros and cons of both methods and get a better idea of why we might use one approach over the other. Okay, so let's take a quick pause right here. When we come back to the next section, I think that we've done a great job on this project, but just one or two last tiny little things, I promise. So quick pause, and I'll see you in just a minute. We've now spent a lot of time working on our linear regression class, and we've learned a lot of techniques that we're going to use in the future on other machine learning algorithms as well. Now, before we move on, there's one last piece of functionality that I want to put together inside the class. We currently have the ability to train the model, and we have the ability to test it, but we don't actually have the ability to make a prediction. Remember, that's the entire point of the model. We want to eventually give it some new set of characteristics about a vehicle, like its weight, its horsepower, and its displacement, and get back a number that predicts what its mile per gallon value will be. So that's the last thing I want to put together. Right above the test function, I'm going to add a new function that I will call predict. So the goal of this function right here is to take in some new set of observations and make a prediction about the characteristics or the observations contained in there. So I'm going to call this thing observations, like so. Now, observations is going to be an array of arrays, very similar to the array of arrays that we've used for our features and test features previously. So observations, let me show you really quickly what it might look like. It's going to be an array of arrays where each inner array has some characteristics of a car. And so inside there will be a horsepower value, a weight value, and a displacement value. And then I want to make sure that my predict method is going to work, so I could pass in as many car characteristics to this thing as I want. So I could do something like that right there, and I should be able to get out like 4 separate predictions for 4 different cars, given different values of horsepower, weight, and displacement. So again, that's what observations is going to look like. All right, so now that we understand what observations is going to be, how are we going to take it and actually make some usable predictions out of it? Well, we've actually gone through that process quite a bit throughout this course already. Remember taking our feature matrix, like that right there, and multiplying it by our weights? When we take the feature matrix and multiply it by the weights, the result of the matrix multiplication is the b plus x1 times m1 plus x2 times m2 plus x3 times m3. And so this cell right here, after doing matrix multiplication, represented a mile per gallon value for a car with that set of characteristics. So all we really have to do is take that observations array of arrays, turn it into a tensor, add on my column of ones, and then multiply it by the weights. And that's going to give us our guess of what the mile per gallon for B should be. All right, so back inside of predict, like I just said, we have to take observations, we need to wrap it inside of a tensor, we need to add on that column of ones, and then we also need to scale it, or standardize it, excuse me. So remember, we actually already put together a function that does all those steps for us down here inside of process features. That was the whole goal of this function. It's going to take in some argument, stuff it into the tensor, add on the column of ones, and then appropriately standardize the values inside there. So to get started inside of predict, I'm going to call this.processFeatures, and then I'll pass in observations. And then after that, to actually make our prediction, all we have to do is a matrix multiplication operation with our weights tensor. So I'm going to add on to the end mat_mul this.weights, like so. And then after going through all that, I'm going to return the result. So what we return from predict is going to be a new tensor that has our predicted mile per gallon values inside of it. So let's now try to use this predict function. I'm going to flip back over to my index.js file, and then down at the very bottom of the file, I'm going to call regression.predict. And I'm going to pass in an array of arrays that has some data on some new vehicles. And these new vehicles, I want to guess a mile per gallon value on each of them. Now, when we put together this array of arrays, the order in which we list out the horsepower, the displacement, and the weight is actually very, very critical. Remember, when we pulled our data out of that CSV file up here at load CSV, we pulled out the data in the order of horsepower, and then the weight, and then the displacement. So the features array of arrays right here has a bunch of inner arrays where it lists out the horsepower, and then the weight, and then the displacement. We need to make sure that when we try to make a prediction at some point in the future, we list out these different features in the exact same order, so that when we multiply by our weights, the weights will be multiplied by our values in the exact same order. So in other words, we need to make sure that the M1, M2, and M3 values line up perfectly with the values or the features that we're passing in. All right, so inside of here, I'm going to list out some first vehicle horsepower, then weight, then displacement. So I'll use a horsepower value of like, say, 120. I'll put in, I don't really know what the typical weight and displacement are, so I'll look at the car.csv file really quickly to get an example of that. So let's see, it looks like my displacement values are usually between 350 and 450, and then typical weight values are around like 1.8 to 2.5 or so. So we'll say that I will put in the weight and the displacement with a value of maybe 2 for the weight, and for the displacement, I'll put in like, I don't know, 380. That should work out just fine. Now, if I wanted to, I can list out other vehicles in here as well. So maybe a horsepower value of 135, 2.1 weight, come on, oh, right there, and a displacement of like, I don't know, 420. So I can list out as many vehicles inside of here as I want to. But for right now, I'll just make one single prediction. So after we call predict with this array of arrays, we then have to get back a tensor that's going to contain our guess or our estimate of the mile per gallon, and to print it out, I'll chain on a.print like so. And that's it. All right, so last thing I want to do before we run this, I'm going to look back to my linear regression. You'll notice that I changed the batch size back to 10 because we had found that the stochastic gradient descent didn't quite work as well as a batch size of 10. So I've got a learning rate of 0.1, 3 iterations, and a batch size of 10. So I'm going to save this file, and then I'll flip back over to my terminal, and I'll run my analysis with node index.js. So there's my result right there. I got a tensor, and inside of it is my estimated mile per gallon value for a vehicle with those characteristics. Horsepower of 120, weight of 2, and displacement of 380. So that's pretty much it. That's how we can make predictions about values in the future after we have trained and then tested our model. Now, one thing I want to mention there is we don't specifically actually have to test the model. We only have to test the model when we are doing the initial development and making sure that it's working the way we expect. After we successfully train the model one time, we would not necessarily have to continue doing the test step again and again. So if I wanted to, I could really drop out both those steps and just do the training and then do the prediction. But usually during development, we will always do the test so that we can look at some feedback and say, yeah, it looks like we're getting a good result here. Okay, so that's pretty much it. That's all we have to do for our linear regression class. And we've now got a class that we can use for any type of regression that you want to run, any linear regression that is, at some point in the future. So let's take a pause right here, and in the next section, we're going to come back and start working on our next project. All right, my friends, I don't know about you, but I'm a little bit tired talking about linear regression. So in this section, we're going to start to move on to our next big algorithm, which is known as logistic regression. Now I want to right away point out the similarities in names here. We've been studying linear regression. We're now moving on to logistic regression. Even though the names of these things are very similar, what they are used to calculate is very different. With linear regression, as you very well know, we are predicting continuous values. So for example, given the horsepower rating of a vehicle, we want to predict its mile per gallon value, which might be 5, 15, 25, 35, or even 35.0001. With logistic regression, which is what we're going to start right now, we are going to use this algorithm to predict discrete values. So in other words, logistic regression is used for classification type problems. In the first iteration of logistic regression that you and I are going to look at, we're going to be working on a very basic form, which is going to be used to do binary classification problems. A binary classification problem is essentially when we try to take an observation and then put it into one or of two categories. Good examples of this would be if we asked a question of the form something like, If a student studies for some number of hours, are they likely to pass or fail a test? Likewise, given an email and the number of times that it has links to other domains, is that email going to be likely spam or not spam? Given a customer and their history with our company, are they likely to accept some sales offer or decline it? And then finally, maybe given some user's age, are they likely to prefer an Apple phone or an Android phone? So the common theme here with all these questions is that we are doing a binary classification. There's either label A or label B that we can apply. One or the other, that's it, no other options. Now, one of the versions of logistic regression that we're going to look at later on, called multinomial logistic regression, is going to allow us to have the ability to apply one of many different labels. So we'll look at a version later on where we can have different labels being applied. Like, for example, we could say, does someone prefer a Apple phone, Android phone, or Windows phone, if those even exist anymore? I don't know. But for right now, we're just going to be only concerned with binary classification. So let's take a quick pause right here. We're going to come back to the next section, and we're going to start walking through exactly how logistic regression works. In the last section, we started talking about logistic regression. In this video, we're going to continue and start to walk through a practical example with this algorithm. Now, before we get started, quick disclaimer here. I want to tell you right now, logistic regression is going to be so incredibly similar to linear regression that you're not going to believe it. Like, really, you're not going to believe how similar this thing is to linear regression. So I want to tell you that right now, because as we start to go through this example, you're going to see some parallels over to the world of linear regression, and it's going to seem like it's really, really similar. And I'm going to tell you right now, it looks similar because it is similar. All right, so don't overthink this stuff as we're going through it. All right, so to help you understand what's going on here, I'm going to lay out a problem that you and I are going to try to solve. So we want to be given a person's age, and given just a person's age, we want to somehow guess or predict whether they like to read books or watch movies. Okay, that's the problem. And when we look at this problem statement, you might notice some distinct, interesting things inside of here, or useful tidbits of information. The first useful piece of information is the fact that we have only one feature. There's only one feature, that's it, a person's age. Secondly, there's only two possible label values that we could apply to a single person. A person either likes to read books or they like to watch movies. And so that means that this is a binary classification problem. Now, before we move on from this problem statement, I want to kind of rephrase it in a way to make our goal a little bit more obvious or a little bit more clear. So the real goal here, what we're really trying to do with this question, is find a mathematical relationship, in reality, a formula that's going to relate a person's age to whether they like to read books or watch movies. Remember, that was the entire goal of what we were really doing back on linear regression. We had said that given a vehicle's engine displacement, a vehicle's weight, and a engine's, what was the other one? Horsepower, we wanted to predict or find a relationship with the mile per gallon value of that car. So we're going to do the same exact thing here. We want to find some type of equation that's going to relate a person's age to their preference of either books or movies. So we want to eventually find an equation that looks like that. Now, when I say like that, I mean our equation might end up looking very different, right? There might be like divided by some crazy value in here and then like square that by some other crazy value. It might look very different, but at the end of the day, I'm just trying to communicate that we want to find an equation that's going to relate our age to the preference of a person. Okay, so with that in mind, let's get started on this example. The first thing we would need to solve a problem like this would be a data set. Just like with linear regression, we have to start with some data set. So let's imagine that maybe you and I walk out along the street and we find people of different ages and we ask them if they like movies or if they like books. Which do they prefer more? And so maybe we put together a data set that looks like this right here. So this is our sample data set. It is a training set that we're going to use to try to find a relationship between our age and our preferred activity. Now, I'm not going to try to make any, I just as a quick aside here, I know that there are many young children out there who prefer to read books. I'm not saying that all young children like to watch movies over reading books. I know that plenty of young kids like to read books, but for the sake of discussion, let's just say that young people like to watch movies and older people like to read books. So that's what our data set is going to look like. So our goal here is to say, or to use this data set to find a relationship between these ages and the preferred activity. Now, the first thing I notice here, looking at this data set, is that when we try to find some type of mathematical model like this, looking at this equation right here, I say that we're going to find something or some equation like that. Preference definitely needs to be a number, right? This needs to be a number. But if you look at this data set, the preferred activities are string values. And so these string values, or these label values as they stand right now, are not at all useful to us in the least. There's no way that I could multiply a number by the string watch movies and get something meaningful out of it. Likewise, there's no way that I could somehow multiply an age by some constant or add on a constant and somehow get a string out of that. It's just not possible. So the first thing we need to do with this data set right here is take this column of preferred activity volumes or values and turn them into actual numbers. So we could use those numbers to somehow relate them back to our ages. So in order to turn this column into numbers, I'm going to encode it. Now, when I say encode, I'm essentially going to look at all the unique values inside this column, and I'm going to replace them with either a 0 or a 1. And so anywhere where I see the value watch movies, I'm going to replace it with a 0. And anywhere where I see a value of read books, I'm going to replace it with a 1. Now, there's no meaning to the order in which I assigned 0s and 1s here. I could have just as easily assigned values of 1 to watch movies and 0 to read books. So I could have very easily done this as well, and I would still be able to find a relationship between my age and my preferred activities. I just decided randomly to assign 0s to watch movies and 1s to read books. The next thing I want to mention is that we are always going to encode these activity or these label values or these classifications with values of either 0 or 1. So whereas I could swap the values of 0 or 1, I cannot do something like, oh yeah, these are going to get 10 and these are going to get 500. It's going to always be either 0s or 1s. Okay, so we now have a data set where we've got our ages and our encoded preferred activities. So as a quick reminder, I want to remind you one more time here, the goal with this data set that we have right now is to somehow find an equation that's going to give us 0 for an age of 5 and somehow give us a value of 1 for an age of 25. That's all we're trying to do. Just give me an equation where I can plug in these values and get out those values. That's the goal. Now, it might seem like I'm harping on this big time, but you're going to see very shortly that keeping this fact in mind is extremely important for what's going to happen later on. All right, let's take a quick pause right here, and we're going to come back to the next section and continue on with this example. In the last section, we took our data set that relates our ages and preferred activities and encoded the activity values to be either 0 or 1. Now, as a reminder, I want to remind you for like the third or fourth time now, the entire goal here is to find an equation where we could plug in 5 and get out 0, and plug in 35 and get out 1, because we want to use that equation to predict the activity preference for some person with a new value age. Now, one way that we've been doing this in the past is to just use linear regression. Remember, with linear regression, we've taken a feature value or set of feature values and a set of label values. We threw them into that algorithm, and we got out some equation that related the two together. So I took this exact data set right here, and I threw it into our linear regression algorithm. When I did so, I got back an equation that looks like that right there. So our linear regression algorithm, with exactly the data set that you're seeing right now, gave me a m value of 0.029 and a b value of negative 0.15. And so if I plotted all this stuff together, I would get a chart that looks like this. My age is running along the horizontal axes, so I've got ages of 5, 15, 25, 35, and 45, and along the vertical axes are watch movies at 0 and read books at 1.0. Now you can kind of imagine that this might be a trend line right here that follows this equation. Now, something that we might do here to validate the accuracy of this equation would be to take our existing data set, so like the values of 5, 15, 25, 35, and 45, and plug them into that equation, and then look at what preferred value we get out of it. And so we can essentially just reuse the same data set, throw it into that equation, and see what our guessed or our predicted values for preferences are. So what would that look like? Check out the new table here on the right. So I've got all of our different ages, I've got the actual preference values, and then for each of those ages, I took them, threw them into that equation, and got these predicted activity preference values. So you'll notice that someone who is 5 years old was predicted to have an activity preference value of negative 0.0011. Someone who is 45 was predicted to have a preference value of 1.19. I also threw on a new prediction point on here, so that was not in our original data set. But if I threw in someone with an age of 55, they would have a actual preference, in theory, I'm just guessing here, they would have a actual preference of 1. That's why I've got the question mark next to it. But the predicted preference was 1.48. So you'll notice that in some cases, we've got predicted preference values that are negative. In some cases, we have values that are greater than 1. And then in some other locations, we've got values that are between 0 and 1. Now, I want you to just take it on faith for just a moment here. Getting a predicted value or a predicted preference value here that is outside of the range of 0 and 1 is not a good result. It is a result that has no meaning to us. Predicted preference values that are between 0 and 1, like these 3 right here, are okay. There is meaning associated with those values, and I'll tell you what the meaning is in just a little bit. But for right now, I just want you to stick with me and just take it on faith that getting these results right here is good, and we're happy with those, but getting these numbers that are outside of the range of 0 and 1 are not good, and we don't want those numbers at all. So if we put that on the chart, we're essentially saying that for whatever equation we come up with, we want to only ever see values that are between 0 and 1, and we don't want to get anything that's above 1 or below 0. Now the problem with this assumption right here, again, just taking on faith for a moment, the problem with this is that if we try to use an equation of mx plus b, we will never be able to satisfy this requirement. The m term in our mx plus b equation, if it's ever non-zero, that means that our trend line is going to inevitably cross over the bounds of both 1 and 0. So anytime that we use an equation in the form mx plus b, inevitably, for some sufficiently large range or large value of x, we're going to eventually cross over to go above 1 or below 0. So what I'm trying to say here is that this equation kind of somewhat gives us some meaningful relationship between our age and our predicted preferences. But the general form of the equation is not going to allow us to ever get a good solution. So the equation of the form, or equation that looks like mx plus b, is just not going to cut it here. It's not going to give us a good fit for relating our age to our activity value. So as a solution, we need to start to essentially shop around a little bit. We need to find some other equation that is going to somehow give us a relationship between our age and our predicted preference that is not of the form mx plus b. So as a quick reminder, when I told you a little bit ago that we want some equation that looks like this, I really meant we want something that looks like this but is not this. So maybe we want something like, I don't know, maybe we want something that is of the form like 1 over mx plus b. Maybe we want something like that. Or maybe we want something like the square root of mx plus b. I don't know. Essentially, the idea here is that the equation in the form mx plus b is not going to cut it, and we need to find some other type of equation that's going to relate our age to our preference value. So let's take a quick pause right here. When we come back to the next section, we'll take a look at exactly what the form of our desired equation is going to be. In the last section, we tried to use linear regression to get an equation that would relate our age to our activity preference. However, we very quickly saw that the equation that we got of the form mx plus b would give us predicted values outside of the range of 0 to 1. And remember, for right now, we're just kind of working on blind faith that getting values outside of the range of 0 to 1 is not appropriate for what we're trying to do here. And again, I'll tell you why in just a little bit. So rather than trying to use the equation of the form mx plus b, we're just going to change the form of the equation that we're going to try to find to relate our age and activity preference together. So I'm going to show you exactly what that equation is going to look like. Okay, so this is it right here. Rather than trying to solve simply mx plus b and guess at different values of m and b, we're going to guess at different values of m and b and plug in different x values to this equation instead. Now, I know this equation right here looks really nasty, but I can't tell you enough. We're doing the same exact stuff we were doing before with linear regression. We're still going to use gradient descent. We're still going to guess at different values of m and b. We're still going to calculate some slope and then adjust the values of m and b using that slope. We're then going to plug them back into this equation and use this equation to get a guess at what an appropriate label value is. Now, this equation, you'll notice, has the e term in here. That is a constant number that's approximately equal to 2.718. So you can kind of imagine that this equation condenses down to something that looks like that, like so. All right. Now, the general form of this equation is what we call the sigmoid equation. So this is what we refer to as the sigmoid right here by itself. You'll see a lot of documentation and a lot of blog posts that refer to the sigmoid equation. Anytime you see that term, you want to think of exactly this equation right here. The sigmoid equation is special because for any value of this z exponent right here that you plug in, we're always going to get an output between 0 and 1. And so that makes it very well suited for the type of calculation or relation that we're trying to make here. Remember, we are saying that only values between 0 and 1 give us some meaningful output. So essentially, if we just plug in some value for z right here, no matter what, we're always going to get out some value that ranges from 0 to positive 1. Now, I'm sure looking at this equation, you're still a little bit doubtful, and you might be thinking, wait a minute, what are we doing with this thing? Well, let me give you a very practical example. I took this equation and I ran a logistic regression analysis with it very quickly using this data set that we've been working with. And I found that I got optimal values of m and b of 0.57 and negative 11.1. So we would take that m and b values calculated using the almost same series of steps that we went through with linear regression, and then we would plug in our different values of ages to it. And then it would spit out a value that would represent our activity preference. And so using our real data set to solve all this stuff, I got this equation right here. I could plug in a value of, say, 5 for age, and as an output, I got 0.00002. Which is very close to 0, which would indicate that someone with the age of 5 wants to watch movies. If I then plugged in an age of 15 to this equation, I got an output of 0.07. Again, very close to 0, which indicates that someone who is 15 wants to watch movies. And then, of course, as I started to go up to age to 25, 35, 45, I got values that were very close to 10, which means that those people probably want to read books as opposed to watch movies. I've said it many times throughout the last 3 videos or so, but the entire goal of all this logistic regression stuff is still just to get an equation that is going to relate some independent variable to our dependent variable. And the only difference this time around is that the dependent variable is going to range in values from 0 to 1, and we only ever want to predict values between 0 and 1. So I can't say it enough, everything we're doing here is the same as linear regression. The only difference is that the equation that we're using is changing its form a little bit. Okay, so you're probably still curious about why we only want values between 0 and 1. And you're also probably curious about what these values of like 0.0002 really mean and why we do not see values of like exactly 0. So let's take one more quick pause. We'll come back to the next section, and I'll tell you a little bit about why we really care about values between 0 and 1 for our activity preference. So I'll see you in just a minute. In the last section, we started talking about the sigmoid equation, and we spoke about how it gives us a higher quality fit for relating features and labels in a binary classification problem than a plain basic mx plus b equation. Now, in this video in particular, I want to tell you a little bit more about why we only care about values coming out of that equation that range between 0 and 1. All right, so here we go. So remember, in this scatter plot right here, I put a little trend line on here. This trend line is meant to represent the sigmoid equation. So the closer this line gets down to 0, the more likely it is that someone likes to watch movies. As the line gets closer towards 1, the more likely it is that someone likes to read books. Now you'll notice that there's an area in here where this line crosses over from 0 to 1. I want you to notice how it's kind of a gradual shift, relatively gradual. This is not going to be a very sudden jump where everyone who is like ages 0 through 15 like watching movies, and then suddenly at age 16, everyone likes reading books. In other words, it's not a stepwise equation that looks like this, where you're 0 years old up through like 20 years old, and then all of a sudden, boom, I 100% of the time like to read books instead. No, instead, it's kind of a gradual shift over. This actually makes a lot of sense if you think about a transition in age related to activity preferences. When someone turns 20, they're not likely to go overnight from saying, oh, I want to watch only movies to I want to only read books. Instead, it's probably going to be a gradual shift as people go to age 18, 19, 20, 21, and over time kind of say, you know what, I'm starting to prefer to read books more instead. To give you some actual proof of that, I took this sigmoid equation with some actual real coefficients on it. Remember, these are calculated using these actual ages, and I plugged them into a little spreadsheet. So on the left-hand column is a different age. On the right-hand column is the predicted activity preference, or the output coming from the sigmoid equation right there. So you'll see that people start off with predicted activity preferences very close to 0, which again means that they like to watch movies. But then as we start to get towards 18, 19, 20, 21 years old, people start to go to 0.31, 0.44, 0.58, and 0.71, which means, again, a gradual shift over to wanting to read books instead. Now, you might be curious, what do values in here that are not close to 0 or 1 really mean for us? Well, to tell you what these values that are kind of very much in between 0 and 1 are, I want to give you kind of an alternate definition of what the output of the sigmoid equation is right here. So at this point, I've been saying, oh yeah, the output to sigmoid equation is the activity preference. But rather than that, I want to tell you what it means instead. Okay, so here's the definition that we're going to be really working with. The output of the sigmoid equation is actually the probability of someone with some given age as belonging to, this kind of awkward way of putting it, but belonging to or needing to be assigned to whatever the one label or the one classification is. Now, there's kind of a very good reason this phrase right here is a little bit awkward. Probability of being the one label. What does that mean? Well, to put it a little bit more straightforward, I would say this is the probability of someone liking books. The reason I put it kind of awkward here is that, remember, when we did that encoding step way long ago, I had told you that what we encode these values as either 0 or 1, is kind of an arbitrary decision. We could have very well just as easily said that all of our watch movie people got a value of 1, and the read books people got a value of 0. If we had flipped the encoding here, then the higher values coming out of that sigmoid equation would signify a higher probability of watching movies rather than reading books. So again, the order in which we do this encoding kind of has a difference on the output in that regard. Okay, so we would say that the output from the sigmoid is the probability of liking books in our case, or being assigned the one label. So if you start to think of it in those terms, this starts to make a lot of sense. So we would say that someone who is 5 years old has a probability of 0.0002 of preferring books. In other words, there's like no chance that they like books. Remember that with probabilities like this, you can multiply by 100 and get an equivalent percentage. And so we would essentially say that the case or the chance of someone who is 5 years old preferring books is 0.02%, very, very low. However, when someone gets to be 18, their probability of preferring books would now be 31%. And then by 20, probability of them preferring books is 58%. And then by the time they get to 35, 45, and 55, the probability of them preferring books goes all the way up to just about 100%. So again, the output from the sigmoid, rather than kind of viewing this as this kind of arbitrary, like random activity preference that doesn't really have a lot of meaning, we instead think of it as the probability of a given observation needing to be assigned to whatever this one label is, or one classification is. All right. So is there anything else here? Yes, one more thing. Okay. So, of course, the entire point of all this logistic regression stuff is not to get a probability. What we really care about is a classification, right? At the end of the day, we want to say, oh yeah, these people prefer books, these people prefer movies. We don't really care about these probabilities quite so much. So at the end of the day, we essentially have to draw a line in the sand. And we have to say kind of everyone with a probability less than this amount is going to be assigned to label 0, and everyone who is greater probability is going to be assigned to label 1. So we refer to that as our decision boundary. A common decision boundary to use would be 0.5. That means that everyone with a probability of belonging to the one label greater than 0.5 would be assigned the one label classification. So in our case, our one label classification is read books. So we would say that everyone with a probability of preferring books greater than 0.5 would be assigned the label of reading books. Everyone with a probability less than 0.5 would be assigned the label of watching movies instead. So we would end up with an output that looks like this right here. So 0.5 would be the division point. Now, in many cases, using a decision boundary of 0.5 makes a tremendous amount of sense, especially in the case of something as benign as liking books or liking movies. Of course, if your probability of liking movies is 60%, I would say that, hey, you're probably someone who prefers movies over books. But in some other problems that you might work on, using a very different decision boundary, one maybe even as high as like 0.99, something like up here, might make a lot of sense. An example of where we might want to have a very high decision boundary is if you're doing some type of safety analysis. So with the safety analysis, if you're saying like how often does something break, like break or not break, or cause a threat to human life versus not cause a threat to human life, you probably want to make sure that you are not causing threat to human life 99.9% of the time. And so you might assign a very high decision boundary as opposed to one simply at 0.5 in that case. Okay. So in this section, we spoke about what the output from the sigmoid function really means. Remember, it is the probability of being the one label. And we also spoke about decision boundaries. So we're going to take one more break. We're going to come back to the next video, and I'm going to give you a quick wrap up to tell you the overall flow of what we're doing with this logistic regression stuff. So quick pause, and I'll see you in just a minute. In this section, I'm going to give you a quick overview of what's different between linear regression and logistic regression for the purposes of actually implementing this stuff. So as a quick reminder, with linear regression gradient descent, we guessed a starting value of b and m, and m2, m3 if we had multiple features. We then calculated the slope using mean squared error, using all of our observations and our current m and b values. We then multiplied the slope by the learning rate and used that to update b and m. So here's what's going on with logistic regression. Basically the same thing. The only big extra step on here is that we now have to also encode our label values as either 0 or 1. So we're then going to guess a starting value of b and m. We're then going to calculate a slope, plugging b and m into the sigmoid equation as opposed to the simple mx plus b. We'll then multiply the slope by the learning rate and then update b and m. So at the end of the day, all the math here still just about identical. And there's going to be one or two little things that we change along the way, but I'm going to give you some very good reason for why we are changing those little things. So let's take a quick pause right here. When we come back to the next section, we're going to start working on our next project using logistic regression. All right, in this section, we're going to start talking about the problem that we're going to try to solve using logistic regression. So we're going to be using the same cars data set that we had used previously with linear regression, but we're going to be solving for a very different problem. So I want to say, given a vehicle's weight, its horsepower, and engine displacement, is that vehicle going to pass or not pass a smog emissions check? Now, just in case you're not aware, a smog emissions check is common in many countries. It's a test that is done to make sure that a vehicle is not putting out too much air pollution while it's in normal operation. And so I would wager that if a vehicle has too much horsepower or too much engine displacement, maybe it's going to be a dirtier vehicle, and so it might fail a smog emissions check. Now, in reality, that's not always true, but for the purposes of our analysis, we're just going to assume that's the case. Now, in order to actually put this project together, I want you to take a look at this question very closely. Notice how we have three features here, three distinct features: weight, horsepower, and engine displacement. But we've only been talking about logistic regression with relation to one single feature at a time. So this will be a slightly more complicated problem, but definitely not by much. The other thing I want you to notice here is that we have two possible label values. So it's definitely a binary classification problem. A given car can either pass or not pass a smog emissions check. It's a either or label that's going to be applied. Okay, so that's the problem. Now, the next thing I want to tell you about is how we're going to be setting this project up. So our current project structure, as we finished it with linear regression, looks like this over here. We've got our index.js file, which is essentially using the linear regression.js file. And then we've also got that cars.csv file. Now, I want to reuse the same folder for this new logistic regression stuff because we're going to end up referring back to the linear regression.js file quite a bit because we're going to be pulling over so much very similar code. So in order to make sure that we still have some separation of files here, we're going to reorganize our project structure just a little bit. So we are going to make a new linear regression folder, and we're going to take our current index.js file and linear regression.js file and put them in there. We're then going to make a logistic regression folder, and we're going to put our new index.js and logistic regression.js files inside there. So that's where you and I are going to be writing a bunch of code in the videos to come. And then finally, just to get a little bit more structure to our project, we're going to make a new folder called data, and we'll put our cars.csv file inside of there. We'll just need to make sure that we update a couple file references inside of the linear regression stuff so that those files still work properly. Okay, so that's the idea. Again, we're doing this because we're going to end up referring back to a lot of this linear regression stuff, and it kind of makes sense to just kind of put all this stuff together in the same project directory. Now, at this point, it's entirely possible that you did not go through the linear regression project with me, or that you didn't write out all the code for it, or that even maybe your code doesn't quite work correctly. So if that's the case, I took all of my current project files and I put them in the next section inside of a zip file for you to download. So if you want to, you can go over there right now, download that zip file and extract it. Just make sure that after you extract that stuff, you run npm install to install any dependencies. Okay, so if you don't have an up-to-date version of linear regression, go over there right now, and then come right back here because we're going to do the reorganization right now. All right, let's get to it. So back inside my code editor, I see my regressions folder here. So inside of here, I'm going to first begin by creating a new folder to house all the linear regression stuff that we did. So I'm going to make a new folder called linear regression. And inside of that folder right there, I'm going to take my current index.js and linear regression files, and I'll drag them in like so. Next up, I'm going to make a new folder called data, and I'm going to take my cars.csv file and drag it into data. And then finally, I'm going to make one more folder called logistic regression. And inside there, I'm going to make a brand new index.js file and a brand new logistic regression.js file as well. And that's pretty much it. So I know kind of dragging and dropping files around like this is a little bit of a pain sometimes, but again, just doing this because we're going to end up referring back to a lot of the same files in the sections to come. Now, last thing I want to do very quickly is repair a couple of file references. So inside of index.js, inside of the linear regression folder, you might recall that we had a reference to the load.csv file, which is no longer inside of the same directory. It's actually up one directory. So in order to account for that, I'm going to put .load.csv. Then the other thing that we have to update inside of here is when we actually call the load.csv function. We are currently providing a relative path to the cars.csv file, so we now have to put in /cars.csv/data like so. Okay, so that's it. Now after doing those little changes, I'm going to save this file, and then I still want to make sure that my linear regression stuff is working properly. So in order to do so, I can go back to my terminal, change into the linear regression folder, and then run node index.js. And I should still see that linear regression stuff working appropriately. All right, so that looks good. Let's take a quick pause here. When we come back to the next section, we'll start working on our logistic regression. In this section, we're going to start working on our logistic regression solution. Inside of my code editor, I see my logistic regression folder, and I'm going to open up the index.js file. We're not going to work on the algorithm just yet. The first thing I want to do here is attempt to load up our cars.csv file and make sure that we can pull the relevant columns of data out of it. Remember, the only columns that we want here are going to be the weight, the horsepower, the engine displacement on the feature side of things. For the label side, we want to see whether or not out of the pristine data set, or essentially our training data set, whether or not a given vehicle is going to pass or not pass the smog emissions. If you open up that cars.csv file, you'll notice that the first column inside there is called past emissions. And so that's the column that tells us whether or not each of these vehicles passed the emissions test. All right, so inside my logistic regression folder, I'll open up the index.js file. We'll first begin by requiring in a couple of different libraries. So I will require in @TensorFlow tf.js node. And then I'm also going to get the TF library itself, which is @TensorFlow tf.js. Next up, I'm going to import the load.csv file. So I'll do a const load.csv is require ... load.csv. Remember that it is now ... because we are going up one directory to get that file. Now remember, the load.csv file has some logic inside of it that can load up a CSV, and later on in the course, in one of the end sections, I show you how you can put together the logic inside there. But for right now, we're just going to use it and assume that's doing everything for us appropriately. And of course, at any time during the course, if you want to figure out how that file is working, you can always flip over to that end section and check out everything inside there. So when we call load.csv, we're going to get back an object with a couple of different properties in it. It has our features, our labels, our test features, and test labels. And that's going to all come from calling load.csv. And I'm going to close my sidebar so you can see that entire line. There we go. So now the first argument to this is going to be the path to the file that we want to load up, which is going to be // data_cars.csv, like so. And then as a second argument, so I'll put a comma in there and then expand it with an object. I'll zoom out so you can see the entire line now. There we go. I'm going to put in a bunch of different options. So the first option we want to specify is the data columns to load up from the CSV. So as we were just saying, from the CSV file, the columns that we care about inside of here is going to be the weight, the displacement, and the horsepower of the vehicle. So I'm going to specify those column titles using exactly as they are displayed inside the CSV. So we got displacement, horsepower, and weight. That's what I want to specify. So I'll say horsepower, displacement, and weight. Next up, we need to specify the column to load as our label set. So for our labels, we want to get the first column out of there that is called exactly past emissions. And take a note of the spelling of emissions. There's two S's there in the middle. So we're going to say label columns is past emissions, like so. Next up, we'll put on two little utility options on here. We want to shuffle our data, so I'll say shuffle true. And we also want to split a test set of data out of this thing as well, so we can eventually verify the accuracy of our algorithm. Remember that with the split test option, we could put in either true to say just split the entire data set in half, or we could put in a number to specify the number of records that we want to have be put inside the test features set. So in our case, we'll split off, say, 50 records into the test feature set. All right, so that's looking pretty good. Now, there's one more option inside of here that we have not used before, but it's going to be very, very useful for what we're trying to do around this kind of encoding of our label column. Let's take a quick pause right here. When we come back to the next section, we'll talk about how we're going to handle encoding the different values that are inside of there. So I'll see you in just a minute. In the last section, we started to put together a little bit of code to load up data from our cars.csv file. We also specified the column to load up as our set of labels. Now, remember, as soon as we start doing logistic regression, at some point in time, we have to look at our label values and encode them all as either a 0 or a 1, because usually the label values are going to be something that don't have a lot of meaning to us, or at least from a numerical standpoint. So in the case of our ages with preferred activity, we looked at the different watch movies and read books, and we set them to all to be either 0 or 1. Now, in our case, back inside the cars.csv file, we're working with that past emissions column. And you'll notice that the values inside there are all either false or true. These true or false values, very much like prefer books or read books or watch movies, don't have any intrinsic numerical meaning to us. So we need to take these false and true values and encode them as either 0 or 1. In order to do so, the load CSV function right here takes an additional little option inside of this options object that's going to make doing this conversion or this encoding very, very easy for us. All right. As a quick reminder here, the load CSV function, you'll see how to put together later on. You can always skip to the end at any point to see exactly how it works. All right. So an additional option we're going to put in here is converters. That's going to be an object. The keys of this object are going to match up against one of the columns inside of the CSV file. So in our case, we want to run a converter, or essentially do a conversion over the values inside of this past emissions column. And so as a key inside of here, I'm going to put the word exactly past emissions, like so, because that is the exact name of the column that we want to run some conversion on. Now the value for this thing is going to be a function that is going to be invoked for every row inside of here that we are pulling out. The only argument to that function is going to be the exact term or the exact value of past emissions at that particular row. So in other words, either a string that says true or false. It's then up to us to return a value from this function right here that's going to replace that true or false. So I'm going to receive the true or false as an argument that I'll call value. And then we're going to say if value is equal to the string true, then we want to return 1, otherwise 0. And I'll make sure that I get a return keyword in front of that. So again, every row inside that column is going to be passed into this function. We're going to look at the value. If it's equal to true, that's great, return 1, otherwise 0. Now one thing to note here, when that value comes into this function, it has not been parsed as a JavaScript value. So true right here is this string true. It is not the JavaScript value true. That's not what it is. So we have to write out specifically the string true in all capitals like so. Okay, so now when we get our labels and our test labels, we should see that they've already been encoded as either values of 0, 1, depending upon their past emissions value. Just to make sure that everything is working as we would expect, I'm going to go down to the bottom of the file, and I'm going to add on a console.log for my labels. And we'll take a look at that and make sure that everything showed up correctly. All right, so to run this, I'll flip back over to my terminal. I'm going to make sure that I change into my logistic regression directory. Don't forget to change into there. Inside of here, I should see the logistic regression.js file and the index.js file. And I'll run that thing with node index.js like so. And so now I can see that I've got values of 0 and 1 for all of those emission values. Perfect. Now, one thing to remember, the values or the order of the values that you see in here, don't forget, they're not going to match up with the order of trues and falses that you see over here inside the actual CSV, because we had specified that we wanted to shuffle all that data before it got imported for us. So the order of ones and zeros, not going to match up with what you see in the cars.csv. Okay, so this looks great. We've now got our features, labels, test features, and test labels. So let's take another quick pause. When we come back to the next section, we'll start working on our logistic regression class. In this section, we're going to start working on our actual logistic regression class. So I'm inside of the logistic regression folder, inside the logistic regression.js file. Now we could write out a ton of code here from scratch, but I'll be honest with you, the vast majority of code that we're going to put into this file is going to be absolutely identical to what we already did inside of our linear regression class. So in order to save a tremendous amount of time, we're going to take the contents of our linear regression.js file, we're going to copy everything out of here and put it into the logistic regression.js file. And then inside of here, I'm going to immediately rename the class to be logistic regression instead. And I'll make sure that I update the export statement down at the very bottom as well. Okay, so believe it or not, we only have to change a few lines of code inside this file in order to make it work with logistic regression. I want to explain why we have to do so few changes to our code here by doing a quick review of exactly how linear regression worked, like the actual calculation steps, and then show you what the calculation steps for logistic regression are. I think you're going to be kind of surprised at how similar these two methods are. Okay, so first off, quick review on what we did with linear regression. Remember, the goal was to find some equation that related our feature to our label, so we wanted to find an equation in the form mx plus b. In order to do so, we used gradient descent. We essentially used this mean squared error metric as a metric of how badly we guessed our values of m and b. When we expanded this equation right here, the actual guess value in every single case would be the mx at I plus b. Now, in order to get our little signal to tell us how to update the values of m and b, you'll remember that we kind of imagined charting all of our possible values of b against our MSE value. And so we had said that if we did a guess at b of 1, we could find the slope at exactly that point, and that slope would give us that negative sign or positive sign that would tell us how to update our value of b. So we didn't really care so much about the value of MSE so much as we did about that slope. And so what we did was we took this original equation, and we spoke about taking the derivative of it, which would give us the slope at any point along this line. We found that the slope equations, or the derivatives with respect to b and with respect to m, looked like these right here. And then through a lot of trial and error and a lot of repetition, we learned that we could take these two separate equations and condense them down to this one single equation, where every term inside of here, except for n, was a matrix. So we essentially did both those equations worth of math at the same time using matrix multiplication and other basic matrix operations. Now, the important thing to keep in mind here was that this features times weights term right here was essentially us calculating our value of mx plus b, or essentially our guess of what the current value should be. Okay, so that's just a quick review on exactly what we did for linear regression. So now we're going to talk about how this changes for logistic regression. And again, I think you're going to be really surprised at how identical and similar it all ends up. Okay, so first thing I'm going to show you here is going to look a little bit nasty, but don't worry about it because it's really not as bad as it looks. Okay, so when we start doing logistic regression, all of those same steps hold true. We're still going to use an equation that's going to be our metric of how badly we guessed our values of m and b. The only difference is that this time around, rather than using that mean squared error equation, we're going to use this other equation called cross entropy instead. Now, I know this thing looks kind of nasty, but remember, this is an equation that is just telling us how badly we guessed at values of m and b. Now, I don't want to think about the equation too much because honestly, we're barely going to have to touch this at all, and you'll see why. Now, the first thing I want to do here with this equation, I just want to make one tiny change to it. You see, we have these guess values in here. Just to be clear, these guess values are not the mx plus b alone. It's going to be the actual sigmoid with mx plus b. And so if I expanded those two guess terms, they would end up looking like that right there, which is even worse than it was before. I know. Okay, so remember, just like before, we had the mean squared error equation. That was the metric of how badly we guessed. So we didn't care about this equation, we cared about its derivative with respect to m and b. And so we just reminded you, we just spoke about it, we eventually condensed that mean squared error equation down to what you see right here. So it turns out, through sheer luck, through sheer chance, that the derivative of this equation right here with respect to m and b, when we put it into that vectorized matrix form, ends up being identical. It ends up being totally identical. And I put on this diagram right here, it's not supposed to be MSC, but cross entropy, that's better. So it just happens by chance that the derivative of that cross entropy function with respect to m and b, when we throw it into this kind of matrix form like so, or vectorized form, ends up looking identical to what we had before with mean squared error. Again, just total chance, it ends up looking identical. The only change here, you'll notice, is that when we calculate previously just the features times the weights, we're now going to do features times the weights, and all the values that come out of that operation are going to be ran through that sigmoid equation. So let me give you a very quick example of how that's going to work. So here's some imaginary features, here's some imaginary weights, and so we're still going to do our features times the weights, and that's now going to give us still those values of mx plus b, but then for every row inside of here, we're going to apply the sigmoid equation. And remember, the sigmoid equation is 1 over 1 plus e to the negative whatever the mx plus b value is. So again, it's like total chance, but it ends up that all the math that we're doing here, as I said several times throughout this section, ends up being completely identical. The only thing we have to do, the only big change we have to make to all these equations and all the math that we have inside of the logistic regression class, is make sure that after we multiply our features times the weights, we apply the sigmoid function. And so that essentially means that inside of the gradient descent function right here, when we multiply features times the weights, we then have to apply the sigmoid function. And then also down inside of our predict statement right here, after we multiply our features times the weights, we then have to apply the sigmoid there as well. Okay, so that's kind of the big reveal. As I've said several times throughout this section, it all ends up being just about identical, again, by sole chance. So let's take a quick pause right here. When we come back to the next section, we're going to start talking about how we can very easily make sure that we apply that sigmoid function to all these mx plus b terms after multiplying our features by our weights. So quick pause, and I'll see you in just a minute. In the last section, we spoke about how all we really have to do in order to update our linear regression to logistic regression is still do that features times weights, but then we're going to take the sigmoid of every single result inside there. So in this section, I want to give you a very quick demo on how we can very easily implement the sigmoid function with TensorFlow. So I'm going to flip back over to that little code editor. Remember, URL is right here if you want to follow along. And then inside of here, I'm going to create a weights tensor and a features tensor. We'll then multiply them by each other and then figure out how we can very easily take the sigmoid on every value inside that result. So I'm going to first begin by creating a weights tensor. And I'm going to assume that I've just got one feature here. So rather than saying that we're working with our horsepower, weight, and our vehicle weight and our displacement, we'll just say that we're like working with just horsepower alone. So this is only going to have two weights to it because we only have those, or that one feature and the B term. I'll then create some imaginary features data. I'll give it the one value, which remember represents the thing that we want to multiply our B term by, and then I'll only put in a horsepower value in here as well. So we can imagine that my horsepower value would be like 95, 120, 135, and we'll do one more, let's say like 175, like so. So now to get the mx plus b term for each of these different observations in one go, we would do the features matmul with our weights. Oops, I put malmul. There we go, matmul. So that essentially is going to do mx plus b, where our value of b is 1, and our value of m is 1 as well. So that's the result that we get. So that would be the result of just doing mx plus b by itself. And that would essentially be just this operation right here. So now we want to take the result of that operation, and for every value inside that tensor, or every mx plus b value that we just calculated, we want to take the sigmoid of the result. So with TensorFlow, like I said, this is going to be so easy to do that I kind of have to put together a couple videos to just make a big deal about this, because it's just going to be such a small change that you're going to say, wait, like, that's it? That's all that changes? What's the real difference here? So the only thing we have to add on to take the sigmoid of any of these values right here is chain on a dot sigmoid function like so. That's it. That's all we do. We just chain on dot sigmoid. So the sigmoid function is already built into TensorFlow. You can call dot sigmoid on any tensor, and TensorFlow is going to do an element-wise operation, where essentially every value inside of this tensor right here, or the tensor that comes out of features.matmul weights, is going to be thrown into the general sigmoid equation. And remember, that would be this one, where is it? Right here, the sigmoid equation. So from the matrix multiplication, we got those mx plus b values. You can imagine that we took all of those and threw them in for that z value right there. So then we calculated the sigmoid, and that's what you see as the output right here. And you'll notice that it's all ones, and that makes absolute total sense. If I remove the sigmoid, you'll see that the values that we got right here was 96, 121, 136, and 176. So if you think back to how we discussed about the structure of the sigmoid equation, we're essentially saying that our value of z right there was like the 100, the 95, 136, and so on and so on. Remember, whenever we put that z term in there, the z term is essentially along this horizontal axis. So we can imagine that we went way far to the right, way farther than this chart is showing, like way over here. And so very far to the right over here, which is where those values of like 136 and so on would be, we would go up and look at the vertical axes, and that would obviously give us a value of 1 out of that. And so from this initial sigmoid call right here, we got all ones. Well, it's because we were very far to the right on this equation, and which would always result in a 1 value. Okay, so that's how we're going to do the sigmoid on the result of features times matmul. So let's take a quick pause right here. When we come back to the next section, we're going to find every location inside of our class right now where we are doing our calculation of that mx plus b term, and we're going to chain on the dot sigmoid call. So quick pause, and I'll see you in just a minute. In this section, we're going to update our logistic regression class to do actual logistic regression rather than the current linear regression that it's doing right now. Now, in order to calculate these kind of sigmoided values, all we have to do is find every location where we had been multiplying our features by our weights and chain on that dot sigmoid method. So to get started, I'm going to scroll down just a little bit to gradient descent right here. Here's where we are multiplying our features by our weights, which essentially calculates those mx plus b values. So all we have to do here is chain on a dot sigmoid method call. And that's it. Now we need to find the one other location where we do our features times our weights. That's going to be down in the predict method right here. So recall, we take our observations and pass them into processed features. That returns a tensor with our processed features inside of it. And then we multiply that by our weights. So now on the very end of this, I'm going to chain on the dot sigmoid as well. Well, that's pretty much it. That's the only two changes we really had to do here to get our class to calculate these values that follow that sigmoid equation rather than the previous very plain mx plus b values. Now we can test out this code right now very quickly. Just one thing I want to mention very quick. Remember that inside of our test function, the entire purpose of this thing was to run some test features and test labels, and then calculate that r² value, or that coefficient of determination value. So you'll recall we had that long discussion about this equation right here, where we calculated the sum of squares residual and sum of squares total. So it turns out that with logistic regression, when we're using this sigmoid equation, this r² value doesn't make any sense anymore. And so if we want to actually get some accuracy value out of our algorithm, we are going to have to do a little update to our test function. So for right now, we're going to just ignore the test function. We're going to refactor it in just a little bit to be more meaningful than it is right now. But for right now, we can still at least do a little bit of a kind of a manual test here to make sure that logistic regression is actually being done properly by our class. So in order to test out these changes to my class, I'm going to flip back over to the index.js file inside the logistic regression directory. Then inside of here, I'm going to scroll down to the bottom, and I'm going to create a new instance of logistic regression. So I'll say const regression is new logistic regression. And then I'll pass into that my features and labels. And then don't forget the third argument is going to be our options object. So this will take all the same options we had previously with our linear regression. So I'll specify a learning rate. And in this case, I'm going to guess a learning rate of 0.5. Remember, our logistic regression class has some logic inside of it that's going to adjust that learning rate over time. So the 0.5 here is just kind of a random number, no good reason for it, and I'm just going to trust that our kind of optimization around learning rate is going to kick in and give us a good learning rate. After that, I'll put in my iterations. We'll run it for 100, and then don't forget we also have to specify that batch size as well. And I'll use a batch size of 50. All right, so then after that, we'll call regression.train to do our training. And then again, we don't really have a good way right now of doing any kind of accuracy metrics, but we can use that predict function. So inside of our class, remember we've got that predict function. We could pass it an array of arrays, where the inner arrays have some data points inside them. So we can manually do a prediction here and just put in manually some data from our CSV file where we already know whether a vehicle passes or fails emissions. And so we could just print out the result and do some type of visual inspection to say, oh, it looks like these numbers are being calculated correctly, or no, they're not. So back over here, we can do regression.predict, and then I'll pass in an array of arrays where this inner array, or this row right here, will have some real data from our CSV file. So I'm going to open up the data cars.csv file, and I'll first begin by finding an instance of a vehicle in here that failed that emissions test. Because remember, that's what we're trying to learn here. So I see this first row right here has a false value. So I can take the horsepower, displacement, and the weight and manually type those values into the predict equation. And then we should see a value come out of 0, which indicates false, this car did not pass emissions, or in theory, close to 0 at least. So as a quick reminder here, it's very important that we remember the order in which we passed these columns into our algorithm, because the order has meaning. We have to make sure that anytime we make a prediction, we pass in these values in the same order. So we have to put in the horsepower, then the displacement, and then the weight. So for that first vehicle, I'm going to use the preview here just to get something that looks better. So my horsepower is 130. My displacement is 307. And my weight is 1.75. All right, and then once we get the result from predict, remember what we get back is going to actually be a tensor with the predicted value for this particular observation right here. And so I will print out that tensor with the .print statement like so. So now I'm going to flip back over to my terminal. I'm inside the logistic regression directory, and I'm going to run my index file with node index.js. So as an output, I get 2.23. So what does that mean? Well, it means that that vehicle that I entered only has a 23% chance of passing that emissions check. So 23%, I'd say that's probably a fail. And in fact, we got a false value here, which means that vehicle did not pass the emissions check. So yeah, that seems like it's kind of positive, but let's try putting in another vehicle, one where we actually definitely got an emissions pass. And so for example, if I find, what's a good one in here? Here we go, a Datsun PL510, whatever car that is. So that got a true value. So I'll try putting in this thing's horsepower, weight, and displacement, and we should see a value come out very close to 1, which means that this vehicle has a very high probability of passing the emissions check. So let's see, my horsepower is 88, my displacement is 97, and the weight is 1.065. And don't forget, we have to put those in the correct order. So I'll put in my horsepower, my displacement, and the weight was 1.065. All right, so I'll save this, and then I can go back over to my terminal again and do another node index.js. And in this case, I got a 0.94 out. So what does that mean? Remember, that is the probability of that vehicle being applied the one label. In our case, the one label, it means that this vehicle has passed the emissions check. And as we very well know from looking at the CSV file, that vehicle did in fact pass emissions. So I'd say that it preliminarily kind of looks like our algorithm is working out pretty well here. But until we get some type of really solid accuracy metric together, it's going to be kind of hard to say one way or another whether the stuff is really working the way we expect. So let's take a quick pause right here. When we come back to the next section, we're going to start discussing how we can get some realistic test function in here that will tell us over our entire data set how we are really doing with our accuracy. So quick pause, and I'll see you in just a minute. In the last section, we got some output from our class that looked pretty promising, but until we fix up this test method right here and get some concrete way of producing an accuracy metric, we won't really know if everything is working the way we expect or not. So in this section, we're going to talk about how we're going to replace this test method with something that's going to work with logistic regression. Remember, inside of here right now, we are calculating that r-squared value, and that value does not have any meaning when applied with this sigmoid function. So in order to get an actual accuracy here, let's take a look at a diagram and talk about the series of steps that we're going to go through. So remember, we have a test set of data right now. Inside of our test set, we have horsepower, displacement, and weight values. And for each of those observations, we have known labels. And so we know whether or not each of those vehicles passed or failed the emissions test. So here's what we're going to do. We're going to take just the features, and we'll pass them into the logistic regression model. The output of that step is going to be our probabilities of each of those being our one label. Remember, we've already fixed up our predict function to give us back those probabilities. So once we get those probabilities, we can then apply our decision boundary to them. Remember the purpose of the decision boundary. At the end of the day, having the probabilities is great, but we eventually have to apply a label to each of these observations. Given the probability, either a vehicle either passed or failed. And so usually a good default decision boundary would be 0.5. So anything below 0.5 would be assigned a value of 0. Anything above 0.5 would be assigned a value of 1. So everything with the 1 means that it passed the emissions test. Once we get these applied decision boundary values, or the actual kind of numeric labels applied to them, we can then take those predictions from that decision boundary step, and we will subtract the values inside of that real labels tensor. Remember, real labels is the actual values of whether or not each of these vehicles pass that emissions test. So we're going to subtract those two tensors from each other. And the result of that is going to be a difference tensor. Now the difference tensor right here actually has some interesting meaning to us. Take a look at the result of each of these subtraction operations. When we have the same value here, or the same prediction, the difference is 0. When we have 0 on both of them, the result is 0 as well. But then any time that we have a difference in our prediction, for example, if our prediction is 1, but the real label was 0, or if our prediction was 0, but the real label is 1, then we're going to see either values of 1 or -1 inside of here. So what we can do is apply the absolute value function to its differences right here. It will turn absolute value will turn all the -1s into 1s. We can then take the sum of these differences after applying absolute value, and we will essentially get back a single number that tells us how many places we made an incorrect prediction. So we can then use that single number to give us a sort of accuracy rating and say, maybe we guessed incorrectly 5 times out of 50 times, or however it might end up being. So that's how we're going to end up gauging our accuracy metric with logistic regression. Let's take a quick pause right here. When we come back to the next section, we're going to start to update our test function to implement this new flow. So I'll see you in just a minute. In this section, we're going to update our test function to make sure that we calculate an appropriate accuracy rating for this logistic regression analysis. So to get started, I'm going to find my test function, and then I'm just going to delete everything inside of here as it stands right now. So totally empty test function like so. Okay, so now inside of here, the first thing we have to do is take our test features and use them to make an actual prediction about all the values inside there, or all the observations inside there. Remember, we've already got this predict function right here that can take an array of arrays and calculate probabilities for all the observations inside there. So we can reuse that predict function inside of our test function. So I'm going to say this.predict, and I'll pass in test features. So this is going to give us back our probability. So that would be this tensor right here. It's got our probabilities inside of it. So the next thing we have to do is apply a decision boundary. Remember, we can use an arbitrary decision boundary, in this case of 0.5. So 50% probability to pass. Anything greater than that will be marked as a pass. Anything less will be marked as a fail. In order to do so, we can use the simple round function from the TensorFlow library. As you might guess, the round function is going to use that 50%. Anything above it will be rounded up to 1. Anything below will be rounded down to 0. Now, if you have a decision boundary different than 0.5, you will not be able to use the round function here, and you will have to use some other method with TensorFlow to actually round these values appropriately. Okay, so that looks good. That's going to give us our predictions, like so. So now the next thing we'll do is take our test labels, and we're going to put that thing into a TF tensor so we can subtract by it in the next step when we go to subtract our predictions from the real labels. So the test labels, I'm going to say test labels is tf.tensor test labels, like so. So now we can do predictions.sub test labels. So that's going to do this step right there. So now we're going to get, as a result, a new tensor that has values of 0, 1, or -1. And we'll see 1 and -1 at any location where there is a difference in our prediction or our test labels. Now, when we sum up all the number of ones inside there, we do not want to somehow accidentally go ahead and subtract or sum a value of -1, because if we do, any -1 will cancel out any value of 1. And so it won't be a meaningful result. So we're going to apply the absolute value function to it like so. After that, we can sum up all the ones in there, and that will give us the number of incorrect predictions that we made. So I'm going to assign that to a variable that I will call simply incorrect. Now finally, at the bottom of this function, I would like to return a single number that represents the percentage that we got correct out of all of our guesses. So the percentage we got correct. To return the number that, or the percentage that we got correct, we can take the number of predictions that we made, subtract by the number we got incorrect, and then divide again by the total number of predictions we made. So to do so, we would say predictions.shape at 0. That's going to be the number of predictions we made. We'll subtract the number we got incorrect, and then we'll divide again by the number of predictions we made. And that will again be predictions.shape at 0. And I'm going to return the entire result of that expression. All right, so I'm now going to save this file. Oh, you know what? I just realized I forgot one little step in here. You'll notice that during this step right here, we're doing some basic math. Well, as it stands right now, incorrect is actually going to be a tensor. Remember that when we call sum, the entire tensor is going to be reduced down to a single number, but that number is still wrapped inside of a tensor. So just a little step I forgot here. We need to add on a .get to get that actual number incorrect out of that tensor. So now incorrect, rather than being a tensor that contains a number, it's just going to be the number that we got incorrect by itself. And so now we can safely do some arithmetic on it during that last step down there. Okay, so now this looks good. So I'm going to save this file. And then to test this out, I'll flip back over to my index.js file. Right now we're doing the training and then a manual prediction. So we don't need that manual prediction anymore. So I'm going to delete that. And then to run our test, we'll do regression.test with test features and test labels. And then I'll do a console log on whatever comes back from that. So again, the console log that we're going to see here is going to be the percentage that we got correct out of all of our estimates. All right, so let's now save this. I'm going to flip back over to my terminal, still inside the logistic regression directory, and I'll do a node index.js as usual. And now I get back a 0.88. So that means that we were correct in our prediction 88% of the time, which is a pretty, it's a pretty darn reasonable metric. So let's take a quick pause right here. We're going to come back to the next section. We're going to see if we can't possibly improve that value at all and just talk about some other quick points around logistic regression. In this section, I want to make a couple quick changes to our logistic regression class just to make it a little bit easier to use. So to get started, I'm going to scroll on down to our test function that we just put together. So in the test function, we do our predictions right here, and then we round the result. I want you to think about how people are likely to use the class that you're putting together. For example, let's assume that this is a logistic regression class that's going to be eventually used by other engineers. When other engineers call that predict method, they're probably going to expect to get back a tensor full of actual label value predictions, not the probabilities that it currently is. So I would make the argument that rather than doing that round operation inside of the test function, we should actually be doing the rounding inside of predict, so that anytime someone calls predict, they'll get back a tensor full of the actual predicted label values. All right, so to make that change, I'm going to delete the .round inside the test function, and I'm going to move it up here to the predict method instead. Okay, so now the next thing I want to work on inside this class is also around the round function. You'll recall that in the last section when we put the round function in here, I had said that this is going to always assume that we have a hard-coded decision boundary of 0.5. So any probability less than 0.5 will be rounded down to a 0 label. Anything greater than 0.5 will be rounded up to a 1. Now, it's entirely possible that we might work on some projects where we want to kind of massage that decision boundary a little bit. Remember, I earlier gave an example of where we would want to have a very high decision boundary as maybe human life safety. If we ever have a 1% chance probability of, say, a bridge failing, maybe we would round that down to a failure. And so we don't always want to use a round of 0, or a decision boundary of 0 at all times. So in other words, I think it'd be really nice if we could pass in the decision boundary as an option to this class, and then have that decision boundary be applied rather than the hard-coded 0.5 that is implied right here. Now, the first thing we would have to do to implement that is figure out how to implement a decision boundary other than 0.5 with TensorFlow. So to give you a very quick example of how that's done, I put together a little kind of test probability tensor right here. So I've got a bunch of different probability values inside of it. So if I wanted to apply a decision boundary of, say, 0.65, that would imply that these records right here would be rounded up to a label value of 1, and everything below that would be given a label value of 0. So to use a decision boundary 0.5, I could do a prob.greater 0.65 like so. And as you can see, anything less than 0.65 will be assigned a 0, everything greater will be assigned a 1. So that's a pretty easy way to implement a decision boundary. So back inside my editor, I'm going to find that predict function. Rather than using round, I'll replace it with a greater. Now the next thing we have to think about is how we would provide the actual decision boundary to this class. Well, again, most likely it would probably come in the form of an options value when we first created the class. So inside of here, I'm going to reference this .options.decision boundary. So now when we make an instance of our logistic regression class, we have to pass in an option of decision boundary. Now up inside the constructor, I want you to recall that we decided that we would default some of the different options that could be passed to this class. And so I think that we should probably provide a sensible default for decision boundary as well, just in case someone does not actually pass it in at some point in the future. So I'm going to default decision boundary to be the value 0.5. So if you don't pass in this option, we'll just use 0.5. That's probably going to work out for the vast majority of cases. Now, in order to test out this decision boundary thing and see if we could improve our accuracy from the 88 that we currently have, or 88%, let's try changing the decision boundary for our analysis. So I'm going to go back over to the index.js file, and then in the options object, I'll update the decision boundary. And I'll try using a decision boundary of 0.6. Oop, little typo there. There we go, decision boundary. Okay, so now I'm going to save this file. I'm going to make sure I save the other file, and then I'll flip over to my terminal, and I'm going to rerun node index.js. And then when I run this, you're going to very quickly see a big error message just like this right here. So I can scroll up a little bit and read the error message. It says the D types of the first bool and second float32 input must match. So what's going on here? Well, essentially, when we use that greater function right here, I didn't really tell you really how this thing worked internally. Even though it looks like all the values inside this tensor are now zeros or ones, TensorFlow is regarding these values as Boolean values. I know that you and I can look at them and say, hey, they're zeros and ones. But again, TensorFlow now regards these as being Booleans, because the real purpose of greater right here is to return a Boolean value saying whether a given value is greater than 0.65 or less than 0.65. So this would be like false, 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 true, 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 true. So the error message that we're really seeing here is that we are trying to do some calculation between Boolean values and values that TensorFlow considers to be float 32, which is an actual type of number value. So how do we fix this? Well, where we put together that greater statement just a second ago, down inside of our predict function right here, after applying the greater function, all we have to do is tell TensorFlow to actually treat all the values inside the tensor that comes back as float 32 values, or actually as numbers, rather than the default Boolean that it treats those as. So in order to do that, all we have to do is chain on a .cast statement, and I'll pass in float 32 like so. So all cast right here does is tell TensorFlow, hey, we understand that you think the result of this is a bunch of Boolean values, but we want you to treat them as float 32 values instead, or essentially as numbers instead. So that's all we have to do to fix up that error. So I'm going to save this now, and then I'll go back over to my terminal and rerun node index.js, and now we'll see that we are back to getting an actual accuracy output here. So in this case, by massaging our decision boundary, we saw that we went from an accuracy of 0.88 down to 0.86. So by changing our decision boundary from the default 0.5 to 0.6, our accuracy actually went down. So if we wanted to, we could definitely try some different values here, like the 0.55. Okay, well, we got 0.8 again. We could try like 0.45. We got 0.86 again. So if we wanted to, we could definitely play around with that option a little bit. But in this particular case, with this particular data set, it looks like we're not going to get super meaningful results by playing around with the decision boundary too much. Okay, so this looks pretty good. Now there's just a little bit more stuff that I want to do around logistic regression. So let's take a pause right here, and we'll come back in the next section. In this section, I want to point out something really interesting about our logistic regression class. After I point out this interesting little fact, we're going to do a little refactor to kind of fix up some unintentional behavior that is introduced by this little interesting thing. Okay, so let's get to it. What is the interesting thing? Well, it's right here in the constructor. It is the MSE history array. Remember, this MSE history stands for mean squared error history, and it essentially records that metric to tell us how good or bad our guess of M and B is for every iteration through gradient descent. The MSE history array gets used quite a bit throughout our class. So you'll recall that there's a reference to it inside the train function, or at least to the record MSE function. And then down at that function towards the bottom of the file, we calculate that mean squared error, and we store it inside of MSE history. And then we make use of that array to decide how to update our learning rate. So the interesting thing here is that we are making use of mean squared error to decide how to update our learning rate. But I had told you a little bit ago that we only make use of mean squared error for linear regression, and that when we start to move over to logistic regression, the metric of how badly we are guessing is going to change to be this cross entropy function instead. So how is updating the learning rate still working, allegedly correctly, because we are getting some good solutions or good results out of our algorithm? How is all that stuff still working even though we are using the wrong equation? Now, to answer that question, the first thing I want to be very clear about is that this is only some weird thing that is affecting how we update our learning rate. Everything that we have for gradient descent right now, all this stuff right here, remember we spoke about how calculating the slope using for the cross entropy equation just by chance ends up being the same as the mean squared error slope equations. So everything we're doing around the actual gradient descent algorithm is a-okay, no issues whatsoever. This is only an issue that is affecting how we are updating our learning rate. So with that in mind, why is it still working? Well, here's why. It turns out that we still could use mean squared error as a metric to decide how to update both our learning rate, and at the end of the day, even if the derivatives between mean squared error and the cross entropy equation were different, we could still use mean squared error as our basis for gradient descent as well if we needed to. The reason that we don't use mean squared error for this logistic regression stuff is that when we use the mean squared error function with specifically the sigmoid function, the relationship between our guesses to B and mean squared error go from that nice parabola that we've seen many times back right, where is it? Oh, come on, I know, right here. So it goes from being this nice parabola, like so, to a kind of wavy function that looks like this instead. So we refer to this nice parabola right here as a convex function. When we say convex function, that means that it has one minimum value. So that we know that whenever we look at that slope value and it tells us to increase b or decrease b, we know that we are always headed towards the global minimum of that line or that equation. And that's always going to give us the optimal value of b at that point. So specifically because we are introducing this sigmoid, the shape of the relationship between the value of b and mean squared error is going to change into this kind of non-convex or wavy function. Think about what a wavy function like this would do to our gradient descent algorithm. With this wavy function, if we guessed initially a value of 1 and we got a slope of negative 999, excuse me, that would mean that we would need to increase our value of b. And so we might accidentally say increase our value of b too much and end up over here. And so at this point, we would find a slope of something like, I don't know, let's say positive 600. And remember, a positive value means we need to change b to be less than it currently is. And so essentially, using this non-convex function or this wavy function might accidentally lead us to a minimum right here that is not the truly global minimum or the most optimal value of b. The most optimal value of b would be way over here. But we've been kind of tricked into thinking that this is a value right here and that, hey, this is probably the best value of b. So that's why we do not choose to use the mean squared error metric to get kind of a history or a value of how good or bad our guess of b and m are. So in other words, we can kind of sometimes luck out using mean squared error. Sometimes we're not going to get this wavy function and fall into this local minimum right here. Sometimes we're going to luck out and still get into the global minimum. But to make sure that this works correctly 100% of the time, we use that cross entropy function instead. So that's what's going on here. We're essentially just kind of lucking out. We're getting lucky and we're not falling into some little pit right now that is not the global minimum. But to make sure that that never happens, then we would want to update this right here to use that cross entropy equation instead, which is going to guarantee that we're not going to have any of those little local minimums. When we use the cross entropy equation, we instead get a fully convex function, just as we did previously with mean squared error back on linear regression. Okay, so with all that in mind, essentially all I'm saying here is that we need to come back to record MSE, and we need to update this to use cross entropy as well, because right now everything's working, but that's just kind of by luck. So let's take a quick pause here, come back to the next section, and we're going to start to update the record MSE function. In this section, we're going to start to refactor our record MSE function to calculate our cross entropy instead. So the first thing I want to do before changing anything down here is go up to our constructor function and rename this instance variable right here. We're not calculating the MSE history anymore. We're now calculating our cross entropy history. We could abbreviate this as CE history for cross entropy. However, that's a little bit unclear. At first glance, not super clear what CE stands for. So instead, I'm going to change this instance variable to be called cost history. Why are we calling it that? Well, in a lot of blog posts, documentation, what have you, you're going to see that a lot of other people refer to this cross entropy equation and the mean squared error equation as cost functions. In this course, we've been referring them to functions that tell us how badly we are guessing the values of m and b, which is what they really truly are. But in a lot of scientific documentation, they are referred to as cost functions. Personally, I like my term for them better because it's way more clear what the purpose of the function is than the term cost, but hey, that's just how it goes. So we'll just stick with community convention and call it cost history instead. Okay, so now we're going to go back down to record MSE, and I'm going to immediately rename that to be record cost instead. Now remember, there's many functions inside of this class that made reference to MSE history and record MSE, so we're going to have to make sure that we eventually do a sweep of this class and make sure we don't have any mislabeled functions or variables inside of here. Okay, so now inside of there, we have to essentially calculate this big, long cross entropy equation. Now you might think, boy, that looks really bad. Well, don't worry, it's not going to be that bad. I want you to recall that when we first looked at the mean squared error equation, we looked at it like so, and we calculated its value using Lodash and what have you in a very kind of imperative iterative form. And so we wrote out all those terms separately. But then over a couple of steps and a couple of diagrams, I showed you how we could implement the same stuff using a vectorized approach instead. And so remember that term vectorized means taking an equation like this and essentially doing all the math inside of it using tensors or matrices to simplify all the operations that are going on. So we can actually do the same thing with the cross entropy function as well. We can rewrite this in a vectorized solution where all the math going on inside of here is going to be using matrices rather than just a whole bunch of for loops with that summation and what have you. So rather than make you watch me go through the process of turning this into a vectorized solution as we did previously, I'm just going to show you how we're going to write this thing out. Okay, so this is the same equation, but actual and guesses are now matrices rather than individual values. Remember, we refer to this as the vectorized solution. So in this case, actual is going to be a column of values, and guesses is going to be a column of values as well. I also want you to recall that the T inside of here stands for transpose. And when we do a transpose on a tensor or a matrix, that's where we take all the columns and we turn them into rows one by one. Okay, so this is all we really have to write out. Now, when I look at this equation, I want to point out right away that the term guesses shows up inside of here twice. So rather than calculate all of our guesses 2 times, I think that we should calculate it 1 time, assign it to a variable, and then reference it later on in the rest of the calculation. Okay, so to do so, back inside of record cost, I'm going to say const guesses. And remember, our guesses is just going to be our features times the weights, and then we throw the result of that into the sigmoid function. So this is going to be features matmul with our weights, and then we're going to throw the result into sigmoid, like so. Okay, so that looks good. So we've now got the guesses tensor for both terms. Now for the second part, we're going to take a look at this very closely. You'll notice that we have actual transpose times the log of guesses plus the result of all this stuff over here. And so to kind of make this calculation a little bit easier in code, we're going to break this up into 2 separate terms. Term 1 is going to be actual transpose times the log of guesses, and then term 2 is going to be all the rest of the stuff inside of here. When we calculate these 2 terms separately, we can then add them together at the end, and it's just going to make our code a little bit more clear as to what's going on. Okay, so back inside of record cost, I'm going to say const term 1. That's going to be my labels, because remember, that's what our actual values are. We're going to take the transpose of that, and then we're going to do matrix multiplication with our guesses, and we're going to take the log values of those guesses. So notice how this log operation is applied to guesses, not to anything around the labels. Okay, so that looks good. Now we still have a little bit of code to write here, so let's take a quick pause. When we come back to the next section, we're going to finish up record cost and the rest of the logic inside of this class. In this section, we're going to finish up our record cost function. We just put together term 1. We're now going to move on to term 2. Now take a look at the first part of term 2 right here. It's 1 minus actual. So that means that we would have to take a tensor of 1s and subtract actual from it. And that sounds like a pain to have to make a tensor of 1s, so we could actually kind of rewrite that term right there to be negative actual plus 1. And that's going to be a little bit easier to write out with TensorFlow than what it is right now. So let me just show you what I mean by that. Back inside of record cost, I'm going to say const term 2. That's going to be this dot labels. And then we're going to multiply everything inside there by negative 1. So that's going to give us this negative actual part right there. And then I'm going to add on to that 1, like so. So this right here is equal to that little part right there. Then after that, we're going to take the transpose of the result. So right here, I'll do a transpose. And then we're going to do a matrix multiplication. So matrix multiplication with the log of 1 minus guesses. So we're going to use the same little trick for doing 1 minus guesses here. We'll multiply guesses by negative 1 to make it negative, and then we'll add on 1. And then we'll take the log of the result, and then make sure that we do matrix multiplication with the first part of the term. Okay, so inside of the matmul, we're going to get that entire second part right here. So I'm going to take guesses, I'm going to multiply it by negative 1, I'm going to add 1, and then I'll take the log of the result. And that's it. Okay, so that looks good. Now the last thing we have to do is add the two terms together, then divide by m. Remember, that's the total number of observations we have. I think usually I refer to it as n, so I kind of messed up my terminology here. Apologies for that. And then remember, we also have to make sure that we multiply by the negative sign here as well. So let's get to it. All right, so down at the bottom here, I'm going to say term 1. We're going to sub, or excuse me, not sub, it's a addition. We're going to add term 2. We're then going to divide by the number of observations that we have inside of our feature set. So I'll divide by this .features.count, or excuse me, .shape at 0. And I'll make sure that I multiply by a -1 here as well. So that multiplication by -1, that's what takes care of the negative sign out front. Okay. Now the last thing we need to do here, the result of all this right here will be a single value. And we want to pull out just that single value by itself. So to get that single value out, we'll do a get 0, 0 like so. And remember, the reason that this ends up being a single value is because when we do some of these matrix multiplication operations, it's going to cancel out the outside dimensions, or excuse me, the inner dimensions, leaving us with just a single number. All right, so now the last thing I want to do, I'm going to assign all this stuff to a variable that I'll call simply cost. And then right here at the bottom, we'll do this .cost history .unshift, because remember, we are kind of reversing the order here. And I'll put the cost in like so. All right, so that's kind of stage 1. We've now refactored record cost to calculate our cost using cost entropy, or cross entropy. And then we push that value into cost history. So now the last thing we have to do is go to this file and update every location where we see MSE history. So now first inside of update learning rate, I see 1, 2, 3. So I'm going to change all 3 locations to cost history. So make sure you get 1, 2, and 3. And then I think the only other location is going to be up inside of our train function. So I'm going to go up to the train function. Here it is right here. Here's the train function. And then inside of those 4 loops, we have record MSE. We rename that thing to be record cost instead. All right, so now last thing I'm going to do, I'm going to do a quick search on this file for MSE and make sure I don't have any other results of that inside of here. Okay, so that's it. Let's take a quick pause right here. When we come back to the next section, we'll test out this new record cost function and make sure that everything is still working the way we expect. In the last section, we finished up our refactor of the record cost function. So now hopefully we're going to always be updating our learning rate using the correct metric. I want to remind you again that in the entire refactor we just did, we only are affecting the output of the learning rate here. Nothing that we just did affected anything around the gradient descent side of things, except for the fact that gradient descent kind of incidentally uses that learning rate. Okay, so this is looking pretty good. Now, the last thing I want to do here is just rerun our analysis, make sure everything still works. And then after that, I want to try to plot out the changing values of our cost over time and just kind of take a look at that plot and see what it looks like. All right, so back at my terminal, I'll do a quick node index.js. And it looks like we're still successfully getting a result here, which means we have no errors. So that's good. And the second thing I want to do is open up my index.js file. And I want to import that plotting library and then use it to plot how our cost is changing over all of our different iterations of gradient descent. So at the top, I'm going to require in plot from node remote plot. And then down at the bottom of the file, I'm going to call that plot function, and as the x values, I will pass in regression.cost history. And remember, the newest values are at the front of this array, and so it usually makes sense when we do a plot to actually reverse them. So I'm just going to reverse those values. All right, so we're going to run this. We'll take a look at the plot and make sure everything looks good. So I'll again do a node index.js. I can then look back at the logistic regression directory, and inside there, I should see a plot that looks like this. So this means that our cost, or kind of how wrong we were, started out up here, and then it eventually went down over time, and around 20 iterations or so, we got a pretty stable reduction in cost. So this would mean that we wouldn't really need to change our do any iterations over the first 20 or so. So we could definitely shorten that up a little bit. Of course, do keep in mind that the number of iterations that we do right here is also dependent upon our batch size. So if we wanted to, we could say change our batch size down to 10, and now we could save this file and rerun node index.js. And then if we looked at that plot again, we'll notice that it gets down a little bit more quickly. Notice how it first starts off up here at 0.22, whereas before it started off at like 0.3 or so. And so in this case, we probably wouldn't even really have to do even 10 or so iterations. We could probably just get away with like 2 or 3, because the reduction in error from 0.22 to like 0.21 is so inconsequential that I wouldn't really worry about it. I know that this almost vertical line right here looks very abrupt, and you might think, whoa, we still need to do a ton of iterations. Well, really the range of values there are so small that we probably wouldn't really need to do that many more. Okay, so this looks great. We're definitely recording our cost correctly now. All right, so that's pretty much it for this first go through of logistic regression with kind of this silly little cars data set. So let's take a quick pause right here. When we come back to the next section, we're still going to work on logistic regression a little bit more, but we're going to be looking at a far more useful and a little bit more complicated version of it. So quick pause, and I'll see you in just a minute. In the last section, we finished wrapping up on logistic regression with regards to binary classification. Remember, binary classification was all about applying either or labels. So either a student passes an exam or they do not pass. Either an email is spam or not spam. Now, this is definitely useful, but clearly there are many types of questions where we do not want to apply either in either or classification. So to move forward, we're going to start taking a look at a little variation on logistic regression called multinomial logistic regression. With multinomial, we have the ability to apply multiple different label values to classify a given observation. So as a couple quick examples, we might ask the question, given a person's number of hours spent driving each day, what type of car do they prefer? They could have options of a luxury car, a sedan, a truck, or a compact vehicle. For this question, there's probably not going to be a single either or answer. Chances are people do not simply prefer either luxury cars or sedans. In reality, they might prefer a wide range of different vehicles. So some people might want luxury, others sedan, others truck, and yet others still would be compact. Now, likewise, we could ask a question like, given the number of times that a person views cat pictures each day, how many cats do they own? Is it 0 cat, 1 cat, 2 cats, 3 cats, 4 cats, 5 plus? And then another good example would be, given a person's age, what type of phone do they prefer? A Apple iPhone, an Android phone, a classic simple feature phone, or even a older Windows phone, if those even exist anymore. Now, on this last example right here, notice how we can kind of easily take these simple binary classification problems, as we had before, where we said, does a person want to use a Apple phone or an Android phone? And we can just tack on additional label values or additional options for these label values, and boom, it turns into a multiple classification type problem. Okay, so how are we going to do this? Well, let's take a quick pause right here. When we come back to the next section, we're going to talk about how we're going to essentially reuse the exact same logistic regression class we put together, but expand it to apply to the multinomial case as well. So quick break, and I'll see you in just a minute. In the last section, we started talking about multinomial logistic regression. In this section, we're going to start talking about how we're going to refactor our existing logistic regression class over to a multinomial solution. Now, I'm going to tell you right now, we're going to discuss 2 different ways of doing this refactor. In total, there's these 2 ways, one which way I would call the smart way of doing this refactor from our current binary classification over to multinomial, and then there's also a really smart way. So a smart way and a really smart way. Understanding the really smart way to this refactor kind of needs you to understand the smart way first, so that's why we're going to talk about these 2 separate refactors we could possibly do. So let's get started first talking about the smart way to do this refactor. Now, to help you understand the refactor, we're going to use another quick example here. So this is the same type of problem we were working on previously with the binary classification. We're going to say that given a person's age, we want to know whether or not they prefer to read books, watch movies, or dance. So we now have this 3rd classification label. So it's definitely going to be a multinomial logistic regression type problem. All right, so here's how we would approach this refactor using the smart way. First off, we would start with our sample data set right here, just as we did before. Notice how we've still got ages 5, 15, 25, and so on. We still like to watch movies for the young people, middle-aged people like to read books, and older people like to dance for whatever crazy reason. So to get started, we're going to encode each of those different label values just as we did before. But instead of just doing that encoding step one time, we're going to do it 3 separate times. We're going to take a look at all the different possible classification values in here. Before we had just 2, now we have 3. So I would look through all my different label values, and I would notice that there are 3 distinct possible label values: watch movies, read books, and dance. I would then use each of those 3 different label values to produce a new, different encoded label set. So I would first produce this encoded label set right here, where I have a 1 for every value where I see watch movies. All other values would be equal to 0. Next up, I would have an encoded activities for read books. So all the different read books get replaced with 0. All the other values get replaced, all read books gets replaced with 1. All the other values get replaced with 0. And then finally, encoded activities for dance. I would look for all the different dance records, set them equal to 1. Everything else goes to 0. So now I've got these 3 different label value columns. I'm going to take those 3 different label value columns, and I'm going to pass each of them to 3 separate logistic regression classes. So in other words, I can make 3 instances of our class. I'll take my entire feature set, and then first this label set, then this label set, and then this label set over here. So I'm going to have 3 different instances of this class. I'll then train each of those instances, and so I would essentially have a copy of logistic regression that is really good for making predictions about whether or not someone wants to watch movies or not. So in this first model right here, we're essentially saying we either want to watch movies or not watch movies. Remember, the zeros indicates we do not want to do, or we do not want to classify something as whatever the 1 label is. The second class right here would be really good at identifying people who want to read books. And then finally, the third one over here would be really good at predicting whether someone wants to dance or not. So then after training each of these 3 separate class instances, I could make a prediction about some future observation. So let's say if we now want to figure out what activity a 20-year-old prefers, we would essentially toss that 20 value into each of our 3 different models. And each one would spit out a probability of whether or not that person is going to want to watch movies, read books, or dance. So let's say that for someone who's 20 years old, there's a 0.34 probability of them wanting to watch movies, a 0.47 probability of them wanting to read books, and a 0 probability of them wanting to dance. And so in this case, we would look over these 3 different probabilities coming out of the 3 different models, and we would select whichever probability was highest. In this case, the highest probability is reading books. And so we would say that the 20-year-old person wants to read books. So this kind of smart refactor back here, that's the kind of smart way of doing this refactor. Essentially, we just make multiple instances of our class, and we feed it these different label sets. Each one gets a different label set. Then when we want to make a prediction, we take those 3 different models and throw them all together at that one single problem. Okay, so like I said, that's the smart way of doing this, and I think you probably have a reasonable idea of how that's pulled off. So let's now take a quick pause. When we come back to the next section, we're going to talk about how we're going to do this the really smart way. So quick pause, and I'll see you in just a minute. In the last section, we started talking about refactoring from binary classification over to multinomial classification. We did so using what I might refer to as the smart or kind of clever way, because it was kind of clever. Now in this section, we're going to learn that there's an even more intelligent way to do this refactor from binary over to multinomial classification. And this really smart way of doing this is going to completely hinge upon a little bit of clever mathematics. So let's get to it. Now, as we established in the last section, we had said that we would make 3 separate instances of our logistic regression class, and each one would have its own separate set of label values. Remember, that was a real key thing. We had said that we would encode our labels here separately for each instance of logistic regression, and each one would get its own different set of labels. Now, if we start to think about the different values that are held inside of each of these different class instances, we can kind of break it out like this. So for logistic regression instance number 1, that is essentially responsible for predicting whether or not someone likes to watch movies, we would have a couple of different instance variables. First off, we would have a unique set of weights. Remember, the weights tensor holds our different values of m and b. We would also have a unique set of labels for each instance as well. So as we just said a second ago, each of these different labels tensors would end up being slightly different. And then in addition, we would of course have our features tensor in each one. And the first thing I want to point out here is that the features tensor inside of each instance of logistic regression would end up being completely identical. At no step along the last section do we ever talk about manipulating this features tensor in any way, shape, or form. So I'm just going to delete that thing because it never changed whatsoever between these three separate instances. However, as we just said, labels is definitely going to be a little bit different for each of these different classes. Because these labels are going to be different, as we go through the gradient descent process, we're going to end up with different weights tensors as well. So essentially, when we think about the differences between each of these three different classes, we start to realize that for each different instance, we end up with a different set of weights and a different set of labels. And so we might draw them all out like so. Each separate instance has its own weights tensor and its own separate labels tensor. Now, here's the issue with this. As we start to think about working with this multi-instance or this multi-model approach with just 3 different label values, it's not the worst thing in the world. But if you can imagine trying to take this approach with like 20 different label values, having a bunch of different class instances starts to turn into a pain. So I'm wondering, is there some little mathematical trick that we can use to get away with just one class instance? Well, let's think about whether or not we could do that. So just for the sake of discussion, let's imagine that these 2 class instances over here no longer exist. I'm just going to delete them. We're just going to pretend they don't exist anymore. However, we still need some place to store all the weights and the labels that belong to each one. So we're going to say that this one instance over here is now going to be responsible for holding a weights tensor related to watching movies and holding a labels tensor related to watching movies, but it also has to hold these other tensors as well. So let's take a quick pause right here. We're going to come back to the next section and continue down this line of discussion where we imagine kind of taking these different tensors and somehow combining them all together inside of a single class instance. So quick pause and I'll see you in just a minute. In the last section, we started wondering if we could remove those other instances of logistic regression and store these different weights and labels tensor inside of this one single instance over here. Now, one way to approach this might be to take these different weights tensors and store them all inside of a normal JavaScript array. So let's imagine that these are our 3 separate weights tensors, and maybe we try to put them as different elements inside of a JavaScript array. Well, maybe we could do that, but I got a crazier idea, a slightly strange idea, and this is where that little trick around mathematics starts to come into play. Rather than storing these 3 separate weights tensors as different elements inside of a normal JavaScript array, I'm going to suggest that instead, we just concatenate them all together. So we'll say that rather than having separate weights tensors that are each a single column, we're going to have one single tensor of weights, where each column inside of it represents the weights for a different type of analysis. The first column here represents weights for trying to do analysis for finding observations that favor watching movies. And then the second column will be weights for read books, and then the third column will be weights for dancing, or people who like to dance. Now let's imagine that we do the same thing as well for our label values. I'm just going to kind of take these different columns and throw them together like so. And so now when we look at our labels tensor, if we have a 1 in the first row here, or if we look along a row, if we have a 1 in the first index, that would mean that this is a label entry right here where this person likes to watch movies. And if there's a 0, or let's say a 1 in the second column, that means they like to read books. And if there's a 1 in the last column, then they like to dance. So again, if we start to join these together, we can view each row here as a separate, distinct observation. And it tells us everything we need to know to decide whether or not someone likes to watch movies, read books, or dance. All right, so at this point, I'm sure it seems like we just kind of arbitrarily took these different weights and labels and joined them together into single combined tensors. So again, we can imagine that we now have a combined weights tensor and a combined labels tensor. So now, using this type of approach right here, or this very different looking tensor, I want to go back to our actual logistic regression class. Here it is right here. And I want to start to think about how we would have to update this class to deal with this fact that weights and labels now have this very different structure. Well, without a doubt, when we initialize our weights right here inside the constructor, we would probably have to make a little change right there. In addition, I think that probably, without a doubt, the gradient descent function would have to change quite a bit, because we are now dramatically changing the shape of our weights tensor and our labels tensor. It would probably have to change, right? Or would it? So that's the key. When we start putting these different tensors together, like we take these multiple columns and we just sandwich them all together, thanks to the rules around matrix multiplication, it turns out that absolutely nothing inside of this gradient descent function and vast sections of the other code we have inside this class have to change at all. We don't actually have to change anything inside of gradient descent. We don't have to change anything inside of train. We don't have to change anything inside of predict for the most part. Once we start to sandwich these different weights tensors and labels tensors together. Let me show you how. Let me run you through a quick example of why all of our matrix math actually ends up being identical to how it is right now. So, as a quick reminder, this is the equation that we're essentially calculating inside of the gradient descent function. We have our features times our weights, that's matrix multiplication. We take the sigmoid of the result, and then we subtract our label values. And then we multiply again by our features transpose. So this is what we're currently doing inside of our gradient descent function. And we've definitely walked through this function in great detail to describe how the matrix math works when weights is a single column and labels is a single column as well. Let's kind of walk through the first couple steps here if weights is no longer a single column and labels is no longer a single column too. So here's what happens. The first step is to take our features and multiply them with our weights. And remember, when I say multiply, that's a matrix multiplication step. So I want to do my features tensor times the weights tensor. All right, so here's my features over here. I've got my age column, and I've appended on that arbitrary column of ones. And I'm going to do matrix multiplication with that kind of joined up tensor full of my weights for the watch movies, weights for read books, and weights for dance. Now the first thing we should do here is check the shape and make sure that these two things can be multiplied by each other. So the shape of my weights over here is 6 rows and 2 columns. The shape of my weights is 2 rows and 3 columns, like so. And so the 2's here are identical, which means they are allowed to be multiplied by each other, and the result is going to be a 6 by 3 matrix. So here's the resulting 6 by 3 over here. Each column inside of here is essentially going to represent the mx plus b values for a different possible classification label. So the first column is going to be identical to essentially the first column, the column that we are calculating right now inside of the binary classification. It's going to be the mx plus b values for just our features tensor and this single set of weights that we're currently using inside that binary solution. Where things start to get interesting is the second column and the third column. So the second column is just our weights tensor for read books times our features. And then the third column over here is just the weights for dance times our features tensor as well. Just to show you the math here very, very quickly, I can take my features over here, put the different weights above, and then we can go through the same matrix math operation that I've showed you before. So we can imagine that we take this times this, and then we add it to this times this. And so we would end up with x1 plus times m plus b1 times 1. And as we said many times, that would essentially reduce down to just be mx plus b. And that would, of course, be mx1. So now we can go over to the next column. Notice how the next column over here has nothing to do with these weights. It's solely this column of weights times our original features. And so there's kind of no cross-pollination between these different sets of weights. And so over here we would do, we can imagine B2, just to be really clear here, in M2. So this would be x1 times M2, or I say times, x1 times M2 plus B2 times 1. And again, that would condense down to essentially be mx plus b, just as before. And the same operation would go on for the third column as well. So even though we've kind of arbitrarily added on these additional columns, it's still doing the exact same operations as we were doing before. Okay, so I think that makes sense for features times weights. So the result of that would be the 6 times 3 full of all of our different mx plus b values. And so we can take the sigmoid of that very easily, just as we have before, using TensorFlow. Remember, sigmoid is an element-wise operation, so no issue there whatsoever. So then the next step would be to subtract by our labels. So in this case, we would have those mx plus b values, where each separate column represents the specific values for watch movies, read books, and dance. Now our labels is now in theory, a 6x3 tensor as well. And so in the first column right here, we've got the encoded labels for watch movies, encoded labels for read books, and encoded labels for dance. And so we could subtract these two by each other, and we still are safe to do this operation as well. Now we could keep on going down this process, and I'm sure you could imagine how we could then multiply by the features transpose right here, but essentially it's the same thing that it was before. So what's the result of all this? Well, essentially, rather than taking these 3 separate instances, we can combine them all down into this one single instance where we have these multiple columns for weights and labels. At the very end of all this, we're going to end up with the combined weights tensor. And so this one tensor, if we want to go and get some prediction using it, here's what we're going to do. If we want to make a prediction, we'll now take that combined weights tensor, which has that much larger shape to it, and we'll multiply by our prediction features. And then we're going to go ahead and take the sigmoid of that, and we're going to find the record with the highest probability. So still, as we did before, we're going to essentially be running the prediction features times the weights, just as we would have back over here when we had the separate model instances, and then we're going to calculate the different probabilities out, and we're still going to select the same highest probability, or excuse me, we're still going to select the highest probability as we did previously. Okay, so that's pretty much it. That's the whole secret here. That's how we would do the really smart refactor. It's just recognizing that essentially all these operations end up being totally identical, even if we have multiple columns on features and labels, multiple columns on weights and labels as well. So with all that in mind, let's take a quick pause right here. When we come back to the next section, we're going to start to refactor our binary classification solution over to a multi-nominal approach, and it's going to end up using very little changes to our code. So quick pause, and I'll see you in just a minute. In this section, we're going to start to refactor our logistic regression binary classification solution over to this multi-nominal approach. Now it's going to revolve around doing very few changes inside of our actual class, so let's get to it without further ado. I'm going to flip back over to my code editor. Now the first thing I want to tell you is that we have this current folder that has the logistic regression implementation inside of it. This currently has the binary solution approach. I want you to have a record of the binary approach to this thing, so I don't want to edit the existing logistic regression folder. I want to keep these files as they are right now, so you have a nice implementation of the algorithm to refer back to in the future. So rather than modifying these files right here, we're going to make a copy of the logistic regression directory, and then we're going to edit that copy instead. So you'll have the nice copy of binary and multi-nominal as well. All right, so let's get to it. The first thing I'm going to do here is open up that folder inside of my File Explorer, like so. I'm going to find inside of my regressions directory the logistic regression folder. And then I'm just going to make a duplicate of that folder, like so. So now I've got this nice copy. Now, of course, if you are in Windows, you probably don't have the duplicate option right there, so just do a simple copy paste. That's all you have to do. All right, so now I'll close that folder explorer, and I now see the copy of logistic regression. I'm going to rename this copy right now, and I'm going to rename it to multi-nominal logistic regression, like so. All right, so now inside of the logistic regression file, inside the multi-nominal folder, we're going to start to refactor this thing to do this kind of multi-column approach for our labels and our weights. All right, so here's my logistic regression file. Again, make sure you're inside of the multi-nominal folder. And then inside of here, essentially all we have to do to get started is find the constructor, and we're going to update the weights that we create right here. Remember, inside the constructor, we're currently creating this weights tensor that's going to have a number of rows equal to the number of columns inside of our initial feature set, and then it's always going to have one single column. So no longer do we want to have one single column right here. Instead, we want to make sure that we have as many columns as we have unique labels. And when we start to think about the labels and start to think about that encoding process, remember that we can either do this encoding inside the class or outside the class. We were previously doing the encoding step for the binary classifier outside of our class. So in other words, by the time we passed our labels to our class instance, we had already gone through the encoding step. So I'm going to make the assumption here that by the time that labels shows up inside the constructor, I'm going to assume that it's already been encoded into multiple separate columns. So we'll receive the labels, and we're going to put that inside of a tensor. So the number of columns of our labels tensor is going to be the number of columns that we want our weights tensor to have as well. So instead of passing this 1 as a second element in the array to tf.zeros, I'm going to instead reference the number of columns that labels has. So I'll say this.labels.shape at 1, like so. Okay, so that looks good. That's going to take care of our weights. Now, I'm wondering if there's anything else that we have to do inside of here for now. You know, I'm looking around and I'm pretty sure that there's really nothing else we have to change. At some point, we're probably going to have to update our prediction function, but let's just hold on to that for right now. Remember, at present, the prediction function is going to just do our multiplication with our observations by our weights and then apply the sigmoid. And as I just told you, to do our predictions in the future, we're going to still do that same process, but then we want to take the highest probability. We'll learn how to do that in just a second, but for right now, let's just leave the predict function as it is. Okay, so I'm looking through here. I don't think there's really anything else we have to change in here for right now. All right, maybe the test function will change a little bit. I don't know. We'll see. Okay, I think that we at least have enough changes to actually do some initial analysis here. All we really had to do was change the structure of our weights. So let's take a quick pause right here. When we come back in the next section, we'll talk about how we're going to update our analysis so that rather than looking at a bunch of different cars, we have some data set that we can actually use for a true multinomial analysis. So quick pause and I'll see you in just a minute. In the last section, we put together a very easy refactor around our logistic regression class. All we really had to change was the shape of our weights as we initialized them inside the constructor. Now we're probably going to have to eventually make some changes to the predict function and test functions, but we'll get to that over time. Right now, I want to leave these as they are because they're actually going to give us a little bit of insight as to how our algorithm is now working. All right, so I'm going to close this logistic regression file and go back to the index.js file inside the multinomial regression folder. All right, so I want to work on a very quick and somewhat easy problem just so we can make sure that this refactor that we're doing is going to work for multiple classification problems. Once we have some early validation, we're then going to eventually work on a much more complicated, harder problem. But again, for right now, I want to start just a little bit easy. So I've got a quick little problem that we're going to try to solve. Here it is. So it's going to rely upon the same cars data set that we've already been using, but it's going to use it in a slightly different fashion. So our question is, given the horsepower, weight, and displacement of a vehicle, is it going to have high, medium, or low fuel efficiency? Now, looking at this question, you'll notice right away that the second part to it is kind of interesting. It says high, medium, or low fuel efficiency. If you go back over to our cars data set inside the data folder, you'll notice that there's no column inside of here that says specifically like fuel efficiency. We've only got past emissions, miles per gallon, and so on over to the end. So rather than trying to make use of some column or values that already exist inside of our data set, we're going to do kind of a synthesis step inside of this problem. Our fuel efficiency right here is kind of the same thing, well, it really is the same thing, as the mile per gallon column right here. Mile per gallon is the fuel efficiency. It rates how much fuel it takes for us to travel some distance. So rather than just making use of some label that's already been placed inside this CSV file, you and I are going to look at the different mile per gallon values that we have, and we're going to try to apply some classification based upon their values. Now, this is going to be a step that's going to take place before we ever start the logistic regression. So let me tell you a little bit more about how this is going to work. First things first, we're going to have to define some metrics for those mile per gallon values on what qualifies a mile per gallon rating as being high, medium, or low. Off the top of my head, we might use some categories like this. Maybe we will say that if a vehicle has 0 to 15 miles per gallon, we'll say that it has low fuel efficiency. If it's 15 to 30, we'll say it's medium. And if it's 30 or above miles per gallon, then we'll say that it's high. So once we have these kind of relationships set up, we can then take our real mile per gallon values. So that would be the straight values out of that column. We'll then do some initial translation step where we will turn them into labeled classifications. So a car with 9 or 12 miles per gallon would have low fuel efficiency. 16 to 27 would be medium, and 32 to 45 would be high efficiency. Then once we have those actual label classifications put together, we can encode the different values into different columns. So anywhere that we see a 1, if it's in the low, that we have a 1, that means that this observation right here is meant to have a low fuel efficiency. Now, the thing to keep in mind about this final encoding step over here is that each row that you see matches up to one singular label value. So this row right here is talking about the encoding for this single 9 mile per gallon vehicle right here. Okay, so that's pretty much it. Now, the one thing I want to point out here that's kind of interesting is that we really just took a linear regression problem, right? Because that's what we were doing before. We took a linear regression problem around fuel efficiency, and we just kind of arbitrarily turned it or pivoted it into a classification problem. And so in reality, you can take a lot of these linear regression problems where we're trying to predict some continuous value, and you can really turn it into a classification problem by just setting up some classes or bounds like this right here. So I thought, even though, remember, we just want a quick little problem to work on, I still thought this was kind of an interesting thing to do. Okay, so let's take a quick pause right here. When we come back to the next section, we're going to work on taking our mile per gallon values and eventually encoding them like so. So quick break, and I'll see you in just a minute. In the last section, we started talking about the problem we're going to work on. So without further ado, let's flip back over to our code editor and get started. So as a reminder, I'm inside the index.js file inside the multi-nominal directory, no longer working inside just logistic regression. So now inside of here, let's first focus on getting in those label values and encoding them properly. The first thing we need to do is find where we're loading up our CSV file. Rather than loading up the past emissions, I'm going to instead load up the MPG column instead. Now, in order to take these MPG values and eventually turn them into these encoded rows like so, we could either make use of this converters option object right here. Remember, this is kind of an override that will allow you to manually convert values inside the CSV, or we could do it manually after the step, or kind of after the thought down here. In this case, we'll make use of converters. There's just going to be one little thing that you need to be aware of, and I'll point it out as soon as we put this thing together. The one thing to be aware of is that this converters option object isn't really purpose-built for you to return arrays, which is what we're trying to do here. We're trying to return an array of values of 1, 0, 0. But again, I'll show you the little consideration that needs to be minded. All right, so for converters, no longer are we going to try to parse the past emissions column. Instead, I want to parse the MPG column. So then inside of here, we're going to take the value. Remember, the value comes in as a plain string value, so we're going to have to turn it into an integer or a float or otherwise a number. So in order to do so, I'm going to say MPG equals parse float value like so. Then after that, we can go through the actual encoding step. And there's definitely probably some clever way we could figure out to actually do this or do the encoding, but for right now, we'll just stay really easy and straightforward. So I'm going to say, if MPG is less than 15, then I want to return my encoded row, which would be values of 1, 0, 0 like so. So all we're doing here is saying if the vehicle has less than 15, so like the 9 and 12 right here, return an array that has 1, 0, 0, where the first element in there indicates that it falls into the low classification. Like I said, we could probably think of a more clever way to do this, but for right now, this is going to work out just fine. Next, we can put in an else if and say if MPG is less than 30, then I want to return 0, 1, 0. So that would be our medium rating right there. And then we'll do an else. Otherwise, we'll just return 0, 0, 1, like so. Okay, so that looks good. Now just do a quick check here. Please make sure that you've got 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now after we load up all of our data, we'll have labels and test labels, which should have these encoded columns. Let's very quickly console log out labels and just make sure the thing is being put together as we would expect. So after the loading data step, I'm going to do a console log of labels like so. And then I'm going to comment out everything else inside this file because we don't want to run any of our analysis just yet. All right, I'm going to save this file, and then I'm going to flip on over to my terminal. I'm going to make sure that I'm inside my regressions directory, and then I'm going to really make sure that I change into multi-nominal logistic regression. Remember, you don't want to be in logistic regression anymore. So I'm going to change into multi-nominal, and then I'll run node index.js like so. Okay, so there is our array of arrays. So it looks like everything got encoded properly. We should see no instance where there are 2 ones on one single line. If you see that, that means that something definitely went wrong. Now the only issue here, and it's kind of hard to see, remember I mentioned just a second ago, I said that using converters, the converters option right here, there was a little something you and I had to be aware of. Essentially, converters is not set up to receive an array in response. It's only supposed to return a number or a string or something like that. So you might notice that inside of each of these rows, the first element is an array, which is what we are returning. So we've got essentially one too many arrays stacked up here. Now, we can deal with this really quickly, but let's just take a break. We'll come back to the next section, and I'll tell you how we can use Lodash to very easily essentially reformat this data set right here to work in the way that we would expect. So quick pause, and I'll see you in just a minute. In the last section, we saw that we were able to encode these different label columns, but we had these kind of double-nested arrays in here. So we can fix this very easily using Lodash. Not a big deal at all. I'm going to flip back over to my index.js file, and then at the very top, I'm going to require in the Lodash library, like so. I'm then going to go back down to the console log. We had a little bit down lower. Here it is right here, and I'm going to wrap labels in a _.flatMap function call. The flatMap function is essentially going to remove one layer of nesting from every element inside of this array. So let's save this. I'll flip back over to my terminal. I'll rerun node index.js, and now we see that we've kind of removed one layer of nesting. And so now we're left with the exact structure that we would expect. One outer array, a bunch of individual elements, and each element is an array that constitutes essentially one single row. All right, so this is looking pretty good. Now I'm going to flip back over to my terminal, and I'm going to remove that console log. I'm then going to uncomment where we create our regression class right there. And then I'm going to make sure that I wrap labels when we pass it in as the second argument with a flatMap function call like so. Okay, so now when we pass our labels into logistic regression, it will have the correct structure. So now before we go ahead and train anything, I want to do one other quick thing, just a quick gut check to make sure we're going down the right path here. If you open up your logistic regression class, you'll recall that one of the only refactors that we did inside of here was to adjust the shape of our weights tensor when it first gets created inside the constructor. And so the weights shape is really dependent upon our label shape now. So I just want to do a quick console log of our weights tensor after it gets created, just to make sure that it has the correct number of rows and columns, just to do, again, a quick gut check and make sure we're going down the right path. So underneath regression, I'll do a regression.weights.print like so. I'm going to save the file, and then I'm going to again flip back over to my terminal and rerun node index.js. Okay, so here's our weights tensor right here. Now, quick question for you. It looks like we have 4 rows, 3 columns. Does this make sense? Is this what we expect? Well, I would argue yes, it probably is. Remember, each row inside of the weights tensor represents a different b or m term. In our case, the first element inside of every one of these columns represents a b term. Then we have m1, m2, and m3. Each of those represent the m values that we're going to multiply our horsepower, displacement, and weight by. We then have 3 columns. Each column represents one different label value that we're essentially trying to do an analysis for. So maybe column 1 right here is the low mile per gallon. Maybe the next column is medium mile per gallon, and maybe the last one is going to be the high mile per gallon. Okay, so I think that yes, that does look pretty good. So now I think we're ready to actually do our training and then make some prediction. Now we don't really have any logic in here for doing the test or the cost history just yet. I'm just going to delete those steps so we don't have to look at the comments anymore. So let's just do our training step, and then immediately after, I want to make a prediction. until we make sure that the testing step is working appropriately. I think that just doing a straight prediction is going to be the easiest way for us to validate and make sure that the class is working as we would expect. So I'm going to say regression.predict, and then remember, anytime we call predict, we're going to pass in an array of arrays, where the inner array represents a single prediction point. Now, I definitely want to put in some realistic data here, so I'm going to open up my cars.csv file and get a sense of what numbers for displacement, horsepower, and weight I should put in. Okay, so the first thing I want to do here is probably find a mile per gallon that's going to be, definitely in like one category or another, like definitely low, high, or medium. So I'm going to say, I don't know, one of these 14s, good enough. I know it's right on the border, but let's just try it out and see how we're doing. So I've got a displacement of 440, a horsepower of 215, and a weight of 216. Now, quick reminder here, anytime we make a prediction, we have to make sure that we pass that data in the same order that we loaded up our data columns. So it's horsepower, displacement, weight. Okay, so down here, I'm going to do my horsepower. Let's see, which one do I pick? Well, it doesn't really matter. I think it's this one right here. 215, my displacement of 440, and then my weight was 2.16. So we're going to call predict with that. Remember, predict is going to return a tensor. And now when we return this tensor right here, it's not going to be a single probability value. It's going to instead have 3 separate values inside of it. And it's going to be the probability that this record is going to fall into the low class, the medium class, or the high class. All right. So let's just print this thing. We're going to print whatever we get back from the predict method, and we'll see how we're doing. All right, I'm going to save this file, and I'll flip back over my terminal and do another node index.js. All right, so there's my weights tensor, and then I get my output here of values 1, 0, 0. Okay, so that looks pretty good. It looks like we're getting the right thing. Remember, the first element inside of here is our probability of this vehicle falling into the low mile per gallon category. So without a doubt, we just put in a vehicle with a value of 14 somewhere inside of here, value of 14, and I got out a low mile per gallon prediction, which makes sense because we had essentially set our cutoff as saying anything from 0 to 15 miles per gallon would be a low efficiency vehicle. Now, one quick thing. I want to mention, if you see 2 1s inside of here, that's totally fine, okay? If you see 2 1s, not an issue whatsoever. We're going to take a quick pause. We're going to come back in the next section, and I'm going to show you some output inside of here that might be a little bit surprising. Okay, so quick pause, and I'll catch it in just a minute. In the last section, we fixed up our index.js file, and then we're able to make a prediction. I saw an output of 1, 0, 0. As a quick reminder, the entire idea here is that after we apply the sigmoid to multiplying the prediction features by our weights, we'll then take the highest probability in that output array, or output tensor. So we would take the highest value inside of here. In this case, it's very easy because we have a value of 1 right there. The other 2 are 0. So without a doubt, this is a low mile per gallon vehicle. But I want to change a little thing or two inside of my index.js file, and I'm going to show you some really interesting behavior. So I'm going to flip back over to index.js. Now inside of here, as a quick side note, I'm going to delete the regression.weights.print statement right there. Okay, just want to get that out of there. We don't really need it anymore. And then I'm going to manipulate the vehicle attributes right here. I'm going to put in a very specific vehicle. I'm going to say 150, 200, and 2.223, like so. And then I'm going to save this and rerun my analysis. So now when we get our output, we're going to see some really bizarre result. Take a look at that. This output right here means that that particular vehicle has a 100% chance of being a low mileage vehicle and a 100% chance of being a medium mileage vehicle. So we saw 200% chances of being 2 distinctly different classifications. Now, when we start to look at this right here, the first thing I want to mention is that if we saw some result, I'm going to put a probability right here. If we saw something like 0.8, 0.2, 0.0 or something like that, I could stomach this right here because this means that we have an 80% chance of being low mileage, 20% chance of being medium, and a 0 of being high. And so if we get different probabilities inside of here, that's totally fine. We can stomach that without a doubt. Remember, the entire goal of that algorithm was to take the highest probability. And so if we see different values or multiple values coming out, we can stomach that. But it's the fact that we've got two 1.0 values coming out as a result that makes me think that something is very off. Okay, so let's talk about why we're seeing this. We are seeing this result for a very particular reason. And like I said, we're going to do the tiniest refactor you can possibly imagine to get this result to go away. But first, I want you to understand why we are seeing this. So let me show you a couple of diagrams. Okay, so as a quick reminder, we spoke about the sigmoid equation a couple of videos ago. And when we discussed it, I used some very particular terminology. You might have not really noticed at the time, I don't know, but I said very particularly that the sigmoid equation gives us the probability of an observation being the one label. Now I want you to keep that definition in your mind for just a little bit as we start to look at the root cause of why we're seeing two ones in our response there, or result. All right, so I'm going to go to the next slide. This next diagram is going to have a little bit of terminology that I want you to understand to really get what's going wrong with this result. Okay, so a little bit of nasty terminology. So marginal probability distribution and a conditional probability distribution. I've got a little definition here next to both these that don't really answer what they are at all, but nonetheless, let's read them over really quickly. So a marginal probability distribution is when we have probabilities that considers each possible output case in isolation. A conditional probability distribution is going to consider all possible output cases together when putting together a probability. Like I said, these don't really tell you what these are at all, so let me give you a little bit more in-depth discussion. All right, so first, a marginal probability distribution. This is what we are currently calculating when we make use of the sigmoid function. Now, I want you to imagine for a second then that rather than using the cars example that we're putting together, let's go back to the example of watching movies, reading books, and dancing. So let's imagine that we do our analysis with this different data set, and we get, as a result, a 0.34 probability of someone wanting to watch movies, 0.47 for read books, and 0.67 for dancing. So if we followed the original rules of our algorithm right here, we would take the highest probability, right? So we would say that this person would like dancing. But before we just kind of isolate that by itself, I want to think about what's really going on with these probabilities and what they are currently really telling us when we keep in mind this definition of the sigmoid equation. So the probability values that we see on here are the probabilities of some observation liking to watch movies, but it's not making a claim about this person's probability of wanting to read books or dancing. Let me repeat that really quick because it's a very, very subtle distinction. I'm going to delete these other two notes right here really quickly. I want to just really focus on this one right here. So it says 0.34 chance or 0.34 probability, 34% chance of this person wanting to watch movies. Notice that when I say that, I say probability of watching movies. I did not say probability of watching movies and not wanting to watch or, read books or dance. In other words, with a marginal probability distribution, we get these probabilities that are only informing the probability of a single output, a single characteristic. 0.34 is just the probability of someone wanting to watch a movie, and it tells us nothing about someone wanting to read a book or dance. What that means is that as our algorithm is working right now, someone can very easily want to watch a movie and read a book. Someone might want to watch a movie and read a book and dance. In the analysis that we just ran right here, this is telling us that our car is both low mileage and medium mileage at the same time. Now with mileage, that doesn't make a lot of sense, right? A car is either medium efficiency or low efficiency. It can't really be both. But applied to the idea of a person's preferred activity, it starts to make a little bit more sense. Someone totally can want to watch a movie, read a book, and dance at the same time. It's entirely possible. But with the analysis that you and I are trying to do, classification, we don't really want to see what some person is capable of doing across a wide spectrum. We don't care that someone might want to watch a movie and read a book and dance. We only care about what their most likely activity is going to be. And so these probabilities that we are calculating, we do not want a marginal probability distribution because a marginal distribution is going to essentially give us probabilities of just these single individual outcomes in isolation. Just watching movies, just reading books, just dancing. And that's what I meant back here where I said considers one possible output case in isolation. The probabilities are just talking about their individual label values and not about the label values or the other label values that are possible. Now, the one thing I want to point out here that you can always use as a tool to figure out when you are working with a marginal probability distribution is to sum all these probabilities together. So if I take these probabilities and sum them together as I did down here, I get as a result 1.48. So what does 1.48 mean? Well, if you kind of think about it, a good way of thinking about this would be to imagine rolling a dice. A dice has 6 sides. So your chance of rolling a 1, a 2, a 3, 4, or 5, or 6 is always going to be 1 in 6. So in other words, we have a 1 in 6 chance of rolling a 1, 1 in 6 chance of rolling a 2, 1 in 6 chance of rolling a 3, and so on. When we think about these odds right here, kind of an interesting way to phrase this would be to not say a 1 in 6 chance of rolling a 1, but to say 1 in 6 chance of rolling a 1 and not a 2, 3, 4, 5, or 6. That's what we're really saying there. So this right here, this would be an example of our conditional probability distribution. Kind of. That's kind of stretching the truth right there. Maybe I don't want to go that far. But let me just say that it would be helpful to think of this dice rolling as saying 1 in 6 chance of rolling a 1 and not a 2, 3, 4, 5, or 6. So when you start to think about rolling this dice right here, and you sum up the chances for each outcome or each probability, so 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, you get as a result 1. So you can always kind of tell if you're working with a marginal probability distribution or a conditional by summing these probabilities and seeing if they total up to 1 or not. If you total up to 1, that possibly means that you are working with a conditional probability distribution and that the different probabilities that you have are kind of interconnected with each other. Okay, so let's now talk a little bit more about conditional probability distribution, but we'll do this quickly because I've kind of think you have a reasonable idea here. So with the algorithm that we have as it stands right now, it would be really nice for us to get a conditional probability distribution, because then we would get some probabilities that have some interconnected meaning with each other. In other words, if we reported a 0.28 probability of watching movies, that means 0.28 chance of watching movies and not reading books or dancing. And so it would essentially help us solve this problem that we're running to over here, where we're saying that this observation simultaneously has these 2 classification labels applied to it. Likewise, if we had a 0.32 probability of reading books, that means 0.32 probability of reading books and not wanting to watch movies and not wanting to dance. Okay, so I think you probably have a somewhat reasonable idea of the difference between a marginal probability distribution and conditional. So let's take a pause right here. When we come back to the next section, we'll talk about how we can calculate a conditional probability distribution instead of the current marginal probability that we're getting. So quick break, and I'll see you in just a minute. In the last section, we started talking about marginal and conditional probability distributions, and we eventually said that it would be nice if we could get a conditional probability distribution in our logistic regression class, or the multinomial one at least. So how are we going to do this? Well, essentially, right now we're making use of this sigmoid equation. The sigmoid equation is always going to result in a marginal probability distribution. If we want to move over to a conditional, all we have to do is use a slightly different equation. So instead of sigmoid, we're going to move over to a different equation called the softmax equation. The softmax equation is specifically written to essentially consider these different output classes and give us probabilities that kind of do not isolate one output by itself. Instead, it's going to take a couple of different probabilities and relate them to us in relation of each other. Boy, that's some awkward English. So let's just walk through a real example here. All right, so softmax is what we're going to use. Now, before I go to the next diagram and show you what the softmax equation looks like, I want to tell you right now, the softmax equation looks a little bit nasty. But I want you to remember, back inside of your code editor, if you open up your logistic regression file, you'll remember that inside of here at gradient descent, when we actually wrote out the sigmoid equation, as nasty as it looked, all we had to do was call .sigmoid. That equation is actually implemented inside the TensorFlow library. So just as a quick reminder here, at the end of the day, a lot of these functions you and I don't have to write out ourselves. So even though the softmax equation is going to look kind of nasty, it's already implemented inside of TensorFlow for us. So when you see it, don't worry that much. Okay, so here it is. Now it looks worse than it is. In reality, it's really not that bad. So the softmax equation, we've got the E value. Remember, E right here is a constant value approximately equal to 2.718. So we're going to take E and raise it to our mx plus b value. Then on the denominator down here, we're going to take the mx plus b value of all of our different classifications. So in other words, remember, we've got those different label columns, right? Like label 1, label 2, label 3. These all have different independent weight values for them. Remember, we've got those different values or those different columns inside of our weights tensor now. So on the denominator, we're going to look at all of the different m and b values that we have. We're going to essentially loop over all of them, and then we're going to calculate e to the mx plus b for each of those, and then sum them all together. So the bottom here looks way nastier than it actually should. So let me show you the next diagram, which is going to give you a practical example of what this equation actually looks like in practice. Okay, so here we go. So let's say individually, we have watching movies with a calculated mx plus b value of 15. For reading books, we have 23, and for dancing, 22. So essentially, we're just going to take those mx plus b values, and we're just going to shove them in there as the exponent for each of these e terms. That's all that's really going on. So if we have 15, 23, and 22, then for applying softmax to the watching movies over here, we would do e to the 15, and then it would be over e to the 15 plus e to the 23 and e to the 22. And then on the next one, it would be e to the 23 over, and then it would be 15, 23, 22 on the denominator, and essentially the same thing for the third one over here. Now, what do these really give us? Well, remember, when we run that sigmoid equation, wherever it is right here, we got back a probability of something being either the 0 label or the 1 label, or being really precise, we got back a probability of a observation needing to be applied the 1 label. When we get back a result from the softmax equation, we are still getting back a probability of this thing being the 1 label for this particular weight category. But in this case, it means we want to be the 1 label rather than the 0 label. That's the difference here. Again, with the softmax equation, we're considering all the other possible outcomes in this case. And the way that you can really detect that in this equation right here is just the fact that it uses the outputs of those different classification values. So when we are essentially doing some processing for watching movies, we are using the outputs of reading books and dancing at the same time as well. Now, I actually took this equation right here using the 15, 23, and 22, and I ran it through a calculator. And so as an output, I would have gotten 0.0002 probability of someone wanting to watch movies rather than reading books or dancing. For reading books, I got 0.73, and for dancing, I got 0.76. And so in total, this should, in theory, total up to a value of 1, so that we always know that we distinctly are going to pick, like, reading books or dancing or watching movies, and we will not, in theory, run into a situation as we had before, where, well, you just saw it a second ago, a situation where we have 2 1 probability values, which we definitely do not want to have, because that makes life really confusing and hard to decide what we should classify this thing as. Okay, so that's pretty much it. All we have to do is use the softmax equation instead. Now, the last thing I want to mention here is that it is still incredibly possible for us to calculate 2 identical probabilities. It's extremely likely at the end of the day, but it is possible for us to get, like, say, a 0.5 probability and a 0.5 and then a 0 over here. Totally possible. It's incredibly unlikely that you're ever going to get a completely equal probability, even though I say it's possible. So as possible as it is unlikely enough that we are not really going to consider the case in which a single observation has 2 equal probability labels needing to be applied to it. So we're just going to kind of forget that case and not really worry about it too much. Okay, so that's pretty much it. All we have to do is refactor from the sigmoid over to the softmax. So let's take a quick pause right here. When we come back to the next section, we're going to do that refactor, and then we'll rerun our analysis and see how we're doing. So I'll see you in just a minute. In the last section, we spoke about how we're going to move forward using the softmax equation in place of the sigmoid equation. Now, there's one thing that I want to address very quickly that you might be a little bit curious about. Remember, when we were talking about the sigmoid equation before, we had a single value of m and a single value of b to plug into the sigmoid equation. But as we discussed just a moment ago, when we run the softmax equation, it appears that there are multiple m and b values that eventually find their way into this equation. And in fact, when I showed you this example over here, and I said to you that mx plus b for watching movies was 15, for reading books 23 and 22, you saw that in this softmax equation, when we actually calculated it out, this was a calculation line specifically for watching movies. But you'll notice that inside of here are some values from these other kind of simultaneous calculations that are going on. So how are we going to address this? Well, honestly, it's all covered for us by TensorFlow. Remember, we spoke about how we are using that super clever solution. This one right here, yeah, like we went through this whole process and we had said that we had these multiple columns that essentially contained mx plus b values for each of our different label values, or each of the different label categories in this case, and each row going down represented a different observation. And so if we wanted to calculate softmax using essentially this tensor right here, we would look at just these three columns in isolation. So this would be like softmax value 1, value 2, value 3, the same ones that you saw subbed in right here, like 1, 2, and 3. So essentially, we want to take those three cells. Come on, where'd it go? Oh no, where'd the diagram go? Here it is. We want to take those three cells and run softmax using them. So let me show you how this is going to be done with TensorFlow. Again, really straightforward. So I'm again in this little coding tool if you want to follow along. Don't forget JSP is capitalized. So let's say that we have guesses, because that's what those mx plus b values are. And this is going to be tf.tensor. And inside of it, let's say that we've got the same kind of structure of three values in a single row, like so. So we could say, let's just use the same values I used in the diagram over here. How about that? 15, 23, 22. So 15, 23, 22. So in order to get that softmax done on this, we would just say guesses.softmax, like so. And believe it or not, yeah, it's just that easy. So now I have 0.0002, the 7.3, and the 2.6, which should be the same that you just saw in this diagram right here. Yeah, 0.02, 7.3, and 0.26. So TensorFlow is essentially going to look along a row for us and use those three values right there to calculate softmax and apply it to every element or every value inside that row. If we have additional rows, no problem whatsoever. We could do like 10, 11, 12, and we'll see that it's done on a per row basis. So no problem here. Using TensorFlow, again, just makes life really, really easy. Okay, so now that we understand that, let's flip back over to our code editor, and we're going to do this refactor. So what do we have to do? Well, it's really easy. We're going to find anywhere we said sigmoid, and we're going to say softmax instead. That's it. That's all we got to do. So inside of gradient descent, I'm going to replace sigmoid with softmax. So there's change 1 right there. And then I'm going to go down to the predict function. Here's sigmoid. We're going to say softmax instead. That's it. Okay, so that sure was not bad at all. So let's save this file, and we're going to rerun our analysis with those same kind of nasty values over here that led to that indecision when we had previously been using sigmoid function. So I'm going to do a node index.js. And then we'll see now we get a very, very clear answer. In this case, that vehicle is a medium mile per gallon vehicle. All right, so that's pretty much it. That is an example of using softmax instead of sigmoid. Now we still have a tiny bit of work to do on our logistic regression class. Remember, our test function isn't really up to par right now, as far as we know. So let's take a quick pause right here. When we come back to the next section, we're going to fix up this test function and make sure that it still gives us a good accuracy value. And then once we're done with that, we're going to take the entire multinomial logistic regression class, and we're going to work on a much more interesting problem with it. So quick pause, and I'll see you in just a minute. In this section, we're going to work on our test function to make sure that we're getting some reasonable accuracy out of our algorithm. So how are we going to do this? Well, it's going to be pretty darn straightforward. All right, so here we go. Right here, you might notice this as being our encoded set of label values. Remember that the output from our predict function actually has the same structure instead. It's an array of arrays with zeros and ones to represent different encoded values. In order to figure out what the actual label value is, or what the appropriate classification for each observation is, we can use a function called argmax. Argmax is going to return the column index of the largest value inside of each of these rows. And so remember that in theory, the largest value in each row represents the highest probability of some particular label needing to be applied to that particular observation. So if we ran argmax on this thing right here, this tensor, we would end up with 0, 0, because that's the location of the largest values in each of these rows. Then 1, 1, because that's the location of the highest value in each of those rows. And 2, 2, because that's the location of the highest value in each of those rows as well. So by running argmax, we're going to get back a single column that gives us the essentially designation of the label we should be applying to each individual observation. Now we're going to apply this argmax to both our input test labels and to our prediction values as well. And so we're going to get essentially two column tensors, each of which have the indices of the highest probability. So here's the column of the max value for our predictions and the column of the max value for our labels. We can then use the not equal function to compare these two things together. So we'll say, is 0 equal to 0? Yes, it is. So we'll put in a 0. The not equal function is going to look for values that are not equal to each other. So if you look at the two values inside of each of these columns, you'll notice that the only location where they're different is right here. Right here, they are not equal to each other. So the output there would be 1 inside this output tensor over here. Any place where they are not equal, we'll get a 1 inserted into this output column. So then we'll take this output right here and we'll just run the sum function on it, and that will essentially give us a number that says how many records were not equal to each other. So like I said, not the worst thing in the world, and there's definitely other ways in which we could gauge our accuracy in a very similar fashion just by using different functions. All right, so let's take a quick pause here again. When we come back to the next section, we'll start implementing this inside of our test function. In this section, we're going to do a quick refactor to our test function and predict function using the strategy that we just discussed a moment ago. So let's first begin with the predict function right here. Now we don't need a decision boundary anymore because now our rule that we're using to decide what the chosen label should be or chosen classification should be is going to be that argmax function. So I'm going to replace the greater and the cast function with a argmax like so. Notice that argmax has a capital M on it. And then remember, when we use the argmax function, this is something that we saw very frequently a while ago, we have to specify the axes for a lot of these functions to operate over. Same thing with argmax. So in order to tell this thing to get the largest value along the horizontal axes, I'm going to put in a 1 like so. Okay, so that's all we have to do for the predict function. So now we'll go down to the test function right here. We've got our test labels. I'm going to chain on the same argmax 1 on there as well, because remember, we want to take those encoded values and pull out the index of the maximum value along the 1 axis. So now we're going to take our predictions. We're going to do a not equal operation with our test labels, so make sure you get the not equal, and then we do not have to do the absolute value operation anymore. We're just going to do the sum, a get, and that's pretty much it. Okay, so this looks good. I'm going to save this file, and then I'll flip on over to the index.js file. Inside of here, we're currently doing the predict step. We don't really need that anymore, so I'm going to delete it, and I'm going to replace it with a regression.test statement. So we're going to put in our test features and our test labels as well. And then don't forget, when we made use of that converter function, we got back arrays in our row arrays. And so we have to do that same flat map operation that we did earlier. So I'm going to wrap test labels in a flat map statement like so. And then finally, I'm going to do a console log of that entire line, because that's going to be essentially our accuracy percentage value. All right, that's it. So I'm going to save this file, and then I'll flip back over to my terminal, and I do a node index.js. And so our output here says that we got a 0.8, which means that we are 80% accurate in assigning labels to our different mileage vehicles. Now this looks shockingly familiar because we saw almost an identical value when we did our regression analysis a while ago, which actually makes a ton of sense. Just because we switched our method of regression here, or the way in which we are processing these values, we didn't necessarily get a big increase in accuracy or any change whatsoever. Because essentially we just put a big proxy in front of those mile per gallon values by assigning the arbitrary labels to them. All right, so this looks pretty good, and we've now got a version of our multinomial logistic regression that we can use in some more complicated project. So let's take a quick pause right here. When we come back to the next section, we're going to do exactly that. We're going to start working on a little bit more challenging project. So quick pause, and I'll see you in just a minute. In the last section, we tested out the accuracy of our multinomial logistic regression algorithm, and it seemed like everything was working out pretty well. So I think that we've got a good implementation of the algorithm. The only thing is that at this point in time, we've only tested it with this very boring data set that we've worked with quite a bit throughout this course already. So in this section, I want to start to pivot to the next problem we're going to work on, the next project. I'm going to tell you a little bit about the next problem we're going to work on, and we'll start to discuss the data set a little bit. And then after that, we'll come back and we'll start to implement this new problem inside of our editor. So here's the problem statement. Here's what we're going to try to solve. You and I are going to be given pixel intensity values from an image. And given those values, we need to identify whether the character in that image is a handwritten 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So essentially, this is a reference to a very classic problem in the machine learning world. It's a reference to a famous database called the MNIST database. This is a data set, essentially, that contains a ton of different images of handwritten digits from 0 up to 9. So it's our job to take this database, take these individual characters inside of it, and classify each character as being a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's our goal. That's what we're trying to do. We want to classify these individual images. Now you'll notice that back in this original question over here, we've got a couple of different things we can learn from just this question. First off, the features that we're going to be working with are pixel intensity values. And we'll talk about what those are in just a minute. Secondly, you'll notice that we have a handful of different classification labels that we can apply to each individual image. So it's definitely going to be a multinomial logistic regression problem. We want to apply one of many different possible labels to each individual digit. Let's take a quick pause right here. When we come back to the next section, we're going to talk about how we're going to take this database and essentially convert it into something that can be actually fed into our logistic regression class. So quick break, and I'll see you in just a minute. In the last section, we started talking about the MNIST database. One thing that I want to start to focus on in this video, because this is going to be one of the big challenges of solving this problem, is how we're going to kind of rectify the structure of our current data set, or these different numbers right here, with how we've put together our logistic regression class. Remember, this class expects to be created with an array of arrays being passed into this features argument right here. So without doubt, everything that we put together inside this class expects features to be an array of arrays. But that's a little bit of a problem, because right now, our data set right here, essentially our features, is a big pile of different images, like raw images. So how are we going to take a bunch of images and provide them as array of arrays to this logistic regression thing? We need to figure out how we're going to essentially take those image files and convert them into some different format that can be understood by our class. Once we do that, maybe then we can figure out how we can use our class to classify all these different images. Okay, so let's start to explore this a little bit and get a better idea of what's going on. To help you understand this, I want you to first understand how all images are put together, all images that you ever view on your computer. So an image file is actually a collection of different pixel intensity values. When I zoom in really far on one particular number right here, you'll notice that this number starts to look a little bit blocky. If I zoom in even further, you'll start to really notice that every little part of this image is actually a different little square. So we refer to each of these little squares as pixels. When you zoom out really far and you essentially look at this from far away, you start to not quite recognize the pixels so much. I know you can still see the pixels here very easily, but you get the idea. The farther out I go, you start to not really notice those pixels anymore, and it starts to just look like a normal character. So every image that you ever view on your computer, every image that you take with your phone or with a traditional camera, is always going to be represented as a collection of these different pixels. These pixels are the key to how we are going to eventually represent this image as an array of different values that can be safely passed into our logistic regression class. You'll notice that when we look at the pixels inside of here very closely, some of them appear to be totally white, like the background over here. Some of them appear to be kind of light, like that one right there. Some are a little bit darker, and then the ones like in the very center here are just about black. So each of these different pixels has a different intensity or a different darkness applied to it. We can take a look at all those different intensity values, and traditionally we represent them on a sliding scale from 0 to 255. So we would refer to these as grayscale values. Anytime that you see a pixel that is pure white, we would assign that a grayscale value of 0. So 0 means white. Then as we start to get darker and darker and darker, the pixel or the grayscale value starts to go up until eventually at pure black, so just as black can be, we have a grayscale value of 255. So we can kind of imagine that we could break down or represent this entire image right here as a collection of different pixel intensity values. We can convert all of these different little blocks you see inside of here to a different grayscale value. Let's kind of go through that process. So inside this diagram right here, I've written out the character 1. You'll notice that at the very center of the 1, we've got some very dark values, but then to the side of it, it starts to get a little bit lighter and then a little bit lighter. Also take note that the overall dimensions of this image is 28 by 28 pixels. So in total, there are 784 pixels. I didn't make up these pixel numbers right here, the 28 by 28. The actual MNIST characters that we're going to use are 28 by 28 pixels as well. So if we look at the 1 right here, we can remove these actual grayscale colors that you see and replace them with their equivalent grayscale values. So for this 1, we might end up with something that looks like this. You'll notice that the darkest characters in the center all were assigned values of 255. And then the next layer out is a little bit lighter, so they have a grayscale value of, say, 180. And then even further out from that, which is a little bit lighter, we get a grayscale value of 90. So we can use this process to essentially represent the overall pixel as a kind of grid of grayscale values. Once we have these grayscale values represented as numbers, we can then take those and pass them all into our algorithm safely. So that's the whole idea. We take an image, we analyze the intensity of each pixel, or how dark each pixel is. We'll represent that as a grid of sorts, and that's going to be our data set, or our features, that we're going to ultimately pass into our algorithm. Now let's take another quick pause right here, and we'll continue in the next section. In the last section, we discussed how an image can be composed of a bunch of different pixels, and each pixel in a black and white image can be represented by grayscale values like so. So the number 0 represents a white pixel, 255 is completely black, and all the values in between are different shades of gray. Once we have that in mind, we can start to represent our image as a kind of grid like this right here, where the intensity of each pixel is reflected as a single number. Now this entire grid, as you see it right here, is essentially going to be our features, or our observation features for a single observation. You'll notice that it's a grid right now, but as we just discussed a second ago, we expect to pass in an array of arrays to the features argument, where each inner array is the complete observation set. So in order to make sure that this all works out, we're going to essentially imagine that we're going to take each row here, so like that second row, and we're going to stack them all up right next to each other, line by line. And so the result is going to be an array that is 784 elements long. So rather than passing in this thing as a 2D array or kind of a nested array into our algorithm, we're going to flatten the entire thing out until it's just one long array of all of the different pixel values inside of our image. So in theory, you can really imagine each of these different pixels right here as forming a different distinct feature. So like this pixel right here, this first little block would be feature number 1. The next one would be feature number 2. And then at the very end of this row, we would have feature number 28. So this means that the total number of features that we have inside of our feature set or our data set is significantly larger than what we had before. Before, on some of the other problems we worked on, we had a total of like 1, 2, or 3 features. In particular, for all the vehicle stuff we did, we had 3 features, just horsepower, displacement, and weight. But now for this problem, we're going to have 784 different distinct features. Pixel 1, Pixel 2, Pixel 3, Pixel 4, all the way up to Pixel 784. So it's 784 because remember, all these different images we are working with are 28 by 28 pixels. So down here at the very bottom right, this would be essentially feature number 784. So without doubt, the scale of data that we're working with here is incredibly larger than anything we have done previously. Not only do we have 2 orders of magnitude more features than we had previously, but you'll notice that the original dataset size that we're working with, where is it? Back over here. We're now working with 60,000 different observations, whereas before we might have had like, 300 or so. Okay, so that's pretty much everything we need to understand about how we're going to take these images and eventually reflect them as something that can be fed into our algorithm. Remember, all we really have to do is understand that we could represent images as grayscale values, understand that we can take this grid of pixels right here and flatten them out into an array, and then every element in that array essentially represents a different feature that is going to be reflected and analyzed inside of our algorithm. So let's take a quick pause right here. When we come back in the next section, we're going to start to write out a little bit of code inside of our index.js file to load up this data set and start to work with it a little bit. So quick pause and I'll see you in just a minute. In this section, we're going to start writing out some code to work with the imnest database. Now we don't have to do a lot of manual parsing here for the image. If you look inside the package.json file, you'll notice that there's a package inside of here called imnest database, or excuse me, imnest data. So this is a very convenient little npm package that contains the entire parse data set for us. So rather than doing the kind of boring stuff around parsing the image, we're just going to kind of use this pre-prepared data set for us. You still have to understand that it has all these different grayscale values inside of it, but it's just going to save us a little bit of time on something that would be otherwise a little bit tedious. So how do we use this? Well, we'll flip back over to our index.js file. And then to get started, I'm going to highlight everything after our require statements, and I'm going to delete all that stuff. I'll then find the load CSV require statement right there, and I'll delete that as well. So we don't need any more of that stuff on this next project we're working on, because we're not loading up a CSV file this time around. Next up, underneath all those require statements, I'm going to put down const imnest equals require imnest-data, like so. Now this imnest variable is actually a function, or it's an object that has a couple of functions on it that we can use to load up a variable number of training sets or training observations and test observations. So for example, we could call imnest data as imnest.training, and then the arguments we'll pass to this thing are essentially a slice in all the possible training images that we want to load up. So let's try just loading up one image right now. I'll say 0, 1, like so. So that means give me all of the training observations from 0 to 1, not inclusive. Now we can do a quick console log here of imnest data, and we'll see what we are working with. So I'm going to save this file, then flip over to my terminal, and I'll do a node index.js. All right, so now you'll see that we've got an object here that has a key of images. And inside of it, we've got a nested object that has a values property. So this values right here is the actual pixel values inside of a single array. We've also got all the appropriate labels for all the images that were loaded up in there as well. So you'll see that right here it says values of 5. That means that the single image that we loaded up, that thing right there and all the pixel values inside of it, that represents the number 5, or that's what this image is supposed to be showing on the screen. So now to kind of inspect the actual data here, we can do a console log of imnest data.images.values like so. Now I'll save this and we'll do another node index.js, and there we go. So that's our actual pixel values. You'll notice that it is an array of arrays. Each inner array right here represents one row of pixels, like that row right there, like just a single row. So we've got a bunch of zeros to indicate that we have a bunch of white space. And then if you scroll up, you'll start to see some more varied values. So you'll notice that we go from 0 to 136 up to 253. So 253 right there indicates a pixel that is rather dark, almost black, but not quite as black as possible. Now, of course, remember, we don't really want to work with a grid here. Grids are not super useful to us. So we're probably going to want to somehow flatten these things out just a little bit and make sure that rather than having a grid, we've got one long continuous array, like we discussed before. I essentially want to end up with a long array that's 784 elements long that has all the continuous pixel values. So to do so, we can go back over to our index.js file. I'm going to remove that console log, and I'm going to make a new variable inside of here called features. I'm going to say imnest.data.images.values, and then we're going to map over that. And for each image grid, and I'll refer to it simply as an image, we're going to use that same flat map function as we did previously. So I'll do a underscore.flat map and pass in the image. Remember, this flat map function right here essentially just removes one layer of nesting inside of, one layer of nesting inside of a nested array of arrays. So I will now put on a console log features after that. We can save the file and then run node index.js again. So now you'll notice that we have a single array inside of here for this first observation. There it is right there, and it's just one long continuous array. And in total, there's going to be 784 elements inside there. Right here, it only says 684 because it printed out 100 already, and there's 684 more elements inside there that were not printed out. All right, so that's pretty much it. That's how we're going to get some number of images out of this data set, and then format them to be essentially one long continuous array for each different observation. So now we could try to load up a couple more images, like let's load up a total of 10 here. We could do another node index.js, and we'll see 10 different images console logged out here. So 0, 1, 2, 3, 4, and so on. Each of those represents all the different pixel intensity values for a separate image. Okay, so that's pretty much it, believe it or not. Now that we understand how we can kind of rip data out of this thing, now what we really need to do is make sure that we encode our different label values appropriately, following that same type of schema we were working with before with our logistic regression algorithm, and then we can create an instance of logistic regression and run some analysis. So let's take a quick pause right here. When we come back to the next section, we'll start to take a look at how we're going to encode our different label values. In the last section, we wrote out a little bit of code to load up and properly format our feature set. So we've now got all of our features put together. Now we need to load up our labels as well and make sure that we encode them properly. Remember, when we're going through this logistic regression stuff, we have to load up our label set, find each unique label value inside of it, and then create a separate column for each of those unique values. Then for each column, we'll go through, and any time that we see an instance, in this case of say watch movies, we'll set that value equal to 1 and all others equal to 0. Then the next column, which over here was for read books, we would find every instance of read books, set that to 1 in the new column, everything else goes to 0. So it's going to be the same exact process this time around for our label values in the MNIST data set. So let's say that we get some label values that look like this. Now note that the different numbers you see in here is what the image in the corresponding feature depicts. In other words, the first feature, or the first observation inside of our feature set is going to be an image of the number 7. And then the second image will be an image of the number 4, 2, 9, and 0. Now we know off the top of our head, without having to do a lot of inspection here, the entire label set of values, like all the possible label values. It's going to be 0 through 9, or 0, 1, 2, 3, 4, and so on, all the way up to 9. So in total, we're going to have 10 different columns being encoded. Each different column is going to represent a different number. So the first column right here represents the column for all the different values of 0. Next one is all the different values of 1, 2, and so on. So essentially all we have to do is look at our label value, in this case it's 7, we'll go to the column responsible for encoding the value 7 and set that first row right there, that index right there, equal to 1. Then we go to the next value, find the column for encoding 4, set that equal to 1. We'll go to the next one, find for 2, find for 9, find for 0, and so on. Now, encoding these values is actually going to be really easy and straightforward because if you really think about it, the numbers here, or the actual label values, tell you the exact index of what you need to set equal to 1. In other words, the 7 right here means go to the 7th element inside this row and set the 7th element equal to 1. So 1, 2, 3, 4, 5, 6, 0 index, so 0, 1, 2, 3, 4, 5, 6, and 7. And so we go to the 7th element, set it equal to 1. Same thing for 4, same thing for 2, and so on. So this is a case where doing the encoding step is going to be really easy and straightforward. Let's flip back over to our code editor and we'll try to write out a little bit of code to do this encoding step. All right, so back over here, I'm going to remove the console log. And the first thing I want to do is just log out our different label values, just so we understand how to access them. So to get at the raw label values, we'll do mnist data.labels.value, like so. I'll save the file and then do a node index.js. And oops, looks like I did should be values right there, my mistake. There we go. So that means that the first observation that we have in our feature set depicts the number 5 inside that image. So now we are going to want to somehow encode that right there. Let's first begin by increasing the training set size here. I'm going to go up to 10, and I'll just run that again really quickly, and I can now see, yep, I've got the first 10 numbers right there. Okay, so we're going to use a little bit of a trick to encode these things. I'm going to say const encoded labels. We're then going to map over all of our different labels by saying imnist_data.labels.values.map. And for each label, we are going to create a new row. This row is going to essentially represent this single row right here. So we're going to create a row of length 10 and fill it up with zeros by default. So to do so, we can say const row equals new array of length 10, and we're going to fill all the elements inside there with the value 0. So you might have not seen this in JavaScript before. All we're doing is creating an array of a set length, and then we are filling that set length array with the number 0. So that's going to essentially set row equal to 0, 0, 0, 0, 0, so on. So now remember, the label value that you see right here is the index inside that row that we want to set to 1. So we can do something very simple like row at that label, because remember, label is going to be the actual index or the number, and we'll set that equal to 1 like so. And then finally, we can return our row. And that's pretty much it. So now we can do a console log of encoded labels. I'll save the file. I'll flip back over and run this again, and we'll see the properly encoded label values. I can check against the previous console log we did. So the first couple elements in there had label values of 5, 0, and 4. So I could go 0, 1, 2, 3, 4, and 5. And I see a 1 in the 5 columns. So that's appropriate. The next one is 0. I see the 1 right there. Next one is 0, 1, 2, 3, 4. And that matches up with the 4, and so on. So that's pretty much it. That's all we have to do to encode our label values. Pretty straightforward this time around. All right, let's take a quick pause right here. When we come back in the next section, I think that we'll be just about ready to start to create and train our model. So quick pause, and I'll see you in just a minute. In the last section, we successfully encoded our different label values. So I think that we're now ready to create an instance of our multi-regression class, or we call it logistic regression right here, and feed in our different features and encoded labels. So let's get to it. I'm going to remove the console log and replace it with a new regression variable. This will be a new logistic regression, and I'm going to pass this thing my features, encoded labels, and an options object like so. So my options object is going to have a learning rate of 1. Iterations, we'll just go for, let's say, 5 iterations right now, and I'll do a batch size of 100 like so. After we create the regression, we then have to train our model, which we can do with regression.train. Now at this point, we don't have any code that's going to do any testing or any accuracy validation or anything like that, but let's just run this file. I'll save it and run it just to make sure that we are not going to run into any early errors here. So I'm going to save the file, flip back over to my terminal, and do another node index.js. I don't see any errors here, so this means that we're probably going down a pretty good path. So now that we know that we can successfully train the model, we now need to make sure that we put in some logic in here to gauge the accuracy of our analysis. In order to do so, we're going to use that imnist library again. We're going to call a different function on it. Rather than calling training, we're going to call testing. The testing function is used to load up different feature observations and labels from the test set of data. Remember, in the official imnist database, we get 2 big pools of data. The training set has 60,000 images, and the test set has 20,000. So eventually, we're going to open this thing up. We're going to feed all 60,000 images in and all 20,000 images into the test or accuracy validation. But for right now, we're just going to start out with some smaller values to make sure that we don't run into any early errors. Okay, so we're going to load up our test set of data, and then we will parse it in a very similar fashion to what we did right here. And we will call regression.test with it, and then eventually print out our accuracy rating. So underneath our train function right here, I'm going to first attempt to load up the test imnist data. So I'll say test imnist data like so. This is going to be imnist.testing, and we'll load up the first 100 images. Now I want to again just console log this stuff out and see what the data structure is that we are working with here. So I'm just going to console log it, I'll save the file, and then do another node index.js. So just as before, I can scroll up a little bit here, and you'll see that we have two properties inside of that variable. We've got one called images, and the actual feature observation values are inside of this values property right here. So it's an array of arrays where each inner array is 784 elements long, and it contains all of our different encoded pixel black and white values. So values going from 0 to 255. I can then scroll down a little bit, and I'll see that the other property inside that object is labels, and just as before, it has the values property that has the actual values, or the actual numbers that are displayed in each of those images. Okay, so we're basically working with an identical data structure to what we had before. Now, in this case, I don't think that we need to do any flattening here, because if you actually look at it this time around, we've got array of, you know what, actually we probably do. We do have to map this thing because we've again got this kind of nested array of arrays right here. So I'm going to pull out two different variables here. I'll get a test features. This is going to come from test imnist data .images .values. And I'm again, just as before, going to map this thing, and I'm going to run a flat map on each element in there. So I'll do a map. I'm going to take each image, and I'll do a flat map with image like so. Next up, we'll do the encoding step for our label values as well. So I'll say test encoded labels. This is going to be test imnist data dot labels dot values, just as we had before. And to be honest, we can really just kind of copy paste this entire block right here. We'll eventually refactor this stuff so we don't have duplicated logic, but for right now, we'll just duplicate it so that we know that everything's going to work just fine. So I'm going to take everything from labels down to the bottom of the map statement, and I'll put it onto the end of test imnist data right there. So I should see test imnist data dot labels dot values. Okay, so that looks good. So now the last thing we have to do is take those two variables and pass them to regression.test. We'll say regression test. That's going to get test features and test encoded labels. And then remember, the result of calling test is going to be a single number that represents our percentage accuracy in predicting the correct encoded labels. So I'll assign that to a variable that I'll call accuracy. And then afterwards, I'll print out accuracy is accuracy, like so. All right, that looks like a good start right there. I think that we've basically got everything that we need to start playing around with this and make sure that we can get some reasonable accuracy. As you're going to find very shortly, we're going to end up having to tweak a ton of different variables in here over time and do a little bit of tinkering to eventually get our accuracy to a good spot. The first time we run our analysis, we're going to see some pretty awful accuracy, but eventually after tinkering with our different learning rates, iterations, batch size, all this different stuff, eventually we're going to end up with a pretty good result. All right, now the last thing I want to do is I'm going to go up to my top where we load up our training set right here. You'll notice that we still are only loading up 10 images for our training set of data, which is definitely not enough to properly train our model. So I'm going to change that to 1,000 instead. We're going to load up 1,000 images for our training set. We will train our model, and then we will try to predict the values for the first 100 images inside the testing set. So this is still a very small sample size of the overall set of data that we can work with. We're only working with 1,100 out of a possible 60,000 and 20,000. But let's just start small and we'll kind of work our way up. All right, so let's run this. So I'm going to save the index.js file. I'm going to flip back over to my terminal and do a node index.js like so. And so as you can see, we have a starting accuracy value of 0.08. That means that we are currently correct 8% of the time. Now remember, if we made random guesses, we could guess correctly, in theory, 1 out of 10 times, because there's only 10 possible values. So our baseline accuracy, if we're just making random guesses here, is 10%. So what we have right here is below essentially random guesses. So we can probably do a little bit better than this. Let's take a quick pause right here. When we come back to the next section, we'll start to dial up some of our different values here for the training set size, our different parameters inside of the model itself, and see if we can't boost up that accuracy a little bit. So quick pause and I'll see you in just a minute. We're now ready to start playing around with the parameters of our analysis so that we can increase our accuracy from its current 8% that we're getting right now. So to get started, I think that two places that we can easily start playing around with is probably the number of training images that we're using to train our model. In theory, when we use more data, we are going to get a better fit model. And so hopefully the accuracy would increase. Rather than loading up just 1,000 images, I'm going to update that to 5,000 instead. And then I'll probably update my number of iterations down here as well. So rather than just going through 10 iterations, I'm going to try doubling that and going for 20 instead. We can leave our test number of images being loaded up at 100 because in theory, changing our test number of images is not going to greatly affect our accuracy. It'll probably have some ultimate results, like maybe these first 100 images are all around the character 0 and we do a bad job of classifying 0, but in general, 100 is enough for us to get a signal of whether or not we are going down the right path or the wrong path. So I'm going to save this file with the updated iterations and the updated training set size, and I'm going to rerun this analysis. Now when I rerun it, you're going to notice that this takes a little bit longer to run than it did before. And when it finishes running, we still get a very disappointing accuracy of 8%. Now the fact that we still have an accuracy of 8% here is telling me that something is probably wrong with our algorithm as it stands right now. Anytime that you start changing parameters and seeing unchanging accuracy or essentially no impact on the results of your algorithm, usually it's a sign that something is going very wrong inside of your algorithm. So I think that we need to do a little bit of debugging and figure out exactly what's happening here. Let's take another quick pause. When we come back to the next section, we're going to start up our node debugger again and get a better idea of how we can go through the process of debugging our algorithm. So quick pause and I'll see you in just a minute. In the last section, we just made an update to the parameters of our model, but we still have a really terrible accuracy. So in this section, we're going to do a little bit of debugging and figure out what's going wrong here. To start up my debugger, remember we can run node -inspect-brk like so, index.js. So now when we start this up, we get a little message that there is a debugger listening. To open up our debugger, we'll open our Chrome browser. Remember, this only works with Chrome right now. I'll set a new tab up, and I'll go to Chrome://inspect. Alternatively, a little bit easier to remember is about:/inspect like so. Either one is going to work just fine. So now we see that we can debug our index.js file, which is waiting to be inspected. So I'm going to click on inspect, and I launch into my index.js file. So I don't really have any idea what's going wrong right now, so I'm going to have to do a little bit of exploration to get a better idea of the data that's floating around inside of my model and try to locate exactly what's happening. Now we've already gone through the process of console logging and printing out our features and our encoded labels after we load them up from the MNIST data library. So I feel like that data is pretty much okay. We've definitely checked it out already. And so that indicates that chances are something is going wrong inside of our logistic regression class. That would be my guess. So rather than worrying about going through all these steps right here, I'm going to set a breakpoint next to the regression.train line right here. And we're going to try walking through the gradient descent process and see exactly where our math is going wrong. After setting the breakpoint right there, I can then click the big blue arrow on the top right-hand side to advance execution down to that line of code. Okay, so now I'm at regression.train. I can now step into that function by clicking the little down arrow right here, and then I go into my train loop. So now we can start to inspect the different variables by referencing them on the console down here and get a better idea of what's going wrong. I'm going to advance another couple lines of code and get into our general for loop, eventually down to gradient descent. So I'm going to go forward, forward, keep going forward, and finally I get down to gradient descent right there. So now I want to inspect a couple of the different variables floating around here and get a better idea of what's happening. I'll first start off by looking at, say, batch size. Well, that's a number. How about batch quantity? That looks pretty good. Those numbers look pretty realistic. Our batch size was 100 when we passed it in as an option to our algorithm. And if we are doing batches of size 100 and we have a total of 5,000 records, then a batch quantity of 50 definitely makes a lot of sense. So maybe the next thing we could look at is like our feature slice or our weights or our labels. Let's look at our labels. So I'll say this.labels.print. Well, that definitely looks appropriate. I'll try looking at my weights, this.weights.print. Okay, that looks more or less appropriate as well. You'll notice that I've got 10 columns here because I've got 10 possible label values. Let's try looking at our features. I'll do this.features.print. And when I do that, I start to see probably the source of our problem right here. You'll notice that inside of our features tensor, we've got a bunch of different values inside of here being set equal to not a number. And so this indicates that something is definitely going wrong, probably when we are initially either loading up our features from the MNIST library, or when we try to apply some type of standardization or normalization to them. Remember, at present, when we pass in our features to our class, they come into the constructor, and then we process them with the process features method. We can then go down to process features. And so down inside of here, we go through the process of applying standardization. We then append on the ones column, and then we return the processed features. Now, the fact that I see that the ones are on here successfully is kind of making me think that something might be going wrong during the standardization process. So let's try restarting this debugging thing right here. We're going to set a breakpoint this time on the process features method. We'll walk through that method and get a better idea of what's happening. So I'm going to close the debugger up here at the top left-hand side. I'll then go back over to my code editor, and I can manually put a debugger statement inside of process features. So right after we take in these features and wrap them in a tensor, I'll put debugger so we can stop execution right there and start to watch what happens as we start to go through the standardization process. All right, so I'm now going to again flip back over to my terminal. I'll run the same command as before, so node inspect break index.js. That starts the debugger back up. I can now go back over to the Chrome tab. I'll click on inspect again, and it starts up the debugger a second time. Now, if I scroll down just a little bit, I'll notice that this breakpoint that I just set is still here, so I'm going to unset that breakpoint. And now I can just click on the blue arrow, and that will automatically advance execution until that debugger statement that we put in. All right, so now we're at the debugger. So now let's try looking at the features tensor and see what we're working with. So features.print, and it looks like I've got all zeros in there. Now, this makes sense that it looks like it's all zeros. Remember, every single element inside of here represents a pixel value. The first couple values that you see right here represent essentially the top left of an image. So those first couple values that you see are essentially those pixels right there. And usually in just about every single image that we have, there's never any number that kind of spans up to this top left corner. In addition, the right-hand side of that tensor that we just printed out represents these cells down here, or these pixels down here on the very bottom right-hand side. And so the fact that we see mostly zeros inside that thing doesn't make me that worried. I still am somewhat confident that we are properly loading up data into that thing. So let's now try going through the standardization process and see what's happening. So I'm going to go down with the step over button. I'll go down, and now we're going to go into the this.standardize method. I want to see what happens during standardization, so I'm going to do the little step into function call so we can walk into that function and see what's happening to our features. So I'm going to walk in. Okay, this looks familiar right here. This is where we apply that moments function and get our mean and variance with the goal of ultimately applying standardization. Now I don't want to walk into this function call, so I'll use the step over again. So I'll step over, step over, step over. So now we can inspect our mean and variance and then see what the output of this line right here is. So I can do a mean.print. Okay, well that's zeros, that's fine. I can do a this.variance. Oops, not this.variance, just variance.print, like so. That's better. All right, and so a variance.print, well, there's zeros in there as well. That doesn't seem that bad. So I'm now going to try writing out this entire statement right here and seeing if something is going wrong during that step. So I'll do features.sub mean.div variance.pow 0.5, and then I want to print the result of that entire expression. And so I'll run that, and I see that that is what is producing our not a number values inside there. So it looks like when we go through this standardization process, something is going very, very wrong. Previously, standardization did not lead to any issues, but now we are getting these tremendous number of not a number variables inside of our standardized features tensor. So let's take a quick pause right here. When we come back in the next section, we'll start to investigate exactly why this is happening and try to figure out some type of workaround. In the last section, we saw that our features tensor was getting not a number inserted all over the place. In this section, we're going to do a little bit of work to fix up this problem. All right, so we got two possible solutions here. The first possible solution would be to iterate through our features tensor and see if we have any columns inside there with only 0 values. If we have a column of 0 values, that means that that entire particular feature or that entire column is really doing absolutely nothing to enhance our analysis. And so in theory, we could just remove that entire column and it would have no impact on the outcome of our analysis. In fact, our analysis might actually go faster because now we have to multiply less numbers. The other possible solution would be to change our method of standardization or normalization to make sure that we better account for columns that contain all 0 values. In this case, we're going to go with the second option here, where we are going to put in a little change to our code to better account for columns that have all 0 values. Now, I'll be honest with you, the ideal solution here is probably this first one, where if we see a feature, like a particular column inside the features tensor that has all 0 values, we really should remove it because it's essentially a meaningless column for us. So personally, I think that would be ideal. However, in this case, using TensorFlow to do this is not the easiest thing in the world. So rather than remove those columns, we're going to go with the slightly easier way over here. Now, even changing our method of standardization to better account for those zeros, we're still going to have to use a little bit of a trick here. Again, this is kind of a weak spot in the world of TensorFlow, and kind of removing those all 0 columns or otherwise removing the not a number columns, even if we allowed it to get that far, is just kind of challenging to do. So let me show you what we're going to do. I've got a quick example put together over here. So you'll see I've got some data tensor. I'll call it features instead. You'll notice that the first column on here has all 0 values. So in theory, I want to somehow deal with that first column. Let's first write out the process of standardization, and then we'll see how we're going to slightly adjust it. So I'm going to do that mean and variance coming from tf.moments along the 0 axes. So now normally to do standardization, we would say data or features sub mean div variance pow 0.5 like so. Now you'll notice this is something that we discussed way long ago in very brief passing. When we're in the browser is going to treat division by 0 slightly differently than when we do division by 0 in the Node.js runtime. And this is solely because of the different environments that TensorFlow uses to actually do these numerical calculations. So in this case, our variance, if we just print it out by itself, here's the variance right here. You'll notice that the first element inside that variance tensor is 0. So technically, in this standardization that we're doing right here, the first column, like that element and that element right there, are the subject to division by 0. But in the browser decides to treat division by 0 and turn it into a 1. Whereas inside the Node.js runtime, it technically goes to infinity, and then TensorFlow does some stuff on that value that turns the infinity into not a number. So just so you know, when we do this quick example over here, you're not going to see the same result that we're going to technically see when we run this in Node. Okay, but nonetheless, I hope you can understand, yeah, we've got variance with 0 in the first element. So in this case, we would want to somehow normalize that, or I shouldn't even say normalize here. We want to somehow just deal with that first element being 0. It'd be really nice if we just replaced it with a 1, because if we then did division by 1 to the 0.5 power, that's still 1. So technically, we'd just be dividing by 1 here. And that's essentially what we're going to do. Inside of our variance tensor, anytime that we see a 0, we're just going to replace it with the number 1. That's going to have absolutely no effect on the actual output here. It's just going to make sure that we don't end up with those not a number variables. Okay, so how are we going to get 1 inside of the variance tensor? Well, this is the part where I had mentioned we're going to do a little bit of a trick here. Again, this is something that's just harder than it should be with TensorFlow, but this is just kind of the situation we're in. So here's what we're going to do. I'm going to take the variance, and I'm going to cast it to type bool, like so. Now remember, this cast right here essentially tells TensorFlow to change the type of all the values inside the tensor to type Boolean. So you can see that after casting it to type bool, all the values inside there go to 0 and 1s. And then as a quick reminder, we could put in variance again. So you can see any non-zero value gets set to 1, any 0 value remains at 0. So now with this, I'll chain on to the cast operation a logical not. That's going to essentially flip all the zeros to 1 and 1s to 0. So now that's the output of it right there. So now we can take this logical not, add it to the original variance, and essentially in any location where we had a 0, we will now have a 1. So that's the trick here. We're basically getting a tensor that has 1s in place of all the zeros. We're going to take that thing and add it to the original variance. And it's just going to find all the 0 values inside a variance and raise them up to 1. So that when we later do division by the variance, we're not going to have division by 0. We'll instead have division by 1. Now, the last thing we have to do on here after the logical not is cast it back to a float 32 like so that we can actually use it inside of our standardization operation. Okay, I know this is a nasty workaround. I know it's not super pretty, but again, we're kind of at the mercy of TensorFlow here. Dealing with these not a number values is kind of a weak spot in the library right now, and hopefully this gets improved at some point in the future and we won't have to do this little janky workaround. So let's take a quick pause right here. When we come back to the next section, we're going to implement this little trick back inside of our standardized function. So quick pause and I'll see you in just a minute. In this section, we're going to implement that little trick that we just discussed to take the variance, find all the 0 values, replace them with 1, and then add that onto the original variance. So let's get to it. I'm going to flip back over to my code editor. I'm going to find where we had that original debugger statement inside of process features and remove it. I'm then going to go down to the standardized function right here. So right before we do our this.mean and this.variance, I'm going to create a new variable right here where we create a new tensor that's going to have essentially just these quick little flips of those zeros into ones. So I'm going to say variance.cast bool. I'll do a logical not, and then I'll cast that back to a float 32 like so. And I'm going to assign that to a variable that I'll call filler. I'm calling it filler because I'm trying to fill in all the 0 values with 1s instead. That's pretty much all we're doing here. And then I'm going to make sure that when we assign variance to this.variance, I'm going to add the filler on. So now inside of variance, any location where there is a 0 will now be placed with the value 1. That's it. That's all we're doing here. Now, the last thing we have to do is make sure that in the last line of code inside of here, you'll notice that we are doing our calculation with the variance variable as opposed to this.variance. The variance tensor has been unmodified. It has not had any filler added into it, essentially. So I need to replace variance right here with this.variance, like so. Okay, so that's pretty much it. So now we should be able to rerun our analysis and see some more realistic result come out of it. So I'm going to first flip back over and close down this debugger. I'll then go back to my terminal. You'll notice that when I close the debugger, I automatically got kicked back to the command line. So now I can do another node index.js. And now we should see a much more realistic result for our accuracy. In this case, I see an accuracy value of 0.87. So we are 87% correct. We have a test size of 100 values. So in this case, we guessed correctly 87 times out of those 100 different values that we tried to make a guess with. So this is looking pretty good. This means that we're going down the correct path now. We've now got 87% accuracy. Let's take a quick pause right here. When we come back to the next section, we're going to make a couple more tweaks to raise our accuracy even higher. So just a quick pause and I'll see you in a minute. In this section, we're going to play around with the parameters of our analysis a little bit more and see if we can get some better accuracy than the 87% that we got just a moment ago. So the easiest way to increase our accuracy is going to be to increase the number of records that we use inside of our training dataset. So back over here where we say in this training, we're currently loading up just 5,000 records. Let's try loading up all 60,000 records. So we're now going to train our model with 60,000 different images. That should, in theory, allow us to account for a lot more variations and have better accuracy when we finally try to apply it to the testing set down here. Now, at the same time, to try to get a better idea of what our accuracy is, I'm going to also increase our testing pool to 1,000 at the same time. And that should give us some more statistically significant result than the previous 100 that we had before. All right, I'm going to save this file, and then I'm going to run our analysis again. Now, quick thing before I run this, I want you to know right now, I expect this analysis to crash, okay? I'm going to expect you to get an error message here. If you don't, that's totally fine, but if you do, don't worry about it. We're going to immediately fix that error up. Okay, so I'm going to run this. Now, this analysis is going to take a little bit longer. If you want to see something kind of interesting, you can open up the activity monitor on Mac OS. On Windows, you could open up your task manager, and you can go to the memory tab and kind of take a look at how much memory Node is using. And you're going to see that it's kind of growing very quickly until at some point in time where JavaScript decides to just entirely crash. We get an error message here that says JavaScript heap out of memory. So essentially, we tried to load up a tremendous amount of data, and the Node.js runtime said, sorry, this is too much for me to deal with, I quit. And we got this crash that you see right here. Now, this error message is totally fine. We can fix it very, very easily. Essentially, when you run JavaScript by default, our heap only gets 1.8 or so, I think it's maybe 1.7 gigabytes allocated to it, which is actually not quite enough to deal with the size of analysis that we are doing here. So we can fix this error by just allocating more memory to the JS runtime, which we can do quite easily by just adding on this very simple argument that you see right here. So we'll say node -- max old space size equals 4096, and then the file that we want to run, just like before. All right, so I'm going to copy that, and I'm going to run that command now. Let me put that on one line so you can see it easily. There we go. So now we're going to run this instead, and we should no longer see that out-of-memory error message. Once again, you can open up your activity monitor or your task manager on Windows and look at the memory consumption, and you're going to see Node just kind of spiral out of control here to a degree as it uses more and more memory. There it starts to go. Now, you still might get a out-of-memory error message here, even with that additional argument. If you see that message again, if you get that error again, that's totally fine. I'm going to show you an additional optimization in just a second. You can see right here, Node is now going up to 7 gigabytes, which is a tremendous amount of memory. I have a 16 gigabyte machine right here. So my machine is dealing with it a-okay, but if you are sitting at like 8 gigabytes or even 4, you might see an error message by this point. I think that at this point, the kind of lesson that we're learning is that, we've got some memory consumption issues here, and it would be really nice to figure out some way to optimize this. Now, flipping back over, I see that my accuracy has gone up to 0.876. Which is a little bit better than what we had before, but certainly still not quite the result that we are looking for when it comes to accuracy. So I think we have two issues here. We have kind of this persistent memory issue that we're running into. You might have seen an error message before this analysis even completed, and at the same time, an accuracy of 87% for this MNIST dataset is actually not the best in the world. We should definitely be able to get over at least 90% without a lot of trouble. So we still have a good bit of work to do here. We have to address the performance, and we have to address the accuracy. Let's take another pause. In the next section, we're going to figure out how we're going to tackle both of these issues. In the last section, we saw that we're currently running into two issues with our current analysis. On the one hand, we have a relatively low accuracy, and on the second hand, it looks like our program is just taking up more and more memory over time. In this section, I want to address the memory issue. In this video and the next couple, I'm going to teach you a little bit about how you can optimize memory usage inside of a Node.js program, in particular when we're loading up vast amounts of data. In order to teach you how to manage memory like this, I'm going to close out my current index.js file and the logisticregression.js file. We're going to write a little bit of test code inside of a new file just to help you understand how to optimize memory usage. So inside the multinominal logistic regression folder, I'm going to make a new file called memory.js. So inside of here, we're just going to put a little bit of test code just to understand memory usage. At the very top of the file, I'm going to require in the Lodash library like so. After that, I'm going to define a function called loadData. Inside this function, I'm going to create a new variable called randoms. And I'm going to assign it a gigantic array, a very large array. So I'm going to use a Lodash function called _.range, and I'm going to call it with arguments of 0 and 999,999 like so. That's a total of 6 nines, or essentially 900,999. Okay, so after we do that, I'm then going to return randoms. And then after that, I'm going to get out of the function. I'm going to create a new variable called data, and I'm going to assign it the result of calling load data. And then finally, at the bottom, I'm going to put a debugger statement, which we're going to use the node inspector. We're going to use node inspector to kind of execute this file and get a better idea of what's going on inside. Now, the first thing I want to do is make sure it's really clear what this range function right here is doing with a very quick example. If I flip back over to this little code editor, I can call _.range, and I'll pass it 0 to 10. The range function is going to create a new array with elements from 0 up to, but not including, the second argument inside of here. So the range function that we're calling right here is going to create a new array with elements inside of it from 0 all the way up to 900,000 and blah, 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 blah. And then we're going to eventually return it and then assign that to data. Okay, so now that we understand the code inside of here, I'm going to launch this file using the node inspector. We're going to debug this thing, and I'm going to show you how you can understand how memory is being allocated inside of a Node.js program. So to do so, I'm going to flip back over to my terminal. I'm going to make sure that I see that memory.js file right there, and then I'll run node --inspect brk memory.js. So no more index.js, now we're doing memory. So I'm going to run that, and then that will start up the node inspector. So I'm going to flip back over to the node inspector tools. Remember, you can get here by opening up your Chrome browser and navigating to About, Inspect, like so. Okay, so I'm going to inspect that memory.js file. And now I'm inside of memory.js. I'm going to advance execution of this program all the way to that debugger statement so that we will call load data, create that array, and assign it to the data variable. To advance execution, I'll click on the blue arrow up here. Okay, so just like that, we have now created a gigantic array and assigned it to the data variable. So now if I hover over data, I can look inside of here and see that it has all those different numbers inside of it. So now the next thing I want to do is run a memory report, or what's called a memory snapshot. This is going to be a report that's going to tell us exactly how Node has allocated memory inside of our program. To do so, I'm going to find the memory tab at the top. I'm going to make sure that I have heap snapshot selected, and then I'll click on take snapshot down here at the bottom. We're going to very quickly see this snapshot created on the left-hand side, and then after a couple of seconds, it's going to open up a new window that looks like this right here. So this is the report that's going to tell us how memory is allocated inside of our program. You'll notice that on the top table right here, we have a column called constructor. This column is essentially telling us about all of the different types of objects that have been created inside of our program. On the right-hand side, we can then see the memory usage, or essentially how much memory each of those different things is taking up. Now let's take a quick pause right here. When we come back to the next section, we're going to dig into this report a little bit more, and I'm going to point out a couple of interesting things about it. In the last section, we took a memory snapshot of our little memory.js file. I now want to take a look at this report and help you understand the values inside of here and get a better idea of how JavaScript treats memory. Now, the first thing I want to tell you is that based upon a couple of very random factors, you might see some slightly different results inside this report than I do. So right now, I want you to click twice on the shallow size column. That's going to sort that column from largest value to smallest. For me, I see the largest value is array right here, and I have a shallow size of 9.4. And then for the second entry, I see string with 2.1 as the value for shallow size. It's entirely possible that you might see a shallow size of around 16 or 18 for array, and you might also see string as the first entry inside of here. If you see that, it's totally fine. Again, a couple of random factors are going to affect the exact output that you see inside this report. Now, having said that, I want to show you a little bit more inside this report. We're going to make a quick change to the memory.js file. We're going to rerun the report, and then I'm going to point out a couple of interesting things about the data inside of here. So let's get to it. All right, so inside the report, the most important column that you'll see is the constructor column. This report tells us about all of the different types of objects that have been created inside of our program, and then it will list out their memory usage. Shallow size over here is the bytes that is used by each of these different types of objects. So right now, the different arrays inside of our program are using 9.4 megabytes of space. Even though you and I think that there's only one single array inside of our program, like there's only that one right there that we had created, behind the scenes there's actually many other arrays that get created to make our program work the way we expect. So if I expand array, I'll see that there are many other elements inside of here. The first element, right here, is the array that you and I created, and it has a shallow size of about 8 megabytes or so. There are many other arrays that are in use to make our program work, but we don't really care about those too much right now. If you click on the largest element inside of this nested array, it will have a shallow size of 8 million or so. You'll notice this bottom tab down here that says retainers. And then inside of this list, one of the values inside of here is data. Data is the variable that we had assigned that array to. Now again, if you don't see data inside this list, you can try clicking on the second element and you'll probably see data reflected in there. Again, depending on a couple of random things, you're going to see a slightly different report than me. Okay, so we've now kind of broken down this report, but I haven't really said anything about how we can use this thing to understand our memory usage just yet. So I'll tell you what, I'm going to take a quick screenshot of this report right here. We're then going to make a quick change to the memory.js file, and then we're going to rerun the report, and I'm going to point out a couple interesting changes between report 1 and report 2. And by pointing out these changes, it's going to help you understand some very basic concepts around memory usage in Node. So I'm going to take a screenshot of this thing. Okay, I've now got a screenshot. Now I'm going to close the inspector. I'm going to go back over to the memory.js file, and I'm going to make a small change to this thing. I'm going to find the return random statement right here, and I'm going to comment it out. So now, just like before, I am creating a very large array, but it never gets returned from the load data function. We still call load data, and we still assign the results of that to the data variable. Because we are no longer returning anything from load data, the data variable is going to be undefined. All right, so I'm going to save this file. I'm going to rerun this program with node inspect memory.js. I'm then going to start up my inspector a second time. I'm going to advance execution to the debugger statement. And then finally, I'm going to go to the memory tab and take a snapshot. Okay, so I've now got two separate snapshots. Now I'm going to pull up the screenshot that I just took. Here it is right here. I'm going to sort this new report really quickly by shallow size, and then we're going to compare the two reports. Okay, so down here is the original report, and here's the new one right here. Now right away, you'll notice that the array entry went from occupying 9 megabytes of memory down to a now present 1.2 in the new report. So it looks like with that very small change that I just made, my program is now making use of far less memory to store all of those array values, or all those randomly generated numbers, essentially, that we created with the range function. All right, now that's a really important thing to take notice of. Let's take a quick pause right here. In the next section, we'll come back, and I'm going to tell you why it is so important to understand why our memory usage went down when we did not return that array anymore. So quick pause, and I'll see you in just a minute. In the last section, we ran two separate memory reports on the memory.js file. And we saw that when we commented out the return statement for that really big array, we no longer had a big allocation to the array type inside of our program. So in this section, I want to help you understand exactly why that's the case, because understanding why our memory usage went down by quite a pretty good amount is going to help you understand how to optimize our current logistic regression file, specifically some stuff that's going on inside of index.js. Okay, so we saw memory usage go down once we commented out return randoms. The reason for this is the JavaScript garbage collector. The garbage collector is a process running behind the scenes that is constantly monitoring your program. It's looking at all the different values and variables that exist inside of your program. If it thinks it can, it's going to try to reclaim memory that has been used by your program. So as we can see between the two distinct reports here, at some point in time between program number 1 and number 2 in the second version, the garbage collector kicked in at some point and decided to reclaim all the memory that was in use by that very large array that we had been created. So the real key here is to understand why the garbage collector kicked in and when it's going to kick in and how we can utilize that to save memory inside of our program. So it's pretty straightforward, but simultaneously kind of confusing. When you look at our program right here, you'll notice how we create this array and then we assign it to a variable. When we assign a value like an array or an object or a number or a string to a variable, we are essentially creating a reference to that value. So we would not say technically that the randoms variable holds an array. Instead, we would say that the randoms variable has a reference to the array. We can reference the randoms variable right here, and it will essentially point us in the direction to the array and where it sits in memory. So long as we have an accessible variable that points at a value like our array, our string, or number, or whatever, the garbage collector is not going to attempt to clean up that object. But as soon as our program gets to a state where we can no longer somehow reference a value that has been created, the garbage collector will kick in and attempt to clean up that value. Now, just putting that in simple English doesn't always make a lot of sense. So let's walk through a quick example here. You can kind of imagine that when our program starts up, we get into the load data function, where then inside of here, we create the array. While we are inside of this array, we have access to the randoms variable, and the randoms variable provides a reference to that big array. So because we have a reference to that array, the garbage collector does not clean it up. However, as soon as we exit the load data function, as soon as we get out of this thing and we go back to like execution right here, there is no way whatsoever for you and I to somehow get a reference to the array that had been created. Think about it. If we did something like console log randoms, we would get an error message because randoms was only defined inside of the inner scope of load data. So once we get out of load data, there is no way, shape, or form for us to get a reference to that big array anymore. Because there's no way that you and I can access that value, JavaScript says, or the garbage collector to be more precise says, oh, hey, you can't get that at that array? Well, if you can't use it, I'm going to clean it up. And that's the entire rule. That's all it is. So long as you and I keep a reference to a value, the garbage collector is not going to clean it up. As soon as we can no longer get at that value, as long as we can no longer somehow refer to it, either through a variable or maybe something like, some other variable dot my big array. If we cannot do any type of reference to that big array, the garbage collector will kick in and it's going to reclaim all that memory. And all the values that were created inside that range, poof, magically disappear. So to put this in kind of a diagram format, which might be a little bit helpful, we can kind of visualize the two executions of our program that we did. This is a diagram of the memory usage over time inside of the original program we did, where we were returning a reference to the array. So inside of there, the program started up right here. We went along and eventually we executed the load data function. Inside there, over a very brief period of time, we allocated a ton of memory to that really big array. So we created that array and then we returned it. When we returned the array, when we returned randoms, we then assigned it to the data variable. And so we had a reference to the big array. Because we still had a reference to it through this data variable, the garbage collector never kicked in and never tried to reclaim that memory. And so our memory usage for the rest of the time was more or less constant until we ran that memory report. Now let's consider the case in which we did comment out the return statement. So with this form right here, once we leave load data, we no longer have a reference to the really big array. And so the diagram of that would look a little bit more like this right here. So now in this case, we start off, we call load data, we create the big array, and we now have a lot of memory in use. We then, just about instantaneous later, return from the load data function. And at that point in time, the garbage collector sees that we no longer have a reference to the really big array. So it kicks in, reclaims all the memory, and we go back to this baseline memory usage, which is the current report that we have inside of our inspector right here, where we do not see any big usages of memory by the array constructor or the array type inside of our program. So that's pretty much it. That's the big lesson. That's the most fundamental root thing to understand. You just have to understand that if we try to create a very big array or a very big object or some big value inside of our program, so long as we carry a reference to it inside of our program, the garbage collector will not kick in and that memory is going to continue to stay in use. Okay, so with that in mind, let's take a quick pause right here. There's one more quick thing I want to mention about the report that you're probably curious about, specifically shallow size versus retained size. So quick pause, and we'll cover that in the next section, and we'll talk about how we can use this knowledge to refactor our algorithm to be a lot more efficient in its memory usage. So quick break, and I'll see you in just a minute. In the last section, we spoke about how the JavaScript garbage collector behaves. We're going to use that knowledge in just a minute to refactor our algorithm, but before we do, I want to point out one really quick thing that you might be curious about. Inside of our report, we have the shallow size and retained size, and you might be curious about what the difference between the two is. Well, the difference between the two is entirely related to this entire idea of garbage collecting working around our references. So remember, we just spoke about the garbage collector, and we had said that so long as we have a reference to a value, it is not going to be garbage collected. Now, to help you understand the difference between shallow and retained over here, I uncommented return randoms. So I uncommented that line between the last video and this one, and I reran the memory report. So I ran this thing again. I did it between videos just to save a little bit of time. So now you'll notice that my top usage of memory is still for this array thing right here, and it's using 8 megabytes worth of memory. So this is basically back to the earlier situation that we were in before. Now I want to point out something really interesting inside of here, something that's going to help you understand the difference between shallow size and retained size. You'll notice that we have array right here. So there's something inside of our program called an array that's using, in total, 9.4 megabytes of memory. Or to be more precise, the big array you and I created is using the 8 megabytes right there. Now, in addition to that lowercase array in parentheses, you can go down a couple entries and you might notice that there's something inside of here called capital A array as well. And if you look at its memory usage, after we expand it, for the first entry, you'll notice that it has a shallow size of 32 and a retained size of 8 megabytes. So if we can somehow figure out what the difference between lowercase array and capital A array is, maybe it will help explain the difference between shallow size and retained size. Okay, so let's get to it. Quick diagram. Now this is a very simplistic diagram of computer memory and a very simplistic way of explaining the difference between the parenthesis array and the capital A array. The capital A array, the one that's using much less memory, this one down here, is the instance of a memory class or a memory object. I'm using the term class here, but remember that JavaScript does not truly have classes. Nonetheless, I'm going to use the term just for simplicity's sake. The capital A array thing that you see are instances of memory objects inside of JavaScript. They have all those very familiar methods that you're used to, such as push and pop. In addition, this array internally has a reference to a data structure that is sitting in memory that is actually holding our big list of values. So when you work with the JavaScript array, you're technically working with kind of two separate things. On the one hand, you've got the array class that has all the methods associated with it. And then on the other hand, you've got the actual array in memory that's holding all of our values. So that's the reason that we see the two copies or the two separate line items here for array. One, this one up here, is the data structure in memory that is holding the actual values. The other one down here is essentially the instance of the class that has all those different methods associated to it. The capital A array also has the reference to the actual array data structure. So how does this relate to shallow size and retained size? Well, essentially, the shallow size that you see is the memory that is in use by this very specific line item right here. In other words, the instance of array that we are making use of only is using 32 bytes. That's all it's in use by that thing. However, that instance of array has a reference. It has a reference over to this big data structure that has all the actual values inside of our array. Because this thing has a reference to that other array, we would say that it has a retained size of 8 megabytes because it has a reference to that other one. Now, why is it called retained size? And as a matter of fact, you'll notice when I kind of hover over that thing, we just saw that data appear there very quickly. So you can see, yeah, like without a doubt, it has a reference to that big array. So why do we call it retained? Well, it's essentially related to all the stuff that we just discussed around the garbage collector. Remember, so long as we have a reference to a value, the garbage collector is not going to clean that value up. So in this case, our array instance has a reference to 8 megabytes worth of some array in memory. Because this array instance has a reference to that, this array, because this array right here has a reference to that in-memory array, the in-memory array cannot be cleaned up. And so we would say that because this thing right here just exists, it is retaining, in addition to itself, in addition to its 32 bytes, it is also causing 8 megabytes worth of memory to sit around in memory, or 8 megabytes to sit in use as well. So that's pretty much it. That's the difference between shallow size and retained size. Shallow size is saying this object takes up 32 bytes. Retained size says this object has a reference that is causing 8 megabytes worth of memory to be unreclaimable at the same time. So if we wanted to somehow optimize memory inside of our program, we could look at this retained size and say, hey, anything with a really big retained size might be holding on to a reference to a very large data structure. And so we could essentially kind of hunt the thing down a little bit and find out why we have, some array right here that's trying to use up 8 megabytes. Okay, so with that in mind, let's take a pause right here. When we come back to the next section, we're going to finally apply all this knowledge and learn how we are going to do a refactor to our index.js file to dramatically decrease its memory usage. So quick pause, and I'll see you in just a minute. In the last section, we got a better idea of how the JavaScript garbage collector behaves. I now want to try to apply this newfound knowledge and figure out if there's some way that we can reduce the memory usage inside of our program. All right, now to get started, I'm going to delete that memory.js file because I don't really need the code inside there anymore. If you want to, you can keep a backup of that file around so that you just have a note of what we did here. In addition, I've already gone ahead and closed down the memory profiler that we had open in the last video. Okay, so I now want to take a look at the index.js file and the logistic regression file. And between these two files, I want to figure out whether or not there's some location where we might be able to do a refactor to somehow decrease our memory usage. Now, the first lesson is anytime we try to do a refactor like this, we need to first do a memory snapshot so that we get a baseline or a benchmark of what our current memory usage is before we start fiddling around and start trying to refactor anything. So I'm going to put a debugger statement somewhere into my code. I'm then going to start up the node profiler and take a memory snapshot, and then I'll take a screenshot of it or otherwise just save the report so that we can compare back to it later on after we do a refactor and make sure that we did in fact get some improvement. Now to get started, I'm going to open up the logisticregression.js file. I'm going to go down to my train function, and then right after the inner for loop right here, I'm going to put in a debugger statement like so. So why am I putting a debugger right here? Well, essentially, if you think about the entire life cycle of our program, we've got kind of two distinct phases, or maybe three. We've got the phase where we do some initial data loading. We've got the phase where we train our model. And then finally, the phase where we load up our test data and do a quick test with it. And so it seems to me like by putting a debugger statement right here, I'm essentially getting a kind of a halfway mark inside of our program. I've got a kind of point here where we've already loaded up some data and we've started our analysis. And so this would be kind of a good intermediate place for me to take a kind of memory snapshot before I go all the way down and finish running the entire program. I want to see if there's some way to optimize the first initial data loading process here. And so that's why I put the debugger statement right here, because by this time I have ran my first iteration of gradient descent. I can then take a memory snapshot and get a good idea of what's happening during more or less the first half of my program. Okay, so I'm going to save this file, and then I'm going to go back over to my terminal and start up Node with that inspect breakpoint argument. So I'll say node inspect brk, and I'll also put on that memory usage thing. So I'll say max old space size equals 4096, and I'll do index.js. Okay, so that started out the debugger. Now, one quick thing I want to mention here, when we do this memory snapshot and we try to run all this stuff, if it takes too long to load up, you can come back into the index.js file and reduce the training set size to something like 20,000. You'll notice that I already did that just so that you don't have to sit around and watch my computer like chomp away at this stuff forever. So I already reduced the size right here just to get this process to go a little bit faster. Okay, so I'm now going to go back over to my inspector. I'll open this thing up. I'm then going to hit the blue button to progress all the way to the debugger statement. Now it's going to take a minute or two to run here. Maybe not a minute, but at least like 10 or so seconds. Okay, there we go. Now, as a reminder, if it takes your program too long to get here, if it seems like it's not progressing, or if you get an error, just go back and reduce the training set size. Okay, so now that we are here at this point, I want to take a memory snapshot. And again, this is essentially our benchmark, our baseline. So I'm going to go to the Memory tab, and then I'll hit Take Snapshot. Now, taking this snapshot definitely takes a little bit longer than it did previously, because we've got a lot more memory in use here than we did before. All right, so I'm going to sort by shallow size like so. And then I'm going to immediately just take a screenshot of what I see. So that's kind of my backup, so that if we start to do any refactor, I kind of want to improve upon the numbers that I see right here as far as memory usage goes. Now I'm going to expand array right here, and I'm going to take a look at a couple of the different entries inside of here and try to get a better idea of what's making use of a lot of memory inside of our program. So I'm going to click on the first element right here. It says internal array, no preview is available. Chances are this is some like internal, yeah, take a look at that. So it's a bunch of like kind of internal stuff to our program, something that's probably not relevant to us. So I'm going to skip on down to the object elements entries here. All right, now when I click on the first object elements here and I look at the retainers tab, this is starting to look pretty interesting to me and pretty familiar. So you'll notice I've got features right here. So what I see right here, if I hover over it, I might get a preview. Nope, not going to. Let's try expanding it. Maybe I can get a preview here. There we go. So I got the preview, and now I can look inside of here. This is essentially my features array, the features array that we had created inside of our index.js file. So this one right here. So it looks like one of the largest consumers in memory in our program as it stands right now is just that features array that we have inside the index.js file. So that's kind of an interesting thing. I want to keep that in mind for just a moment. Now I'm going to go to the next element here. I see encoded labels. Okay, well that's definitely the encoded labels that we assign right here. And I'm going to look at the next one, and this is where things start to get a little bit more interesting. So on this third object elements right here, quick aside here, remember you might be seeing output very different than what I see, but just kind of roll with this for just a little bit. On this third object elements, you'll notice that I have values, images, and I also have inside of here something called imness data. And then if I go to the next entry, I have values labels. So I see values images and values labels. So what are these two entries right here? These two entries are the initial data sets that we loaded up with the imness training function call right there. So when we first enter the index.js file, we call imness training, and we load up those gigantic data sets. Now, quick question for you. What happens after we load up that data? Well, immediately after, we map over imness images values, and we produce a brand new array of values, brand new, completely unassociated with the original imness data value. We also map over imness labels values. We map over that thing and produce a second array of values, completely new and original values that are completely disconnected from the original data inside of imness data. We then take features and encoded labels and we pass it off to logistic regression. Now here's the key part. After we do that mapping statement right here and pass features and encoded labels off to logistic regression, is there any point, any reason whatsoever for us to maintain a reference to imness data? The answer is no. After we do these two mapping steps, we consume the values that are inside there, we process them, and we return some new values based upon what we saw inside of imness data. But after features and encoded labels, there's no longer any reason whatsoever to hold on to a reference to imness data. So if we could figure out some way to convince the node garbage collector to release the reference on this big, gigantic training set of data, then we could knock off two of the largest consumers of memory inside of our program. They're definitely not the largest, not by any long shot here, but two of the largest consumers of memory inside of our program. We could somehow figure out a way to get these things essentially deleted. So that's what I want to do. Let's take a pause right here. When we come back to the next section, we're going to figure out some clever way to make sure that after we make use of imness data, we can essentially release that reference and not hold it around in memory anymore. Okay, so quick pause, and I'll see you in just a minute. In the last section, we took a look at the memory usage inside of our program, and we very quickly realized that we could probably get away with somehow releasing the memory stored by this imnist data variable right here, that gigantic array with all of the training values, because after we do the mapping steps, we don't need that thing anymore. Now, as a quick reminder, I already took a screenshot of this little tab right here, that little report. So we're going to do a refactor, and then we're going to compare the output that we have right here with the new refactored output and see if we did in fact reduce our memory footprint. So I'm going to close the profiler, and then I'll go back over to my index.js file. Okay, so the idea here is we want to somehow release our reference or our hold on this variable after we have used it. So in order to do so, essentially we're going to do the same thing that we saw inside that memory.js file. We're going to create a function where we call imnist.training and get a reference to this big, gigantic array of data. We'll then do the mapping stuff, we will return the mapped values, and then we will exit the function. And when we exit the function, we're going to make sure that we do not somehow hold on to a reference to imnist data. As long as we do not hold on to a reference to it, the garbage collector is going to kick in and make sure that that big, gigantic array, this thing right here, is going to be cleaned up. So to do so, basically all we have to do is wrap this thing inside of a function. So I'm going to call this load data, just like we called it inside of the memory.js file. I'm going to close the function down here after the two mapping statements. I'm going to indent all this stuff, and then after we do the mapping, I'm going to return features and labels. And labels in this case is going to be the encoded labels variable, like so. So now after we define that function, I'll call load data. I'm going to destructure features and labels. And then I'm going to take features and labels and pass them into the logistic regression class. So here's features, and I'm going to rename encoded labels to be simply labels, like so. And that's it. That's all we had to do. So now in theory, we call load data. We load up all of our training data. This is going to be a gigantic array with a ton and ton of data inside of it. We're going to consume the values inside there. Features and encoded labels are going to be two completely brand new arrays that do not contain any references to the original imnist data. We then return those two arrays. And when we do so, we no longer carry any reference to this imnist data variable or this imnist.training array anymore. And because we no longer have a reference to it, the garbage collector should kick in and clean up that gigantic array of data. All right, so I'm going to save this file, and then we're going to run our program again with the same conditions as before. So still doing the node inspect breakpoint. We're going to open up that memory profiler. We're going to take another snapshot, and then we're going to compare our memory usage between the two. So let's take a quick pause, and we'll take care of that in the next section. In the last section, we introduced the load data function to release our reference to the imnist data training set. So now I'm going to flip back over to my terminal. I'm going to run the node inspect breakpoint command again. I'm going to go to my remote target inspector right here. I'll open this thing up. I'm going to resume execution with the blue arrow to go to the debugger statement that we have inside of our train function right here. I'm going to wait just about 5 or 10 seconds or so. And there we go. So now I'm at the debugger statement, and I can take another memory snapshot, and we can figure out whether or not we reduced our memory usage. So I'm going to flip over to the memory tab. I'll take a snapshot. Here it is. And I'm going to sort by my shallow size, like so. So now I see that my top consumer of memory is still array, which is to be expected. I'm going to pull up the original or the screenshot of the report that I did just a moment ago. Here it is right here. And now we can compare some of the top entries. So right away, I see that array right here is dramatically smaller than it was, or is now dramatically smaller than it was before. In fact, just about half. So I see that my array memory usage went from 281 down to 141, which is definitely a good improvement. You'll also notice that it looks like the array right here has dropped from 20 down to about 1.5 right here or so. I can now look inside of here, and I should be able to look at the different object elements, and I'm not going to see anything inside of here that makes a reference to imnist data or images, values, anything like that. Now the first element that I see right here, I see two labels, like labels and labels right here. The reason I see the two is that's the encoded labels. So we take encoded labels, we take that array right there, and we assign it to a property on this object called labels. And then later on, we assign it to another variable right here called labels as well. So that's why we see labels in there twice. Now I can go to the next one. I see features. I see features again for the same reason. We have the object right here, features, and features as a variable named out here as well. That's why we see features 2 times. And then we can basically keep on looking down here, and we're not going to see any other big sources of memory usage by anything called features or labels. And in fact, I don't immediately see anything inside of here that's at all related to the original data set. So I would say that's definitely a good improvement. I think that we definitely reduced the memory usage of our program in a very significant way. Now, a quick thing to remember here is that for these examples that I've been giving you or showing you, I've only had the 20,000 records being loaded. So in theory, the memory that we just saved is not just that amount, it's 3 times that amount, because ultimately we're going to use 60,000 as our training set size like so. Okay, so I would definitely say that that was a good success. However, it looks like we still do have a couple of records inside of here that are rather large. Labels and features are 2 entries that we're probably not going to be able to meaningfully reduce over time, because we just plain need those things in order for our class or our entire program to work correctly. But when you start to go down a little bit further here, you'll notice that, like say right here, I can scroll down to the bottom and I'll see a mention of TensorFlow. So some of the records that you're seeing a little bit lower on down here are allocated to TensorFlow and all the data that is sitting inside of our different tensors. So let's take a quick pause right here. When we come back to the next section, we're going to start taking a look at how we can now optimize the data or the memory usage of the TensorFlow library as well. And don't worry, the TensorFlow stuff is going to be a little bit easier than the stuff we've done so far. So quick pause and let's get to it. In this section, we're going to go through the same type of profiling process to get a better idea of how much memory TensorFlow is taking up. So to do so, I'm going to go back over to my logistic regression file. I'm going to find the debugger statement that I put inside of the train function. So here it is right here, and I'm going to delete that thing. I'm then going to go back over to the index.js file, and I'm going to put a debugger in right after we finish the training call. So right after we finish training, I want to do another memory profile, and I want to see how much memory TensorFlow is taking up. And then we'll start to investigate how we can improve the memory usage of TensorFlow. Quick tip, we're going to do a dramatic decrease in our memory usage here, tremendous, absolutely huge, by doing a couple tiny changes to the TensorFlow side of things. Okay, so I'm going to save this file, and I'm going to again run my program with node inspect breakpoint. All right, I'll inspect this thing. One other thing I want to mention here, well, let me do the advancement there. That's better. One thing I changed here was I increased my training set size up to 60,000. So now we're going to be looking at some very real use case memory usage here. Might end up being rather large memory usage. All right, so this is going to take a second or so. So I'll tell you what, I'm going to do a quick pause between now and the next section. I'm going to let the thing hit the debugger statement, and then I'm going to take a snapshot, because taking the snapshot is going to take like 20 or 30 or 40 seconds or so. So another quick pause. When I come back to the next section, we're going to take a look at the snapshot that is generated. Okay, I just finished running my snapshot, and I've now got all my memory report put together here for an entire run through the training function inside of our logistic regression. So now we can take a look at the output here and get a better idea of what is now using a lot of memory inside of our application. Now, before we start looking at the shallow sizes or anything like that, I want you to take a look at some of the values next to array, object, and tensor. You see how there's the x 120,315 right there? That means that our application has created 120,000 different tensors. That's a lot. That's a lot of tensors. When you expand this thing, you can scroll through a couple, well, a lot, and at a certain point, you'll notice that it says a couple buttons right here. It says show all 120,000. So no two ways about it, we have created a tremendous number of tensors. Now, there's something kind of intrinsically just a bit off about TensorFlow. Remember, this entire idea of the JavaScript garbage collector works by trying to find different values that no longer have a reference to them. The TensorFlow library, by default, has a setup that looks a little bit like this. We've got the main TensorFlow library. The TensorFlow library holds a reference to every single tensor that gets created and the data inside them, the actual arrays that hold the real values. It maintains a reference to every single one of those tensors and every single array that is created inside them. So with every single tensor that you and I create inside of our application, it always eternally sits around, unless you and I do something to clean it up. Now, maybe that doesn't sound bad, but it really is kind of bad. If you go back into our logistic regression file, here's our gradient descent function. Remember, inside of here, we do say features times matmul this weights. The result of features matmul weights is a tensor. We take that tensor and then we apply the softmax function to it. The output of that is another tensor. We then take the result of all that and we subtract our labels. The output of that is a tensor. Every single tensor that is created with every single function with TensorFlow inside of our application creates a separate tensor and all the values inside of it that just sit around and around and around and never ever get cleaned up. So even though our gradient descent function returns only holding a reference to this dot weights, so in theory everything else inside of here would get cleaned up, but in reality that's not the case because the TensorFlow library again holds a reference to everything that you see inside of here. As a quick little test, something I just want to show you, I just did a little bit of digging here. If you flip over to this tool, so remember JS Playgrounds, I created a couple of different tensors here. Well, you know what, I'll just do a quick refresh here. So I'll do a refresh, and then I'm going to paste that again. So I just created a couple different tensors here. Now I'm going to open up my console and go to the actual console tab. And then I did a little bit of digging in the actual TensorFlow library on where TensorFlow keeps all the different references to the different tensors that are created. So you can do tf.env.registry.webgl backend text data, like so. And this returns something called a weak map, which is a very special JavaScript data structure. We can expand it, and we'll see that at this point in time, 27 separate tensors have been created and registered with the TensorFlow library. I can expand one of these, go to value, and inside of here, I'll see the values property, and that has values 1, 2, 3 that correspond with 1, 2, 3 inside of here. Now, if I start to create more tensors inside of here, like I'll create a couple more, I can then reference that same property again, and I'll see that it's now expanded to 784. Now, just so you know, the way that this tool works, it kind of does like an incremental execution. So every time that you make a change to the code over here, it reruns every file or every line individually. So there's definitely many more tensors being created here than you might think. But you can kind of basically use this as proof right here that TensorFlow maintains a reference to every single tensor and all the values inside of it for all time. So clearly this is definitely not good from a memory usage standpoint. So let's take another quick break right here. When we come back to the next section, we're going to figure out how we can somehow dramatically reduce the memory usage of TensorFlow as well. So quick break, and I'll see you in just a minute. In the last section, we saw that TensorFlow maintains a reference to every single tensor that ever gets created inside of our application. So in this section, we're going to figure out how we can prevent that and make sure that we don't hold quite so many values in memory. Now, inside this little editor right here, you'll notice I have a bunch of tensors right here. I'm going to wrap the creation of all these with a call to tf.tidy. I'm going to put an arrow function inside there, and I'm going to wrap the creation of all those tensors with tf.tidy, like so. The tf.tidy function is used anytime that we want to automatically clean up a whole bunch of tensors. Any tensor that we create inside of this arrow function right here is going to be automatically deleted once everything inside there gets executed. If we want to maintain any of the values inside of tf.tidy, we have to return it at the very end. So as a quick example here, I could return, say at the very end, tf.tensor 567, like so. And so now the result of the call to tf.tidy would be this tensor that I just returned. So I could say up here, const values equals like so, and then if I print out values, I'll see a result of 567. Now, as a quick example here, I'm going to copy the contents over here. I'm going to refresh this page, paste this code back in, and then again do this little kind of secret reference over here to see that in fact I only created like one single tensor as opposed to all these other ones that got created as well inside the tf.tidy call. All right, so I'm going to refresh the page. So if I now look at that property right there, I should have an empty set of tensors. And it looks like I do. No tensors whatsoever. So now I'm going to paste that code in. And now I should have only one tensor inside that reference. So if I look at that reference one more time, I'll see inside of here, I have 3 in total. That's totally fine. Again, remember the way that this code editor works, it's got some little tricks inside of it to make sure that it can print everything out. Essentially, values down here, or this tensor that we created and then returned, in reality only gets created one single time, not the 3 that you see over here. But you can notice, more importantly, that none of the other tensors inside the tf.tensor call has a retained reference. So all these different tensors essentially got cleaned up after we exited the tf.tidy inner function. So let's take a quick pause right here now that we understand how to get TensorFlow to automatically clean up after itself. When we come back to the next section, we're going to go back over to our logistic regression file and find some really choice locations inside of here that we can wrap inside of a tf.tidy call so that we'll automatically do a little bit of cleanup. Okay, so quick pause and I'll see you in just a minute. In the last section, we learned how we can clean up some memory usage with TensorFlow by making use of tf.tidy. Remember, the big lesson here is that we have to return a tensor at the very end of the body of the tf.tidy call. Whatever we return there is going to be retained by TensorFlow. Everything else we do inside this function is going to be thrown away. And so this is a very easy and straightforward way to manage memory when we're working with very large data sets. So now that we understand this, we're going to flip back over to our logistic regression class. We're going to do some work inside of here to integrate this idea of the tf.tidy call. Now I'm going to be honest with you, integrating or setting up the tf.tidy stuff is something of an art form, and there's not really a hard set rule that I can give you that's going to work in all cases. The best thing I can do is tell you to look at your code and really understand the final value that you are trying to calculate. You're going to want to do all your math to calculate that final value and then return just that final value from a tf.tidy call. So a really good example of this would be to look at the gradient descent function. Inside of gradient descent, we do a tremendous number of calculations inside of here. Remember, every single one of these different method calls is going to return a brand new tensor that's going to be retained in memory for all time. But the result of everything that we're doing inside of here all gets condensed down, or essentially ends up just updating our weights right here. Everything inside of here, the only purpose of it is to generate a new weights tensor and assign that to this.weights. So in this case, we could kind of do an easy little refactor here. Just about everything that you see inside this function could be wrapped inside of a tf.tidy function call. And then at the very end of the tf.tidy, we could return the tensor that contains our updated weights. And so we would return that and assign it to this.weights. I want to very quickly show you what that would look like. Now, I encourage you, don't change your code because we're going to actually implement this tf.tidy call in a different location. But I just want to very quickly show you what that would look like. Okay, so I would take the entire body of this thing and wrap it inside of a tf.tidy. Like so. And then at the very end of the tf.tidy call, rather than assigning some value to this.weights, I would want to return the updated weights. So that the result of this operation right here, like the updated weights tensor, is going to be returned from tf.tidy, and so it's going to be retained. And then finally, remember the result of tf.tidy will get whatever we return from in here. And so I could take that and assign it to this.weights like so. So this would definitely be an improvement. All these different steps, we would no longer retain the tensors that are created during every one of those operations. And the only thing that we would retain is the this.weights tensor, which is generally a very small tensor, not very large, for most of the problems we work on. Now, like I said, this would definitely work, but it's not the final refactor we're going to do here. I just wanted to give you a quick example. All right, so I'm going to undo that. Now I want to take a quick pause. When we come back to the next section, we'll talk about where we're going to actually implement our tf.tidy call, and it's going to encapsulate our gradient descent function and some other stuff that we're doing inside of train as well. So quick break, and I'll see you in just a minute. In the last section, we took a look at how we would wrap our gradient descent body using the tf.tidy function. Now, like I said, there's kind of a better location to put a tidy call than directly inside of gradient descent. So if you scroll down just a little bit to train right here, remember we've got the two nested for loops. In the inner for loop, we are iterating over all these different batches of our features and labels. And then in fact, right here and right here, we're taking slices of our feature set and label set. Now these slices, just as with everything else, are going to be retained in memory. Remember that if we are doing multiple iterations of gradient descent here, we're essentially going to be creating the same slices again and again and again. And each of those identical slices are going to be retained in memory. So we don't only want to wrap the body of gradient descent right here with the tf.tidy call, we probably want to wrap the slicing right here as well. So here's my idea. I think that we could wrap these three statements right here with a tf.tidy call, and so doing the slice operation, and then doing all of the matrix math inside of here, all of that stuff is going to be cleaned up. And the only values that we have to retain during that entire process is the weights update tensor right here, the thing that we try to assign to this.weights. So in this section, we're going to do a little refactor here, where we're going to wrap all this stuff inside of a tf.tidy call, and we're going to make sure that at the end, we still retain the updated weights tensor. Okay, so let's get to it. So the first thing I'm going to do here is wrap those three statements right there with a tf.tidy call. So then I'm going to take the feature slice, label slice, and the call to gradient descent, and I'm going to put it all inside of there. And then I'll fix up a little bit of indentation. Okay, so that looks good. Now remember, we want to eventually return the updated weights tensor. So right here with gradient descent, when we call gradient descent, we're not actually returning any values from that function yet. Let's go up to gradient descent. We're going to make sure that when we call it, we return the updated weights tensor, so that we could eventually return that from the tf.tidy call and assign it to this.weights. So up here in our gradient descent function, rather than assigning the updated weights tensor to this.weights, I'm going to return it, like so. So now when we call this.gradient descent right here, we're going to return the updated weights tensor, and so in turn, I'll simply return it from the body of tf.tidy. And so after this entire function right here returns, it's going to, or excuse me, executes, it's going to return the updated weights tensor, and we'll just take that thing and assign it to this.weights, like so. And that's pretty much it. That's all we have to do. So now when we go through each iteration of gradient descent, and for every single batch, we're going to take the feature slice, the label slice, we're going to do all of this work inside of gradient descent, and every tensor that is created along every step of the way is going to be discarded. And the only thing we're going to retain is the updated weights tensor. Okay, let's do a quick save of this file, and then we're going to test this out, do a quick memory report, and see if this reduces our memory footprint at all. Okay, so I'm going to save the file. I'm then going to flip back over to my terminal. I'm going to rerun my node inspect breakpoint command here. I'll then go and start up my inspector. Now, just as before, I'll go ahead and hit go, or go to the debugger statement. Now remember, this is going to take a little bit of time, so I'm going to again take a pause right here between this section and the next one. I'm going to hit the debugger statement, and then I'm going to again get a memory snapshot so we can do a quick comparison. So I'm going to do both those things between now and the next video. So quick pause, and I'll catch up with you in just a second. In the last section, I reran on my analysis here. Here's the memory snapshot, and I can see that I now have about 158,000 unique arrays being created. Remember, the capital A array are essentially instances of the array class. And again, I use the term class loosely with JavaScript. And then for instances of actual value holding arrays, as you see right here, I'm down to 171,000. So I'm going to sort by shallow size. And then as a method of comparison, I'm going to pull up a screenshot of the previous report. All right, so here's the previous report right here, the one that I had taken just a little bit ago. So this is without the tf.tidy call. Now at a moment's glance right here, you can tell very plainly that we reduced the total number of arrays by about a factor of 3. And that's for the actual value storing arrays. In the case of the array class instances, we also went down by a factor of 3 as well. And for the total number of tensors, I had 120,000. Now I'm down to 12,000. So I would say that this was definitely, without a doubt, pretty darn successful. I think that maybe there's still some locations that we could do a little bit of improvement inside of our logistic regression class. But for this tiny little bit of effort right here, we definitely significantly reduced our memory impact of our program. Let's take another pause. When we come back in the next section, we're going to do maybe one or two other little uses of tf.tidy and see if we can reduce our memory usage even further. So quick break, and I'll see you in just a minute. In this section, I want to do one last little memory optimization inside of our logistic regression class. If we scroll on down to the record cost method, here it is right here, you'll notice that we do a tremendous number of operations inside this function as well. We take our entire features matrix, multiply it by the weights, apply the sigmoid, we then take the transpose of labels, and you get the idea. We could go on here for quite a bit. After we put together the guesses, term 1 and term 2, we then eventually do a little bit of math right here, and then the end result of all of this work is to condense all these operations down to a single value, a single number called cost. But in the process of doing all this, we are maintaining a tremendous number of tensors. Again, I can't tell you enough, every time we chain on one of these methods, we're creating a brand new tensor with all of these unique values being inserted into it. So the last little memory optimization that we're going to do is to simply wrap this thing inside of another tf.tidy call, and we're going to make sure that we just return the single one number that we care about, the cost. So let's give it a shot. Inside of record cost, I'm going to wrap this thing with a tf.tidy. I'm going to take everything from guesses down to the get statement right there. I'm going to cut it and then put it into the tf.tidy call. And then finally down here at the very bottom, rather than us creating a new variable called cost, I'm going to return the result of the get operation. And so now the end result of all this tf.tidy stuff, after we do this call, we're going to be returned a single number that represents the cost of our current iteration. So I'm going to assign that to a variable that I'll call cost like so. And then down at the bottom, no other changes required. We're just going to take that cost variable and push it into cost history like so. Okay, so that looks pretty good. Now I want to, again, very quickly measure the memory impact of this tiny little optimization. I'm not going to make you watch me do it again. So essentially, I'm going to go through the same process that we just saw. I'm going to rerun my analysis. I'm going to start up that debugger. I'm going to progress the debugger, take the memory snapshot, and then we'll come back to the next section together and we'll do one quick last comparison on our memory usage. Okay, so I'm going to go through those steps and I'll see you in just a minute. All right, I reran my heap snapshot. You're seeing it here on the screen. I'm going to pull it up like so and compare it against the previous report that we ran just a second ago. Now the screenshot that you see right here, this is the optimized version. This is the version where we put together the tf.tidy call inside of the train function. So by wrapping all the record cost stuff inside of a tf.tidy call, it looks like we were only able to reduce the total number of arrays that got created by about 1,000. So not great, but definitely an improvement, I would say. So that's pretty much it for optimization. Now, if you want to see something kind of interesting, you can open up your activity monitor or task manager, whatever it is you are using, and take a look at the memory usage by node this time around. For me, I'm down at 1.7 gigabytes. So everything that we did essentially got our memory usage from around 14 gigabytes down to 1.7. Without a doubt, a tremendous improvement. Now, there might be one thing that you could be a little bit curious about. You'll notice here that on the kind of first refactored version I have of the report, I have a shallow size of 420,000. And then if I pull up the original report, so this is the original one right here where we had a tremendous number of arrays, I've got a shallow size of 438. So it seems like with all the work we did, the total number of arrays was decreased by a tremendous amount, but for some reason, the size or the shallow size number here didn't get reduced by a tremendous amount. So you might be curious why that is. To be honest with you, I don't have a very good answer. I do not know why we were able to reduce the total number of arrays by a factor of 3, but not see a commensurate decrease in our shallow size or retained size as well. So if you have any ideas about this, feel free to chime in on the QA section. Maybe someone out there has more experience with memory profiling than I do, and maybe you can help me understand why that was not quite the proportional decrease that we saw. Nonetheless, even with the shallow size and retained size right here, we can really use our activity monitor or task manager as real proof that we did, in fact, dramatically reduce our memory usage. So overall, I would say good success. Perhaps we just don't know, or I should say, I don't know how to use these tools quite well enough to understand why we did not see that decrease on the shallow size. Okay, so overall, this looks pretty great. Let's take a quick pause right here. When we come back to the next section, we're going to start to address that last little thing that we need to kind of figure out inside of our logistic regression algorithm, which is the addressing the accuracy. Remember, our accuracy right now is at like 87.5, not super ideal. I think we can do better. So let's take a quick pause and we'll start to figure out what we can do in the next video. Now that we've got these memory issues fixed up, we can now start thinking about the accuracy of our analysis. Between the last section and this one, I increased the number of training samples that I'm loading up to 60,000, and then did a quick analysis. It looks like the current accuracy that I'm getting is 0.876, or 87.6% accuracy. So I think that we can probably go through a couple steps to hopefully boost the accuracy here, just a couple of percentage points, maybe get into at least the 90% range. Now, the first thing that we're going to do to get a better idea of how we can tweak this algorithm and get a little bit more performance out of it is going to be to chart or plot our cost history. Remember, inside of logistic regression, we've got that cost history array, and that's telling us essentially how incorrect we are over time or for each iteration. If you recall, that's generally going to be kind of a downward sloping chart or plot, and so we can use that thing to get a better idea if incrementing our number of iterations is going to lead to some better accuracy or not. So that's step one. Let's put that plot together and see how we're doing. Now, one quick thing here, notice how I've still got my debugger statement inside of here on index.js line number 30. I'm going to take out that debugger like so. Very good. Now I'm going to go to the top of the file. I'm going to make sure that I have already required in the plot library. I did right there. So now I can go back to the bottom of the file. And after doing all of my analysis, I'll run plot. We're going to plot on the x-axis. I want to get my regression.cost history values. And remember, just for coding simplicity, we have these things from the most recent run to the last run or the earliest run. And so in a plot, usually we might want to reverse those. That might have been like a bad technical decision, but whatever, we're kind of stuck with this now. Okay, so I'm now going to run my analysis. Now, just for the sake of getting this done a little bit more quickly, I'm going to bump my number of training samples here down to just 10,000, so you don't have to sit and watch me run this thing forever. Okay, so I'm going to run this again, and then in a couple of seconds, I should see my accuracy report. Even with the 10,000 samples, I still get at least somewhat close. It's not as good, but again, I'll at least be able to look at that plot and see if the number of iterations that we're using is appropriate or not. Okay, so now inside of my project directory, I see the plot.png file. I'm going to open it up, and lo and behold, it is totally empty, which is very much unexpected. So why would that be empty? Well, let's go back down to where we're putting the plot together down here. And in addition to trying to plot our cost history, I'm going to try to console log it out. And we'll take a look at the values inside of there and get a better idea of what they are. Now, in this case, for the console log, I'm not going to reverse it just because I don't really care what order it's in. I just want to take a look at the numbers that are in there. All right, so I'm going to run this again. All right, and there's our cost history. Every single value is not a number. Well, that's definitely not good. Not only does that mean that we cannot plot out our cost history and get a better idea of how our different number of iterations is treating our accuracy, the other problem is, remember, that cost history array is used inside of our, way down here, update learning rate function. So update learning rate is really expecting those values to be meaningful. Right now we're comparing not a number against not a number, which is without a doubt a very bad comparison. It likely means that we are always going to be increasing our learning rate or always decreasing it by a factor of 2, one way or the other. Either way, getting these not a number values that we're getting right now inside of our cost history is a very bad thing. So let's take a quick pause right here. We're going to come back to the next section, figure out what's going wrong, and then start to fix this up. So quick break, and I'll see you in just a minute. In the last section, we printed out our cost history, and we saw that we were getting not a number. So in this section, we're going to do a tiny little bit of troubleshooting to figure out what's going on here. We're going to end up going through the same process that we've seen in the last couple of videos, where we set a debugger statement and we print out a couple of different values using that Chrome inspector, once again, that we've been looking at nonstop over here. So let's get to it. Now I'm going to flip back over to the logistic regression class file. Inside of here, we have a method towards the bottom that is called, come on, where is it? Here we go, record cost. So without a doubt, probably makes sense that we are making a mistake inside the record cost function, because this is the only place where we take some values and insert them into that cost history array. So right inside this tf.tidy statement, I'll put a debugger statement like so. I'm going to save the file, and then I'll run it back over at my terminal with the node, or excuse me, the inspect brk, like so. Index.js. There we go. Okay, now we're listening. I can then go back over here, find the inspect button, click that, and we're in. So now I'm going to go ahead and hit play, and we're going to very quickly hit that debugger statement in just like a couple seconds. There we go. All right, so now, just as we did before, we can kind of either walk through this, or we could print out some of the different terms as we are calculating them. Now, in this case, I know exactly where the problem is, so I'm just going to kind of jump ahead a little bit and show you exactly what's going wrong here. But again, if you wanted to kind of do this a little bit more organically or figure out how to do the debugging on your own, what I would probably do is step over like 1 or 2 statements like so, and then maybe print out guesses and say, okay, do I have any not a number values inside of here? Does anything inside of here look weird? That's the general idea. Okay, so like I said, I already know what's going wrong here. If you look at term 2, you'll see that we have guesses. We then multiply by -1, add 1, and then take the log of that. Now, before I tell you what exactly is wrong with that little part right there, I want to show you something very quick inside of my browser. So I'm just going to pull open a calculator really quickly, and I'm going to take log of 0, like so. So log of 0 is -infinity. And likewise, if we take log of a negative number, like -10, we end up with an error as well. So if you try to take log of 0, we get -infinity. Log of any negative number is an undefined operation. So if we ever take log of a negative number or 0, we're probably going to end up with some mistake. Now, with that in mind, if I go back over to my debugger, you'll notice I printed out guesses right here. Inside of guesses, you'll notice that inside of my first column, I have a 1 right there, and inside of that column right there, I've got a 1 right there as well. So now look at what we're doing with this little block of code right there. We're saying guesses, multiply by -1, and then add 1. So anywhere inside of the guesses tensor where we have a value of 1, we're going to turn that into a -1 and add 1. And what's the result of that? The result is 0. So at some locations inside of guesses, we end up taking the log of 0, which is equal to -infinity. So just to show you that in action, notice how I have 1 right there and 1 right there inside of guesses. So I'll say guesses.mul -1, add 1. I'll just run that right now. I'll do a print just to show you that we do in fact get 0 and 0 right there. And then if I take the log of that operation, yeah, I end up with a nice little, it's because I did it on print. I'll do the log and then the print like so. All right, that's better. So now you're going to see that in some locations inside of here, even though it's kind of funny formatted, there we go. I now have -infinity and -infinity. So that's the issue. Essentially, through some very natural steps of math that we're doing here, we end up with -infinity, which is going to end up eventually turning into not a number when we eventually try to record our cost. So let's take a quick pause right here. We're going to come back to the next section and figure out how we solve this. In the last section, we saw that our not a number values for our cost history are coming because we are taking the log of 0 inside of our record cost function. Now, between the last video and this one, I stopped that node debugger tool. I'm also going to remove the debugger statement that I have right here. All right. So how are we going to fix this? Well, we're going to go through a little change here, a little trick. Remember that several times throughout this course, we've kind of introduced little tricks here and there, and we've said several times that it feels like introducing these little tricks, as we call them, would end up changing our answer in some very substantial way. So the little trick that we're going to use to solve this issue is going to be another one of those things where it feels like, hey, we're doing some little change here that's going to kind of arbitrarily change our results or change our data set or something like that. So let me show you what we're going to change, and I'll tell you why making this change is not really going to be the worst thing. All right, so right here on guesses, we're going to do guesses multiplied by -1. We're going to add 1, and then we're going to introduce an additional add statement. I'm going to say add 1 e -7, like so. So what's this do? Well, first off, 1 e -7 is the same as 1 times 10 to the -7th power, which is more or less equal to 1, 2, 3, 4, 5, 6, 7.1, like so. So essentially 1 e -7 is a very, very small number. By adding in 1 e -7, we're essentially going to make sure that we never take the log of a value exactly equal to 0. Instead, we're going to take the log of a value very, very close to 0. Now, the log of this right here is not equal to -infinity. So the entire idea here by adding in this little constant is just to make sure that we never take the log of exactly the value 0. Now, like I said, this is going to seem like we're just arbitrarily changing our equation here or changing our formula for calculating cost history. And, well, yeah, we are. We are making an arbitrary change. But again, this arbitrary change right here is just to make sure that we do not get a result of -infinity from the log statement. The number that we're adding in is so small that it's going to have an absolute negligible effect on the actual output of our cost history. Now you're going to see in many other algorithms little steps like this where we add in tiny little constants just to make sure that we don't do some numeric operation, such as taking a log of something that's going to end up giving us infinity or -infinity or undefined or anything like that. Okay, so that's pretty much it. Now I'm going to remove that comment. I'm also going to add that same add statement up here on term 1 as well. Notice how we have guesses.log right here. It's entirely possible that we might end up with a guess exactly equal to 0. So I want to make sure that that never happens, or we never end up taking the log of 0. So I'm going to add in that same add statement here as well. So I'll say add 1 e -7, like so. All right, so that's pretty much it. Now, last thing I want to mention here, you might be curious why I split the add statement out into 2 successive adds in a row. We could have definitely done something like 1 plus 1 e -7. Totally would have worked just fine. The reason I split this out into 2 separate add statements is that if anyone comes back in the future and kind of takes a look at my code, I might put a comment on here that just says add a constant to avoid log 0, like so. That's the only reason I put it here, just for clarity for future's sake. All right, so that looks good. Now let's flip back over to our terminal. We're going to try running our solution again and just making sure that we're no longer getting not a number for our cost history. Okay, so I'll flip back over and I'll do another node index.js. I'll wait just a second and then we're going to eventually see our cost history print out. There we go. And you'll notice that I do not have any values of not a number inside of here. So now that we've got this, we can go ahead and check out our plot that we had been generating inside of our index.js file. Here's our plot. Inside of my directory, I can find plot.png, and there we go. So now we get an actual plot of our cost history, or our cost value, essentially telling us how wrong we were for each iteration. So now that we have this, we can start to try to tweak our learning rate and maybe our number of iterations as well to try to get some higher accuracy than what we're currently getting. So let's take a quick pause and start that process in the next video. Now that we can actually see our cost history changing over time, we can try to make a couple changes to the parameters of our analysis in order to increase our accuracy. So at present, I have parameters of learning rate of 1, 20 iterations, a batch size of 100, my training set has 10,000 records inside of it, and my test set has 1,000, like so. With those parameters, I currently have an accuracy of 0.878. So like I said, I think that we can probably get this analysis a little bit better. The first thing I want to do here is remove our console log of the cost history. We don't really need that anymore. We only put that in there for a little bit of debugging purposes. So now, how would we increase our accuracy? Well, as it really came down to it previously, what we want to do is start playing around with the different parameters. our learning rate, iterations, batch size, the size of our testing set, and the size of our training set as well. So at this point, I would encourage you to go ahead and play around with these values a little bit. Remember, our training set size can go all the way up to 60,000, like so. Our test set size can go all the way up to 10,000. And then you can start to vary your learning rate, iterations, and batch size as you please. So let's take a quick pause right here, and I want you to start playing around with these values a little bit. Keep in mind that every time you run the analysis, it might take all the way up to 30 seconds, 1, 2, 3, 4 minutes, just depending upon the specs of your machine. I want you to try playing around with these different values. We're going to meet up in the next video, and we'll kind of get a better idea of what some optimal values are for these parameters. So quick pause, and I'll see you in just a minute. In the last section, I told you to play around with your model parameters just a little bit in order to increase the accuracy of your analysis. I ended up with an accuracy of just about 93%, or 92.5, rounded up to 93. In this video, I want to tell you about how I got to this 93%, and hopefully you can get to this point as well. All right, so let's look at some of the numbers I used inside the index.js file. Now, the first thing I did was increase the number of training examples in my dataset to 60,000. In general, the more data or the more observations that we throw at our model, the better result we're going to end up with. And so anytime that we're going for accuracy, the first thing I might try changing is increasing the number of observations that I'm feeding in. The next place to play around with was our model parameters. So the learning rate, the number of iterations, and the batch size. I left the learning rate at 1 because remember, we have a little bit of code to optimize that learning rate over time. The next thing I did was change the iterations to 80. By changing to 80, we're going to allow that learning rate to change many times and get optimized over time so that hopefully we'll eventually narrow in very precisely on our optimal values for the different weights inside of our model. You'll notice I also changed the batch size to 500. Remember that in general, having a lower batch size, like 100 or even say 50, will lead to a faster learning for our different weights inside of our model. The reason I put it at 500 was just to make sure that the analysis ran a little bit more quickly. In general, as you start to increase your number of iterations, you can also increase your batch size and still get the same accuracy. In general, the number of iterations and batch size, you kind of want to have a balance just to make sure that the model doesn't take too long to train. If I went to, say, 10 iterations, then I might take the batch size all the way down to something like 20 as well, to make sure that I'm still getting enough training in on my model. And then finally, for my testing set, I left it at the absolute max of 10,000. Now, going to 10,000 doesn't really affect the weights that we are calculating. Of course, this is just for the accuracy test. But going up to 10,000 just made sure that I had a very statistically significant accuracy value. All right, so that's what I put in here to get the 93%. Now, last thing I want to show you is the plot of my cost history over iterations. So it looks like my initial guess right here had a relatively low cost history. But then after one iteration, it jumped way up. So my cost went to be pretty large, which indicates that my learning rate was probably initially set too high. I then went back down, and then we took these kind of gradual steps down until around, say, 30 or 40 iterations, I started to kind of level out here. So what this tells me is that after I get to 30 iterations or 40 iterations, running additional iterations is not really getting us any big gain for the purposes of accuracy of our analysis. So with that in mind, I might choose to decrease my iterations here to 40 or so. By doing so, my model is going to train twice as quickly, but I'm not going to suffer a big loss in the accuracy of my analysis. All right, so that's pretty much it. Now, 93% right here, as far as handwriting recognition goes, is not the greatest. There are other people who can very easily get far higher accuracies on the MNIST dataset than our 92.5%, but usually they're using different algorithms, such as k-nearest neighbor or a neural network, and a lot of times they'll do some additional kind of preparation or massaging of the dataset before they feed it into the algorithm. So for what we're doing with logistic regression, this 92.5% is pretty darn reasonable. And if you go online and look at some other people who are using logistic regression on this data set, you'll see that we're actually doing pretty darn well with the accuracy that we've got. Okay, so that's pretty much it on logistic regression. I don't really have a lot of other stuff I want to talk about. I think that we've covered this topic from quite a good number of angles, and we've got a really good idea of how to use it to do this multiple type of classification. So let's take a quick pause here, and we're going to continue with our next topic in the next section. In this section, we're going to start to learn how the load CSV module was put together. So inside of my project directory, I'm looking at load CSV right here. Obviously, you can take a look at this file directly and try to read the contents of it and get a better idea of what it's doing. But just in case you want a walkthrough on how I put this custom CSV loader together, stick around and we'll walk through it step by step and get a better idea of how it was put together. All right, so we're going to put this thing together step by step. So back in my terminal, I'm going to create a new project directory. You'll notice that I changed out of the ML-Kits folder, and I'm now in kind of a workspace directory of sorts. Inside of here, I'm going to make a new project directory called simply load CSV, and then I'll change into it like so. Now inside this new project folder, which is where we're going to write this load CSV module, I'm going to first begin by generating a new package.json file, because there are 1 or 2 dependencies that we're going to need as we put this thing together. To generate a new package.json file, I'll run the command npm init. I'll then be prompted with a couple of quick questions right here. I'm just going to hit enter and use the default values for each one. Okay, so now if I list out my files and folders inside of here, I'll see that I do in fact have the package.json file. I'm now going to run npm install and add in 2 dependencies. The first is our favorite Lodash, and then the second is something called shuffle seed. So I'm going to install both those, and it looks like we're good to go. So now the last thing I'm going to do is start up my code editor inside this directory. As a quick reminder, you're only going to be able to run code dot like I am right here if you have set up your code editor in this fashion. All right, so now I'm inside my project directory, and inside of here, I'm going to make a new file called load-csv.js. So we're going to eventually write a bunch of code in here that's going to load up and parse our CSV files. Let's take a quick pause right here. When we come back to the next section, we'll get started working on this file. So I'll see you in just a minute. In the last section, we put together a new little project directory for the sole purpose of learning how to load up and parse CSV files. We created a load.csv.js file, which is where we are going to eventually put all of our code to parse the thing. But before we start adding any code in here, we kind of need a little test CSV file to work with. Now, if we want to, we could definitely go back and get that vehicle data set or some other file like that. But for the purposes of what we're doing here, we could very easily put together a little test CSV file. So inside of my project directory, I'm going to make a new file called data.csv. And we're just going to manually put together a tiny little data set for us to work with. The first line inside of a CSV file is always going to be the headers, or the title of each column inside of our table. I'm going to give my CSV file some headers like, say, past, about ID, height, and value. Now I'm just totally making up these headers off the top of my head. They're going to work out for us pretty well. I'm going to give 3 different rows inside of here. So we're going to ultimately have 3 different kind of observations or values inside of our CSV file. I'm going to give them values like, say, true, 0, 10, 20. Let's say false, 1, 11, 21. And how about another true, 2, 12, 22. All right, I think that's a good place to get started. So now our job is going to be to load up this CSV file, parse all the rows inside of here, and somehow get them into an array of arrays. And then also have a couple of other options, such as the ability to shuffle our data set, split it, and all the other things that we saw as we went through our original implementation, or actually made use of it inside of this course. So now that we've got the test data set put together, we'll take another quick pause and then start putting together some implementation inside of load CSV. In this section, we're going to start adding in some code to our load.csv.js file. At the very top, I'm going to first begin by defining a new function called load.csv, like so. So this is going to be the primary function in the file. We're going to eventually put a ton of logic inside this thing that's going to load up a CSV file and parse all the data inside of it. Now, without a doubt, we're going to have to call load.csv with some path or some file name of some CSV file that we want to load up. So I'm going to refer to this first argument as file name. And then we'll have a second argument in here that we'll refer to as our options object. Eventually, we're going to replace the options argument name with a little bit of destructuring and also have some different default arguments to put in here as well. But for right now, just calling it options will work out just fine. Inside of load CSV, the first thing that we're going to do is attempt to load up the contents of the data.csv file, or whichever file we specify with this file name argument. In order to load up a file, or essentially read all the data out of it from our hard drive, we're going to need a built-in standard module from the Node standard library. So at the very top of the file, I'm going to require in a new library called fs. Now again, this is a built-in standard module, so we don't have to npm install it or anything like that. The fs module has a ton of different functions included on it for working with different files on your file system or on your hard drive. In order to load up the contents of the data.csv file, I'm going to call fs.readFileSync. I then need to specify the file that I want to load up, so I'll pass in the file name argument. I also have to pass in a second argument to this thing that specifies the encoding of that file. We're going to use a default encoding of UTF-8, like so. Now the result of this function call right here is going to be the raw data inside of that data.csv file, or of course whatever we specify as our file name. So I'm going to assign that to a variable that I'll call data, like so. Now for right now, just to make sure that everything is working the way that we expect, I'm going to console log out data. And then underneath our load CSV function, I'm going to try calling this thing, and I'm going to attempt to print out the contents of data.csv. So I'll call load CSV, and I'll pass in data.csv. So now let's save this file, let's run it at our terminal, and just make sure that we can print out the contents of what we see inside of here. All right, so I'm going to flip back over to my terminal. There's my load CSV file, so I'll do node load csv.js. And then I see as plain text, so that's text right there, there's no data structure applied to it, it's just plain text, the contents of that file. So this is looking pretty good. Let's take another quick pause and continue parsing this thing in the next section. In the last section, we put together a quick console log just to make sure that we had correctly loaded up the CSV file, and we definitely had. So now that we have a big string that contains all of our data, we want to somehow parse this string and pull some information out of it. So in order to do so, I'm going to first take that data string, this thing right here, and I'm going to split it on all the new line characters. So we have a couple of different new line characters. There's one there, there, and there. By splitting on our new lines, we're going to end up with an array of strings, where each string is a separate row. So like one row, row 2, row 3, and row 4. All right, so back over here, I'm going to do a data.split on new line. Let's do a quick console log on this as well, just to make sure we're going down the right path. I'll flip back over, rerun that, and now we can see that, yep, we've got an array of strings. So now the next thing we're going to want to do is take each of these string rows, as you might call them, and turn those into arrays as well. In order to do so, I'm going to remove that console log, and then I'm going to map over the result of split. So that's going to give us each of these individual rows, which right now are simple strings. I'll then do another row.split, and this time I'm going to split on the comma character. So now I'll console log this out as well. And if I do another node load CSV file, or excuse me, execution, I'll see that, yep, I've got my nice classic array of arrays. Each inner array is separated based on those inner commas. So I now have element 1 of being the string true, then 0, 10, 20, and so on. And of course, the first row is the different column headers. All right, so that looks good. Now there's something kind of interesting that we're going to do for this next step. Let me tell you exactly why we're going to do it. If you open up the data.csv file, you'll notice that we have a very well formatted CSV here. Like there's no extraneous characters, no extra commas or anything like that. It turns out that if someone does a CSV export from a variety of different spreadsheet programs, and if they do this export incorrectly, they might accidentally add a couple of empty columns to the CSV file. you can recognize empty columns as a collection of kind of trailing commas at the end of the file, or at the end of each row, like so. So this would represent a couple of empty columns inside the CSV file. And again, this happens very commonly anytime that someone does an export from a spreadsheet program. So we're going to want to make sure that we somehow trim off these extra commas at some point in time. Let's take another quick pause right here, and we'll figure out how to trim those things off in the next section. In the last section, we spoke about how we need to somehow trim off these trailing commas, which frequently occur when we do a bad export out of a spreadsheet program. So I'm going to flip back over to my load CSV file. I'm going to take out the console log that I was using, and I'm going to make sure that I assign the results of that entire operation right there to some variable. So I might call it something like const parsed rows or something like that. Now, if we take this type of approach right here, where for every operation we assign it to a brand new variable inside of here, we're going to very quickly end up with a lot of very crazy variable names. So rather than trying to create a new different variable for every single operation, I'm going to instead just overwrite the data variable. And then if I want to do so, I'll need to make sure that I change const right here to be let instead. So that's going to allow us to just keep on reusing the data variable throughout this function without renaming it all over the place. Okay, so now inside of here, the next thing I want to do is somehow make sure that I drop off all those extraneous commas at the end. In order to do so, I'm going to map over my data. So I'll do map. I'm going to get each row. And then for each row, I'm going to make use of a nice little Lodash function called _drop right while. The drop right while function is going to take in an array, and we're going to give it some criteria on what we want to drop out of this array that we are putting into it. The word right inside of here means that it's going to start at the very end or the right-hand side of an array when deciding what elements to drop. All right, so then for each row, we're going to take each value inside that row, which I'll just abbreviate as the word val, and we're going to say that we want to drop the stuff if it is equal to empty string, like so. Okay, so after that, I'm going to reassign that back to the data variable. I'll do a console log of data, and then let's also not forget to require in the Lodash library at the top, like so. Okay, so let's do another quick test here. And I can see that I've now dropped off the tailing or the end columns that were at the very end of each row. Just as a quick test here, we could comment out that line and do it again, and we see, yep, we did in fact drop off those trailing commas, or columns. I keep on saying commas. Okay, so this looks pretty good. Let's take another quick pause right here, and we'll continue parsing this thing in the next section. We've now got some of the basics of the load CSV function put together, so from here on out, we're going to start to pick up a little bit of speed. Well, let's get to it. Next thing we're going to do is get a reference to just the headers inside of the data array of arrays right here. Now, the headers are essentially the column titles. It's this first row at the very top. So in order to get a reference to those, I'm going to say const headers is _first data, like so. Now, if I did a console log of headers, I can rerun this and see that I get just the headers or just the column titles of that array of arrays. We're going to make use of these headers quite a bit throughout the rest of this function. Now, one thing to keep in mind here is that it does not remove the first row from the data variable. Those headers still exist there. So why do we not just remove this thing? Well, you'll see why in just a second. It turns out that we still need to very easily be able to reference the different columns that exist inside of this array of arrays. That's why we did not just remove that first row outright. And the next thing we're going to do is put together the main mapping statement that's going to parse all the different rows inside that CSV file. So I'm going to do a data.map, and I'm going to look at each row and index inside there. And we're going to parse some of the different values that are inside of it. The first thing I'm going to do inside of here is look at the index variable. If index is equal to 0, that means that we're operating on the first row or the headers row, and we want to skip over that entirely. So I'm just going to return row in that case. Now, again, you might be curious why we're maintaining that reference or that headers row inside there. Again, that's going to get a little bit more obvious in just a little bit. So now the next thing we're going to do is for each row inside of here, we're going to map over it. So I'm going to do a row.map. We're going to look at each element and each index inside there in turn. So now this inner mapping statement right here is going to be our opportunity to parse an individual value inside of each of these rows. It's going to be where we're going to try to turn, say, the string 0 into the number 0, or the string true into either a Boolean true or false, and other stuff like that. So the first thing we're going to do inside of here is attempt to parse float on element. And I'm going to return or assign the result to that to result like so. So if we're working with a number, we're going to try to parse the number out of that string and assign it to something we'll call result. Now, in order to make sure that we don't accidentally parse some string that is not actually a number, I'm going to say, is this not a number? Is the operation we just did, is that not actually result in a number? If that's the case, then I'm just going to return the element by itself. Otherwise, I'll return result. I'm going to make sure that I return that entire thing. And then I'm also going to make sure that I return the result of the row.map. So now let's do a console log on data at the bottom. And if I run this now, we'll see that I've taken all the different numeric values and turned them into actual number values, as opposed to the strings that they were previously. Okay, so that's pretty good. Let's take another quick pause. When we come back to the next section, we're going to make sure that we have the ability to take these true and false strings and turn them into actual Boolean values as well. The next thing I want to do is make sure that we have the ability to take these string values and turn them into something meaningful. Now, it's not really going to be up to our load CSV module to look at the string and see that it contains the value true or false and turn it into the appropriate Boolean. Instead, we're going to set up a system called the converters system that's going to allow our user of this module to optionally pass in a function that can be used to parse just this column of values right here. So we will leave it up to someone who's using this module to decide to turn the string true into the Boolean true or the Boolean false. Because at the end of the day, rather than seeing like values of true and false here, it might just say like T and F and T. And it would be really challenging for you and I to come up with some schema inside of load CSV to decide exactly how to parse or kind of understand each of these different variables. So in order to do so, we're going to start to expand this options argument, the options argument right here just a little bit. I'm going to destructure a property out of it that I will call converters. Now by default, this is going to be an empty object. So the idea is that if someone wants to parse a single column in a very specific way, they will pass an argument into this converters property right here. Let's take a look at what that might look like. So it would look something like this. We would say object converters. That's going to be an object in turn. The key of this object is going to be the name of the column that they want to pass with some they want to parse with some custom function. So I'll give it a key in this case of passed, because that is the column that they want to attempt to do some special stuff on. Then we'll make sure that this thing gets called eventually with all of the different values inside of each row. And then in this case, we'll say if value is equal to true, then I want to return true, otherwise false. Now this statement right here could be easily reduced down to just val equals true, like so. That will return the same thing as a ternary expression. Okay, so now we need to make sure that if we are working on the column of passed, we're going to make use of this converter as opposed to the default, which is to do this little kind of parse float operation. So inside of that inner map statement, we're going to say if there is a converter at headers index. So headers index is going to give us the name of the current header that we were working on. Remember, index right here is that index variable. It's the current column that we're working on. So if we have a function on that converters object, then we're going to use that instead of doing this default parse float. So if that's the case, we're going to say const converted is converters at headers index, and we're going to pass in the element to that. So this is some kind of fancy syntax right here. That statement right there is going to just return this function. And then we're going to call that function with the element that we're currently iterating over. And then we're going to get whatever comes out of that function and assign it to converted. Now we're going to make sure that we return that thing. We'll do that same is not a number check just to make sure that we did not do a bad job of parsing the value. If we did get back not a number, then I'm going to return the original element. Otherwise, I'll return the converted value. Like so. Okay, let's save this and we'll do another quick test. And so now you can see that the true, false, and true values have been turned into actual booleans of true, false, or true. Now, if we wanted to, we could just as well say, rather than return a straight boolean here, maybe I want to return a 1 or a 0, depending upon whether it's true or false. So I could put on $1:0, and then if I rerun this, I can now get 1, which indicates true, 0, which indicates false, and 1, which indicates true. Okay, so that looks good. We've now got the ability to do some custom parsing inside of the values of our CSV file. Now let's take another quick pause. We'll come back to the next section. And we're going to start to make sure that we only extract the columns of data that we actually care about from the CSV file. So quick pause, and I'll catch you in just a minute. We're now able to convert all the values inside the CSV file, or otherwise parse them in some fashion. The next thing we want to do is make sure that we only return a set number of columns from our data set. So remember, we might only want to get the past column right here as our label values, or maybe only our height and value as our feature values. We might want to completely disregard the ID column entirely. So in order to do so, we're going to add in 2 more options to the load CSV options object. We refer to these as data columns, which is going to be an array, and label columns, which is an array as well. We then put the name of the columns we want in each of these. So maybe for data columns, we want, say, height and value. So I'd put in height and value like so. And then for label columns, maybe we want past. So I'd put in past like so. So now these are going to show up as 2 additional arguments inside the load CSV function. I'm going to make sure that I destructure those out of the options object, and I'm also going to default their values at the same time as well. So I'm going to add in data columns is going to be an array by default, and label columns will also be an array by default as well. Okay, so now after we do that conversion step around line 13 or so, we now need to make sure that we extract out data columns and label columns. In order to do so, we're going to add in a little helper function right above load CSV. I'm going to call this helper function extract columns. Like so. And then we're going to pass this thing our entire data set and the column names that we want to extract. So the idea behind extract columns right here is that we're essentially doing the exact same step for extracting the data columns and label columns. So rather than writing out that logic twice inside of load CSV, we're just going to write it out as a single separate function that we can call with however many different types of columns we want to extract at some point in the future. Now inside of extract columns, the entire job is going to be to look at our entire data set, the array of arrays, and only pick out our column names. That's the only thing we want here. So to get started, I'm going to first get my headers off this thing. And then I'm going to get the indexes of the columns that I want to extract. So right now we just have the column names. The names alone don't really tell us a lot. We're going to get the index of the column. So like index 0, index 1, 2, 3. And that will tell us exactly what elements we need to eventually pull. So to get those indexes, I'm going to say const indexes is underscore map column names. So we're going to look through each different column name, and we're going to match up that column name with a headers index of column, like so. So this step right here is just going to look at the headers array, compare it with column names array, and decide exactly what the indexes of each column we want to pull out are. So now the next thing we're going to do is we're going to do the actual extraction step. So I'll say const extracted. We're going to map over all of our data, and for each row, we're going to pull out a very specific set of indexes. In order to pull out just the indexes we care about, we're going to use another Lodash function called pull at. We'll pass in the row and then the indexes like so. So pull at does exactly what you might guess. We put in an array and a list of indexes. Then whatever list of indexes we indicate in here, we're going to pull out just those specific elements out of that row. Okay, so then the last thing we have to do inside of here is return the extracted data that we now have. So now we can make use of this underneath the data conversion step. So right above the console log that we have right now, we're going to say our labels is going to be extract columns, and we'll pass in our data and our label columns. And then we'll also update our data as well. We'll say extract columns with data and data columns. All right, so if we now save this file and rerun this in the terminal, remember we have the console log right here of data, we should see only the columns of height and value inside there. All right, so I can flip back over. Oop, not that. Let's do a node load csv.js. And now this is kind of multi-lined right now, but you'll notice it is an array of arrays, and we have only our height and value and the entries on each subsequent array. Now from this point on, we don't really need those headers anymore. We only were carrying around the headers just to easily get those indexes inside of the extract columns function. So after this point, we can do a data.shift and a labels.shift as well, and that's going to dump those first columns, or the first row that specify the column titles. So now I can save this and rerun it again. Oop, I misspelled shift right there. And now we're left with just the actual data itself. Now that, of course, is the data. We could update the console log to be our labels instead. And there we go. Now we've got our labels too, without any header at the very top. Okay, so this is looking good. Let's take another quick pause. We just have a couple of more quick little steps inside of here, and then we'll be all set. The next option that we're going to add into our load CSV's function is to make sure that we can shuffle all of our data by default. So remember, shuffling our data set is really important with a handful of different algorithms, such as, say, k-nearest neighbor. Not quite such a big deal with our regression type algorithms, but it's still a big deal when we start doing that batch type testing. All right, so we're going to make shuffling an option. So on the load CSV call down here, I'm going to add in shuffle true, which would indicate that by default, I do in fact want to shuffle my data. Now, we'll set up shuffling as being the default here, because in the vast majority of cases, we always want to shuffle our data. All right, so in order to shuffle this, I'm going to make sure that I carry in that shuffle option to my options object right here. So I'll add in shuffle, and I'm going to default it to be true like so. Now, shuffling our data is actually kind of an interesting thing, because remember, right now we have labels and data as two separate arrays of arrays. So if we simply call shuffle on each of these, they're actually going to be shuffled in completely different orders, and they will no longer have their indices actually match up, having the same observations match up to the same labels. So however we do this shuffling, we need to make sure that we do it in some intelligent fashion. One way we could do it would be to join our data and our labels back together, but that's maybe not the most efficient thing in the world. An alternative thing we could do would be to shuffle all of our data before we start to do any parsing or anything like that. That would be an option as well, but I've got another option, a third option, that is actually going to end up being pretty nice and really actually have kind of a really nice side effect. So at the very top of this file, I'm going to add in a new require statement. I'm going to say shuffle seed is require shuffle seed. The shuffle seed library is a little tiny function that can be used to shuffle an array of records. It takes a seed phrase, which is essentially a shuffling option. If you put in a seed phrase, which is a simple string, identical between two separate arrays, they'll be shuffled in the exact identical fashion. So we can use this package right here to make sure that the data and label arrays get shuffled in the same exact order. It also has the nice side effect of making sure that whenever we shuffle our data, if we do subsequent shuffles by, like, say, rerunning our analysis, the data will always be shuffled in the same order each time. Now that's good from the standpoint of doing debugging, because it means that you and I, like if I show you my shuffled array and you see your shuffled array, they will always be in the same order together. So like I said, it has a couple of pretty good benefits to just using this package. So now to make use of this, we'll go back down to the bottom of this function. And after we do our shift step, I'll see if we want to shuffle. So just if shuffle. Remember, that's going to be a Boolean, either true or false. So then inside of here, we can do data is going to be shuffle seed dot shuffle. We'll pass in our data and then a shuffle phrase, or excuse me, a seed phrase right here. So this can be any string. The only requirement is that it has to be identical between shuffling our data and our labels. So for right here, I'll just say, like, say phrase. That works out just fine. And then our labels will be shuffle seed dot shuffle labels, and I'll put in phrase as well. Again, the only requirement here is that this string has to be identical between the two. Now, if we wanted to, we could certainly make this shuffle string right here a option to be passed in when we called load CSV to make sure that if we wanted to change the shuffling order, we could simply put in a new string right here and we'll get a new order out. But I'll leave it up to you if you want to implement that additional step. All right, so this should shuffle our data. Now I'm going to do a console log here of both our labels and our data right above each other, and then we're going to rerun this file and make sure that our data got shuffled in the exact same order. All right, so I'll flip back over. I'm going to do another node, and what do we call this thing? Load CSV. All right, so we have 1020, 1222, and 1121. That goes true, true, false. And off the top of my head, that definitely seems accurate. You could go back over here. So a true went with 10 and 20. So true, 10 and 20. Then we had a true with 12 and 22. So 12 and 22 had a true, and 1121 had a false. So 1121 had the false. So without a doubt, these things got shuffled in the same order. And if we rerun this again, we're going to get the exact same result out. However, if we go back over and we change this string right here and use a different seed, like say phrase 1 like so, I can save this, rerun it, and I should see a different shuffling order. And in fact, I do. I now have 1222, 1121, and 1020. Cool, so that looks good. Now, like I said, you could totally extract this little seed phrase right here to be an option if you want to make sure that you have the ability to actually really customize or reshuffle between runs, but it doesn't really matter in the long run as long as you're shuffling your data at least one time. Okay, so this looks good. Let's take another quick pause right here. And the last thing we have to do is make sure that we add the option to split all of our data into a test set and a training set. So let's take care of that in the next section. Last thing we have to do inside of our load CSV module is make sure that we have the ability to split our training set and test set out into two separate data sets. So I'm going to add on a new option to the load CSV function down here. I'm going to put this thing in and I'll call it split test. Now remember, in the original course, as we went through with this module, split test can either be a Boolean, like true or false, or it can be a number. If it's a number, it's going to specify the number of records that we want to have inside of our test set or our training set. We can definitely set it up to be either one. So let's first start and make sure that we can split this thing off into some like X number of records. So if I put in a 1 like so, that would indicate that I want my test set, or again my training set, we could figure out which one it is, to have 1 record inside of it. All right, I'm going to again make sure that I default this argument up inside of load CSV right here. So at the very end, I'll put in split test, and I'm going to default this to be simply false, like so. So by default, we're not going to do any splitting whatsoever. Okay, so now we'll go back down to the bottom of the function, and I'll say if split test, and we'll take care of both cases with a if-else statement. So if we are in the else case, that means that we do not want to do any splitting of our data set whatsoever. If that's the case, then we can just go ahead and return our features and our labels. So I'm going to return an object here with features of data and labels of labels. And of course, we can use a little bit of ES 2015 syntax here to shorten that up like so. Now, since we have some return statements in here now, I'm going to remove the 2 console logs we had at the bottom. Now we'll take care of the if case. So this is the case in which we do in fact want to split our data out. So the first thing we have to do here is decide whether or not we are splitting this thing using 50-50. So that would be the case in which the split test variable right here is equal to true, or if we have an actual number that would indicate the number of records that we want to put into our test set or training set. So in order to figure that out, we can use a Lodash function of _is_number, and we'll look at split test. So if that is a number, that's going to tell us the number of records we want to put into, say, our training set. So if that's the case, I'll just return split test. Otherwise, if that is a Boolean, then we're going to want to take it and we're going to just say that we're going to split our test and training set into 2 equal pools, or as equal as we possibly can. Remember, right now we only have 3 observations. So in order to split this thing into 2, I'll look at data.length, I'll divide it by 2, and I'm going to hit this up with a math.floor to round it down. And I'm going to assign the result of all this to train size. So like I said, this can be either the size of the training set or the test set. It's totally up to you. This thing is called split test, so I don't know. You might make the argument to say that if it's a number, it would specify the number of records to be in the test set, but as I've said several times, totally up to what you want to do. Okay, so then after that, we have a number now that tells us how many records should be in the training set. So I'm going to return an object with keys of features, labels. I'm just going to put in all the keys first, test features, and test labels. So now to get some actual values in here, we're just going to look at our data array and our labels array, and we're going to splice them out. So I'll say data slice, excuse me, if I said splice, I meant to say slice, not splice. We're not splicing here, we're slicing. So I'll do a data slice, train size. So that's going to give me everything from 0 up to train size. And I'll do the same thing for our labels as well. Labels, slice, train size. Excuse me, I just said it's going to take us everything from 0 up to that. That's incorrect. It's going to take us everything from this value all the way to the end of the array. For test features, we'll do data slice everything from 0 to train size. And for test labels, we'll do labels slice everything from 0 up to train size as well. Okay, and that's pretty much it. So now the last thing we have to do is test this thing out. So down at the very bottom here, we've got load CSV. Remember, we should end up with one record inside of our training set. So I'm going to do some destructuring on whatever gets returned here. I'm going to take my features labels, test features, and test labels. And I'm going to console log out all of them. Features, labels, test features, test labels, like so. All right, so now we can rerun this. All right, so this all ended up on the same line, which is not super useful. Maybe we should go ahead and split this out to a couple of separate console logs. Let's do that really quickly. So let's say console log features, and we'll just repeat the same kind of step going down. So I'll say features, labels is labels, test features is test features, and finally test labels is test labels. That's going to be a little bit easier to understand. Okay, there we go. So now my features has 2 elements inside of it. My labels has 2 right here. I've got test features with just the 1020 and a test label of 1. Now, looking at this right here, it's immediately evident to me that we probably have a little bit of a mistake here. I had said split test. What I tried to do was make sure that split test meant that I would only have one record inside my training set. So the reason this is probably coming up a little bit funny is just because of how the slice argument right here works. If I want to get the true sizes or the sizes I'm trying to really specify here, I think that I should actually split the order of arguments, or reverse the order of arguments here for the slices between features and test features. So I think that in reality, I should probably do something closer to this, and then remove the arguments in the second one. Yeah, that definitely makes more sense. So let's try rerunning this now. I keep on rerunning my get step. My apologies for that. There we go. All right, that's much better. So now features has just one element inside of it. We've got the 1020 with 1, which indicates true. And we've got test features with all the remaining records inside of it. Now, just to do another quick test here, I should be able to go to my load CSV, and if I flip split test to false, I should now have everything inside of features and labels, and test features and test labels should be undefined. So let's try that out really quick. And yep, there we go. So I've got everything inside of features and labels, and test features and test labels are undefined. All right, so that's pretty much it. That is how we put together this CSV loader file. I hope this is a little bit more helpful. There's definitely many other libraries out there for loading up CSV files with JavaScript, but when I took a look at all of them, they all had their own kind of little challenges and limitations, and they weren't quite set up for all the options that you probably would want when you're doing some machine learning type stuff, like, say, easily extracting columns, easily shuffling, easily splitting it up, and some custom converters. We could easily load up CSVs with tons of other libraries, but it'd be really nice just to have all those things inside of one single function or one solution. And that's why we put this custom thing together. Okay, so that's pretty much it. Let's take a pause here.